Hello everyone, welcome to our FPGA design course with VHDL. In this video, we will give you a little brief about what we are going to cover in this learning series. By the end of this course, you will be able to design your complex FPGA projects with confidence using VHDL. So let's dive in and start mastering this language together. Throughout this course, we will work on the variety of projects and practical exercises to develop the deep understanding of VHDL and FPGA. We will begin with the straightforward projects and then gradually increase the complexity of our projects to design bigger systems. To test these projects, we will use the Cyclone 2 development boot for the experiment with the real hardware. In this course, we will cover the essential topics such as signals, constant, generics, variables, and many more things. These are fundamental concepts that form the basic building blocks of VHDL. We will explore the various data types in VHDL and learn how to create the custom data types as well. Additionally, we will go into the type conversions. This feature will enable us to convert the data between different data types. We will use the typecasting functions and VHDL functions to convert between different data types. After that, we will learn about the VHDL operators. There are around 30 VHDL operators and we will cover each one in details later. Next, we will explore the process and block statements in VHDL. We will cover both the registered version and the combinational version of these statements, including the sensitivity list. You will learn that how to determine which signals should include in the sensitivity list. We will also discuss the general structure of the VHDL files. We will cover the entity declaration, the architecture declaration, and the overall structure of VHDL files. Additionally, we will learn how to instantiate components and create the structural designs. We will discuss nearly all the VHDL keywords, including both concurrent and sequential statements. Lastly, we will explore the functions and procedures which are useful for performing the actions that need to be repeated multiple times. We will also explore the VHDL libraries and packages, both existing ones and how to create your own. Throughout this course, we will use the numerous example to demonstrate how to apply VHDL concepts in various scenarios. These examples will demonstrate the use of specific keywords and the options available when we are using them. Next, we will be creating the full designs including finite state machines, shift registers, serializers, memory components such as RAM, ROMs, etc., multiplexers, tri-state drivers, comparators, etc. We will walk through these examples step by step. Additionally, we will talk about several FPGA projects that we will implement and load onto the FPGA development board. This hands-on approach allows us to test our code in real hardware and interact with it to ensure that our FPGA designs functions as expected. Our first project will involve reading the input from a single switch and controlling a single LED output. This project is focused on understanding the tools and procedures required to implement a project and program the FPGA on board. Next, we will implement a simple state machine on the FPGA development board. This example will demonstrate that how the state machines can be implemented and run on the real hardware. Next, we will tackle a slightly more complex topics, which is how to synchronize the asynchronous input. We will focus on debouncing a switch input and discuss the approach how to achieve this. We will explore that how to generate a PWM pulse width modulation signal using an FPGA. We will cover a simple method for generating pulses, including how to vary the period and adjust the duty cycle of it. Next, we will dive into designing a shift register on the FPGA development board. This topic adds a bit more complexity to our project. We will develop a 4-digit 7-segment display on the board to show a number that corresponds to how many times the switch has been pressed. This project adds a practical aspect by interacting with the boards and its components, and it will add a hands-on element to our learning experiences. Lastly, we will develop a communication module, a UART, Universal Asynchronous Receiver Transmitter module. This module will work alongside the state machine and enable the communication between the FPGA development board and a computer over the RS-232 interface. We will make the extensive use of Intel Quartus software in this course. We will use it to create and compile our FPGA projects as well as performing the pin assignments. Pin assignment is the tool which involves mapping ports in a VHDL file to the physical pin on the FPGA device itself. Pin assignment is the process of mapping ports in our VHDL code to the physical pin of the FPGA device. This step is crucial for ensuring that our designs functions correctly on the actual hardware. I will walk you through how to perform this in this course. I will also give you a basic understanding of how to use the Quartus IP catalog. This catalog contains pre-designed VHDL components that you can select, drag and drop into your VHDL project. This feature simplifies the designer's life because most of the work has already been done in these catalogs. All you need to do is just learn how to generate these IP designs and then incorporate them into your own projects. I will provide an example to show you how to use Quartus IP catalog in this learning series. Additionally, I will demonstrate how to use the USB plaster to program the FPGA. This is particularly useful for testing purpose right after compiling your projects on the development board. We will also explore some of the output reports of the Quartus packages, including the netlist viewer. This tool is quite useful because it allows you to see the hardware realization in your design. When you write your VHDL code, it exists in the text editor. However, on the physical device, it's implemented using the registers, combination logic, and gates such as AND gate, OR gate, NOT gate, etc. And all these things are connected by some wiring, right? The netlist viewer provides a visual representation of this hardware realization, helping you to understand how the physical hardware performs the functions, which you are describing into the VHDL. We will also explore the fitter reports, which is the another type of report provided by Quartus. This report is valuable for understanding the resource consumed by your VHDL design. It provides the detailed information about the allocation of the resources on the FPGA and giving you the insights into how efficiently your design is using the available hardware. You will be able to see that how many registers and gates your design uses among all other things. This report gives you a comprehensive overview of the resource uses and help you identify where the resources are being utilized. We will also explore the Quartus assignment editor. This tool allows you to fine-tune the implementation of your design. While your VHDL code describes the behavior of your design, the assignment editor helps you to optimize how that code is translated into the physical hardware by the Quartus compilation process. We will also explore the other settings, options, and optimizations available within the Quartus. Additionally, I will provide a basic introduction on the timing analyzer and how to create a basic timing constraints, including generating an SDC file. However, this coverage will be introductory. For verification and simulation, we will be using ModelSim. I will demonstrate that how to create and compile ModelSim projects, write module label and system label testbench models, and use text files to generate inputs and output vectors for testing. By using the assignment editor, you can influence how a specific section of your code or design are implemented in the hardware. This optimization can lead to better overall design efficiency. Understanding how to test a complex FPGA design is very crucial. We will cover that how to perform the simulations using ModelSim, including developing the comprehensive test benches, especially for the final project. We will write the test benches at the module level for the various modules and ultimately design a system level test bench to ensure the entire system functions correctly when all the models and all the modules are integrated. We will use the wave window in ModelSim to analyze our results and ensure that they are aligned with our expectations. This approach ensures that our FPGA designs are thoroughly tested and functions as intended. This FPGA development board with the Cyclone 2 device looks great. It has 7-segment display which will definitely come in handy for our projects. It seems like a very capable board for learning and experimenting with FPGA design in budget. You can also try the mid-range FPGA devices as well, like Cyclone 4 devices, etc. The other thing that is highly useful about this development board is that it has these header pins. These general purpose input-output headers on the board let you easily connect other hardwares on the FPGA for experiments. This flexibility is great for trying our new ideas. This is quite useful if you want to experiment by plugging in other hardware modules onto your FPGA development board. There are also an LCD connector at the side, which means you can connect and control an external LCD device with this FPGA. This summarizes what we will cover in this course, giving you a good understanding of FPGA designs. Hope you are looking forward to it. In the next session, I will show you the easiest way to grab the Quartus Prime software for free to practice the exercises of this course. In this session, I will show you how to download Intel Quartus software and how to install it in your PC for free. This will be needing for your practical exercises to compile your VHDL designs and implementing that into the FPGA. So please follow the steps with me to grab it and set it up on your machine. This edition is absolutely free and safe to download. Okay, so for the Quartus Prime software, we will go to the Intel official webpage. So type www.intel.com on the URL. So this is opening. Now go to the product section or product tab. Now there are many things. We will go to the FPGA and programmable devices. And here you will see Quartus development software and tools. So just click on it. So this is the page. There are a couple of options here for the Quartus Prime design software. So this is here, and this is here. Just click on any of the link. Every link will land you on the same page. So this is the current version 24.3, and if you want, you can just read these release notes, that what's new or kind of thing, or else straight go to the download section. So click on it. So now there are 3 editions. Number 1 is Pro Edition, second is Standard Edition, and third is Lite Edition. Because we are looking for a free edition, so we will select this Lite Edition because this is free. So click on this go to download button. Okay. So this is the FPGA development tool. You have selected this Quartus Prime Lite, and for this version or this edition, the latest version is 23.1.1. So you can see this is the latest one. But if you select Pro or Standard, then your version can be different. So for this Quartus Prime Pro, the latest version is 24.3. Okay, this is operating system, Linux or Windows. For Mac, it is not available. So this is Pro 24.3 is the latest. We will select this Lite edition because this is free. And we have this 23.1.1 that is latest. Select the operating system, Windows. Okay, so go down, and this is our download section. This is recently added, that is installer. So this is 28 MB in size. So this is not a full setup. This is just a web-based installer. You download it and run it, and then the downloads will be started during the installation process. So you can try it now, but there are more options. So I will explain that. So this is multiple download tab. So if you select, you will have this download button, and this is one single set of file. This is zipped, and this is 6.1 GB in size, and total GB is required 30 GB near amount. 6 GB is zipped, 6 GB unzipped, and 17 GB around for installation file. If you do not want to download this, or if you have the bandwidth issues or hard disk space issues, then you can select this individual tab as well. So you can select individual setups if you need it. So this is mandate, of course. We are looking for this one. So this is Quartus Prime. This is 1.6 GB in size, and installation size is this one, 8.55 GB. Other than that, we have this Twista simulator. So if you are not using any other simulator or third-party simulator, so you can use this. This is of course free again. So this is 802 MB in size, and installation size is 3.31 GB. Then there are some devices. So if you are working on the FPGA, you can select which device you are working. So yeah, these are additional setups. Next is additional software. So there are some applications like Quartus Prime Help or standalone software like Programmable and Tools. So you can download if you are working on the FPGA. And if you are completely new with the Quartus Prime, then you can download this help section as well. I'm not worried about my bandwidth or my space in my hard drive. So I will choose this multiple download section. It has everything. So it has Quartus Prime, it has drivers for your FPGA devices, it has quiz test simulator, it has everything. So this is just one single download file. So just click on it. And now there is some legal disclaimer. So read it and accept it. And once you accept it, your download will start. So you can see my download is started here. So I will pause the recording here so that it will download. And once it's download, I will come back. So the download is completed and this is the zipped file or compressed file that is downloaded. I have right clicked on it and just unzipped it. So I'll get this unzipped folder. Now I am going here. Now there's component section. I will go there. So you have Quartus Lite setup, you have quiz test setup and few additional help setup. There are devices. So I will double click on this Quartus Lite setup, or you can just right click and click on run as administrator. Okay, so the setup is starting. Now click on next. Just like you install any other application, it is just same like that. I accept. Next. This is some default location for the installation. Click on next. I will suggest at least select at least one device from here. So what I want Quartus Prime, some devices. I am installing Quista as well. So everything is, I'm setting default. So click on next. Click on next. Now the installation process is started. So it will take some time. So I will fast forward this video so that it won't take long. Okay, so it is almost done and it took near about 20 minutes just to install, but it's just about to finish. And here you go. Leave it default and click on finish. Now this is for programming. So just click on next and everything is good. So just click on finish. So this is Quartus Prime software and it is starting. Okay, so let's have a quick demo so that we can start practices. First, click on New Project Wizard and click on Next. Everything's fine. Just give it some name. Suppose I am giving Test01. Then click on Next. Create an empty project. Next. Next. Choose any device, doesn't matter because we are not working on the FPGA at the moment. We are just doing the simulation. So select any device and just click on next. Now you can choose your tools. So for simulation, I just wanted to run on Quista Intel FPGA. So just select it and then click on next and then finish. So this is our Test01. Okay, now click on New and select a VHDL file because we are writing a VHDL code. So select this and click on OK. Quickly type a code. So library IEEE use IEEE.std_logic_1164.all entity test01 is port. Suppose A is in std_logic type, B is out, and this is study logic. Bracket close, semicolon, and entity. Test 01. Now architecture, behave of test 01 is begin. Let's say B getting the value of A, that's it, and behave. So that's it. So what we are doing, we are taking an input A and we are moving that value to the output B. That's it. We are just doing the simulation. Okay, so just save this program. Now go to the tool and run simulation, or you can just compile your design first. So just click on it. So it is processing. Okay, so everything is done and everything is okay. Now click on tools and go to this run simulation tool and click on RTL simulation. Okay, so it is saying that we are launching Quartus simulator, but we didn't install it. So we will go to the folder once again. And here we have this Quartus setup. So we will click on it and we will open it. So this is now starting. Click on next. So just select this. Click on next. I accept the agreement. Click on next. Intel FPGA 23.1 standard. Click on next. Then next. So it may take some time to install it. So I will just fast forward this video again. Okay, so it is done now. Now click on finish. Okay, now we might have to restart it, but just try it once. Click on options. Now EDA tools options, and I think this is good. So click on OK. Let's see if it is starting. Yeah, and here you go. So this is our Quartus simulator. At the bottom, we have this work library. Okay, so just expand this one and you have this test 01 as an entity. Okay, so just click on simulate. So you can see that your input output ports are in the object section. So just select these two and drag it to the waveform window. Now A is our input, right? And B is our output. So whatever we will give into the input A, that will go to the output B, right? Because we have written that B gets the value of A. So we are giving a clock to the input A, like apply clock. So everything is good. Just click on OK. Now we will run it for 100 nanosecond, for example. So you see A is 1, so B is also 1. A is 0, then B is also 0. A is 1, then B is also 1. So this means this is working fine. Now suppose I make some changes. I wanted to make B gets the value of not of A. So this is inversion. Means if A is 0, then B will get 1, right? So I will save it again and we will compile it once again. Let's close this for a moment. Okay, now this is processing. So now this is compiling. Okay, so everything is good. So you can see that green tick mark. So everything is okay. Now go to tools and click on run simulation tool and select this RTL simulation. Now it is starting again. Okay, so again go to the work library and select our test 01 module. Same, right click and click on simulate. Now you will get your input and output ports in the object section. So just select both of them and drag it to the waveform window. and give A some, you can force some value or you can give clock, because we just wanted to check it for the both of the values. So I will just giving the clock frequency. So select A, then right click, modify, apply clock. Okay, now run it for 100 nanosecond. So you can see that when A is 1, then B is invert of A, means 0. At this point of time, when A is 0, then B is 1, means it is doing not operation on the input A, right? So that's how you can check your VHDL program. Now go to the Quartus Prime once again. So here there are many things like analysis and synthesis and filters, assemblers, and timing analysis, and EDA netlist view. Okay. Now suppose you wanted to see that how your structure looks like for this VHDL code, right? That's the purpose of VHDL designing, right? We wanted to see that how your structure is designed from a high level language or like VHDL or Verilog SDL. So we will go to this netlist viewer and then we will have this RTL viewer. Okay, so just double click on it. So you can see this is a NOT gate. So we have input A and NOT gate operation is happening and we are getting output B. So that's our code, right? Right. B gets the value of not of A. So you can write your VHDL programs for any of your designs and then you can see how the structures will be generated, how the gates are interconnected with each others, how the RTLs are connected with each others. So this is the beauty of this program. Okay, so that's it for today. I have shown you that how to download your Quartus Prime software and Quista simulator software for free, how to install it on your machine and how to set it up. Then we have seen a quick demo for a VHDL program and we simulated that into the Quista simulator, and then finally we seen the RTL viewer or RTL structure designs for that program. Just a small note here, because the newest Quartus Prime software do not support old FPGA devices like Cyclone Cho. So I will also set up an old version of Quartus in my machine when working on the FPGA board. So do not confuse if you see two versions on my machine in future videos. But for most of the practical sessions, latest version is enough to simulate and test your designs. Before we start exploring VHDL, it's important to understand some basics about FPGA. This knowledge is important because the code we write in VHDL will ultimately run on the FPGA devices. So let's understand some fundamental concept of FPGA in this video. An FPGA or field programmable gate array is a reprogrammable device composed of logical gates such as AND gate, OR gate, XOR gate, NOT gate, etc. The term field programmable means that the devices can be reconfigured multiple times to implement different logical functions. Modern FPGAs contains more than just logical gates. Now there are few additional elements commonly found in the modern FPGAs. Configurable logical blocks, CLBs. These are the basic building blocks of an FPGA containing logical gates and flip-flops that can be configured to implement various logical functions. Input-output blocks, normally called as IOBs. These blocks manages the interface between the FPGA and the external devices such as sensors or displays, etc. Block RAM or BRAM. This is dedicated memory within the FPGA that can be used to store the data. DSP blocks, normally called as digital signal processing DSP blocks, are specialized blocks within the FPGA designed for performing the complex mathematical operations quickly. Next is clock management resources. These resources help manage and distribute the clock signals within the FPGA. These elements work together to make the FPGA highly flexible and customizable with a wide range of applications. All FPGA devices consist of logical gates, registers, and configurable routing. Most modern FPGAs also include built-in block memory resources for implementing RAMs and ROMs within the device. They also typically feature PLLs, that is phase locked loops for clock frequency scaling along the frequency multiplexing and division. Some FPGAs, including dedicated arithmetic blocks for tasks like multiplication, addition, subtraction, etc. To cater to the diverse range of application for FPGAs, vendors often add other elements into their FPGAs, known as hard peripheral blocks. While these blocks may not be that much configurable or flexible as other FPGA resources, but they play the important role in specific applications. Some FPGAs include built-in ADCs, analog to digital converters, or DDR memory controllers, etc. For example, the latest semiconductors cross-link FPGAs features MIPI interfaces that can transmit video streams from cameras to the MIPI displays. These built-in features like ADCs, DDR memory controllers, and MIPI interfaces are the example of the hard peripherals in the FPGA. The key concept is to understand that the most of these elements in the FPGAs are fully programmable. However, it's important to note that the hard peripherals like ADCs, MIPI interfaces, and DDR IOs may have the dedicated IO pins. So you will need to pay attention to these details in these devices' datasheets. As we progress throughout this course, we will learn more about the flexibility of the FPGAs. The two major FPGA vendors are Intel and Xilinx. However, there are several other companies that manufactures FPGA. You can also find FPGAs from companies like Lattice Semiconductors, Macrosemi, and even Macrochips, among others. The beauty of programming FPGA is that you can use VHDL for all of them. When describing an FPGA, it is important to understand its basic structure. While all the FPGAs consist of logics and registers, these resources are just placed randomly within the device. If you keep an FPGA under the microscope, you should see the repeating patterns of tiny cells. These cells, numbering in the thousands, are identical to each other and form the basic building blocks of the FPGA. We refer to these as the configurable logical elements, or CLBs for short. Each CLB contains the carefully organized logic and registers. This diagram shows the example of a CLB. You just need to note that the different FPGA vendors uses different names for the CLBs. For instance, Intel called it Adaptive Logical Modules, while Xilinx has its own terminology. The CLB contains a lookup table, LUT in general we say. You can see it in this example where we have the 4 input LUTs with inputs A, B, C, and D. The lookup table is just like a truth table and is used to implement a combination of the logical functions. For instances, in this example, the LUT can be configured to act as a 4-input AND gate or a 4-input OR gate. It can also implement more complex 4-input logical functions that require multiple logical gates. The lookup table LUT is a powerful and flexible component within the CLBs. FPGAs do not have the individual gates like AND gate or OR gate. Instead, they have the lookup tables to implement all the combination logics. The output of the lookup table feeds into the D-type flip-flops, also known as 1-bit register, and the output of the flip-flop also goes into the multiplexer. The flip-flop receives the clock and reset signal, and its output is connected to the multiplexer, which acts as a simple switch to select which input goes to the output F. And that's the basic structure of an FPGA. In summary, a typical CLB includes a lookup table for implementing the combinational logical functions, a flip-flop or register, and a multiplexer. The exact content of the CLB can vary between the FPGA vendors and the devices. So it's important to refer to the device datasheet for the specific details. For example, your device might have a 6-input lookup table or multiple flip-flops in its CLB. This slide demonstrates the arrangement of the CLBs and other resources within the FPGA. The gray lines represent the programmable interconnects, these facilitating the connections between the various FPGA resources. Highlighted in red are the I/O cells, which directly link to the I/O pins of the FPGA. Interconnects between the I/O cells and the CLBs are also displayed here. Additionally, this slide showcases the PLLs for clock frequency scaling and a RAM block for the memory implementation. It's important to note that this diagram is simplified representation. In reality, FPGA contains thousands of CLVs and hundreds of input-output cells, along with many more resources which we are showing here. However, if you understand this basic concept, then combining the larger FPGAs becomes straightforward because a larger device simply contains more of these blocks. FPGAs are valuable for implementing custom digital circuits. For example, in data acquisition scenario, where data from the several high-speed ADCs need processing, FPGAs can filter the data, performs the real-time calculations like FFTs, or store it in the memory. Unlike the microcontrollers with the fixed architecture, FPGAs offer immense flexibility in their capabilities. For instance, in the microcontrollers, you are limited to a set number of peripherals like counters, timers, UARTs, and SPI peripherals. However, in the FPGA, you can have many peripherals as needed by you, provided you the highest flexibility of using all the resources or CLBs. This flexibility allows you to create your own peripherals or modules to suit your specific needs. As an example, we will create our own UART peripherals by the end of this course. Additionally, you can even design a basic microcontrollers in VHDL to run on the FPGA and act as a microcontroller. Another approach is to utilize the pre-made modules, also known as IP blocks. FPGA vendors such as Intel or Xilinx provide a variety of IP blocks for free. Some of them are freely available, but there are some which are paid as well. Once you are proficient in the FPGA design, you can create your own modules and you can share them with others for their designs. It's important to write the reusable VHDL code even if you don't intend to distribute your modules among others. This way, when you need a new FPGA design in the future, you can easily incorporate your reusable modules into your new designs. We will cover that how to design those reusable modules, which is valuable practice. FPGAs don't have a fixed hardware structure. They are fully reconfigurable by design. As we discussed earlier, FPGA consists of many configurable logical blocks that can be programmed to perform the various digital functions. Regarding the I/O pins, they can be configured as inputs, outputs, bidirectional pins, or remain tri-stated. You can assign any function to almost any input-output pin. Additionally, most Intel and Xilinx FPGAs allows you to set the input-output drive strength for each GPIO line in milliamperes to control the edge rate of the signal. In summary, there is no fixed hardware structure in FPGAs. You can configure them to perform almost any function. And this is the main advantage of FPGAs, that they are completely reconfigurable and you can develop any sort of your system in a single board. Think you are building a cool new gadget and you get everything wired up and working, but then an amazing idea for an extra feature pops into your mind, or even customer demanded. With the regular ICs, that may need to start all over again. Might be wiping out the old circuit boards and building a new one. But that's where the FPGAs comes in. FPGAs are like super flexible building blocks. They can completely change their functions on the go without needing to touch the circuit board itself. Today's FPGA are also pretty speedy. They can run at clock speeds of 200 MHz, sometimes even faster. While that might not seem super impressive compared to some processors that can hit speeds of gigabyte range or gigahertz, but FPGA have a secret weapon, that is parallel processing. Imagine a computer with just one person working on the task, one after another. That's kind of how a regular process works. Now consider a computer with hundreds of people working on the task and all at once. And that's the power of parallel processing. And this lets the FPGA tackle the huge amount of data extremely fast, which making them the perfect fit for the situations where information needs to process super fast. A great example is processing audio and video signals, where a lot of data involved in those tasks and no problem for the FPGAs, which is why they are often used for the communication devices as well. The FPGA configurability allows for virtually unlimited data path widths. For example, inside the FPGA, you can simply create a 32-bit bus between the modules. But if you feel that is insufficient for your project, then you can double it to 64 bits or even further to the 128 bits to achieve the necessary bandwidth for your project. This level of flexibility is not achievable with the processors because their data path is fixed. Usually, this width is either 16 bit or 32 bits or 64 bits in the modern processors. Because of their parallel natures, FPGAs are better for intensive data processing applications that involve continuous calculations. Even though FPGAs are powerful tools, but still there are some situations where they might not be a best choice for your projects. For example, the cost can be one factor. FPGAs tends to be more expensive than the microcontrollers. If you are working on the tight budget and your project does not require the full capabilities of an FPGA, then a microcontroller might be a more economical option for you. Another consideration is the type of tasks your project involves. FPGA leads at handling multiple tasks simultaneously. I mean parallel processing. However, if your projects involve a lot of tasks happening one after another, like sequential processing, then a microcontroller might be a better fit. Microcontrollers are often optimized for these type of tasks. Finally, the speed and the latency, generally says delays, are the important factors as well. While FPGAs can be fast, speed isn't always the most important thing. If your project does not require the lightning fast processing and extremely low delays, then a microcontrollers might be a simpler and a cheaper option for you. But the good news is that the reality is changing. Now the FPGA prices are dropping and they have the smaller and more affordable options available that can compete with the microcontrollers cost. This means that the FPGAs are becoming more attractive for even budget-conscious projects. So while the FPGAs are the powerful tools, but it's important to consider the cost, task type, and speed requirements for your projects before making a decision. In the next session, we will be talking about how these FPGAs gets programmed, what is the design flow, and what is the implementation flow. We will briefly talk about the important terms and features required in the whole process. In the last session, we made some understanding about the FPGAs, how it works, and how it is different from the microprocessors and microcontrollers. Now, in this session, we will talk about the FPGA design process, and we will also cover the important features which are needed during the whole process from designing your system to the FPGA integration of your system. So let's start. To program an FPGA, the most common method is to use a hardware description language, normally called as HDLs. HDLs are the programming languages specifically designed for describing the hardware behavior and structure of your digital circuits. With HDLs, you can directly specify the functionality of your hardware components such as registers and logical gates. But this is not only the option you have. Alternatively, you can use the higher level languages like C or C++. However, this requires using a high level synthesis tool to convert the code into a lower level representation, which can be implemented on the FPGA. Some developers prefer the graphical methods such as schematic editors or state machine editors to design their FPGA projects. These tools allows you to visually create and connect the components with each other, which can be more easier approach for some users. Popular hardware description languages HDLs include VHDL and Verilog SDL. In this course, we will focus on VHDL. VHDL and Verilog SDL both are powerful languages that provides the full control over the FPGA designs. It is widely used among the FPGA engineers and students. Verilog SDL is weakly typed language, which means it allows you to write code that may not be valid. This can lead to the faster compilation of your designs, but in this case, the debugging will be more challenging during the testing and simulation process. However, VHDL takes a different approach compared to the Verilog SDL. VHDL is a strongly typed language. This means the compiler can identify the errors early in the development process. And this can save you a lot of debugging time later on. VHDL language is more deterministic, means its behavior is easier to predict, which make it more suitable for the safety critical applications such as in the medical field and aerospace fields, etc. However, VHDL requires more words to write to achieve the same results as compared to the Verilog SDL. Despite this, I will say that the VHDL is the valuable choice for the reliable FPGA programming because of lesser bugs and easy debugging. However, this does not mean that one is good and another is bad. VHDL and Verilog SDL both are powerful enough for FPGA designing. The purpose of the HDL languages like VHDL or Verilog SDL is to have the code which is synthesizable, which means the code which we write that should be translated into the hardware. This subset is generally referred to the RTL code, which is also said as Register Transfer Label code. This RTL describes the hardware using the basic building blocks like registers and the logical gates, etc., and the interconnections between these elements. Behavioral code in VHDL describes the functionality of your digital system at the higher level, which has more focus on the behavior of your digital systems rather than its physical implementation details. The problem with the behavioral code is that it cannot be directly mapped to the hardware. Although this behavioral code is good for simulation to test the functionality of your digital system, hence we are needing the RTL code which describes the hardware components and their interconnections. And this can be mapped with the hardware elements in an FPGA or ASIC. Register transfer label or the RTL code describes a digital circuit which can tell that how the data moves between the registers. You can assume that RTL code is like the blueprint of your digital circuits, which uses registers and logical gates to describe how the data will flow throughout the FPGA. To write the RTL code effectively, you need a solid understanding of your digital circuit which you are designing, including the logical operations and how the data flows between the registers. There is one important thing to note is that in the RTL code, you do not specify the delays directly. Instead, timing is described in terms of clock adds. RTL code is used as input for the VHDL synthesis tool where it is converted into the netlist of the logical gates and flip-flops. We will write our RTL code later in this course, so it is okay if it seems complex at the moment. We will cover it later in details. Now, the behavioral code describes the high-level functionality of your digital system design, and it is primarily focused for the simulation. It cannot be directly synthesized and run on an FPGA. Hence, this type of code is often used to model the environment around your designs in simulation. Behavioral models are useful for the verification and can be compared against the RTL models to ensure the correctness. We will also explore how to write the behavioral code later in this course, so it is okay if this concept is a little bit unclear at the moment. The FPGA design process involves the several steps that differ from the microcontroller designs. This is a typical FPGA design flow which I am explaining here. However, if you are just trying to test some of your small VHDL code and integrate it into the FPGA for your test, you can skip some of the steps. Okay, coming back. So the process starts from understanding the high-level requirement of your digital system design, like what you are designing and what you wanted to achieve with your requirements. And then you will create some outline of your different ideas to achieve that requirements, right? Sometimes this looks simple, but maximum times when you're designing the complex system, then you will see them complex. Hence, you will need the requirement documentation or the specification sheets. And based on that, you can split the requirements into the multiple blocks and you will create some blueprints of those designs. Here, each FPGA block is a self-contained module that performs a specific task, like SPI or FIR filtering or anything else which is needed for your main requirement. Once the blueprint of your high-level design is ready, then you can start writing your VHDL code to describe each of your blocks. This process is typically done using the RTL code or Register Transfer Label code, as you want this code to be synthesizable for the FPGA. Next, you would write the test benches to test each of your FPGA blocks which we have designed, usually using a combination of RTL and behavioral code. So, we test each block individually to ensure that they are functioning correctly. Because if you see any bugs in your design, then those issues can be fixed at the block level, which is just a small part of a big and complex requirement. Hence, it is easy to identify them and fix them. Instead, if you are just writing your code until your system level design is completed, and then you start testing, then you will have the many untested blocks. So you can imagine the challenge to find the bug if your system do not behave as per your expectation. So remember this, that splitting the complex design into the smaller blocks and individual testing of those blocks is a better approach to design the big and complex systems. Okay, coming back. So once we have tested all of our individual blocks and we are confident that all of our individual blocks and modules are working as expected, then now it's time to bring everything together. This is where we create our top level designs of the FPGA design. You can say it is our final assembly. To ensure the entire system functions as intended, we then write a comprehensive test bench that simulates the entire FPGA design as a whole, allowing us to identify and fix any bugs before we move on. And once we are confident in our design functionality throughout the simulation, then we can proceed with the next step, which is synthesis, where the HDL code gets translated into a format which FPGA can understand. You can say that synthesis is the bridge between your HDL code and the FPGA implementation. It takes your VHDL code and translates it into the netlist, which is detailed blueprint that specifies all the hardware components and how they are wired together. But the FPGA needs more than just a blueprint. It needs to know that how fast everything needs to work. That's where the timing constraint comes in. You provide the informations like clock speeds and the delays caused by external connections. By taking these constraints into the account, the tool can try to create a layout that meets your design timing requirements. That ensures the data flows throughout the circuit at the right speed so that everything can function properly. After synthesis process, which creates the blueprint or netlist of your design, now it's time to translate that blueprint into the real hardware plan for the FPGA. This is where the implementation stage takes place. Here, you tell the tool exactly which pins of the FPGA will be used for external connections like clocks, data inputs, and outputs. The implementation stage then takes the netlist, timing constraint, and the pin information to perform these three tasks. Number 1 is placement, number 2 is routing, and number 3 is optimization. Let's understand them in brief. So first is placement, where system will figure out that where each component of your netlist will be physically located into the FPGA chip. Then routing determines how these components will be interconnected using the FPGA internal wires. And finally, the optimization ensures the design is as efficient as possible. The end result of this implementation is a binary file, a special set of instructions that the FPGA can understand, which can be used to configure itself according to your FPGA designs. This binary file is like the master plan that tells the FPGA that how to perform the task. The implementation stage does not just translate your design, it also provides the valuable information and reports to you. Along with the binary file that configures the FPGA, this tool generates the reports detailing resource uses. This includes that how many resources are still available and how many input-output pins are used, etc. But the most critical report is the timing report. This report verifies if your design meets the speed requirement you specified earlier in the timing constraint. By checking this report, you can ensure that your designs functions correctly on the real FPGA hardware. The timing report confirms that your designs can keep up with the speed demands of your project. This report is essential because even if your design seems to work during the initial testing, but failing to meet the timing constraints can lead to unpredictable behavior of your designs. Think a bit that you have designed a machine and it does not meet the timing constraint requirements. Well, it might work most of the time, but they suddenly act differently, or maybe it can fail entirely at some unpredictable moments. These intermittent failures can be a nightmare to debug because they might only occur under some specific conditions, like extreme temperatures and something else. And in such cases, even reproducing the problem would be a challenge itself. For example, if you load your design onto the 100 of identical FPGAs, you might see that out of these 100 test FPGAs, your system is working perfectly fine on 95 devices, but they are not doing their jobs on rest of 5 FPGA devices. Then what? By carefully reviewing these timing reports during the implementation, you can catch these potential issues early, and you can ensure that your designs run smoothly and reliably on the FPGA hardwares. So that's the importance of analyzing the timing constraint of your designs. So in brief, these timing constraints are like the speed limits for your designs. If your designs violates them or fails the timing constraints, you may face the potential troubles later. The good news is that the FPGA tools can pinpoint those bottlenecks. They can identify the areas where your design can struggle to meet the speed requirements. Armed with this information, you can strategically rewrite your VHDL code to optimize its performance. By addressing the timing constraints and optimizing your code, you ensure that your designs run smoothly and reliably on the FPGA hardwares in the real world. Do not worry, the importance of timing constraints will be further explored when we will design our UART peripheral systems later in this course. For now, remember that the proper timing constraints and optimized code are essential for ensuring the reliable FPGA functionality. We will discuss about it deeper into the later sessions. After the implementation stage equips you with the FPGA configuration file and the timing report, now it's time to bring your design into the life. Unlike the macroprocessor that load the code from internal flash, most FPGA rely on the external flash only to store the configuration image. This is because that the most FPGAs do not have any inbuilt flash memory for storing the configuration image. Hence, this external flash memory acts like a storage bin for the FPGA memory. There are several ways to program this external memory. You can use a separate microcontrollers to write the image into the flash, or you can use a JTAG interface which can be used to program the external flash chip. We will explore these programming methods in more details later in this course. A simple schematic can display a typical method for storing the FPGA configuration images. Once the flash is programmed, then simply turn on your FPGA device and it will automatically load the image from the flash and initiate its operations. Now it's time to quickly summarize what we have learned in this session. This video provided a comprehensive overview of the FPGAs. We talked about the FPGA basic building blocks. We talked about the CLBs, configurable logical blocks. These CLBs are like the key elements of the FPGA, combining the lookup tables for implementing the logical operations and the D-type flip-flops for storing the data like single bits. Many CLBs comes together to form the FPGA fabric, along with the additional resources like embedding the memory and the input-output cells. We then explored the FPGA applications where their custom hardware capabilities shine. VHDL and Verilog HDL were introduced as the primarily programming languages for FPGAs. Finally, we have explained the FPGA design flow, guided you throughout the entire process, transforming your initial concept into the FPGA design, performing the simulation and test, ensuring your design meets the timing constraints, and ultimately generating the configuration image that brings your design to the life of the FPGA hardware. This knowledge equips you with a solid foundation of your future FPGA projects, which we will be covering in this series. In the next session, we will be talking about the signals and data types. In our last session, we discussed about the FPGA fundamentals and their implementations. We also highlighted that the hardware description languages HDLs are primarily used for designing the FPGA systems. In this video, we are starting our journey into the VHDL by exploring the signals, which are like the internal wirings of an FPGA. Just as the physical wires carrying voltage representing ones and zeros in the digital system, signals in FPGA also convey these logical labels. However, signals can do more than just carry the binary values. The type of information which a signal can carry is determined by its data type. While signals can indeed convey the binary values, they can also represent a range of other data types. For example, using a specific data type called std_logic. Also, signals in VHDL allows more than just binary data types, like for example, integers, booleans, or even the multi-bit basis like a 16-bit data bus. Understanding and defining the appropriate data type for each signal is essential for ensuring the accurate and efficient communication within the FPGA design. As we progress, we will understand that how to define those signals, integrate them into your designs, and using them to develop the efficient FPGA solutions. Before diving into the VHDL, let's cover some basics. So VHDL is not a case-sensitive language, means that the uppercase and the lowercase letters are treated as same. This applies to everything like object names, keywords, and identifiers as well. Keywords, also known as reserved words for the VHDL, have the specific meaning in VHDL and they are used for the special purposes. Identifier, on the other hand, are the names which you assign to your variables, signals, or the VHDL modules. Identifier in VHDL must follow some certain rules, like they must start with a letter and then can be followed by letters or some digits. Spaces are not allowed in identifiers. Additionally, the identifiers cannot be the same as reserved keywords in VHDL. In VHDL, signals are essential for connecting the components within a digital system. They serve as a pathway for the data transmissions similar to the wires in a physical circuit. Like variables in C or C++, signals must be declared before they can be used. This declaration specifies the name and the data type of the signal, allowing it to carry the data between different parts of your designs. There are two examples of how you can declare the signals. The word signal, which is highlighted in blue, is a VHDL keyword. As I said, that the keywords are reserved in VHDL and cannot be used as identifier or the object name. So for example, I cannot define a signal by the name signal because signal is a keyword and it is reserved. You can easily identify those keywords while you are writing your code in the VHDL programming tools because these keywords will be displayed with a different color in editor. Generally, it is blue. Okay, so we write our signal name followed by the data type of our signal. And finally, we end the statement with a semicolon. The data type of a signal is crucial because it defines the type of data which that signal can carry. In VHDL, this can range from simple logical state like 0 or 1 to the more complex types like 16-bit bus or even integers. VHDL provides a variety of built-in data types to cover the many scenarios. But in case these predefined data types don't suit your needs, then you can create your own custom data types. This flexibility allows you to tailor the signal data types to match the requirements of your designs. VHDL signals, unlike some wires you might encounter, don't automatically start with a specific value. When you declare a signal without an initial value, like in your first example, it begins in an undefined state. Think of it like a brand new wire, its state is unknown. However, the second method offers more control. By assigning an initial value during the declaration, like in the second example, you can set the signal to a known state from the very beginning. This can be helpful for initializing your VHDL design and ensuring it starts in a productive way. Assigning an initial value during the signal declaration in VHDL is a powerful tool, but it is important to understand its limitation. So the first thing that you should know that this initial value only applies during the simulations, which are like the test runs of your VHDL code on a computer. It does not affect the actual behavior of the signals when you run your designs on the real FPGA hardware. Since the FPGA does not receive this initial value, the signal will still power up in the undefined state. This can lead to the unexpected behavior in the FPGA compared to the simulation, because the simulation assumed a defined starting state for your signal. Remember this difference that the initial values are only for the simulation purpose. So you might ask that how do I make sure that my signals are initialized correctly? But do not worry, this is actually very easy to do and we will discuss those other ways to manage the signals states during the FPGA power up in the later parts of this video. So till now, we have explored that how to declare the signals in VHDL, which acts like a digital wires within your FPGA designs. Now we will quickly see that how we do the assignments in VHDL, means how you will assign some values to the signal or how you can connect the wires in the general terms. So this is achieved by the assignment symbol. In VHDL, the assignment statement is not represented by an equal sign as in C or C++. Instead, in VHDL, it is less than sign followed by the equal sign, which serves as the VHDL assignment operator as highlighted in the red. This operator resembles like an arrow which is indicating the direction of a data flow. Like for example here in this expression signal underscore A less than equals to signal underscore B semicolon, the value of signal B will be assigned to the signal A. In the next session, we will be talking more about different types of VHDL data types, which are pre-supported and what information these signals can carry, how to define them, and most important, how to assign the values into those signals. In the last session, we had some overview of how we define the signals in VHDL. Now, in this video, we will talk about the data types which are pre-supported by VHDL. We will understand what type of information those data type carries in the signals. This is important because you can only connect one signal to the another signal when their data type is same. If you attempt to assign a signal of one data type to the another signal of a different data types, the VHDL compiler will flag an error. This strict type checking helps maintaining the consistency and avoid the unexpected behavior in your designs. In VHDL, the assignment statement is not represented by the equal sign as in C or C++. Instead, it is less than sign followed by the equal sign, which serves as the VHDL assignment operator as highlighted in the red. This operator resembles like an arrow which is indicating the direction of the data flow. Like for example here in the expression signal underscore A gets the value of signal underscore B semicolon. Here the value of signal B will be assigned to the signal A. So now we know the syntax of the signal assignment. One of the most common signal type in VHDL is std underscore logic, which is similar to a wire as it can carry a logical 0 or logical 1, representing a single bit of the data. The std underscore logic data type is declared in the std underscore logic underscore 1164 VHDL package. So to use this data type, you need to declare the std underscore logic underscore 1164 package in your VHDL code. A single bit represented by either logical 0 or logical 1. You can think of it as a single light switch that can be on or off like 1 or 0 to use this data type. So these are the most common values of the digital systems. But the std underscore logic offers more than just the binary values like 0 and 1. It can also represent a high impedance state denoted by Z. This is like a neutral state where the signals isn't actively driving a 0 or 1. You can imagine a wire that is disconnected from its source. However, using the tri-state signals require more cautions. While they are useful for external input-output pins that can be disconnected and controlled by the other circuits, most internal signals within the FPGA cannot be tri-stated. You are only allowed to tri-state the signals that directly drive to the I/O pins of the FPGA. This is because only the I/O pins having the tri-state buffers, while all the internal signals in the FPGA do not have the tri-state buffers in hardware. Therefore, you cannot drive the internal signals in the FPGA to the tri-state. Beyond the digital values like basic zeros and 1 values and the Z state, which we just discussed, we have more states in std underscore logic. We have H and L state indicating the weakly driven high or low states respectively. Imagine a wire with a weakly pull-up or the pull-down resistors, influencing its voltage but allowing a stronger driver to override it. Similar to the tri-state and weakly driven signals, W represents a weakly driving signal with the unknown value. This can occur during the simulations if the signal's true strength is unclear. The U state signifies an uninitialized value, which is a reminder to properly initialize your signals in your FPGA code. Now things get interesting with the X state. This arises when two conflicting drivers try to assign the different values like 0 and 1 to the same signals simultaneously. Then the simulator keeps this in the confusion, marking the value as unknown, means X state. To avoid this, you need to ensure that your designs has the clear ownership of each signal to prevent such conflicts. Finally, the dash, that is don't care state, allows the design synthesizer some creative freedom. It can choose to assign any value from 0 and 1. In this state, to optimize the circuit for the speed and area, resource usage, it is important to remember that these extended states like W, U, X, dash, H, and L are primarily for simulation purposes. While they can help the model in the real world scenarios like pull-up registers or pull-down registers, they cannot be directly implemented in the FPGA hardware. For example, the H state or the L state can be used to simulate the pull-up registers or the pull-down registers. And some of the other states are used to indicate the undefined signals or the uninitialized signals only in the simulation state. We will go deeper into the FPGA implementation details in the later part of this course. But remember that the code that can be synthesized must always use logical 0 or logical 1 or try state. All the other states mentioned in the std_logic can only be used for the simulation process only. Std_logic signals are widely used, and you will also use it often in your VHDL designs. You will encounter that the std_logic signals when connecting the logical gates, which are the basic building blocks of a digital circuit. Similarly, they can be used to connect the flip-flops which store the data bits. Even clock signals and reset signals, which control the timing and the initialization of your designs. And they rely on the std_logic signal for their 0 and 1 logical labels. Now let's explore that how to declare the std_logic signals in VHDL code. The first example showcases a basic declaration. It is similar to that how you might label a wire in a circuit diagram. The second example demonstrates the initialization, where you assign an initial value, like 0 in this case, to the signal during the declaration. This is helpful for setting up your design to a known state from the start. Finally, the last example which shows the signal assignment, where the value of signal B is assigned to the signal A. Think of it, you are copying the information from one wire to the another wire. But make sure that both the signals are of same data types as we talked earlier. Let's have a quick example where you can use the std_logic signal type. So take a look at this example featuring an inverter and a D-type flip-flop. They are connected seamlessly using two std_logic signals, sig1 and sig2. Imagine that sig1 as a wire carrying the data from the inverter's output to the flip-flop's input, and sig2 acts as a bridge between the flip-flop output and the inverter's output. Just like wires in the traditional circuit, these signals facilitate the communication between the components. Furthermore, the clock signal CLK connected to the flip-flop is also an std_logic signal here, because the clock signals typically toggle between 0 and 1 to control the timing of the operations within your designs. By understanding that how the signals connect and interact with the logical elements like flip-flops and respond to the clock signals, you are laying a solid foundation for the mastering the VHDL designs. Think of these signals as the communication channels that allow the logical elements to exchange the data and perform their operations. This is the fundamental concept in building the digital circuits in VHDL. Now that we are comfortable with the single bits, VHDL introduced the std_logic_vector data types for handling the multiple bits together. Imagine a bunch of wires grouped into a single cable. That is the essence of a vector. An std_logic_vector acts like an array of vector of individual std_logic signals. In simple terms, it is the group of bits traveling as a unit, similar to a multi-lane highway carrying the multiple data streams simultaneously. Just like the std_logic, it requires including the std_logic_1164 package for proper use in the VHDL code. Get ready to explore how to declare and use the std_logic_vectors to represent more complex data in your FPGA designs. So, the std_logic_vector data type empowers you to handle the collection of bits for the std_logic signal types. Imagine a data bus or an address bus in a computer. They carry the multiple data lines simultaneously, like 8-bit, 16-bit, etc. An std_logic_vector is just like that. An array of vector of std_logic signals bundled together. This make it perfect for representing multiple data like registers, counters, and timers within your FPGA designs. Declaring std_logic_vector is similar to declaring a single bit std_logic signal, but with just a small twist. Since it is an array, so you need to specify the number of bits in the vector using a range, and the keyword down to gets used for it. Here we see two examples, an 8-bit signal named as A and another 8-bit signal named as B. The second signal B is initialized with the hexadecimal value A1. Notice the value inside the double quotes. The bottom of the slide highlights the bit ordering, where index 7 represents the most significant bit MSB and index 0 represents the least significant bit LSB. Assignments with the std_logic_vectors are slightly more complex, so we will understand its assignments with some examples. Assigning values to the std_logic_vector signals is straightforward when dealing with the signals of the same size. So if you look over the example where I am assigning signal A to signal B using the assignment operator, then this will work perfectly fine because both the signals are std_logic_vector type and having the same length, which is 8 bits. The second row of the table demonstrates the vector slice assignment. Imagine a scenario where you only want to copy the specific lane, a bit here, from the vector type signal to the another vector type of signal. Like here, bit 3 and 2 from the signal B are assigned to the bit 6 and 7 of signal A. This is also allowed in VHDL because the number of bits are same between them, which is 2 from signal A and 2 from signal B. This targeted assignment lets you manipulate the specific portion of your multi-bit data within your FPGA designs. Now continuing to the vector slice assignment, the third row showcases the assigning a single bit. Like here, bit 0 from signal B is assigned to the bit 4 of signal A. This allows you to insert a single data bit into a specific location within your multi-bit signal. In the fourth row, we assign bit number 6 of signal A to the logical signal C. So in short, VHDL offers the powerful features called array attributes, which come in handy when working with std_logic_vector signals, essentially the array of bits. These attributes provide the value information about the vector's structure. The left attribute tells you the index of the leftmost bit of the vector, while the right attribute reveals the rightmost bit of the vector. Similarly, the total lengths tell you the total number of bits in the vector. By using these attributes, you can write more readable and adaptable VHDL codes. In the next session, we will be talking about the attributes of vector type signals and how you can use them for clean and generalized VHDL codes. In the last session, we had some overview of vector type signals and std_logic_vector data type. Now, this is important session where we will talk about the attributes of vector type signals, and I will show you that how you can use those attributes for the clean and well generalized VHDL designs. So let's start. So we discussed that the VHDL equips you with the powerful tools called as array attributes, especially useful when dealing with the std_logic_vector signals, which are essentially the array of bits. These attributes are very important and can be reused in your VHDL designs. By using these valuable details of your vector type signals, you can write the cleaner and more adaptable VHDL codes. Let's take an example of vector type signal, which is signal sig_a, and this is vector type signal having 8 bits and its range is 7 down to 0. In this example, your left attribute tells the MSB of this vector, means you will get the value 7 as the left attribute. Similarly, right attribute tells the LSB, least significant bit of this vector, means you will get the value 0 as the right attribute. Same way, the length attribute of this vector will give you value 8 because it is 7 down to 0. Hence, it has total 8 bits, so length is 8. And range of this vector will give you 7 down to 0, where 7 is the leftmost bit and 0 is your rightmost bit. By leveraging these attributes, you can write more readable and the maintainable VHDL codes. Let's quickly recall the values of these array attributes here in this example, and then I will show you how you can use them in your VHDL codes. So left is 7, right is 0, length is 8, and range is 7 down to 0. Very straightforward, right? Now the table below displays that how these attributes can be applied, and you will also see their corresponding expressions. To start, consider the declaration of signal B. So signal B colon std underscore logic underscore vector, then a dash range semicolon. This example uses the range attribute to set the size of B to match whatever the range of signal A. So range of signal A is 7 down to 0. Hence the range of signal B will also be 7 down to 0. This is exactly same if you write signal sig B colon std underscore logic underscore vector 7 down to 0 semicolon. Continuing with the another example, signal C is declared as signal sig C colon std underscore logic underscore vector a dash left to a dash right semicolon. So signal A's left is 7 and signal A's right is 0. So we will have the signal B which will have the range of 7 down to 0. So this is again same if you write signal sig C colon std underscore logic underscore vector 7 down to 0 semicolon. Similarly, signal D is declared using the high and low attributes. So signal sig D colon std underscore logic underscore vector a dash high down to a dash low semicolon. This is equivalent to the signal sig D std underscore logic underscore vector 7 down to 0 semicolon. So here is a quick question for you. Do you see any benefit if you use these attributes in your VHDL codes? Let me know if you figure out any benefit of using this approach for writing your well-generalized and reusable VHDL codes. If needed, you can take a small pause here. Okay, let me tell you the advantage of using these attributes in your VHDL codes with one example. So suppose today you developed a system with the 8-bit data bus line, which is supposed to process parallel 8-bit data. Now, in future requirement, you are asked to develop the same system but with the increased bandwidth. Say now you have to design your same system with the 16-bit data lines. And if you are using these attributes in your VHDL code, then it will be quick for you, as you just need to change the range of your signal A, and all the other signals will sync according to the new range of signal A. But if you declare your signals like the regular approach, say 7 down to 0 or 15 down to 0, then you need to make changes for all the declared signals one by one. Let's conclude this in short that it is highly recommended to use the array attributes throughout your VHDL code. Why? Because it makes your VHDL codes more readable and adaptable. Imagine the code that automatically adjusts their vector sizes whenever you wanted to change them for your designs. And that's the power of attributes. This readability and flexibility also lead to the fewer bugs, as you are less likely to introduce errors during the modifications. Incorporating the array attributes into your VHDL design practices is a valuable strategy for writing the clean and maintainable and robust codes. While there is a broader range of VHDL attributes to explore, but we will discuss them as we progress on this course. For now, we have covered the fundamental concepts which you can use to work effectively with the data types like std underscore logic underscore vector and perform the arithmetic operations using signed and unsigned data types. Now let's talk about few more data types in VHDL similar to the std underscore logic underscore vector. VHDL offers additional data types specifically designed for the numerical operations like signed and unsigned data types. These are essentially bit vectors, similar to the std_logic_vector, but with the focus on representing the numbers. They can hold the same signal states as the std_logic, like logical 1, logical 0, or tri-state, etc. std_logic_vector are good in handling the databases where multiple bits are grouped together, but they are not ideal for the arithmetic operations. This is why the signed and unsigned data types comes in. So an unsigned value represents any non-negative numbers, which also includes 0 as value. For example, a counter. On the other hand, signed values can have both positive and negative numbers, which make it suitable for the calculations which involves positive or negative numbers. To work with these data types, you will need to include the numeric_std package in your VHDL code. Whenever your design involves the mathematical operations, signed and unsigned data type should be your preferred choice. This slide shows that how you can declare the assigned and unsigned signals in your VHDL code. This structure is very similar to the std_logic_vector declarations. VHDL offers the straightforward approach to assign the values between signals, as long as the signals share the same data types and size. I mean the array length for vectors, where you can perform a direct assignment. So signal X is assigned to signal Y using the assignment operator. This assignment is fundamental concept for the data flow within your VHDL designs. In the next session, we will be talking about the another most important data type, which is integer. And I will tell you about the best practices of using integers in your VHDL codes. In the last session, we talked about the std_logic_vector data type, and we talked about the array attributes. We also discussed how you can use those array attributes to code your VHDL designs more effectively. Now, in this session, we will be talking about another most important data type, which is integer. And I will tell you about the best practices of using integers in your VHDL designs. So, integer data type is designed to represent the whole numbers. However, VHDL does not specify the width or size of bits for the integer values, but most VHDL implementations provide at least 32 bits of data to store these integer values. This ensures a broad range for your numerical calculations within the FPGA circuits. VHDL offers the integer data type as a fundamental building blocks for representing the whole numbers in your FPGA designs. Unlike some other data types which require some specific packages to include in your VHDL code, integers are by default available within the VHDL programming itself. So you can use them straight in your VHDL codes without worrying about any package declaration. Integers are quite useful in applications such like counters and array indexing, etc. And they make integers a popular choice for various VHDL designs. Okay, now let's see how to define integers in VHDL. The first example is the basic way to declare an integer signal in the VHDL, which is signal sig a colon integer semicolon. This signal a can have any value between -2 to the power 31 to the +2 to the power 31. The second example declares an integer called signal b, and this have the same range like signal a, but it is just initialized to some starting values, like we discussed about the initial assignments earlier. However, these two examples, like declaring signal A and declaring signal B, are valid ways to create the integer signals, but this approach is actually not recommended because the implementation may allocate 32-bit registers to implement these integers. This is fine if you actually need a 32-bit number for your data, but in most cases, we do not need such a wide range. Hence, most of the hardware resources will be wasted if you practice this type of declaration in your VHDL designs. There are more resource-efficient approaches which we should consider for our VHDL designs. So, to avoid such unnecessary resource uses, the best way is to limit the range of your integer. The next two examples demonstrate this efficient approach of declaring integer signals by specifying a range of allowed values. So here is the syntax: signal, signal name, colon, integer, range, minimum value to maximum value, semicolon. For example, signal 6c colon integer range 0 to 255 semicolon. In this case, the signal C can only hold the values from 0 to 255, and this will offer significant advantage to your VHDL designs. First is resource efficiency. Now the FPGA can implement signal C using a smaller register, potentially a 8-bit in this example, because it only needs 8 bits to store the values within this limited range. This translates to the more efficient hardware utilizations. Second is the code clarity. Specifying the range enhances the code readability because it clearly documents the valid values which signal C can take. This makes your designs easier to understand for you and others. You can also initialize your signal with some initial value, like the same way we did earlier. You can refer to the last example here. So signal, signal name, colon, integer, range, minimum value to the maximum value, colon equals to initial value, semicolon. For example, signal sigd, colon, integer, range -128 to 127, colon equals to 35, semicolon. Here, signal D has a range of -128 to the plus 127, and it will get the initial value of 35. By adopting this range constraints, you can create more efficient and readable VHDL codes, while also optimizing the resource uses in your FPGA designs. Now let's quickly look at the integer signal assignments. VHDL allows the assignment between the integer signals as well, like we did for the std_logic signal types. So the syntax is same: signal name of destination, assignment operator, signal name of source, semicolon. As long as both signals share the same data types like integer in this case and having the same compatible range, you can directly assign the values of one signal to the another. For example, signal Y gets the value of signal X, semicolon. This statement will assign the current value of signal X to the signal Y. Remember that it is crucial to ensure that X and Y having the same range. Assigning any value to signal Y that falls outside its defined range may lead to the unexpected behavior in your FPGA designs. In the last few sessions, we talked about the std logic data type, signed and unsigned data type, and also the integer data type in VHDL. Now, in this session, we are continuing with more supported data types by VHDL. We will start from the Boolean data type. VHDL offers this built-in data type specifically designed for representing conditional values. It has the core concepts of true and false, forming the foundation for decision-making and conditional statements within your FPGA designs. Since it's an integral part of VHDL language, so you do not need to include any additional libraries to start using Boolean data type. Let's explore that how to declare Boolean signals in VHDL. Same like the other data types, here are two types of examples. First is uninitialized declaration. So syntax is signal, signal name, colon, Boolean, semicolon. For example, signal, sig_e, colon, Boolean, semicolon. This example will create a signal which is named as sig_e that can hold either true or false values, but with no initial values is assigned. Now second is declaration with the initialization. So syntax is signal, signal name, colon, Boolean, colon equals to true or false. For example, signal, sig_b, colon, Boolean, colon equals to true, semicolon. This example will declare a signal named as sig_b and which will be assigned as initial value of true. You can also initialize it to false using colon equals to false. Now let's talk about the enumerated data types. Enumerated data types are the powerful features in VHDL that allows you to create the custom data types. You can use those custom data types for your specific needs because these data types can be more representable in your VHDL designs because you are creating them for some specific needs for your project. Enumerated data types allows you to define a set of named values that your data can hold. These named values called enumerations. This can help to make your code more readable and self-documenting. For example, that you are working with a traffic light system. So instead of using generic numerical values like 0 for red, 1 for yellow, 2 for green, you can create an enumerated data type which is named as traffic light with the clear enumerations like red, yellow, and green. And hence, this can significantly improve the code readability. Suppose you are reading them exactly like red or yellow or green, instead some numerical code words like 0 or 1 or 2. So you can feel the simplicity in such use cases. Okay, now let's see that how you can declare those enumerated data types in VHDL. So let's understand it with some example. So write type traffic light is bracket red, comma yellow, comma green, bracket closed, semicolon. So this statement here defines a new data type named as traffic light, and this traffic light is having three possible values. First is red, second is yellow, and third is green. Okay, once we define our custom data types as an enumerated data type, the next step is to use that as a signal type. This means that we need to declare some signal with this data type named as traffic light. So, like we have the other examples, this also can be declared with and without initialized value. So first example is declaring the signal without initializing the value. So the syntax is signal, signal name, colon, traffic light, semicolon. For example, signal, current state, colon, traffic light, semicolon. Here, the current state is the name that we chosen for our signal, and the traffic light is the enumerated data type which we have defined earlier. We can also declare the signal by initializing some values. For example, signal, current state, colon, traffic light, colon equals to red, semicolon. Now this initializes the value red to the current state, which is one of the enumerations within our traffic light data type. You can also assign the values into the signal, just like you can assign the values in the other data types. For example, next state gets the value of green, semicolon. This statement will assign the value green to the next state, which is one of the enumerations within our traffic data type. Enumerated data types are the valuable tool for creating clear and maintainable code for such use cases. While VHDL offers a high-level abstractions with the enumerated data types, it is important to understand that how these translate to the underlying FPGA hardwares. During the synthesis, these type of typical implementations uses flip-flops. Now the question is that how many number of flip-flops? So to encode three different states like we have here, red, yellow, and green, we are needing minimum of 2 flip-flops. This is because that each flip-flop can store a single bit, either 0 or 1, and 2 bits can represent the 4 unique combinations, that is 2 to the power 2, that is equals to 4. Next important thing is encoding. For example, that state red is encoded as value 0, 0, and yellow is encoded with 0, 1, green is encoded with 1, 0, and 1, 1 is a known state here, because we have only 3 values. As we have only defined 3 states in this data type, so assigning 1, 1 would result as an undefined behavior. Note that this is just an example. The exact implementation might vary depending on the synthesis tool. So here are some key points. Number 1 is that enumerated data type enhances the code readability, but they have an underlying hardware representation. N number of flip-flops are generally required for 2 to the power n enumerations. The specific encoding scheme might differ based on the synthesis tool and settings. Understanding this hardware representation can be beneficial when you are designing the complex VHDL code and optimizing the resource uses as we discussed earlier. Enumerated data types allows you to define your own custom data types by listing out all the possible values that they can take. For example, think of the std_logic data type in VHDL, which represents the different logical states like 0, 1, tri-state, high impedance, weak high, weak low, etc. So all of these states are all enumerated when the std_logic data type is declared. When you are declaring an enumerated data type, you are essentially defining a set of named values that the data type can take on. The std_logic data type is defined in the std_logic_1164 package, which is why you need to include this package to use std_logic in your programs. Similarly, you can create your own enumerated data types by listing out all the possible values inside it. And these data types can be used to define the signals, variables, and other data structures in your VHDL code. In the last session, we learned that VHDL allows you to create your own custom data types for your specific needs in your VHDL designs. Now, in this session, we will go one step further and we will talk about the array data types, and we will combine them with the predefined and user-defined data types. So let's start. So we will understand it with some examples. First, this example demonstrates that how to create a custom data types for state machines in VHDL. Here the data type is SM type, that is defined to represent the three states of the state machines, that is idle, do work, and done. These states are listed in the type declaration. The SM state signal is then declared using the SM data type. This signal will hold the current state of the state machine. Initially, the SM state is assigned with the initial value, which is ideal. This indicates that the state machine is in the ideal state at the moment. Now later, the SM state is assigned to the other values like do work, which is indicating a transition to the do work state from the ideal state. The SM state signal can only take these three possible values, which represents the three different states of the state machines. Internally, this signal will be implemented as a 2-bit value in the FPGA as we discussed in the last slide. However, as a designer, you do not need to worry about this implementation details. All you need to focus on these three states, that is idle, do work, and done, which define the behavior of your state machine. Everything else will be taken care by VHDL and the tools. Now let's talk about the arrays in VHDL, which is a powerful concept in VHDL. They essentially functions as a collection of the signals or grouping of the signals which are having the same data types. This allows you to group the numerous signals under a single name. A prime example of an array data type is a built-in std_logic_vector data type, which we have talked about in the previous sessions. This data type represents the collection of logical values, commonly used for the situations like 8-bit data buses. So basically, an 8-bit std_logic vector is a group of 8 std_logic signals, which are treated as a single body. Well, this is predefined, right? But VHDL does not limit it to this predefined data types. VHDL is just more capable than this, because you can also create your own custom array-based data types by using the array keyword. So the high-level concept which you should know is that when you are defining a custom array-based data type, you are needing two key elements. Number one is element data type. This defines that what type of data those elements can carry. For example, it can be integer, or it can be Boolean, or even it can be user-defined data types, such as SM type, which you have just described in this session. Next important thing is the range index. This range index tells the valid range of elements, like how many elements your data type or array-based data types can carry. You can also access the individual element of this array as well, whenever it is needed. So, once you have a signal that is declared as an array data type, you can access and modify the values of individual elements using their indexes within the square brackets. For example, if your array name is myArray, then you can access the second element which is indexed at position 1 by using myArray bracket 1. Now let's take the previous example and imagine that you are declaring a signal that is named as int array based on your custom array based data type. So we will write signal int array colon array 0 to 3 of integer semicolon. And this statement will create a signal by name as int array, which is capable of storing 4 integer values. You can then assign the values to the specific elements like this. Int array bracket 0 gets the value of 13 semicolon. And this will assign the value 13 to the index 0 of int array. Same way, you can assign the integer value to the index 1 and index 2 and index 3 as well. Like for index 1, write int array bracket 1 gets the value of 14 semicolon. Similarly, for index 2, int array bracket 2 gets the value of 15 semicolon. Same for index 3, write int array bracket 3 gets the value of 16 semicolon. So when you will execute these statements, your index 0 of int array will have the value of 13. Similarly, index 1 of int array will have the value of 14. Same way, index 2 of the int array will get the value of 15, and index 3 of int array will have the value of 16. The image you see in the screen shows that the data is stored within an array. The 4 boxes represents the 4 elements of your array. Each box is capable of holding an integer value. The number besides each box like 0, 1, 2 and 3 are like the indexes of these elements. These indexes acts like a unique address for each element within your array. Looking at the assigned values, you can see that the element at index 0 has the value of 13, the element at index 1 has the value of 14, and so on. This demonstrates that how the array provides a structured way to store and retrieve the data. You can access any element in the array by simply specifying its index. VHDL also offers the unconstrained array, which provides the flexibility for the situation where you are not sure about the length of your array size. Unlike the fixed size array, unconstrained arrays don't have the predefined set during the data type declaration. So in such cases, the actual size is determined when you are declaring the signal based on this data type. To declare an unconstrained array data type in VHDL, you specify an array with an unspecified range. This allows you to create an array of different sizes depending on your needs. For example, you can declare a new array data type called ABC as an unconstrained array of integers. So inside the brackets, you need to use greater than and less than sign to indicate that the array index is an integer data type with an undefined range. Means this is unconstrained data type. Once you have declared the unconstrained array data type, you can simply use it to create your signals without worrying of declaring the maximum index for your project. So the question is that how the system will know that how many indexes are needed for your project. So the answer is during the signal declaration. When you are creating a signals using the ABC array data type, which is unconstrained array data type, then you must specify the number of elements in that array signal. So each signal will have its own length of this data type. Hence, when you are declaring all of your signals in your VHDL code, then the system will take the highest index as the constrained index of your array data type. Simple. And this will allows you to create the signals with the different sizes based on your requirements for your designs. Let's quickly see that how it works in practice. So we have created an unconstrained array data type named as ABC that can hold the integer values. Now imagine that you have two signals, sig1 and sig2, and both the signals uses the ABC array data type. But sig1 is declared to have the 8 elements, means index from 0 to 7, while sig2 having the 16 elements, indexed from 1 to 16. Or simply say 15 down to 0. So in this case, your array data type will have 16 indexes, which is the maximum covering of the indexes in this example. This flexibility allows us to create the arrays of different sizes as they are needed for our designs. Unconstrained arrays are particularly useful when you are needing to work with the arrays of varying length. In the next session, we will discuss on the more insights of different data types which are being used in VHDL. In the last few sessions, we have covered VHDL signals and data types. We talked about enumerated data types and also pre-supported data types in VHDL. Till now, we have covered std logic vector, integer, boolean data types, as well as enumerated and array data types. Let's quickly recall the data types which are predefined in VHDL standard package definitions, and we will also see std logic, stdu logic inside the std_logic_1164 package. So first we are talking about VHDL standard definitions. Okay, so first is bit data type, which has two values 0 and 1. Hence you can see it like type bit is 0, 1 semicolon. Second is boolean. So suppose you wanted to create similar by your own, so you can write that type boolean is false, true, semicolon. Next data type is character. So write type character is, then all the sky character inside this, semicolon. I didn't mention individual values or iterations here because ASCII has 255 characters. But if you are defining this data type, then you need to copy all the ASCII characters in this area. Another is severity label, which is generally used for the test functions to specify some warnings or note or error or failure kind of stuff. So write type severity label is, then note, warning, error, failure, semicolon. Now just quickly see std logic and stdu logic data type, which are defined inside the std underscore logic underscore 1164 package. So you will see that type std underscore u logic is, then u, x, 0, when, z, w, then l, h, dash, semicolon. Note that all the values are written inside the single quotes. We already talked about these states and enumeration in our previous videos. We also talked about std logic, which gonna be widely used in our designs. Do not confuse with the std underscore u logic and std underscore logic data type. I mentioned std underscore u logic here because std logic is just a subtype of std underscore u logic and hence having the same values. I prefer to use std underscore logic widely in our designs. VHDL subtypes are the subsets of the base data types. Additionally, you can declare subtypes in VHDL. So subtypes are usually a subset of the master data type, and that allows you to define more specific constraint of the values. And this can help make your code more readable and maintainable by providing more precise control over the data types you use. Let's understand this with some examples. So in the standard package, you will find natural subtype, which is defined as a subtype of integer data type. And the range of natural data type goes from 0 to the highest value of the integer type, which is 2 to the power 31 minus 1. The high attribute returns the highest value. So how you will declare this if you wanted the similar data type? So write subtype natural is integer range 0 to integer dash high semicolon. Similarly, you can create something like subtype positive is integer range 1 to integer high semicolon. Or even you can specify any range based on your project requirement. So now we know that how to create custom data types and sub data types. And even now we know that how predefined data types and sub data types are defined in the VHDL packages. Now we will see that how we will use them in the VHDL code. So suppose we are declaring some signals in VHDL with subtype natural and positive subtype. So how we will write them? Well, they are exactly same, like we declared the signals earlier. Even the syntax is exactly same. So write signal sig underscore natural colon natural semicolon. Next is signal sig underscore positive colon positive semicolon. You can use any signal name by your wish. Just remember the rule of identifiers. The only difference between the natural subtype values and the positive subtype values is that the natural values includes all the positive numbers up to 2 to the power 31 minus 1, including 0 value. But positive subtype does not include 0. That's it. So by now we have seen that how the predefined subdata types declared in VHDL packages and how they were defined inside the packages. Now just quickly see that how we can create our own custom subdata type and how they can be good choice for our designs. Let's understand this with some examples. So first user defined subdata type which I have written is address underscore line. This is integer and required to address 256 elements. So I have written subtype address line is integer range 0 to 255 semicolon. Another example is defining byte subdata type, which have 8 bits inside it. So write subtype my byte is std underscore logic underscore vector 7 down to 0 semicolon. Now we will use these subdata types to declare our signals, which you can see at the bottom. So signal sig underscore address colon address line semicolon. Another example signal sig underscore data colon my byte semicolon. Now you do not need to worry about your 8-bit data length and defining std underscore logic underscore vector. Just use my byte straight for 8-bit data. You can also use individual element of this data. Like if you wanted to use MSB or 7th index of your byte, then just use signal with the index ID inside the bracket. This is as simple as that. This is super cool, right? So try to prefer to use your own data types and sub data types in your projects and deliveries. They will make your VHDL codes more readable and easier to use for future. These codes are more impactful and customizable for future as well. Also, your chances of error will definitely reduce if you prefer to use these good practices, because you will encounter errors early, like something out of range values, etc. In the next session, we are going to learn more on the array data types, custom data types and their use cases. And I will tell you that how you can use these VHDL concept in your practical designs. In the previous sessions, we learned about a lot of standard VHDL data types. We talked about custom data types, which you can create specifically for your project needs. We talked about array data types, etc. Now, in this session, we will brief everything so that you can recall and summarize the learnings. This is important session because I am going to explain that how you can use these standard and custom data types and array data types effectively in your VHDL codes. That too with the help of examples. So do not skip this. First, we will see some of the standard VHDL array data types, and here are some examples which you can also see in the VHDL standard definition packages. So first we have a string array data type, which is simply a collection of characters. So write type string is array positive range less than greater than of character semicolon. Then there is Boolean vector, same like the std underscore logic underscore vector, but Boolean vector having the array of values true and false. So write type Boolean vector is array natural range less than greater than of Boolean semicolon. Then there is a bit vector type, which is a collection of bits. So write type bit vector is array natural range less than greater than of bit semicolon. Lastly, we have an integer vector data type, which is a collection of integer data. So write type integer vector is array natural range less than greater than of integer semicolon. These are standard array data types in VHDL, but we didn't specify the range of the array. Means we didn't specify the length or size of the array during this data type declaration. So you must have noticed the less than and greater than sign when declaring these arrays. This shows that the array is unconstrained, means we are not specifying the number of elements at this moment while defining those array data types. And hence we must need to specify that when we are going to declare signals using these data types. By practicing this approach of declaring your array data types, you can write better VHDL codes which are easy to use in the different situations. I hope you agree with me on this. Now we will see the signal declaration part. This is important because if you are just defining the custom data types, but if you are not using these custom data types in your VHDL projects, like you are not defining any signal with those data types, then there is no use of defining those data types because you are not using them anywhere. So look over the bottom section of this slide. We are defining some signals here. So first is signal sig underscore character array colon string 1 to 10 semicolon. So this statement will define a signal which is signal character array. This is a string and having 10 number of characters. This means you can assign 10 character data in this signal, like hello VHDL. Now, if you want to access single character of this signal, then you can also do that by specifying the index of the character. For example, signal underscore character array 1 gets the value of h semicolon. This means that the character h will be assigned to the first index of this signal. Very simple. Okay, coming to next, signal sig underscore boolean array colon boolean underscore vector 7 down to 0. I think now you may guess it that this statement will create a signal sig underscore boolean array which will have 8 boolean data and the indexes will be 7 down to 0. Same way you can assign true or false to the any of the data or index of this signal. Last one here is signal sig underscore bit array colon bit factor 15 down to 8 semicolon. So this statement will create the signal sig underscore bit array which will have 8 binary values. But you should notice here that the index range is different. It is 15 down to 8 here. This means that when you are assigning any data to its first position, then you need to use index 15 because index 15 is present at the first position of your signal. Okay, so in the last slide, we discussed the array data types based on the existing predefined standard data types like characters, booleans, and integers. Now, in this example, we are creating our own array data types, which uses custom data type and which we have created for our traffic light project. So this will be followed in 4 steps. Number 1, we will create a simple enumerated data types for our traffic light. Suppose it is named as traffic light and this data type represents 3 colors of our traffic light, which are red, yellow and green. Simple. So we will write type traffic light is red, yellow, green, semicolon. Now we have our custom data type named as traffic light. Next, we wanted to use this traffic light for 4 ways traffic signal. And for that purpose, we are needing 4 traffic lights, right? So now we are creating an array data types for those 4 traffic signals, which will use the traffic light data type, which we have created in the previous statement. So we will write type traffic light group is array natural range less than greater than of traffic light, semicolon. So if you notice here that I didn't specify the range or number of traffic lights here in this declaration so that we can use it for diversified use cases. Like maybe at some different location we can have multiple lanes and that may require more set of traffic lights. This is called unconstrained array, means we created an unconstrained array data type here for the traffic light. Now the third step, and in this step we have declared our signal for 4-way traffic light system and hence we specified the range of traffic light here, which is 1 to 4 because we are needing 4 set of traffic light here for each way. So we will write signal sig underscore 4-way TL colon traffic light group 1 to 4 semicolon. Here signal is sig underscore 4-way TL traffic light and each index belongs to one set of traffic light. Now the final step, which is the assignment of data. Obviously we declared signal to assign some specific value inside those specific signals, right? So I will say like signal underscore 4-way TL 1 to 3 gets a value of red semicolon. Signal underscore 4-way TL 4th gets a value of green semicolon. This means that the traffic signal of the real system is green for the 4th way and red for the other 3 sides. Simple. I hope that I made this concept clear to you, and I believe that you will also follow the good practices for your VHDL designs, which we have discussed in the last few sessions. These all concepts which we talked about was quite basics, but they are very important to know, because these things are the key part of your VHDL designs and you will heavily use these things in your VHDL designs. So following the good practices is very important. So by the time we have only learned that how to create a data type or array based data type, which has some set of similar data types, right? But what if we are needing some kind of mixed data type? Means inside one data type, suppose you have the data which is integer, some data is std logic vector, some is boolean, some is string, like that. Means any type of data you can have here. So how you can create such data types? Confused? No worries, because in the next session I will tell you that. In VHDL it is known as record type, and I will show you that how you can create a single data type which includes different type of data types inside one single record. In our previous sessions, we learned about the standard VHDL data types, custom data types, and array-based data types, etc. And we learned that what are the good practices and how to use those data types and their concepts effectively in our VHDL designs. However, those concepts was great for grouping the same data types, but they do not allow you to work when your project needs group of different data types. For example, some data can be integer, some can be std logic vector, some can be boolean, like that. So in VHDL, you will have record feature to work on such a specific requirement. Records in VHDL allows you to group different data types into the one single record. Let's understand this with some examples. So suppose we are designing a RAM module which is acting as a memory element in some high-level system. So first, let's figure out that what we are actually needing to design a simple RAM element, which has 8-bit data lines for reading or writing of data. It has address line and one read-write select pin. So this RAM module has 8-bit data lines. This means that we have two signals of STD logic vector 7 down to 0, one for reading the data from the memory and another is writing the data into the memory. So it can read 8-bit data from the RAM or can write 8-bit data into the RAM, and this will be controlled by the select pin. So we have another std underscore logic signal which is rw underscore select. Suppose 0 is for reading the data and 1 is for writing the data. There is one more important thing in RAM which is address. So you need to specify from which location RAM should read or write the data. So I am needing address signal as well. I defined it as an integer which is having the range of 0 to 255. Simple. Okay, so once we are done with this requirements, it's time to create the VHDL record. So for this requirement, I will write type, RAM type is record, signal, data underscore write, colon, std underscore logic underscore vector, 7 down to 0, semicolon. Next, signal, data read, colon, std underscore logic underscore vector, 7 down to 0, semicolon. Next, signal, address, colon, integer, range 0 to 255, semicolon. Signal, rw underscore select, colon, std underscore logic, semicolon. And record, semicolon. Let's quickly understand this. So first signal is for writing the 8-bit data into the memory. So this is std underscore logic underscore vector 7 down to 0. Same, the second signal is for reading the 8-bit data. So this is again std underscore logic underscore vector 7 down to 0. Address is integer type and having the range from 0 to 255. RW select signal is for selection. Either memory is being used for reading the data or it is being used for writing the data. Okay, so first of all, this is just a sample. Actual RAM would also require more pins like chip select, clock signals, etc. So you can configure whatever it is needed for your project. Okay, so we have created a record, but now the question is that how I will use it in our project. Because just creating a record will not do anything in your design until you are defining a signal and use that into your project. So after defining the VHDL record, second step is to declare a signal for your record data type. So syntax is exactly same like we did many times in the previous sessions, which is signal, signal name, colon, data type, semicolon. For example, signal, RAM, colon, RAM underscore type, semicolon. Now look at the bottom section of the slide. Here you will see that how you can use the signal for assignments. It's not that straightforward like the set of single data types which we have used in the previous sessions. Because this record data type holds 4 different types of signals inside it. So you need to specify that what signals you are currently using for assignment. Well, this is very easy to read. To access any element of your record, you need to use a dot symbol next to the signal name. For example, first is ram.data_write gets the value of x80 semicolon. Now this statement will assign hex 80 value to the data write pin of the RAM signal. Same, to access the RAM address, simply write ram.address gets the value of 14 semicolon. So the address point 14 will be selected for action. Next example is rw select. So write ram.rw select gets a value of 1 semicolon. So this signal will tell that I am going to write on the RAM. Simple, right? Now to conclude here that you must notice that there are 4 elements in this RAM type record, like read pins, write pins, address line and the RW selection pin. However, this is not mandate to use the records for all such type of requirements. As an alternate option, you can also declare those 4 elements individually by creating 4 individual signals, right? So the question is that why you should use record. Or even should you prefer records feature in the VHDL? Well, it's completely based on the preferences. However, if you are reusing this structure in your VHDL designs very frequently, then it is better choice to use the VHDL records because you declared everything which is needed in one single place. So you do not need to declare all signals every time. But if you have the requirement where you need this only once, then you can also declare individual signals inside your designs. Okay, so now it's time for a quick summary, whatever we have learned in the data types yet. So we learned standard VHDL data types like std logic vector, integer, boolean, string, and custom data types as well. We learned how to create custom data types. We learned that how to declare any type of signals. We learned that how the assignments works in VHDL. We learned about the array-based data types for grouping same set of data types. We talked about unconstrained array. We learned about the records in VHDL for grouping set of different data types. So I hope that now you have the good foundation on VHDL data types and their use cases. And in the next session, we will be talking about constant. In our previous sessions, we have covered data types, either standard and predefined or custom data types. We talked about array data types for grouping the same set of data type elements, and we also talked about the record data type for grouping the set of different data types. Now, in this short video, we are going to cover constant. We will talk about that how to use them and where to use them in your VHDL designs. So let's start. Constants in VHDL are very similar to the constant in the software programming languages like C or C++. Let's quickly see the syntax first. So write constant name, colon, type, colon equals to initial value, semicolon. For example, constant and point, colon, integer, colon equals to 256, semicolon. So this statement will create a constant which is integer type and having the fixed value of 256. Now you cannot change this constant value in your VHDL code for your design. So the endpoint is having fixed integer value of 256. Like you can use this endpoint for your counter, which count the numbers from 0 to 255. So the endpoint can be used as 256. You can use any data type, whatever is needed to declare your constant. Like it can be boolean, it can be string, it can be integer, it can be std underscore logic, or even they can be array or record data types. So you can see that the declaration of constant is very similar to the declaration of a signal. So you do not need to memorize different syntaxes to use them. Like here, the only difference is that it is started with the keyword constant because it is a constant. And because this is constant, so you are mandated to initialize this constant by giving some initialized value. Note that you cannot modify it after this in your code. And once you define a constant, that you can use it anywhere in your code. As we said earlier that the FPGA hardware does not support any initialized value when we are declaring them into the signals. But this is not true for the constants. Constants must be initialized during their declaration and will be implemented in the hardware. Well, this is because the working behavior of constant is different from the signals in VHDL. So here are some important notes about the VHDL constants. So the constant must be initialized during the declaration. Once initialized, then the constant value cannot be changed throughout the VHDL code. Once you declare the constant in your VHDL code, then you can use it anywhere in your design. You can use any data type to declare a constant in your VHDL designs. Like you can use std logic or std logic vector. You can use boolean, you can use integer, or even you can use array data types or record data types for your constant. Constant declaration is exactly same as like the signal declaration, but the constant are mandated to have the initialization. But for signal, this is optional. So you can see that use of constants can make your VHDL codes more adaptable, more agile, and more readable. And considering all these benefits, you can also see its importance. So you should also prefer to use the constant in your VHDL designs whenever you feel like it. So this was the quick short video, but still worthy and useful. And I will see you in the next session where we will talk about the VHDL operators. After data types, VHDL operators are the another important thing which you will use broadly in your VHDL designs. So deep understanding of VHDL operators are equally important. So by now we are aware of different VHDL data types, as we discussed all the standards data types and even custom data types. We talked about array-based data types and also record-based data types. Now it's time to start another important topic in VHDL, which is VHDL operator. These are super important to understand all these VHDL operators, because after data type, these are the another thing which you are going to use very widely in your VHDL designs. So you should must know that how to use them perfectly and effectively. So like every programming languages, VHDL also have set of standard operators which can be used for logical operations, arithmetic operations, Boolean equations, comparison expressions, and such like many more things within your VHDL designs. So first of all, let's see that what all type of VHDL operators we have by default. So I have listed all of them in one single screen. And also they are grouped together by different coloring based on their characteristics. So you can use this slide for your future references in your designs. Well, I have listed them in two columns. The first 7 operators in the left column are logical operators colored in yellow. Second operator is concatenation operator written in the red. It is used for joining the data or register together. It is AND symbol. Next, the operators written in white are the rotation and shift operators. Now in the right column, the green set of operators are mathematical operators and the blue set of operators are used for comparisons. You can take a quick pause here to read all of them if needed, but do not worry because we are going to cover each and every operator in details in the upcoming slides. Let's talk about the logical operators first. So in this slide, we are seeing the VHDL logical operators. So VHDL offers 7 predefined logical operators, and these are AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate, and XNOR gate. I am assuming that you are already aware about the functions of these operators, like what AND gate do, or what OR gate do, or what NOT gate do likewise. So I'm not going deeper here, but if you feel any difficulty, then let me know. I will cover that in the separate session. Okay, so now let's see that where you can use these logical operators in VHDL. Note that we will need to declare VHDL package std_logic_1164 to use these operators in VHDL. So first you can use them with bit data type or bit vector data type, which supports 0 and 1 value. And you can also use these operators with std logic and std logic vector data type. You can use them with Boolean, but the most important is that they would be widely used with the logical conditioning. We will see that with the example in the upcoming slide. Okay, so let's look over to the first example. C gets the value of A and B semicolon. So this statement will perform the AND operation on the std logic type signals A and B, and the result will be assigned to signal C. Another example, Y gets the value of not of X semicolon. So this statement will inverse the value of signal X and will move the output to the signal Y. Note that these X and Y signals are Boolean data type. Now let's quickly see that how you can use those operators with the logical conditioning. So I have written if sig A equals to 1010 and enable equals to true, then some action to do when the condition matches, and if semicolon. So this statement will check both the condition, and it will execute the statements only when if the signal A has the value 1010 and enable signal is also true. So you have seen that when both the condition required to be true, we uses AND operation. If my requirement has that the statement should be executed when any of the condition matches, then we would use the OR operation. Likewise, you can use any other operations too. Do not worry if this is not 100% clear at the moment, because we are going to have lot of work on these operations in this series. So these are going to be practiced many times and you will learn them by doing. Now let's cover one more example. So this is the example of assignment operation with the logical operators. So we have 3 signals here, which are signal A, signal B, and signal D out. Note that all these 3 signals are std logic vector 3 down to 0. This means that each signal has 4-bit data inside it. Okay, so we have written the expression that D out gets the value of A and B semicolon. Now because all these three signals having the same data type and having the same length, hence this is absolutely correct. Remember, I said that for assignment, this is mandated to match the data type and its length if the data type is array type. So this single statement will give you the exactly same results like when you are doing the logical AND operation for the individual bit of these signals. Means if you write it 4 times for individual bit like dout 3 gets the value of A3 and B3 semicolon, dout 2 gets the value of A2 and B2 semicolon, dout 1 gets the value of A1 and B1 semicolon, dout 0 gets the value of A0 and B0 semicolon. So both the statements doing the same job here. So quick recap. So we talked about the logical operators in VHDL. We know that VHDL has AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate and XNOR gate pre-supported logical operators. These are crucial for logical operations between the signal assignments and logical conditionings. We've seen one example of how these operators works with the array data types as well. In the next session, we will demonstrate the comparison operators. In the last session, we were talking about the logical operators. Now, in this session, we are going to explore the comparison operators in VHDL. So let's start. So you can see all the comparison operators listed here, which are supported by VHDL, and the respective symbols to use those operators are also listed here. Do not confuse with the comparison operators supported by the other programming languages, as they are little different in symbols. So you need to remember these symbols to use them in VHDL. So first is equal to, and the symbol is one single equal sign. Another is not equals to, and the symbol is slash followed by the equal sign. Next is greater than equals to, hence the symbol is greater than sign follows by the equal sign. Next is less than equals to, hence the symbol is less than sign follows by the equal sign. Next is greater than and the symbol is greater sign. Last one is less than and the symbol is less than sign. This is very straightforward. Now let's understand some of the basics of VHDL comparison operators. So the comparison operators are used to compare two signals. You must remember that the data type of the signals which you are comparing must be exactly same. If these are array data type, then their length also must match. The result of the comparison is always a boolean, means either the condition will be true or it will be false. To use these comparison operators, you must declare std_logic_1164 package in your VHDL designs. Some of the examples you can think of, like if A equals to B, then execute some statements, and if semicolon. So here signal A and signal B can have any data type, like they can be integer, they can be std logic, or they can be vector, or they can be string, anything. But whatever it is, they both must be of same data type. And the output of this condition will be boolean, means either this condition will be true or it can be false, right? Similarly, you can compare like if x is greater than y, then execute some statements and if. You can also compare the signals with the assignment operators. For example, look over the first case. Signal y gets the value of x greater than 1010 semicolon. So here signal y must be boolean data type, as it will get either true or false based on the value of signal x. Signal x, maybe you already guessed that it is 4-bit std_logic_vector. Hence you will get true whenever the value of signal x is 1010, else you will get false in signal y. Look over the second example. You can also use comparison operator with some values. Like we have written, if int signal is less than 31, then execute some statement and if. Now with this statement, your expression will execute whenever the value of int signal will be less than hard-coded value 31. And for rest of the time, condition will not met. Hence the expressions will not execute. In this case here, that int signal must be integer data type. These operators are essential in VHDL designs, and we are going to use them frequently in our FPGA designs in the practical sessions. So do not worry if these are not 100% clear at the moment. Just understand the basic concept here, and we will practice them in the later sessions. In the next session, we will be going to cover shift operators and rotate operators in VHDL. These are essential for the std underscore logic underscore vector and bit vector type of signals, which are useful for shift registers kind of applications. In the last session, we talked about the comparison operators. Now, in this session, we will be talking about shift operators and rotate operators in VHDL. Let's quickly see that what shift operators and rotate operators are defined in VHDL and how these are declared in VHDL. In the screen, you will see four operators. First two are shift operators and bottom two are rotate operators. First is SLL. This is shift left logical. Means this operator will shift the array data to the left by the specified number, and it will add 0 in the shifted index from the right. We will be talking about that number in some time. Second is SRL. This is shift right logical. Means this operator will shift the array data to the right by the specified number, and it will add 0 in the shifted index from the left. Third is ROL. This is rotate left. Means this operator will shift the array data to the left, and this will also move the shifted data to the right indexes. Means the values of shifted index, they will move at the right index. Fourth is ROR. This is rotate right, and this is reverse of ROL. Means this operator will shift the array data to the right, and this will also move the shifted data to the left indexes. Means the value of the shifted indexes, they will move at the right indexes. Do not confuse, we will be talking about that in details in some time. These standard shift and rotate operators are defined in std underscore logic underscore 1164 package. Hence, you need to use std underscore logic underscore 1164 package in your VHDL designs. These shift and rotate logical operators majorly being used with the std underscore logic underscore vector and bit vector data types. You are going to use them widely for the shift registers type of use cases. So let's quickly see that how these functions. First, we will talk about the shift operators. So take an example of shift left logical SLL. At the first step, this operator will shift the array data to the left, and then it will add zeros in the right indexes, which are shifted. So first, the data will shift to the left by some specified indexes, and then zeros will be added at the right indexes. SRL is just the reverse of it. Means the array data will be shifted to the right and the zeros will be added to the left shifted indexes. In case of rotate array like ROL, still there are two steps. Number one, that the array data will be shifted to its left indexes. And then at the second step, instead of pushing the hard code is 0 in the right, simply the shifted index will take the position of the rightmost indexes. One important note that you can also specify that how many indexes required to be shifted. You give this number in the operator statement. So for each index, this cycle will repeat itself. Means if you shift or rotate one array by two indexes, then it will execute in two loops of 2. Means at the first cycle, the first index will be shifted and then the another cycle of shifting will be performed. Let's understand shift left logical SLL in details with some use cases. So in this example, we have two signals declared, signal A and signal B. Both of these signals are 4-bit std underscore logic data type, and sig A is initialized with 1011 value. And we will assign the data in the signal B after shifting the signal A data. Okay, so these two signals are signal sig A colon std underscore logic underscore vector 3 down to 0 colon equals to 1011 semicolon. Signal sig B colon std underscore logic underscore vector 3 down to 0 semicolon. Now we write the statement that signal B gets the value of sig A SLL 1 semicolon. So as I said that you can specify that how many times your data will shift in the array. So here this 1 specifies that. means in this statement, data will be shifted by one index to the left. So sig E is initialized with 1011. So step 1 is shifting this data to the left by one index. So look in the step 1. Here we have shifted 1011 by one index to the left. So the bit 3 or index 3 is out from this range now. And now the index 3 is replaced by the index 2. Same index 2 is replaced by index 1 and index 1 is replaced by index 0. But index 0 is left blank at the moment. So as we discussed in the last slide that the right indexes will be replaced by the hard-coded value 0. Hence index 0 will be 0. So you will see the value 0, 1, 1, 0 after this expression. And we are assigning this value to the signal B. So sig B would be 0, 1, 1, 0 in this example. So you see that value 1011 becomes 0, 1, 1, 0. When you used SLL operator for the one iteration. First three indexes you received from the shifting of signal E data, so you get 0, 1, 1 and last index is replaced by 0 and hence you get 0, 1, 1, 0 as an output. I hope I made this clear to you. If you are still a little confused, then let's look for the another example in the next slide. Now let's look over this one more example. This time we are shifting our data to the right by two indexes. So we will use SRL operator. So let's see how it returns the output. So signals are again same here, signal A and signal B, and signal A is initialized with 1011 value. So write signal sig A colon std underscore logic underscore vector 3 down to 0 colon equals to 1011 semicolon. Signal sig B colon std underscore logic underscore vector 3 down to 0 semicolon. Now the expression is signal B gets the value of signal A SRL 2 semicolon. Now this expression is telling that shift the signal A data to the right by two indexes. Okay, so let's see that how it happens. We will understand it in two cycles. So first cycle will shift signal A data to the right by one index and then the second cycle will shift the data by second index. Okay, so the first cycle that shift the data to the right by one index. So 1011 will become dash 101. Now cycle 2, this will again shift the data by one more index. So dash 101 will become dash dash 10. Now replace dash dash of the left indexes with 0. So dash dash 10 will become 0010. And now this value will be assigned to signal B. Hence we shifted 1011 to the right by two indexes and we get the result 0010. Last two values of signal B, that is 1, 1 from the first and 0 indexes are shifted out and index 2 become index 0 and index 3 becomes index 1. So 1011 becomes 0010. Now this slide displays you the inputs and outputs of both the last examples we discussed. So signals sig A and sig B are common for both the examples and signal A is initialized by 1011 value. So quickly recall, first example, signal B gets a value of sig A SLL 1 semicolon, which is shifting signal A data to the left by one index and then it will assign the data to the signal B. So 1011 becomes 0110. So signal A is 1011 here and signal B will be 0110 here. How? Because the leftmost bit, which is at index 3 and it is 1 here, that is shifted by one index and becomes the fourth index. And hence this is out of this index window. And the remaining 3 bits, which is 110, shifted to the left by one index. So index 3 is replaced by index 2. Same index 2 is replaced by index 1 and index 1 is replaced by index 0 and index 0 is replaced by the hard-coded value 0. So the 1011 becomes 0110. If this is clear, then let's move to the second example. So signal B gets a value of signal A SRL 2 semicolon. Now this statement is shifting signal A data to the right by the 2 indexes. Now I am not going in deep much here because I hope that you can relate it very easily. Simply that the 2 bits from the rightmost data is out because they are shifted to the right, hence out of specified index window. So 11 from the last are shifted out and 1011 becomes dash dash 10. Now this dash dash replaced by 00 and you will get the value 0010. Now this 0010 value will be assigned to the signal B. So finally signal A will be 1011, which was initialized value, and signal B would be 0010 after shifting the 2 bits to the right. Simple. Okay, now if the previous two concept is clear to you, then this will be easy to understand for you. We are now rotating signal A to the left by 1 index in this example. So we will be using the ROL operator here. So example is same here. We have two signals, sig A and sig B. Both the signals are 4-bit std_logic data type and signal A is initialized with 1011 value. Now we are using the expression that signal B gets the value of signal A ROL 1 semicolon. So this will rotate the signal A data to the left by 1 index. Okay, so let's see that how it functions. It happens in 2 steps. Step 1 is same, that shift the data to the left by 1 index. So 1011 becomes 011 dash, right? So here the first bit, which is 1, is out from the index range and dash is added in the rightmost index. So now here is the tweak at the second step. When we were using the shift operators, then this dash was replaced by the hard-coded value 0, right? But here, when we are rotating the data, then instead 0, it will be replaced by the shifted values. So you can see this is 1 in our example. So dash will be replaced by 1 here. This means your index 0 will be replaced by the index 3. Let's say in steps that what is happening with the data. So signal A is 1011. Now shift this data to the left by 1 index and you will get 011 dash, right? Now replace the data with the shifted value, which is 1, and you will get 0111. And finally this data will be assigned to the signal B. So signal A is 1011 here, which is initialized, and signal B will be 0111 in this example. Now this is the example of ROR, rotate right operator. This is same like ROL, rotate left, but instead rotating the value to the left, ROR will shift and rotate the data to the right. Let's understand this with the same example. So we have two signals, sig A and sig B. Both the signals are 4-bit std_logic type and sig A is initialized with 1011 value. Now the expression is sig B gets the value of sig A ROR 2 semicolon. This is rotating 1011 to the right by 2 indexes. Again, we will be doing it in 2 cycles. So the first cycle will rotate 1 bit and the another cycle will rotate the second bit. So the first cycle, that's shifting 1011 to the right by 1 index. So 1011 becomes dash 101. Now dash will be replaced by 1, which was the shifted bit of index 0. So after rotating this first cycle, that 1011 will becomes 1101, right? Now its second cycle, so 1101 will shift to the right by 1 index. So 1101 becomes dash 110, and now replace this dash with the shifted value, which is again 1. So dash 110 becomes 1110. And now this 1110 will be assigned to the signal B. So signal A will be 1011, which is initialized data, and signal B will be 1110 after rotating the signal A to the right by 2 indexes. I hope I made these concepts clear to you. Let's quickly recall both the examples. So signals are same for both the cases. We have two signals, sig A and sig B. Both the signals are 4-bit std_logic type and sig A is initialized with 1011 value. So the first example is sig B gets the value of sig A ROL 1 semicolon. This is rotating signal A data to the left by one index. So at first step, 1011 becomes 011 dash, and then dash is replaced by value 1, which is shifted out from 1011. So 1011 becomes 0111. Means if signal A is 1011, then signal B will be 0111. Now coming to the second example, signal B gets the value of signal A ROR 2 semicolon. This is rotating signal A data to the right by two indexes. So in the first cycle, 1011 will become dash 101, and then dash will be replaced by shifted data, means dash will be replaced by 1 here. So 1011 becomes 1101. Now the second cycle, so 1101 will become dash 110. Now replace dash by 1, which is the shifted data. So 1101 will become 1110, and this will be assigned to the signal B. Means in this statement, if signal A will be 1011, then signal B will be 1110. This was quite a big video, but I hope that you have the good understanding of shift and rotate operators in VHDL. In the next session, we will be talking about arithmetic operators, which are one of the widely used operators in VHDL designs. In the last session, we had a lot of explanation on the shift and rotate operators in VHDL. Now, in this session, we will be talking about one of the most widely used operator in VHDL. These are arithmetic operators. There are 8 basic arithmetic operators in VHDL, which are very straightforward. First is addition, and symbol is plus sign. This will be used to add two numbers, and it will also indicate a positive value as well. Second is subtraction, and symbol is minus sign. This will subtract one number from the another number, and it also denotes a negative value as well. Third is multiplication, and symbol is star symbol. This will multiply two numbers. Fourth is division, and symbol is slash sign. This will divide one number by the another number. Fifth is modulus, and the operator is MOD, mod. Sixth is remainder, and the operator is REM, rem. This will find the remainder of the division of one number by the another number. Seventh is exponential, and the symbol is double star sign. This will raise a number to the power of the another. Lastly, the eighth one is the absolute value, and the symbol is ABS, abs. This will return the absolute value of any number, which is the number without its sign. Arithmetic operators are defined in the numeric_std package in VHDL. Hence, to use these arithmetic operators, please ensure that you declare the numeric_std package at the beginning of your VHDL code. This declaration will allow you to perform the arithmetic operations on the signed or unsigned values or the integer data types in your VHDL codes. Now let's see some examples of the arithmetic operators. So first example is addition. So sig C gets the value of sig A plus sig B, semicolon. In this example, signal C is assigned the sum of signal A and signal B. All these three signals are defined as bit std_logic_vector of the same length. Note that all the signals must have the same length to avoid any compilation error. Second example is subtraction. So sig W gets the value of sig X minus sig Y, semicolon. Here we consider that all these three signals, which are signal W, signal X and signal Y, are integer data type. And sig W will be assigned the value after subtracting sig Y from the sig X. Now look for the third example. This is sig D gets the value of 2 star star 4 semicolon. Here sig D is integer type and it will get the value of 2 to the power 4. Last fourth example is sig W gets the value of sig X RAM 5 semicolon. Here sig W and sig X are integer data type. So in all four examples, you must notice that we highly focused on the data type, because if you do not follow the right VHDL guidelines to use the same data type while using these operators, then you are tend to get the compilation error in your code. Hence, this is super important to remember while using them. This is the basic fundamental of the arithmetic operators in VHDL. This is just a simple concept, so I think these are sufficient examples to understand these. You just need to remember these arithmetic operators and their symbols to use them in your VHDL codes. So just make a copy of them. Another important thing is that you must follow the thumb rule, that the data types and its length should be same to use these arithmetic operators. You can use any of these VHDL arithmetic operators in your design based on your project needs. This is quite a short video, and in the next session, we will be talking about the concatenation operator, which is very useful for vector or array data types in VHDL. In the last session, we talked about the VHDL arithmetic operators, and we learned that how to use them in VHDL. Now, in this session, we will understand the concatenation operator, and we will see that how this is important for vector and array data types. So let's start. First, we will see its symbol in VHDL. It is and sign. In the US keyboard, it is Shift plus 7 key. In VHDL, this is concatenation operator, and this will allows you to create a large array from two or more smaller array or elements. Physically, you can think of concatenation as merging two datasets to create a larger one. Simple. You can use this operator with the std_logic_vector data type or bit vector data types. And you can also use this with signed and unsigned data. But make sure that the assigner and the assignee both should have the same data elements to use this operator. If they are not same, then you may see the compilation error. So make a note of that. You will need to use std_logic_1164 package to use the concatenation operator in VHDL. Let's understand this in details with some examples. So here you see some examples. First, we have declared 4 signals. All 4 signals are std_logic_vector type, but having the different length. Like signal A has 4 bits, signal B also has 4 bits. These two signals, like signal A and signal B, are assigned with some initial value. And these are 1011 for signal A and 0110 for signal B. We also have signal C, which has 6-bit data, and signal T, which has 8-bit data. So I will quickly read this declaration here. So I have written that signal A colon std_logic_vector 3 down to 0 colon equals to 1011 semicolon. Signal B colon std_logic_vector 3 down to 0 colon equals to 0110 semicolon. Signal C colon std_logic_vector 5 down to 0 semicolon. Signal D std_logic_vector 7 down to 0 semicolon, right? And now we have 3 examples. In the first statement, C gets the value of 0 and signal A and 0 semicolon. Remember the value of signal A, this is 1011. So we have first concatenated 0 with signal A, so it becomes 0 1011. And now we again concatenated this value with 0 in the last. So the final value will become 0, then 1011, then 0. So the final value is 010110 will be assigned to signal C. Now the most important thing is that A has 4 bits and we added 1 bit in the start and 1 bit in the last. So it becomes 6-bit data. Hence, the target signal must have std_logic_vector data type with the length of 6 bits. Like here, our signal C is 6-bit in length. In case it is not matched with the 6-bit length, then this statement will give you the compilation error. Let's look for the another example. So C gets the value of 1, concatenation A, concatenation B, 0, semicolon. So let's decode this statement. So here C is 6-bit std_logic data. We added hard-coded 1 at the very start. Then we added signal A, which is the 4-bit data. And in the last, we added B, 0. This is 1-bit data of signal B at the 0 index. Hence, the final output would be 1, then signal A data, which is 1 0 1 1, and in the last B 0, which is 0. So the output will be 1 1 0 1 1 0. Now the last example, this looks very straight. So D gets the value of E and P semicolon. This AND is concatenation operator. So we concatenated signal E and signal B. And because both of these signals are 4-bit long, so we will have the total 8-bit data. This means that signal D must be 8-bit in length. So you can see that we declared signal D as 7 down to 0, and this is 8-bit in length. So we first added signal A data, which is 1011, and then it is merged with signal B data, which is 0110. So the output will be 1011 0110. So this value will be assigned to signal D. Okay, so by now we have discussed all these listed operators here supported by VHDL. We covered multiple examples and demos to understand them and their functions. And now we know that how to use them as well. But still, we need to use them very carefully, especially when you are writing the statements by combining multiple operators in the single statement. In such cases, VHDL follows the operator's precedence to perform the actions. And if you do not follow the right precedence level, then you may not get the expected output. Hence, in the next session, we will be covering operators precedence in VHDL. So don't miss out the next session, because I will also tell you the best practices when you need to use multiple operators in one single statement so that you get the right results for your designs every time. In the last few sessions, we covered all these operators in VHDL, and we've seen a lot of examples to understand how and where to use these operators. We discussed that what are the restrictions and what are the good practices while using them. We also talked about the common mistakes and how to avoid them in the general practices. Now, this session is important to understand, especially when you need to use multiple operators in one single expression or statement. Because when you are using more than one operators, then VHDL follows the operator's precedence to perform the action. And if you are not aware about this VHDL precedence, then you may not get the right results. So keep this in mind. So the first question is that what is this precedence all about? In simple, when you are using two or more different operators in VHDL, then all the operators having some precedences, and they perform the action based on what operator having the higher precedence or higher priority, you can say. Let's understand this with one simple example. So you have the expression that D out gets the value of E and B or C, semicolon. So how you will read this? First option is that when signal E and signal B doing the logical AND first, and then the result will be logical OR with signal C. But you can also read it as second probability. I mean, signal B and signal C will perform the logical OR operation first, and then the result of this will be logically AND with signal A. So, which one is correct? This is one question, but the important question is that how you wanted to get the output from this expression. Did you write this for option A, or did you write this for option B? Or do you think that both the options will give you the same output all the time? Well, the straightforward answer of this is no. You won't get the same output if you execute them in those two different ways. Next question, that how VHDL or tool will perform the action then. So as I said, the operator with the higher precedence will execute first, and then the second operator with the lower precedence will execute. Unfortunately, here AND gate operator and OR gate operator having the same precedence in VHDL. Hence, VHDL will not allow you to execute this, and you would be getting compilation error here. Because VHDL do not know what to execute first until you tell the tool that what need to be executed first. So, how you will tell the tool that what should be performed first? Simply by using the brackets. If you need E and B and then OR C, then use the bracket with signal E and B like in this example. And if you need the OR operation first between signal B and C, then use the bracket with signal B or C. Simple. So the conclusion is that you should try to use brackets as much as possible when you are dealing with two or more different operators to avoid any such confusions and errors. Well, this is very street problem because VHDL has the same precedence in this example. So the compiler gave you the error and you corrected it, right? But consider the scenario when you use two operators of different precedences, and in this case, VHDL or tool will not give you any error. VHDL and tool will execute the statements, but the problem would be that your output or result may not match with the expected results if you did not use them carefully in your expressions. And now we will be discussing that in the next slide. But before this, let's quickly see the precedence level in VHDL for commonly used operators. You can see this list for the reference while using two or more different operators in your VHDL codes. However, you do not need to remember this precedence if you are using the brackets in your expressions, because this precedence will only be taken by the tool when you do not specify that. If you are telling this to the tool in your VHDL code, then it will always follow your instructions. So absolute operator, not operator, and exponential operator having the highest precedence in VHDL. Second is mode, remainder, multiplication, and division. Then third is plus or minus sign. Then fourth is plus or minus arithmetic operations and concatenation operator. Then fifth is shift and rotational operators like SLL, SRL, ROL, and ROR. And last is logical operators like AND gate, OR gate, NOT gate, NAND gate, NOR gate, XOR gate, and XNOR gate. Remember that operators listed in the same label having the same precedence label. Hence, if you are using them in one single expression, then VHDL and tool will be confused that what need to be executed first. So when you are using them, you must need to use brackets, as we seen in the last slide. Now take this example when your operator precedence label is different in your expressions. Let's take these three examples. Now you also know the precedence label of these operators as well. So you can evaluate these three expressions, that if you execute them in VHDL, then how VHDL or tool will perform the action. Take a small pause here and think of that. And let me know in the comment section if you did it correctly. If not, then this is fine too, because in our projects, we always try to follow the best practices. Okay, so it's time to reveal that. First expression is signal x gets the value of 2 multiplication 3 plus 10 semicolon. And this expression will be evaluated as multiplication will happen first and then 10 will be added in the output. Second example, signal y gets a value of a ROR 2 plus 4. So here the addition will happen first and the VHDL execution will be a ROR 6. So we have added 4 plus 2. Third example, signal z gets the value of minus a multiplication. So signal g gets a value of minus a multiplication with b. So here the multiplication will happen first and the sign will change after that. Okay, so I hope that I made this concept clear to you, and with this we are closing this chapter of VHDL operators. In the next session, we will be talking about VHDL structure, which is the base fundamental of VHDL and FPGA programming. So by now, we have covered the FPGA fundamentals in the initial sessions. Then we learned about the signals and data types and constant. And we also talked about the VHDL operators, which are the core basics to start with. So we know that how to write them and how to use them, but still we do not know that where to write them, right? So in this session, we are talking about the VHDL structure, like what are the VHDL modules, what is entity, and what is architecture all about. These are essential for all of your VHDL programs from very small to the big systems. But before this, my question is that what we are going to do with VHDL? What is our goal? So the goal is that we are designing a digital system like a digital chip which can perform some specific task, right? So assume that this box is actually a chip. So if you've seen any integrated circuit, then what physical thing do you see in it? Pins, actually lot of pins. Some are power pins, some are input pins, some are output pins, like that, right? So before we design our digital system in VHDL, first we design our chip body, okay? So we tell that what would be our input pins, what would be our output pins, etc. So when we are defining the outer body of our designs, we define them inside the entity block. So suppose this is our integrated chip and this is for logical AND gate, simple. First, give it a name, AND gate. Now we are needing input and output signals. So define them. So I have two inputs which are A and B, and I have one output which is D out. Okay. Note that we do not specify the power or ground pin in VHDL. So do not confuse. So this is our graphical view, but we are using VHDL, which is a programming language. So you need to write the text or VHDL code for this definition of AND gate. And this will save in the text file, which have the file extension as .vhd. You can use any editor to write this code, like you can use it from the tools itself, or you can simply use Notepad++, which is free. We will come to this later. Okay, so let's see that how we will define this in VHDL. So what I said that in VHDL, we call this entity. So write entity. Now give the name of your IC. So what is the IC name? IC name is AND gate. So write it AND gate. Now write is, this is the keyword. Now next line, and we will write port and bracket start. Now here we will define all the input and output signals of our design. So write A colon. Now tell the direction. So A is input type. So for input, we write in, then space. Now write data type. Suppose this is std_logic type. So write std_logic and semicolon. Now second pin, same, that B colon in std_logic semicolon. Now D out colon. Now this is output pin, right? So for this we write out. So D out colon out std_logic. Okay, so now we have defined all three input and output signals of AND gate. So close this bracket and use semicolon. So here we have the important note that remember this common mistake that when you define your last port of your entity, first you need to close the bracket and then use semicolon. This indicates that the port declaration has been done now. This is very common mistake happens in starting. So just make a note of it. And in the last, write AND entity and semicolon. Okay, so we define our IC outer body. We tell the tool that we are designing AND gate IC and it has two inputs and one output. And all the signals are std_logic type. That's it. But we didn't define that how this IC will work, how the data will flow from input to the output. Because till now we have just defined the blank pins. So we define all the functional things inside the architecture body. So in general, assume this that entity tells the outer layout of your IC, like IC name, input pins, output pins, etc. And architecture tells that how your design will work. So coming to the architecture declaration, this is our high level VHDL structure. So here we have our VHDL module. The file name of this module is andgate.vsd. .vsd is the file extension of VHDL file. This VHDL file will have the entity block and the architecture block. We already talked about entity and we already seen that how we declare the entity for the VHDL modules. Now let's write the architecture for the same module. So the architecture starts with the keyword architecture followed by the architecture name, then write of followed by entity name and then write is. Now the next line is begin. Then you can write your statements here to design your model. And in the last write and architecture semicolon. This statement tells that now the architecture of your design is ended. So this is called your architecture body. And here we are designing a simple AND gate. So I have written that D out gets the value of A and B semicolon. And that's it. You have just completed your first VHDL design. Simple, right? Well, we will combine everything in some time to get this worked in practice. This was just to make you familiar with the VHDL designing. This is very important before we move to the practical sessions. So let's recall everything what we have learned on the VHDL structure session. First, you use VHDL editor to write your VHDL codes. You can use any editor like Notepad++, etc. to program your VHDL design as well. VHDL file saves with the file extension .vsd. A basic VHDL design includes the entity declaration and architecture declaration. You need to define entity name and port declaration in the entity block of your design. Ports include all the input and output signals of your modules. Architecture block used for circuit declaration, where you define that how your design will function. You can also declare signals in your architecture block. Architecture block normally process the statements concurrently. However, there are some special steps by which you can execute your statements sequentially. In VHDL, these statements written inside the process block. This is just a high level. We are not going in deep at this moment so that you won't confuse with the VHDL items. If you understand this basic VHDL structure, then let's quickly see the VHDL code for our AND gate design in the next slide. Okay, so this is our VHDL code. At the top, we have the entity block, and in the bottom section, we have architecture block. So I will quickly read the entity block. So entity AND gate is port A colon in std underscore logic semicolon B colon in std underscore logic semicolon D out colon out std underscore logic, now bracket closed and then semicolon and entity semicolon. Okay, so a quick brief here. So AND gate is our entity name and it has three ports A, B and D out. All these three ports are std underscore logic type. However, A and B are input ports, but D out is the output port. Next, coming to the architecture block. So I will read it thoroughly first. So architecture behave of AND gate is begin. D out gets the value of A and B semicolon and architecture semicolon. So behave is our architecture name here. AND gate is the entity name for which we are writing our VHDL design, and we are executing the statement that D out gets a value of A and B. We already talked about the assignment operator in our previous sessions. So this is very straight statement using the assignment operator and logical AND operator. In the next session, we will be talking about the general syntaxes and other important functions and declarations. In the last session, we had some high-level overview of VHDL structure. Now, in this session, we will cover this in more details with little more complex designs. We will also see the general syntaxes to write any VHDL design. So let's start. In the last session, we learned that the VHDL file has two major components, entity block and architecture block. Let's look at each of these components in details. So first is entity block. The entity block specifies the name of your entity, which represents our circuits. It also lists all the input and output ports of the circuit, which allows the data to flow in and out of the circuit. Now the entity block syntax. The entity block is defined using this syntax. Entity name is port bracket start, port name colon direction data type semicolon. In the last, bracket closed for the port and then semicolon, and in the last, and entity name. So here the first line is entity name is, so this declares the start of the entity block with the entity name. Now the second line is port, and this keyword specifies that this is the start of port declaration, which specifies the list of ports of your circuits. So next section is for ports. So port name colon then direction, then data type, and then semicolon. So this declares the port with its name and its direction, which can be in or out, and the data type. And in the last, and entity name, semicolon. So this is the end of entity block. Now coming to the architecture block. So the architecture block contains the actual description of your circuits. Within the architecture block, we can declare and use our signals as per our needs. The architecture block is the section where we write the code to describe our circuit behavior using VHDL. Now let's see the architecture block syntax. So I will read this first. Architecture name of entity name is, then signal name colon data type semicolon, begin, then number of concurrent statements, then AND architecture, architecture name, semicolon. Okay, so let's decode this. So architecture name of entity name is, so this line declares the start of the architecture block with the architecture name and the associated entity name. Now there is a section between this line and the begin keyword. You can use this section for some other type of declarations, for example, signal declaration. This is completely optional and you will use this section based on your project needs. For example, here we have written the syntax of the signal declaration. So it is signal, signal name, colon, data type, semicolon. This will declare the internal signals. Note that anything which you have declared here in this signal declaration and whatever which you have defined in the port declaration in the entity section, all the signals will be available for use in the architecture body. Now the next line, which is keyword begin. So this specifies that all the declaration in the above section has been completed, and now from here we are writing our circuit behavior. This we call architecture body. And the last statement is end architecture name, semicolon. So this tells that now this is the end of architecture block. Okay, so this is the high level view of our VHDL designs. There are a couple of things which you must remember. Number one, that in the architecture body, every statement you write that executes concurrently. Means all the statements in the architecture body are concurrent statements. You cannot write any sequential statement here in this section directly. To write the sequential statements in your designs, you must need to use process block. Anything you write inside the process blocks, that will execute sequentially. You can write multiple processes in your architecture body, so there is no limitation on that. But although all the statements inside the process blocks execute sequentially, but all the process blocks inside your architecture will still execute concurrently. And this is very important to remember when you are using more than one process block in your designs. Number two is that you can declare any number of signals inside the architecture block. There is no limitation to that. You must need to declare all the signals between the architecture start and begin keywords. Number three, that entity block tells you about the input and output ports of your VHDL design. So you declare all the input and output ports of your IC here. Number four, that all the signals which you declare in the architecture block and all the ports which you declare in the entity block will be available to use in your architecture body. You can use all of them there. Now signals in VHDL, so you can simply relate it with the wires, which are not input or output of your IC, but they are just internally connecting your elements with each other. Do not worry, we will be talking about that in some time. Number five, that VHDL file saves with the file extension .vsd, and you can use any editor for your VHDL coding. Congratulations, you learned the very basics of VHDL, which is needed to start your first VHDL design. So it's time to design the first simple circuit in VHDL and write full end-to-end program for this. So this is the structure which we are designing here. I hope now you can relate that the entity name would be my design. This entity will have 4 ports. Out of these, A, B, and C would be our input ports and D out would be our output port. This means that we have everything for our entity section, right? Now architecture block. So we can see that there is signal X which are connecting AND gate output to the OR gate input. We can also see that there is an AND gate which is connected with the input A and input B. The output of this AND gate going to the input of OR gate through the internal wire called as signal X. Also, input C is also connected with the second input of the OR gate. Now the output of the OR gate is our final output D out. So now we know everything about the architecture as well. So let's create a VHDL code then. Okay, so this is our real VHDL code for this design, which you can use in your simulation tool and synthesis tool. We will also do this in our practical sessions as well. So let me read this first and then we will decode this. So library IEEE semicolon use IEEE.std_logic_1164.all semicolon. Entity my design is port A:(in std_logic semicolon). B colon in std underscore logic semicolon, C colon in std underscore logic semicolon, D out colon out std underscore logic. Now bracket close and then semicolon, then and entity semicolon. Architecture behave of my design is signal x colon std underscore logic semicolon, begin x gets the value of a and b semicolon, d out gets the value of c or d semicolon, and architecture semicolon. So you must notice that we have added first two lines here for which we didn't talk much, right? And these are library IEEE semicolon and use IEEE.std underscore logic underscore 1164.all semicolon. This package is mandatory to include here because if you do not add this here, your program will not execute. And the reason is in the basics, which we have learned in our previous sessions of data types. Because here we have used std underscore logic data type for our ports and internal signals. And this data type is defined inside the std underscore logic underscore 1164 package. So if you do not add this in your VHDL code, then you will not be able to use their elements in your VHDL codes. So this is mandatory one for most of your VHDL designs. So add them by default in all of your designs. But this is not the single one. We have more packages and we talked about them in our previous sessions of operators and data types. Anyway, so entity declaration is very strict. Entity name is my design. Ports are A, B, C, and D out. All are std underscore logic type. A, B, C are input ports and D out is the output port. Now notice the semicolon at the last declaration of the port list. We didn't use the semicolon at the end of D out, which is the last port list. Instead, we need to use this semicolon after closing the bracket. This only applies to the last port declaration, and this indicates that this is the end of port declaration. Remember this because this is the very common mistake happens with the beginners. Now architecture block. So we declared signal X here. So this is also std underscore logic type. Okay, so we have declared everything for our design. Now let's start the expression for our VHDL design and tell the system that how my design will work. So in the structure, we clearly see that signal X is the output of port A and port B. So write X gets the value of A and B semicolon. Next we see that the signal X and port phi connected to the OR gate input and the output is D out. So write D out gets the value of C or X semicolon. In the next session, we will be doing our very first small projects with LED and switch. Today, we will design a simple project in VHDL and then we will implement it on the FPGA board. So this will be full of practical session, but this is your first practical session, so we will keep it very simple. So what we will do that we will have one switch as an input and one LED as an output. You press the switch, then LED will on, and when you release the switch, LED will off. So this is a very simple task. The only purpose is to show you that how you code your VHDL programs in Quartus and how you implement it on FPGA boards. We will also explain some important tools inside the Quartus, which we will use in this project, like compiler, pin planner, binary files, and programmer, etc. Okay, so this is enough introduction. Let's jump straight to the Quartus Prime software and start designing this project. So first, we will open our Quartus software. So open it, Quartus. So we will open this Quartus 10.1 web edition because we are working on Cyclone 2 device. And the latest version which we have installed on our machine that is not supported that old Cyclone 2 device. So we are using this version. Now when you will open this Quartus, you will see this project wizard window. Okay, this is the startup window. So what we are creating a new project. So for that we have this button here. So this is create a new project wizard. So we will click on it. Okay. So this is the startup window. Just click on next. Now first we will create our new project and we will give our project name as well as the directory of your project. So suppose I am creating a new directory for that. So go to this and now I am creating. So click on make a new folder and give it some name. Suppose switch LED project. Okay, now I will copy it and then select it and click on OK. Now give the project name. So use that same name, switch LED project, and then click on next. Now, if you have any existing file that you wanted to use in this project, then this is the time where you can add your files in your project. For example, just select it from here from three dots and add that file into your project. Now, because we are creating a fresh project here, so we don't have any file to add. So we will leave this blank and we will click on next. Now at this page, you will select your FPGA device. For example, I am working on Cyclone 2 device, so I will select that. Now you have a couple of filters here. You can use that to find your FPGA device more easily. For example, I have this PQFP package, then pin count. So I have a device which is having 208 number of pins. So I will select it, and speed rate, that is 8 for my device. So you can see that there are 4 devices which is filtered out based on these specifications or these filters. Okay. So I need to choose my device from this list. So I have this device, that is EP2C5Q208C8. And this means that you have PQFP package that will have 208 number of pins and that is having the speed rate of 8. So C8, right? Now this is my FPGA device placed on my development board. But if you're using on some other development board, then you need to select your FPGA device. Okay. Now once you select it, now click on next button. Now if you are working on some simulation, then you can select it from here. Like we have couple of tools here, and suppose we are using Vista Simulator. So I will select it and then click on next. So this is a summary page, what you have selected during the previous step. Now just review this one and click on finish. Now once you finish it, then Quartus will create your project here. So you can see this is the project switch LED project, right? Now a quick brief about the different windows present here. So this is called Project Navigator, and all of your files will be displayed here. And in the bottom, you will see some different versions of it, like how you wanted to view it. For example, this is the hierarchy version. Do not worry, we will explain it later. But at the moment, I'm just telling you that what are these options. Files, this is the simplest version. Like this is the file folder and all of the files will be listed here. Now we are working on a fresh new project, so we don't have any files at the moment. So this is blank at the moment. Same, we have another design units. So let's move to the hierarchy, that is the best visualization, and we are going to create a new VHDL file very soon. But before that, let's look at this bottom section. So this window is our task window, and that is having many options. So you can see at the moment they are grouped together based on their specification or their jobs. For example, this is compile design, and when you expand it, then you will see there are many options here, right? So it is analysis and synthesis, where your program will check for your syntax error and will tell you if everything is good or not. So this is the first step of your compilation process, where tool will check for any syntax error in your program. Then you will have this netlist viewer, where you can see your RTL structure for your VHDL code through this RTL viewer. Next, we have design assistant, and then we have input output assignment analysis. And this includes pin planner as well, where you will tell that what pin of your FPGA device will connect to the what port of your VHDL program, right? And then we have the next step, that is fitter, place and route. Then you will see this assembler, and that will help you to create the bit file for your program. and that bin file will be programmed to your FPGA device. Next is timing analysis. Well, this is a big topic and we are not going to discuss in this session itself, but we will cover this in the later sessions. Now go little down. So you will see this verified design option that will have your floor plan and chip editor. Again, these are advanced topics, so we are not covering this in this session. Okay, so let's collapse all these things and let's create a new VHDL file for this system or for this project. So here is a button for creating a new file, or you can go to this file option or file menu and you will see this new Control N, right? So you can use anything. So I will click on this new button and then we will select VHDL file because we are writing our code in VHDL, right? So select this VHDL file and click on OK. Now this is our editor where we will write our VHDL program. Okay, so quickly write our program for a switch LED project. That is a very simple thing. So we will start from the library and package declaration. So write library IEEE use IEEE dot std underscore logic underscore 1164 dot all. Now we will write our entity. So entity, this is switch LED project is port, and this project is only having two ports. One is switch, that is input, and one is LED, and that is output. So write switch, that is input type, and this is STD logic data type. Okay, now we have LED output, so LED, that is out, and STD underscore logic bracket closed semicolon and entity, so switch LED project. Now we will write the architecture section. So write architecture behave, it's the name of architecture of entity, and it means switch LED project is now begin, and in the last and architecture. So we have created the body for our architecture, right? Now we will start writing the functioning of our system. So what is our task? So what we want that when we press the switch, the LED should on, and when we release the switch, then LED will be off. Okay. Now before writing the concept of this, I need to tell you about pull up and pull down design, because our switches are pull up type of switches. Means by default they are connected to the logical 1. Means if it is not pressed, then it will give you logical high, and when you press the switch, then it will turn to the logical low. So consider that in your mind, that when you are pressing your switch, then you are applying logical 0 to the input pin, and we are not pressing it, then you are applying logical 1 to the FPGA pin. Okay, and our LED output is very straight, means logical 1 to glow the LED and logical 0 to switch off the LED. So from this logic, what we need that when switch is equals to 0 means the LED is pressed, then LED should on. And when switch input is 1 means you have released the switch, means that is not pressed, then your LED output will be 0. So this is a simple table that you need to remember. So based on this, simply write your statement in this architecture section. So what we want LED that should be reverse of your switch, right? So we will use NOT gate. So LED gets the value of not of switch and semicolon, and that's it. This is a single line VHDL code, and the operation is very simple. When your switch input is 0, then your LED will on, means that will glow when switch is on. Okay, and when switch is off means switch value will be 1, then your LED will be 0, means it will not glow. So first we will compile our project to check if it is having any syntax error, right? So here is a button at the top. This button, this is kind of play button. So this is for compilation. So I will click on it, start compilation. So it is saying that we have not saved our project. So by default, Quartus create a new project with the name of VHDL1.VSD, and that you can see at the top here as well. So this is VHDL1.VSD, and this do not look good, right? So we should rename this by saving it. So it is asking, do you want to save your changes? I will click on yes. Now we will save it at some location. So I will choose this switch LED project. Now I always prefer to save my code in a separate folder. So instead of this default folder, I will create a new folder named as source. So SRC. So I know that every VHDL code is now saved at this location. Okay. So I will open it and I will say that save this switch LED project.vsd file in this source folder. Now click on save. We have already triggered our simulation right from here. So it has started compiling our program and then give the result. So it is saying that full compilation was successful. Now click on OK. There are a lot of messages are recorded in the bottom section. You can see here, these are the logs of what we have did or what tool has did till now, right? Just shrink this window so that we can have the better view of it. And at the top, you can see we have this switch LED project.vsd file. Okay, so you can select it from here as well. Okay, so this is the compilation report and this is your VHDL file. Okay, so now we have compiled our project and we have seen that there is no syntax error in this VHDL file. Okay, but there is one step pending, that we have not told our Quartus Prime software that where these of input output ports are connected to the FPGA pin, means where it need to be connected with the FPGA device. And same this LED output where it should be connected to the FPGA pin, right? So for that we have pin planner. Okay, so at the top you will see this pin planner option. So I will open it from here. Now this is our FPGA device, right? That we have selected. So we have selected Cyclone 2. So this is Cyclone 2 device and this is our device name. That is EP2C5Q208C8. We have selected this FPGA. Remember at the starting state of creating a project, we have selected this FPGA device, right? And this FPGA has 4 sides. So this is side A, this is side B, this is side C, and this is side D. Each side having multiple number of pins. So you can see these different symbols here. At all 4 sides of this FPGA, these are FPGA pins. Out of these pins, some are VCC, some are ground, and we have lot of many GPIO pins, means global input output pins. Now, if I zoom in this image, then you will see these pins in more details. So I will select this pan tool here. Let's go to the top. So this is our starting point. This is side A and pin start count from 1, 2, 3, 4. Like this side ends at here, like 52 number of pins at this side A. Then side B starting from 53, 54 up to 103, 104. Then side C starting from 105, 106 up to 155, 156. And this is side D starting from 157, 158 up to 208. So this FPGA device has total 208 pins. Means there are a lot of input output pins for you to use. But at the moment in this program, we are just needing 2 pins. One for the input as a switch and one for the output as an LED. Now, one important thing about the FPGA device that your FPGA device will have multiple banks and these banks are powered individually. For example, if this device or this FPGA device having total 8 number of banks, then that 8 banks will have their individual power. So some bank may be operated at 1.2 volt, some can be operated at 3.3 volt, some can be operated at 2.5 volt, like that. And that depends on the manufacturer of your board, of your FPGA board, right? So let's zoom out this view and now move to this window here. So this window having all the input output ports of your VHDL design. So for this design, we have LED as an output and we have switch as an input. And there are few fields, these are blanks at the moment. So we will fill those details now. So first we have switch, so that is input. And for my FPGA board, my switch is connected to pin number 27. So write pin underscore 27. It is very simple, just append the pin number with pin underscore. So do the same for the LED output. So write pin, then the pin number for your output. And we have connected our output with pin number 15. So write this. So switch LED is at pin number 27 and LED output is at pin number 15. Now if you notice, there is no save option for this. And that is because Quartus software automatically save this for you. Means when you change anything, then Quartus Prime will automatically save this. That is why there is no save button. Now, if you notice that when I select this pin, like pin number 15, pin number 27, then this tool has automatically filled this bank section. So these both pins, means pin number 15 and 27, they are connected to the bank number 1 in this FPGA device, right? And next thing is input output standard. So these are standard at 3.3 volt LVTTL. Now in the recent model, you can configure these voltages as well. But for this device, this is fixed to 3.3 volt LVTTL. So we can't do much. So what I have did, I have assigned LED to pin number 15. I have assigned switch to pin number 27 of this FPGA device. Now we will close this window because that has automatically saved. Now because we have changed the pin planning of the FPGA device. That means we need to recompile our design. So again, go to this button for start compilation and click on it. So you can see the compilation process has been started. You can see the bars here. Okay, so everything is good and completed successfully. Now we will program this project into the FPGA device. And for that, you will go to the programmer section and you can open it from this button here. So this is for programmer. So click on it. Okay. Now expand this little so that I can explain these things to you. So first you will see this USB blaster here. If you are not seeing this, then you can just click on this hardware setup and your USB blaster should be listed here. If you don't see any USB blaster listed here, that means your USB blaster is not properly connected with your PC. Maybe you have not connected the USB cable or might be there is some driver issue. So in that case, just update the driver and try to reconnect your USB device. And once you see it here, then just select it and click on close. So you will see this USB blaster listed here. Now this is our project file. So this is switch LED project that has been created from the last step from the Quartus Prime. Next is device section. So this is EP2C5Q208. So we have selected this device, right? So if you have not selected it correctly, then you might get error at this stage. So make sure you have correctly selected your device during the project startup step. Now this is some checksum to see if everything is good for the binary file that was created to program our FPGA device. Next is user code. So we don't have any user. So this is all one FF. But make sure that your program and configure button is ticked like here, right? And this is a progress bar. So you can monitor the progress from here, that how much section of your program has been coded into the FPGA, right? Now select the file, this switch LED project, that is our project file. And you will see this start button here. And this button will start the progress of writing your design into the FPGA device. So just click on it and start it. So once you click it, you can see this progress bar. So this is 100% successful now. Means our VHDL program has been successfully implemented onto my FPGA device. So now let's move to the FPGA board to see if our program working well or not. Means if we are pressing the switch, then our LED should glow. And if we release our switch, then our LED should off, right? Okay, so this is our LED and this is our switch. Okay, so you can see that when I'm pressing the switch, my LED is turning on. And when I'm releasing the switch, then my LED goes off. Like on, off, on, off, on, off, like that. So this works well for today's project. Okay, so I hope that this session is helpful to you, and I believe that now you are familiar with some of the important tools of Quartus Prime software, and you know that how to program your VHDL programs and FPGA devices. One important thing which I wanted to tell you that the program we have loaded into the FPGA that stores in the volatile nature means your program will only work until you power on your FPGA. Once you switch off your power from the FPGA device, your program will be wiped out from the FPGA. So you need to program it again when you power it on next time. So after power reset, if your design is not working on FPGA, then do not worry about it. Just program your FPGA again, okay? Okay, so we have covered VHDL data types, we covered VHDL operators, we talked about VHDL signals and constant. Now this is the most important concept of VHDL programming. This is process block. So by now we have learned that VHDL executes its statement concurrently or parallelly in the architecture body. But we also said that VHDL allows you to write your code in sequential mode whenever you need to execute your statements sequentially. So how this segregation will happen? How VHDL compiler will know that what statements should execute concurrently and what statements should execute sequentially? Well, this has been decided by the VHDL process block. Anything which you write inside the process block will execute sequentially. So the VHDL compiler knows that, okay, so this is written inside the process block, so execute them sequentially, and the other statements which are written outside the process block, then execute them concurrently. Simple. Okay, so let's quickly see some of the important informations first about the VHDL process block. So as I said, VHDL process block executes the statements sequentially. Next, the process blocks are being written inside the architecture body. You can write as many process blocks as you need it for your projects. There is no limitation to that. But make a note of that all the process blocks will execute concurrently. Don't be confused here, because although the statements inside the process block will execute sequentially, but all the process blocks inside the architecture body will execute concurrently. So follow the signal assignment guidelines in those such requirements. Do not worry, we will be talking about that later in the series. Next most important item is the sensitivity list in the process block. This is the key part of your process block. If you miss it to write a proper sensitivity list, then your program will not behave as same as you are expecting from it. We will be discussing that in some time as well. Note that this process block concept is one of the most important thing in your VHDL and FPGA designing journey, because this is going to be widely used in your VHDL and FPGA designs. So do not skip this. Well, let's talk about its syntax. Let me read this first and then we will decode this. So it is process name, colon, process, sensitivity list in the bracket, then there is some declarative section, then begin, then the body section, and process, semicolon. Let's decode this now. So the first line, process name, colon, process, sensitivity list. So this indicates the start of the process block with the name and a sensitivity list. The sensitivity list includes signals that trigger the process when they change. We will talk about this in some time. Process name is optional here, but as a best practice or a good practice habit, always try to specify the name of your process. This will be helpful when your program will have multiple process blocks. So if you give them some name, it will be easy to identify them in future, that what process is written for what function. Anyway, then we have the section between this process start line and the begin statement. Here you can make any declaration for your process block, like you can declare any variable here as per your needs. Note that whatever the variable you are declaring here in this section, that will be available for this process block only. These declarations will not work outside from this process block. So make a note of that. Next statement is begin. So this is the indicator that you are starting writing your sequential statements from here. Write any sequential statement, whatever is needed in this section now. So once you are done with your statements, you need to close the process block or and your process block. So the last statement is and process name. So this is the end of your process block. Now some quick notes for you in the bottom section about the sensitivity list. So sensitivity list is a list of signals which are going to be used within the process block. Process block will only run when any signal from this sensitivity list changes its state. We will be discussing this in more details in some time. But before that, let's quickly see some of the examples. So this is our example 1. I will read it first. So task 1, colon, process, sig1, begin, sig2 gets a value of sig1, semicolon, and process, semicolon. Let's decode this. So this process block name is task 1. Sig1 is written in the sensitivity list, then begin statement, and we retain our statements that sig2 gets the value of sig1, semicolon, and in the last and process, semicolon. Now because we added sig1 in the sensitivity list, so this means that this statement sig2 gets the value of sig1 will execute every time when sig1 state will change. Means whenever sig1 value will change, this process block will run. Means this statement will execute and sig2 will get the value of sig1. So this is very strict. Now let's see the another example when you are using two signals inside the process block. Okay, so we have this example of simple AND gate function. So I have written task2, colon, process, sig underscore A, sig underscore B, begin, sig C gets a value of sig A and sig B, semicolon, and process, semicolon. So the process name is task2. And in the sensitivity list, we have sig A and sig B. Both of these signals are using inside the process block for doing the AND gate operation. So we written begin and started writing our simple statement. Sig C gets the value of sig A and sig B, semicolon, and in the last AND process. Now let's talk about the sensitivity list first, and then in the next slide we will see that what will happen if you forget to write any signal in the sensitivity list and why it is important to write sensitivity list carefully. So the sensitivity list is simply a list of signals that act as an input to a process. The process block does not execute continuously. Instead, it waits for one of the signal in its sensitivity list to change their state. And when a signal in the sensitivity list changes, the process block starts to execute. And once all the statements within the process blocks are executed, the process block stops and waits again for any signal in the sensitivity list to change its state. So the key points are, number 1, triggered execution. So the process block executes only when there is a change in any signal, listed in the sensitivity list. Number 2, sequential execution. When the process block triggered, then all the statements within the process blocks will execute sequentially. Number 3 is simulation behavior. So during the simulation, in case of multiple process blocks, all the process blocks will execute once at timestamp 0. Means at the very start of the simulation, regardless of the sensitivity list. If a process block has an empty sensitivity list, then it will continuously execute in a loop, and this may cause the simulator to hang or crash. So do not leave the sensitivity list blank in any case. So this means that the sensitivity list is a crucial component of a process block in VHDL, and that need to be determined very carefully in your VHDL designs. So coming back to the example, now I hope that you can understand this very easily. So this process block will run whenever the value of sig A or sig B will change, and you will get the output, which is the AND operation of these two input sets. It is very straightforward. Now let's see that what will happen if you forget to add sig B in the sensitivity list of the same example. I have just explained you this, that what the sensitivity lists do. So give a guess that what would be the output when you don't list sig B in this example. Okay, so let's reveal this now. So here at the bottom, I'm showing you two waveforms outputs. Note that our process block here, so we did not list it sig B in the sensitivity list, but we are using sig B signal for the AND gate operation. This means that when your sig A will change, then only your process block will run and your statements will execute. But when the sig B will change, your process block will not run, and hence your statement will not execute as well. And because nothing is executing, so there would be no change in the output. And you see this in the waveforms at the bottom. See the first waveform when sig A changes. So the simulation starts when both sig A and sig B are 1, and hence the output of sig C is also 1. And when A changes to 0, the output signal C also changes to 0, because this is AND gate. So this is expected behavior, means AND gate is working fine. But now come to the second waveform. Here again the simulation starts when sig A and sig B both have value 1. Hence the output at sig C is also 1. So this is okay till here. But then the signal B changes to 0. Hence as an AND gate operation, we should see the output signal 0. But look at this waveform. We did not get the output 0 here. Even there is no changes in the output. Why? Because when signal B changes, then this process block did not run, and the statement also did not run. And hence there is no changes in the signal C output. So it is continue as its last value. And this is wrong, because we are expecting the output 0 here as an AND gate operation. Okay, so we learned about the sensitivity list in the VHDL process block, its role and how it controls the execution of the process. We also looked at an example to see the sensitivity list working in practice. We learned that why the sensitivity list is one of the most important part in writing the efficient and correct VHDL processes. So it is important to ensure that the sensitivity list is not empty. If a process block has no signal in its sensitivity list, then it will execute continuously, which can cause the simulation to hang. Always include at least one signal in the sensitivity list to avoid this issue. Always add all the signals inside the sensitivity list which are input to the process block. This must be added in your good practice habits. There is an exception to this rule, which we will discuss when we cover the suspensions in VHDL. In the last session, we talked about the process blocks. We understand that the statements inside the process block executes sequentially, and we've seen some simple examples which demonstrated that what and how you can write your sequential statements inside the process block. Now in this session, we will talk about registered process block, which uses the clock signal within the process block. This is useful when you are needing flip-flops or registers in your designs. So let's start. So first, there are some small key points which you should know about the registered process blocks. A registered process must have a clock signal in the sensitivity list. This is mandatory. Optionally, you can include a reset signal as well. It's advisable to have a reset signal here. This means that when defining a registered process, only include the clock signal and optionally the reset signal in the sensitivity list. No other signals are suggested here unless they are being used other than clock transition statements. So the registered process will always check for either the rising edge or the falling edge of the clock signal. This is used to implement flip-flop or register type of applications. We will talk about their use cases later in this series, as they are going to be widely used in many of our designs. So in short, clock signals or clock, this is the main signal that triggers the process block. Next is reset signal or reset. This is an optional signal which can be used to initialize or reset the process. Next is the rising edge or falling edge. The process checks for the rising edge or the falling edge transition of the clock signal to perform any operation. Now let's create a simple flip-flop circuit with the registered process block now. So first let's understand the requirement. So we have this D flip-flop and the input of our flip-flop is connected to signal D in. The output of our flip-flop is connected to signal D out. The clock input of our flip-flop is connected to signal clock and the reset input of our flip-flop is connected to the signal reset. So let's write the process block first with the sensitivity list. So write registered process reset clock begin, then some blank space and process semicolon. So if you see, we added clock and reset signal in the sensitivity list here. We did not add D in the sensitivity list. And this is the only difference what we have learned in the last session of VHDL process block, when we are using the process block for simple executions without clock signal. And that time we said that it is mandatory to add all the signals in the sensitivity list which are being used in your process block, because you will only see the changes in the simulation if your process statement executes, and they will execute when it detects any changes in the sensitivity list signals, right? Now in the registered process block example, we have this D flip-flop. So as the basic property of D flip-flop, it really does not matter that when your input signal D in is changing, because your output will only be changing at either the rising edge or the falling edge of the clock signal. This means your input will pass to the output when the clock signal changes, either at the rising edge or the falling edge. So there is no benefit if you execute registered process block other than the clock signal changes. We have also added reset signal in the sensitivity list. This is fine. I hope you are clear now that why registered process block mainly include clock signals only and why we ignore other input signals. But note that this is only applicable for the signals which are going to be used for the clock transitions. If you have any other signal which is not dependent on the clock signal changes, then these signals must be included in the sensitivity list. We will see the example of these scenarios later. However, you can use separate processes to avoid that situations as well. Anyway, our registered process block is ready. Let's quickly write the code for this flip-flop design in the next slide. So this is our code for the D flip-flop design. Let me read this first. Registered process reset clock begin. If reset equals to 1, then D out gets the value of 0 semicolon. Else if rising edge of clock, then D out gets the value of D in semicolon. And if and process. Okay, so the definition is very straight here. The process block is sensitive to the clock and reset, which we discussed already. Now the first statement is if reset equals to 1, then D out gets the value of 0. This is the master condition. If reset equals to 1, then your output signal D out is straight 0, no matter what is your input signal D in. Now the second condition, else if rising edge of clock, then D out gets the value of D in and if. This statement will only check the clock signal when first condition do not meet, means reset signal is 0. So when reset is 0, then it will check for the rising edge of the clock signal, means when your clock signal changes from 0 to 1. And at this transition, your input signal D in will pass to the output signal D out. Do not worry about the if-else syntax at the moment, as we are covering this very shortly. But remember the process block and how and where to use them. But as a quick brief here in this example, the if-else syntax is if, then condition, then write then, which is the keyword, then write statements here. They will execute when the condition meets. You can write many number of statements here, but remember that they will all execute sequentially, means one after another. Now you can write your second condition, and for that write else if, then condition, then the keyword then, and then write your statements here. Again, you can write as many statements as you need it, but remember these statements will only execute when the first condition did not meet and the second condition meets. Note that if your first condition meets, then these statements will not execute, even if your second condition meets also. So remember that. Second note here, if you notice the spell of else if, it is not ELSEIF, but it is ELSIF in VHDL. So please remember this, as this is very common mistake happens with the beginners. Although your tool will tell you the error if you mistakenly used else if wrongly, but still you should remember this. And in the last, you need to end your if statement. So for that, you need to use and if semicolon. We will talk about them in detail separately, so we are not going in deep at the moment. Now coming back to our topic. So the most important keynote here with the process block is that this kind of process creates a flip-flop. A registered process must have a clock signal and optionally a reset signal in the sensitivity list, but nothing else. The registered process must include a statement checking for the rising edge or the falling edge of the clock signal. And the main key point is that any assignment within the body section of a registered process always creates a flip-flop, like we saw in our earlier example when we have one signal assignments in D out. Now let's make this little complex and assume that now you need to use 3 assignments for 3 output signals for the rising edge or the falling edge of the clock signal. So how you will write them and how you will get the outputs in structural design. For example, you have 3 output signals, Dout1, Dout2 and Dout3. And you have 2 input signals as well, signal A and signal B. Now the requirement is when the reset signal is high, then all 3 outputs are 0. But when reset signal is low, then you have 3 different logical operations happening for each output signals. For example, let's say for Dout1, input signal A is transferring to the output signal Dout1. For Dout2, you are doing the logical AND operations of input signal A and input signal B. And for the Dout3, you are doing the logical OR operation to the input signal A and input signal B. Okay, so you can see the VHDL code in this slide here for this requirement. I will read it thoroughly first. Demo2 : process reset, clock begin if reset equals to 1, then Dout1 gets the value of 0, Dout2 gets the value of 0, and Dout3 gets the value of 0. Else if rising edge of clock, then Dout1 gets the value of A, Dout2 gets the value of A and B, and Dout3 gets the value of A or B, semicolon. And if and process. This is very simple code. If you understood the requirements and if you understood our last designs of simple D flip-flop, then I hope you can relate it very easily with our requirements too. Now think a bit that how the tool will develop the structure for this design. Remember that all the signals which are driven by the registered process block, they always create a flip-flop in design, and you will receive the output through that flip-flops. Now take some time to think before proceed. Let me give you a small tip here. So it will create 3 flip-flops for your design. 1 for each output signal, means 1 for Dout1, second for Dout2, and third for Dout3. Okay, let me show you quickly. You can relate this with the simple architecture in this slide. We have 2 input signals, input A and input B, and we have 3 output signals, DOUT1, DOUT2, and DOUT3. So first we can see three flip-flops, one for DOUT1, second for DOUT2, and third for DOUT3. All these three flip-flops have the same clock signal as an input and reset signal as well. Do not confuse from the image, as I didn't add the reset signal here to make it simple, but assume that there is a common reset signal which is connected to the reset pin of all these three flip-flops here. Okay, so the first output is DOUT1 gets a value of A. So you can see that input A is straight connected to the input of first flip-flop. So at the rising edge of clock signal, your DOUT1 will get the value of input signal A. Next, DOUT1. So you can see that the input of the second flip-flop is not straight. First, we did the logical AND operation on input signal A and input signal B, and then the output of this is going towards the input of flip-flop, and the output of this flip-flop is our final output DOUT2. Same for the output 3, which is signal DOUT3, and this is doing the logical OR operation on signal A and the signal B. Hence, the output of this logical operation is going to the input of third flip-flop, and the output of flip-flop is connected to the DOUT3. Note that all these three flip-flops having the same clock signal, means same clock signal is connected to the clock pin of all these three flip-flops. So this is the hardware realization of a generic registered process. Registered processes are one of the most commonly used circuits in the real-life designs. This circuit is so important to understand the key concept of registered process block, although the internal architecture of an FPGA is optimized to do the exactly same things what is shown in this picture. If you recall from our first video, we explained the basic building blocks of an FPGA, which is called configurable logical blocks or CLBs, which contains a lookup table or LUT and a flip-flop. The LUT performs the combinational logic and its output is connected to a flip-flop, just like you see in this picture here. So we can see that the basic building blocks of an FPGA are optimized for implementing the registered processes. And you will use these registered processes in almost all the designs in your future. So it is very important to be familiar with them and understand them. Okay, so if you understand the basic concept of registered process block, here is the example 3. Let's look at the general case of a registered process. So here we have a simple example of a process that drives signal DOUT. The output signal DOUT here is determined by a function that takes several inputs labeled as x1, x2, x3, and so on. And they can configure any type of structure design based on the requirement. Now, since this is a registered process, and we already know that the DOUT will be implemented as the output of a flip-flop, means our function takes the input from x1, x2, x3, and so on, and the output is some function of these inputs. And this output will be the input to the flip-flop, and the flip-flop output will be our final output signal DOUT. So this is the hardware realization of this generic registered process, which include the basic building block of an FPGA called the configurable logical block or CLBs. This CLB contains a lookup table or LUT and a flip-flop. The LUT performs the combinational logic and its output is connected to a flip-flop, just like in this picture here. Let's consider that this cloud is some kind of combinational logical circuit here, which is the function of inputs, and once it has the output, that will be passed on to the output DOUT at the rising edge of the clock signal. Now in this slide, let's quickly see the predefined VHDL functions for rising edge or falling edge of clock signal. You can use these functions straight like this. These both functions described inside the std_logic_1164 package means you need to include this package to use these predefined functions. So rising edge of clock is the same statement like clock event and clock equals to 1. This means that when the clock signal changes its value and the value of clock signals becomes 1, then this condition will be true. And hence the statements for this condition will execute. So both will do the same job. You can use any statement here, either rising edge of clock or clock event and clock equals to 1. Similarly, we have another function for falling edge of clock. It is falling underscore edge clock. This is again defined in std underscore logic underscore 1164 package. This function is same as clock event and clock equals to 0. This means that when the clock signal state changes and the value of clock signal becomes 0, then this condition will be true and the statements of this condition will execute. Means you can use either falling edge of clock or clock event and clock equals to 0 in your VHDL designs for such requirements. Note that the output of conditions are always Boolean. So either the condition will be true or it will be false. And based on that, your statements will execute inside the conditional statements. In the next session, we will be talking about one of the widely used conditional feature in VHDL, that is if-else. In the last few sessions, we talked about the VHDL process blocks and we made some basic understanding of it. Now in this session, we will discussing some of the examples and we will talk about some good practices while you are using those process blocks. Okay, so let's start. Okay, so this is our example 1. Now look at this example. Here we have two process blocks. First is process 1 and second is process 2. As we already talked about this and we already knows that all the process blocks within the architecture body executes concurrently. So this means that both of these processes will execute together at the same time. There is no problem in this, but look over the assignments inside these process blocks. Both of these process blocks are assigning the data into the same output signal, which is dout. So process 1 is saying that dout gets a value of A and process 2 says that dout is B. And now there is a problem because they both execute at the same time. And suppose signal A value is 0 and signal B value is 1, then what will be your output signal dout when both the assignments run at the same time? Note that both the assignments running at the same time because these two statements written in the separate process blocks which are executing concurrently. Now you may say that the execution of process blocks will only happen when the signals in the sensitivity list changes. So if A changes, then the dout will get the value of signal A, and when B changes, then the process 2 will execute and the dout will get the value of signal B. Let me know from the comment section if you are also thinking the same. If yes, then here is the question. So what will happen if input A and input B changes at the same time? This means both the processes will execute now at the same time. And now what will be the output dout? Confused, right? Well, this is the reason that this type of codes are not allowed in VHDL. This means that the output signal must be driven by the one assignment only. Either you are using it inside the process block or even if you are doing the assignment directly inside the architecture body. Now, if you understand this, then I have another scenario for you in the next slide. Okay, so look at this example now. Here I have removed the second process block and I have written the statement of that second process inside the process 1. So in the last slide, dout was getting the value of signal B, right? Now this statement is here in the process 1. So now the code is process 1 colon process A comma B begin dout gets the value of A semicolon, then dout gets the value of B semicolon and process semicolon. So in brief, here we have the scenario when we have the two assignments on the same output, but they are inside the same process block. Now my first question is that allowed? So the answer is yes, definitely this is allowed by the VHDL compiler. Reason is that there is no conflict in the assignment of output because these two statements inside the process blocks will be executing sequentially. Means first the statement 1 will execute and then the statement 2 will execute. But this is the problem itself. Well, this is not the syntax error or the compiler error, but this is the logical error. And the VHDL compiler will not tell you about this functional error. Can you guess that what is this functional error here? Well, here the problem is that the first statement, which is dout is A, has of no use because dout signal will always overwritten by the second statement, which is dout is B. Means whatever the value of A, you will always see signal B data in the output, because first the data of signal A will move to the Dout, and then the data of signal B will move to the Dout, and output signal will be overwritten with the B signal. Now, if this is clear, let me tell you what is the good practices then when you are working with multiple process blocks in your designs. Now look at this example here. So this has two process blocks. Process 1 is here. Process 1 colon process A begin, Dout gets the value of A and process. So in this process, we have signal A and we are assigning signal A data into Dout1. So this is the one output of our design. Now process 2, so it is process 2, process B begin, Dout2 gets a value of B semicolon and process. Means this process block using another signal B and its data is being assigned into the another signal Dout. This is our second output. Means there is no overlapping on the output signals here, and there is no conflict as well. Well, you can also write these two assignments in one signal process block. Now look over this example. Process 1 colon process A comma B begin, Dout1 gets the value of A semicolon, Dout2 gets the value of B semicolon and process semicolon. So when this process block will execute, at the first statement signal A will be assigned to Dout1, and at second statement signal B will be assigned to the Dout2. Means you will be getting the same results what you are getting in the last slide. Okay, so that's it for today. I hope you have a clear view of the process blocks in VHDL. But before we conclude, here is a quick recall on the sensitivity list, because this is one of the most important factor of the process block. So for the combinational processes, you need to include all the signals in your sensitivity list, which are being used inside the process block. Note that the sensitivity list cannot be empty. It is not allowed in the synthesis. If you are designing registered process, then you should include clock signal and reset signal in the sensitivity list. Now you should remember that the VHDL compiler will not give you any error if you are adding more signals in the sensitivity list. Either you are writing the combinational process or you are writing the registered process. But you will see the differences in your simulation results and in your synthesis results, because the output may not function correctly, or the output you are getting may not be expected from your design. And this will happen if you are not following the good practices with the sensitivity list when you are working with the VHDL process blocks. Although there are some situations when you can leave your sensitivity list blank. However, there are some conditions to that. Like the first condition is that such process blocks can only be used for the simulation purposes only. You can use them for the test functions only. Such process blocks must have the wait statements inside, which will be alternative to the sensitivity list, which tells your compiler that when the process block should run. But the most important keynote is that such VHDL codes which has the process blocks without the sensitivity list, these are not synthesizable. This means that you cannot implement them into the hardware or FPGA. In the next session, we will be talking about one of the widely used conditional feature in VHDL, and that is if-else. In the last session, we talked about the VHDL process block, and we also understood the concept of registered process block and combinational process block. And now we know that the statements written inside the VHDL process blocks to execute sequentially. Now in this session, we are talking about one of the widely used features in the VHDL designs, which are need to be used inside the process block. And this is if-else statement. So let's start. Like other programming languages, in VHDL, the if statement is also used for conditional branching within the process block. It allows you to execute different blocks of codes based on the certain conditions. So here is the general syntax of an if statement. So this is a little different from the software programming languages. So please remember this. Okay, so the syntax is if condition 1, then now you can write the statements here when the condition 1 is being true. Else if condition 2, then now in this section, write the statements when condition 2 being true. Else, now write the statements if none of the above conditions are true. And if semicolon. So this is very clear with the structure here that the condition 1 has the highest priority. If this condition 1 is true, then the statement group 1 will execute, and after that you will exit from this if-else condition. Means now it will not check for the condition 2 and condition 3 and so on. And hence the statement group 2 and the statement group 3 will not execute in this situation. Now condition 2 having the second priority means this will only get checked when condition 1 did not meet, right? And if this condition 2 is true, then the statement group 2 will execute and the compiler will take the exit from this if condition. Same with the statement group 3. When the condition 1 and condition 2 are not true, then this set of statement will execute. Now there are some important keynotes about the VHDL if-else statement, and these are: first, if-else statement must be written inside the VHDL process block. They cannot be written outside the process block in VHDL. This is because if-else statement required sequential executions to perform any task. Second, each and every if statement in VHDL must be ANDed with the AND if statement. So you can see AND if semicolon in the last. Third, you can write multiple else if condition with one single if statement. But remember the priority, because the top condition is having the highest priority and the last condition is having the lowest priority. Fourth, notice the spelling of else if. It is ELSIF, not ELSEIF. Fifth, you can write as many statements as you want in the statement groups. But remember that all the statements here will execute sequentially. Sixth, the condition output are Boolean. Hence, your condition either can be true or it can be false. You can also allow to combine multiple conditions with the logical operations as well. Note that in this example, the syntax has 3 statement groups, but they all are the part of one single if-else statement. Now, in this slide, we also have 3 statement groups, but this is a little different because here we have 2 if-else statements. And these 2 if-else statements are completely separate. Means here compiler is not having any priority with the conditions. They are separate and hence they both will execute all the time. Means condition 1 will check and also condition 2 will be checked. And based on the conditions, statement groups will be executed. Means if condition 1 is true, then the statement group 1 will execute and the compiler will exit the first if-else statement. But now there is a second if-else statement. Means now compiler will also check this condition 2. And if this is true, then the statement group 3 will also execute. If condition 1 is false, but condition 2 is true, then the statement group 2 and the statement group 3 will execute here. Now, if condition 1 is false and condition 2 is also false, then only statement group 2 will execute. Because in the second if-else statement, there is no else statement. Means there would be no changes in the signals with this if-else statement. Note that you can write multiple if-else statements inside one single process block, and you are also allowed to write multiple if-else statements in the separate process blocks. But there are some limitations and there are some good practices which need to be followed when you are working on more than one process block and if-else statements. First, let's have a quick recall. If-else statement must be written inside the VHDL process block. They cannot be written straight inside the VHDL architecture body. Remember the best practices of sensitivity list when you are writing combinational or registered process blocks. Sensitivity list plays an important role here. If you are not using it correctly, your results either in the simulation or in the hardware may not function like what you are expecting from it. You can write as many statements as you need inside single conditional group. When using the if-else statement, the first condition will have the highest priority to check. If this is true, then no other conditions will be checked for that if-else statement. Similarly, the last condition will have the lowest priority. You are also allowed to use nested if-else statements in VHDL. Else if in VHDL is written as ELSIF. It is not ELSEIF. So make a note of it, because it is like a very common mistake in starting. Every if statement needs to be ended with the AND if statement. You cannot use the assignment on the same signal from the two different process blocks. Does not matter they are written inside the if else condition or outside the if else condition, because they may execute concurrently at the same timestamp and can create the conflict in the output. You are allowed to use multiple if else statements inside one single process block. All the if else statements inside the process block will execute sequentially. Means if you written two if else statements, then both the statements will execute, but they will execute in sequence, one after one. Well, this is very basic of if else statement. Hence, we are not going deep at this moment. Although there are some more good practices which need to be followed to write a good VHDL design, like what are latches and how they are created in the hardware from the improper if else statements in the VHDL codes, and how to write a VHDL code to avoid such latches in your hardware designs, etc. But we will be covering them little later when we will become more familiar with the if else statement and VHDL general features and functions. In the next session, we will be talking about VHDL components, and we will also talk about how to instantiate components in the VHDL structural designs. In this session, we will design a small and simple finite state machine project. Although we will cover finite state machine topic little later, but this is just to give you a little brief that how you write VHDL designs in Quartus Prime and then implement it on FPGA board. So what we will do that we will develop a simple traffic light using finite state machines. We will write VHDL code for this and then we will implement it on FPGA as well. So for traffic light, we will have three lights: red, yellow and green. Red will turn on for 2 seconds. Yellow will turn on for 1 second and green will turn on for 3 seconds. So our one complete cycle will be of 6 seconds just for this design. So how we will do that? First, we will define a data type and signal for this traffic light, which will have three values: red, yellow and green. Then we will write a process block for generating 1 second signal. Basically, we convert 50 MHz clock into 1 second signal. And then we will count it from 1 to 6 seconds. And when this signal becomes 1, our red state will trigger. Then it will hold for 2 seconds, means when the signal becomes 3, then our state will change to yellow. Then hold again for 1 second, means when this signal becomes 4, then we will change our state to green. And this cycle will run in an infinite loop. So this is the plan for this project. So let's jump to the Quartus software and start developing it on FPGA board. Okay, so we will start Quartus Prime software. So go to Start and write Quartus. We will open this Quartus 2 10.1 web edition. We are selecting this version because we are working on Cyclone 2 device, and recent Quartus release do not support those old FPGA devices. So we have this version here to work on Cyclone 2 devices. But steps are almost same if you are working on the recent release from Quartus. So once you open Quartus, you will see this create a new project wizard. Now click on this button. Okay. So this window is new project wizard. So once you see this window, just click on next. Now at this page, we need to give project directory name and your project name. So give it. So click on these three dots here. Now select the respective folder where you want to save your project. Suppose I want to save my project in this projects folder and I want to create a new folder for this new project. So here is a button, make new folder. So click on it and give it some name. Suppose this project is traffic light. So give some name, traffic light. Now copy this because we will use this as a project name. Okay. Now select it and click on OK. And now it is asking for your project name. So just copy your project name here. So this is traffic light. Now once you finish up with this, just click on next. Now this is add file section. So if you have any existing file which you want to use in this project, then you can add that particular files from this page here. But because this is our fresh project and we do not have any file to add at the moment, so we will click on this button next. Now this is important page here because here you will select your FPGA device in which you are working. For example, I am working on Cyclone 2 device, so I will select this Cyclone 2. Now you can see there are many FPGAs listed here for this Cyclone 2 and we need to select our FPGA. So you can select it from this big list or you can filter down this list by using some additional filter, and these are listed here. For example, my package is FPQFP, so I will select this, then pin count, then my FPGA has 208 number of pins, so I will select it. Now it is asking for speed grid and that is 8 for my FPGA. So you can see that we have only 4 FPGA devices with these additional filters. So it is shorten list to select your FPGA. For example, my FPGA is EP2C5Q208C8 and this means that we have 2C, this is Cyclone 2 device, 5Q208. So 208 is number of pins, Q is your QFP package and C8 is your speed grid. So that's why it's 2C5Q208C8. So select my device and click on next. Now at this page, you can select your simulation tool if you have more than one simulators. For example, there are a couple of simulators listed here. For example, you are using this QSTES simulator. Then you can select it from here and then your SDL language. For example, Verilog SDL if you are using Verilog. If you are using VHDL, like in our case, we will select this VHDL. But for this project, we are not doing simulation. So you can leave it as default and just click on next. So this is our summary page and it is showing whatever you have selected during the previous step. For example, this is our directory location. This is our project name, traffic light. We have selected Cyclone 2 device and this is our FPGA device name. We have selected QSTES simulator as a simulation tool and VHDL as a language. So this is just a summary page. So just review it and then click on finish. Now, once you click on finish, then Quartus will create a project for you. So you can see that Quartus has created this traffic light project for you here. Now this is hierarchy view. You have more views like files. So you can see this is empty here because we have not added any files and we have not created any files yet on this project, right? So this is blank at the moment. Now just switch back to the hierarchy view and now create a new file. So for that, we will go to this file tab and click on this new button, or you can just directly press Ctrl N from a keyboard. Okay. So once you click on that, you will see this big list here. Now you are working on VHDL. So click on this VHDL file and then click on OK. Now this is your VHDL editor where you will write your VHDL program. This is the project navigator where all the files will be listed here which you are using for this project, right? And this is task view where all the options are listed which are needed for your project. For example, this is compile design. This is for check your syntax and for check your RTL viewer, for pin planner, and there are many tools listed here. But few of them which we will be using in this project, this is number one, this is analysis and synthesis. Next is pin planner because this will tell the Quartus software that what FPGA pin will be connected to the what pin of your VHDL design. Next, we will use this filter, place and route option, and we will use this assembler. So this will generate the binary file for your FPGA, which you can program in your FPGA device. And finally, we will use this program device or open programmer to program our FPGA device. So these are few of the tools which we will be using in this project here. And for the other tools, we will be learning them in a separate session. Now go back to the editor, and the first step what we will do that we will save this project because you can see that this is named as VHDL1.vht that Quartus give by default when you create a new file. So first we will save this file with the pattern name. So click on File and click on Save As. Now locate your project directory. So my project is this traffic light. So select it. Now I want to save all my VHDL files in one single folder. So for that, I will create this new folder and I'm giving this source src. Okay. So I know that all of my VHDL files or VHDL source are located in this folder only. So select this and give the name traffic light and click on save. So now you can see that our file is saved as source trafficlight.vsd. Now we will start writing our VHDL code. So first we will give the library and package declaration. So give it library IEEE use IEEE.std_logic_1164.all. Now give the entity declaration. So give it entity traffic light is port. Now and entity and traffic light semicolon. So we have created this entity body here, and now we will define all our input output ports in this section. So what we will have? So we have clock as an input. So give it clock in std_logic. Now we have three LEDs, that is red, yellow and green, right? So you can create three separate outputs. For example, LED 1, that is out std_logic, LED 2 out std_logic, and LED 3 out std_logic. So you have one input as in clock and you have three outputs, that is LED, right? Now there is one more way to declare these three LEDs. How? So I will write this as an LED. Now this is out and I'm saying that this is std_logic_vector. And this is 1, 2, 3. So what I am saying that I have a LED as an output and this output is having three elements inside it. That is LED 1, LED 2 and LED 3. So this port is equivalent to these three LEDs output. So either you can use three separate lines to define these LEDs as an STD logic output, or you can define this single STD logic vector signal as an LED. And in this LED output, you have three elements inside it. Okay. So these three line of code and this one single line of code is equivalent. Okay. So we will use this line LED as an output, STD logic vector 1, 2, 3, and we will remove this. Okay. So this is our entity declaration. Now it's time for the architecture declaration. So write it. So write architecture behave of traffic light is begin and behave. So what I have did, I have just defined the body of this architecture. And now we will write our functioning for our project. Okay. Okay, so first what we will do that we will create a process which will give us 1 second signal, because our traffic light will drive based on this 1 second signal. Remember, as we said that red light will turn on for 2 seconds, then yellow light will turn on for 1 second, and then green light will turn on for 3 seconds. So first we will create this 1 second signal. So for this we will use a process block. And this will be a registered process block. So write it. So give some name to this process. Suppose my process is process clock. Now process. Now because this is a registered process block, so we will use clock as a sensitivity list. Now begin and end process. Okay, so this is the body for our process block. Now write the condition for a registered block. So give the condition if rising edge of clock, then and in the last and if. Okay, so this is the body. So we are using this rising edge of clock. That means we will be getting the registers version of our signal, and this will generate a flip-flop in our physical design. Now this is important step because we are using 50 megahertz of clock frequency on our FPGA board, and we need to generate 1 second signal from it, right? So what we will do that we will use a counter that will count from 0 to 50 million times. so that we can get our 1 second signal, right? So write the code for this. So what I am writing that if our counter is greater than 49,999,999. So this number is actually one less than 50 million because we are starting our counter from 0, not from 1. So we are counting this up to this number, not 50 million exact, right? So if counter is greater than this, then what will happen? Then our counter will reset to 0. So give it counter should be 0. Else, now what will happen if counter is less than this value? So we want to increase our counter by 1, right? So give it, so counter should be counter plus 1 semicolon. Now we are using this counter here as a signal, but we have not defined it in our VHDL code, right? So first we will define this. So write signal, now counter, and this is integer type, and it is having the range from 0 to 50 million. So 50, 0, 0, 0, 0, 0, 0, semicolon. Now we are creating another signal that will count each second based on our 1 second signal, right? So suppose this is a signal named as sec, and this is integer type and having the range from 1 to 7 semicolon. Just correct it, integer range from 0 to 50 million, right? So this is the right syntax. Okay. Now go back to our process section. So we are saying that at every rising edge, our counter will increase by 1. And if it is reaching to 50 million or this 49,999,999 number, then it will reach that to 0, right? So we have written all the conditions here. So just terminate this if condition by and if. So this is completed now. Now the second part comes where we will use another if condition that will count our second signal from 1 to 6, right? And based on this second signal, we will drive our LED outputs like red, yellow, and green as we discussed. So we will write that if a second greater than 6, then what will happen? Our second should be reset to 1, right? Else, what will happen? Second should be second plus 1, okay? And if. So what we have did that this counter signal, this is counting from 0 to 50 million times, and it is giving us 1 second cycle. And we have this another condition. This is driving our second signal. But here is the problem. Because what will happen that this second signal will count and increase its counter at every rising edge of clock, right? At this, because we have this condition. But what we want, that we want to increase this signal at every second, right? So we need to write this inside one additional condition. So we will use that ELSIF instead of else, and we will say that else if counter is equals to 0, then this condition will happen. Okay, so this second will increase by 1. Now this counter will be 0 at every 1 second. Why? Because this counter starts counting from 0 and it will increase by 1 at every rising edge of clock signal. So it is increasing 1, 2, 3, 4 up to 49,999,999. And because we have this condition that is counter is equals to 0, so this condition will only met when this counter counts 50 million times, and that will be our exact 1 second, right? So at this point of time, we will increase this second by 1 factor, okay? So it will start from 1 and it will go up to 6, right? Because as soon as it reaches to number 7, it will reset to 1 again, right? Because we have this condition here. When sec is greater than 6 means when it will touch 7, it will reset to 1 again. So it will count from 1 to 6. Okay, so that's one part that is completed now. So we will go back to our architecture body. So what we have did, we used 50 megahertz of clock cycle and we converted it to 1 second signal, right? Then we counted our 1 second signal up to 6 times. So now it's the time to drive your LED outputs, which is red, yellow, and green based on this second signal, right? So we will write another process for that, which is for state diagram. So give some name to this process. Suppose this is state process, right? Now process, again, this is a register process block. So we'll use clock as a sensitivity list. Now begin and end process. Okay, so we have created the body for this process now. Now write the basic structure for this register process block. So write if rising edge of clock, then and if. Okay. Now before we start writing this state machine for our project, let's define a new data type for our traffic light so that we can use it. So we will define it inside this architecture and begin section. So write type TL for traffic light. So give type. So this is TL type is red, yellow, green. Okay. So we have this TL underscore type as a new data type, and it will have three values. This is red, yellow, and green. Okay. So we have defined the data type. This is the new data type for this project. And now we need to create a signal for this data type, right? So create signal and give it some name. For example, traffic light. So this is TL. And now this is TL underscore type semicolon. So this TL signal will have three values, that is red, yellow, and green. Okay. Now we will go back to our state process so that we can define our state machine, right? So first we will write the basic structure of our state machine. And for that purpose, we generally use case statement, right? So we will use case traffic light is, now define the state. So we have three states, right? So first state is red. So when red, what will happen? We will define it little later. Just we are writing the body here. So red, now yellow, then it will do something. And when green, then it will do something. And in the last, when others. Okay. So this is mandatory to write others when you're working with the case statement. Okay. Because these three states, that is red, yellow, and green, these are known states. But if in any situation your device jump to some unknown state, maybe because of some hardware issues or glitches, then this other sections will help you to reset your condition. Okay. So what we will do when this other condition will meet, we will jump to some known state. That can be anything. That can be red, that can be yellow, that can be green. For example, in our case, we want to jump to this red state, was in safe side, right? So when others, then our TL will become red. Okay. So we have reset this TL signal to the red state, and we want that our red LED should on. So our LED output will be 100. Don't worry, I will explain this number in some time. So now let's jump back to this when red state is happening. Okay. So what will happen that when you are at this red state, so your red LED should on and your rest two LEDs should be off, right? And suppose our LED first element is red, second element is yellow, and third element is green. So our LED first element should be 1, right? LED 2, that is our yellow LED, that should be 0, right? And LED 3, that is our green LED, that is again 0, right? So this will be our output. Now because we have used LED as a vector data type, that is std underscore logic underscore vector. So we can write this LED as an output like 1, 0, 0. So this 1 is our red LED. This 0 is our yellow LED. And this 0 is our green LED. So this single line is equivalent to these three lines here. Okay. So either you can use these three lines or you can simply use this one single line. Okay. Both will do the same thing. Okay. So we will use this single line statement, that is LED. It's the value of 100. So we will remove these three lines. So let's delete it. And we have this one single statement. Okay. Now we will define that when we are at this red state, then what will be our next state, right? So after red, the next state will be yellow. But when? After 2 seconds, right? And that is we have defined for our project, like 2 seconds for red, 1 second for yellow, and 3 seconds for green, right? So write that condition that if this second is equals to 2, then what will happen? Our state will change to yellow, right? And if so, we have finished this red state. Now let's move to the yellow state. So what will happen at yellow state? So our yellow LED should on and rest two LEDs should off, right? So right LED should be 0, 1, 0, right? So this is red, this is yellow, this is green, okay? So we have met this. Now semicolon, and now we will write what will be the next state. So what is next state after yellow? That is green, right? So write it. If second is equals to 3, then our next state means traffic light should be green and if. So now why we have used 3 seconds here? Now second is equals to 3 because for 1 or 2 seconds it will be at red state and then second will be 3. So this is 1 second after red, right? So we have used this second equals to 3, then next state will be green. So next jump to the green state. So when green, now our LED output will be 0, 0, 1 because this green LED is on and rest two LEDs are off. Now we will define that what will be the next step or next state, right? So write it. What if sec is equals to 6, then what will happen? The next state will be again red. Okay. Now and if. So what is happening that when you are at this red state, then red LED will on and it will wait for 2 seconds. And after 2 seconds, it will jump to the yellow state. And when you are at yellow state, then your yellow LED will turn on and it will wait for 1 second. 1 second, why? Because 2 seconds is already completed here. So when we jump from 2 to 3, that will be exact 1 second, right? So this means that 2 seconds for red, 1 second for yellow. And after that, we will jump to this green state after 1 second of yellow. Okay. So when this green state comes, then our LED output will be 0, 0, 1. So this is red, yellow, and green. And when this completes 1 cycle and it will wait for the 3 seconds on the green state, then it will jump to the red state again after 3 seconds on green, right? So this is happening in the loop because from red to jump to yellow, and then from yellow you jump to green, and from green you jump to red again. So this is red. Okay. So you are doing it on the cycle. Okay, so this is our VHDL code. So I think that everything is completed. Nothing looks wrong with this code. So let's save this code and compile it. So you will see this button here for this compilation. So just click on it. And now Quartus is compiling your VHDL code. So as you can see that it come up with some syntax error. So click on OK. We will click on this error and it will jump to the problematic area of your code. Okay. So I already figured out that what is the problem. We have used this case statement, but we have not terminated it. So we need to terminate it with AND case statement. Okay. Now save this and compile again. So you can see that full compilation was successful and there are few warnings. So we will ignore these warnings at the moment because few warnings would be related to your timing constraints because we have not defined it yet. Few warnings would be related to net list because we have not defined it yet again. And we will be doing this in some time. So we are just ignoring these all warnings at the moment. Okay. So we can see that our VHDL code is successfully compiled and that is everything is okay in this code, means there is no syntax error, right? Now the next step is pin planner. So you will see this button here. So you can open this pin planner from this button here, or you can also open it from this taskbar. Okay. So here you will see this pin planner. So you can double click on it, or you can just simply click on this button. Okay. So I will open it. Now this is your FPGA view. Okay, so this is Cyclone 2 device and this is your device name, which we have selected during the initial step of defining this project. Now this FPGA is having the 4 sides. So this is side A, this is side B, this is side C, and this is side D. Each side is having some specific number of pins, right? So you can see there are number of pins listed at this side, same at this side, same at this side, and same at this side. So if you zoom it little, this particular view from here, and let's zoom in little, so you can see these numbers here as well. For example, so this is your starting point and your pin count starts from here. So it is starting from 1. Let's take the pen tool and let's slide it little so you can see all the pins listed here. So this is side A and it has total 52 number of pins on this side. So this is side B and the pin count start from 53 to up to 104. And this is side C up to here. And this is your side D. So you can see that total number of pins are 208. Okay. So let's zoom out. Now look at this window here. So you can see that Quartus already listed all the input output ports here. Like you have one clock signal and you have one output, but that is LED steady logic vector signal. And this is having 3 elements inside it. So Quartus already differentiated it for us. So this is LED1, this is LED2, and this is LED3. Now what we are doing here, that we are defining that which port of your VHDL project is connected to which pin of your FPGA device, right? So that's what we are doing here in this window. Okay. So for example, this clock input. So you can see this is a clock signal. This is input and there are some fields. These are blank here and we are going to fill these informations. And for this data, you need to look into your board specification. So you need to see that in your FPGA board where this clock input is given, right? For example, for my FPGA board, this input pin is connected to pin number 23. Okay, so write pin underscore 23. So this is the way how you define your pin number. So this is pin underscore, then your FPGA pin number. Like for example, in my FPGA board, my clock frequency is connected to this pin number 23. Okay, so I have written this pin number 23. Okay. Now we are having 3 outputs and we need to connect each LED to the FPGA pin, right? So in our case, our LED1 is connected to pin number 15. So write it 15. Next LED is connected to pin number 13. So pin number 13. And third LED is connected to pin number 11. So pin number 11. So our clock is connected to pin number 23. So if you click on it, and it will highlight the respective pin in the FPGA view as well. So for example, I have selected this clock as an input. So this is highlighted that this is pin number 23, right? So you can see this is pin 23. And if I zoom it little, so you can see that this is connected to pin number 23. You see this blue border here. So this is defining that this particular pin is actually selected. Okay. So same way, if you select this LED1, then it will highlight this pin number 15 because this is connected to pin number 15. Okay. Now if you select LED2, so this is pin number 13. Okay. LED3, this is pin number 11. Likewise. Okay. Now this is important thing, that is input output bank. So each FPGA is having number of banks and each FPGA pin must belongs to some specific input output bank. So for example, we have selected these 4 pins of our FPGA, right? And it is saying that all these 4 pins are connected to the IO bank number 1. And this is having the default 3.3 volt LV TTL as an input standard. For this FPGA, this is standard and fixed. But if you are working on some recent FPGA, you can select the voltage on this. And again, this must be specified by your FPGA board manufacturer. Okay. But for our device, this is pretty standard. Okay. So let's zoom out little and close this. Well, important note here that you do not need to save this pin planner after making the changes. And if you notice, then there will be no save button here. Why? Because this pin planner automatically saves whenever you make any changes on this view. Okay. So if you change this clock or if you change any LED output pin, then it will automatically save after you make any changes in this window. Okay, so you do not need to save it. Just specify the thing and then close the window. And now it is already saved for you. Okay, now because we have changed the pin planning for this project, that means we need to recompile our design. So you see in this task view, everything is defined as a question mark. Okay, so we will run the compiler once again. So click on this play button to start compilation and it will start compiling. Okay, so it will take few seconds to complete and it's done. So it is full compilation was successful and now there are 8 warnings. Okay, so click on OK. Now this is the time when you program your design into the FPGA board, right? So for this purpose, we will use this programmer. Okay, so there is a button so you can directly open it from here, or you have this same option here as well. So you can see this program device, open programmer. So you can open it from here or from here. Okay, so just click on it. Click on OK. Now this is your programmer window. I will just make it little wide so you can see it properly. So this is your programmer. This is your traffic light.sof file. So this is your binary file which will be flashed or programmed into your FPGA device. Okay. And this is your device name, that is EP2C5Q208. Checksum, that is for some validation. User code FF, that means none. And make sure that your program or configure button is ticked like here. Okay. Now this is your progress bar. So once you start flashing your program into the FPGA board, you will see the progress here. Okay. And this is your hardware setup. Now this is showing that USB blaster is already connected. But in your case, if you don't see anything here, then just click on this hardware setup button and your programmer should be listed here as an USB blaster. Okay. If you are not seeing your USB blaster here, then there might be a connection issue. So make sure that you have connected your USB with your FPGA board, or it also may be a driver issue. So if this is the case, then update your drivers and then check again that your device is listed here or not. So once you see your device listed here, just select it and then click on close. Okay. Then you should see your USB blaster listed here. Okay. So once you see it, now click on your binary file and you will see this start button flashing here. Okay. So just click on this start button and you will see the progress. So this is very quick. That is 100% successful. This means that we have successfully flashed our program into the FPGA board. So next we will jump to the FPGA device and we will see if our program is working well or not. So let's jump into it. So this is our FPGA board. Now suppose this first LED is our red LED. This LED is yellow LED and this LED is green LED. And we have programmed it like 2 seconds. It should be in red state. Then it will jump to the yellow state for 1 second. And then it will jump to the green state for 3 seconds. Means 2 seconds red, 1 second yellow and 3 seconds green. So let's see if this is happening or not. So this is red, now yellow, now green. So red again for 2 seconds, now yellow, now green for 3 seconds. So this means that our VHDL program is working well as a traffic light and we have developed it using a finite state machine system. Okay, so that was our demo for this project. Hope you liked it and learned from it. So you see that first we converted 50 MHz clock into 1 second signal. And then we counted it for 6 seconds. And finally, based on our project specification, we change the state at specific time. And we get our final traffic light, where red is on for 2 seconds, yellow is on for 1 second, and green is on for 3 seconds. Just a note, because I am using Cyclone 2 device, so I have used this Quartus old version, but steps are almost same for design and implementation on Quartus. In the future sessions, we will be covering more such projects and we will implement them on FPGA board as well. We will see different real life issues like bouncing of switch and we will learn that how to solve them. In the last session, we talked about VHDL process block and if-else statement. Now, in this session, we will be talking about VHDL components and how to instantiate them in the VHDL structural design. So, let's start. Okay, so till now, we have designed some standalone VHDL entities and we write the architecture for them. Hence, everything is in a single file. Now, we are going to explore that how you can combine two or more entities to create more complex designs. Alternatively, you can say that how you can use your existing VHDL designs as a component in a bigger system. Now look at this simple VHDL module. So we have this VHDL design which is named as sub1. This module has two input signal. One is sig A and another is sig B, and it has one output D out. And let's assume that this module is doing the addition operation. We are not mentioning the data type at the moment, but we will define them in some time in our code, so don't confuse. This means we are writing a VHDL code for a module which has two inputs, sig A and sig B, and you will be getting the output D out, which is sum of these two input signals. Simple. Now look at this block diagram. So suppose we have developed this entity sub1 as we talked in our last slide, and now we wanted to use this existing module in our another design. So you can say that you wanted to use this already developed VHDL design in some bigger VHDL design. Now the name of this big system is suppose top level entity, and it has input signal X and another input signal Y, and it also has one output signal which is D out. Now in this top level entity, you wanted to use sub1 design as a small element. This is what we are going to do in this session. In VHDL, we call this component, means sub1 will be used as a component of a bigger VHDL module named as top level entity, or in general, you can say it instance. So you can see in the slide that you can use your component multiple times in your top level entity. There is no limitation to that. For example, we are using the same component of sub1 two times in this top level entity. You can use different components and you can also use them as many times as you need it. This approach is helpful when you are designing some big architecture in VHDL, or if you are going to use some modules very frequently in your designs. For example, you are designing a microcontroller which has multiple elements inside it, like it has arithmetic operation unit, it has counters, it has serial communication module inside it, it has memory, it has timers, etc. So instead designing all of these elements inside one big VHDL module, you can prefer to design them separately in separate VHDL modules. And once you have developed them and test them separately, and once you are ensured that each and every module is working fine, then you can combine these all modules in one single VHDL design. And hence it will ease your whole design process and also testing process as well, because now you can test your individual modules. And if any module has some bugs, then you just need to look at this problematic module, not the whole big architecture. Another benefit is that if you have a team of people, then you can share your modules between them, which will ultimately shorten your designing time. Also, if you are using some modules very frequently in your other designs, then you do not need to write them again and again. You can just design it once and then you can use them multiple times as a component in your top level entity. So these are some of the benefits of using components in your VHDL designs. So you can see this block diagram now. This is very clear. We are using two instances of sub1 entity in this top level design. This has some internal signals as well to connect the component ports with the wires or signals of your top level entity. So let's quickly brief this because we are going to write a VHDL code for this design. So we have two components of entity sub1, which are component 1 and component 2. Component 1 has signal sig1, sig2 and sig3, which are connected to sig A, sig B and D out respectively for component 1. Next is component 2, and it has signals sig4, sig5 and sig6, which are connected to sig A, sig B and D out respectively of component 2. top level module has two inputs, sig X and sig Y, and one output, dout. In the next slide, we will see that how these component ports are internally connected with the wires of top level entity. But before we write the VHDL code for this, let's have some quick recap of how we write the VHDL codes for our designs. This is simple template for a VHDL module. First is library declaration section at the top. Here you need to declare all the libraries and packages which are you going to use in your VHDL design. For example, library IEEE. Then write library IEEE semicolon use IEEE.std_logic_1164.all semicolon. You can write more packages as well. Now the next is entity declaration. This section defines the name of entity and its input and output ports. Then we give the architecture declaration. This has two sections. One section is between the architecture statement and begin statement. And another section is between the begin statement and end architecture statement. So section 1 is called declaration part. Here you will declare all the signals and constants which are needing for your project. Note that here you need to declare components as well, which we are going to use in our designs, which we are currently discussing. So note that we need to declare those components in this section here. Next section is architecture body, where you will define your module behavior and you will write the functionality of your project. Now let's come back to our component topic. So look at this architecture view of our top level design. So first we need to know that what this entity sub1 will do here. As I said, this sub1 entity is doing the addition operation on the integer number. And this module is able to add any two numbers which can have any value between the range of 0 to 9. Okay, now in this top level entity, we are using two instances of this component. Its first instance taking the input from the top level entity and giving the sum at the output. And then the output of the first instance is being used as an input to the second instance of component and giving the output. Note that we are giving the same input on the both ports of the component 2. Now the output of component 2 is directly connected to the output of our top module. I hope the requirement is clear to you. If this is clear, then let's write the VHDL code for this. Please note that we are writing them in parts to explain things one by one, and then we will combine the whole code in the last. So we will start from writing the VHDL code for our submodule, which is sub1. So here is the VHDL code for this. Entity sub1 is port A colon in integer range 0 to 9 semicolon. B colon in integer range 0 to 9 semicolon. Dout colon out integer range 0 to 36 bracket close semicolon and entity semicolon. Architecture behave of sub1 is begin dout gets the value of A plus B semicolon, and this performs the addition operation as mentioned in the comment section. And architecture semicolon. Let's quickly decode this. So we have entity name sub1. It has two input ports, input A and input B, and it has one output dout. These input output ports are integer type, and we have also specified their range as well. As we said earlier, this module is designed which can add numbers which can have the value from 0 to 9. So inputs have this range. But when you add those numbers, then you may have the dout value anything from 0 to 18. So you need to use dout integer range from 0 to 18. Although I have specified 36 here to make it simple, as we are going to use its output in the second component later in the top module. So this output can go up to 36. Well, you do not need to specify that range here for this module, but I just wanted to make this easy at the moment. So consider the range is 0 to 36 for dout. Then AND entity. Now the architecture section. So we simply said that it is adding two inputs. So the statement is dout gets the value of A plus B semicolon. And in the last, AND architecture. Okay, so now we have created the sub1 module. Now it's time to design the top level entity for our requirements. So in this slide, we are just writing the entity of this. So write entity, top level entity is port x colon in integer range 0 to 9 semicolon y in integer range 0 to 9 semicolon dout colon out integer range 0 to 36 bracket close semicolon and entity semicolon. A quick brief of this. So we have the entity named as top level entity. This has two inputs x and y. Both are integer type and having the range of 0 to 9. This range is exactly same as the range of sub1 module if you remember. And this top level entity has one output which is dout, again integer type and with the range of 0 to 36. Now coming to the architecture body part. So we are needing both the sections here of architecture body, means declaration section and architecture body. In this slide, we are writing the declaration section. So write architecture behave of top level entity is signal sig1, sig2, sig4, sig5 colon integer range 0 to 9 semicolon. Signal sig3, sig6 colon integer range 0 to 36 semicolon. Now component sub1 is port a colon in integer range 0 to 9 semicolon b colon in integer range 0 to 9 semicolon c colon out integer range 0 to 36 bracket close semicolon and component semicolon and begin statement. Now because we have internal signals here in this top module, so we define them inside the architectural declaration section. These are sig1, sig2, sig4 and sig6 which are integer type and having the range of 0 to 9. If you notice, then we have written multiple signal names with the comma separations. This is allowed in VHDL, that you can declare multiple signals in one single statement. And you can do this just by adding commas in between signals. But remember that those all signals should follow the same data type like here we did. Now because sig3 and sig6 has different integer range, hence we need to declare them separately from sig1, sig2 or sig4 or sig5. So we declare sig3 and sig6 together, which is having the same data type and integer range. This is very important to remember when declaring multiple signals in one single statement, that they should match the data type and the length of range, etc. Now we declared internal signals. And now it's time to declare the component of sub1 in this VHDL code. This component declaration also need to be written here in this section only. So all the components which you are going to use in your design, just declare all of them here in this section. Component declaration is very simple. Let's see what I have written. So this is component sub1 is port bracket start a colon in integer range 0 to 9 semicolon b colon in integer range 0 to 9 semicolon c out integer range 0 to 36 bracket close semicolon and component semicolon. Now if you notice that it is exactly same as you defined the entity of sub1. The only difference is that the entity keyword is replaced by the component keyword, because now you are declaring the component here as sub1, not the entity. So copy the text of sub1 entity and paste it here and then replace the keyword entity with the keyword component, and that's it. Rest everything is exactly same, like port declaration and component, etc. Once you declare everything for your design here, then start the architecture definition with the keyword begin. Okay, so it's time to write the architecture definition for our design. So we started from the architecture begin statement. Okay, so let me read the code first and then we will code it. So it is begin instance 1 colon sub1 port map bracket start a equals to and greater than sign sig underscore x, comma, b is assigned in sig y, dout is assigned in sig3 bracket close semicolon. Now coming to the instance 2. So instance 2 colon sub1 port map bracket start. A is assigned to sig3 comma B is assigned to sig3 comma D out assigned to sig6 bracket close semicolon, and in the last D out gets the value of sig6 semicolon and AND architecture semicolon. That's it. Just notice the symbol here. It is equal to sign followed by the greater than symbol. So this is reverse of assignment operator, and you can read this as connected to, like I read. A is connected to sig x, B is connected to sig y, and D out is connected to sig3, and so on. So look at the first line. Instance 1 colon sub1. So we have given some name to this instance of component sub1. So this means we are using sub1 component, and this is one element of our top level entity which is named as instance 1. Now write keyword port map. Now it's time to tell that what signal or pin of the sub1 module is connected to what signal or wire of the top level entity. So look at this block diagram of component 1 connection. So signal A of first component is connected to the input signal of top level entity, which is sig x. Now the second port of component, which is port B, this is connected to the second input of top level entity, which is sig y. Now if you see the output of this component 1, then it is going to be treated as input of another component, which is instance 2 or component 2, and that is connected with the internal wire sig3. So let's map the port of component 1 or instance 1. So port A is connected to the sig x, port B is connected to the sig y, and port D out is connected to the sig3. Again, notice the symbol here. It is just reverse of assignment operator. This simply tells what port is connected to the word signal. Like here, A and B and D out are the ports of sub1 module, and signal X, signal Y, and sig3 are the port or signals of top level entity. So if this is clear, then let's write the component for instance 2. So it is instance 2 colon sub1 port map bracket start. A is connected to sig3 comma B is connected to sig3 comma D out is connected to sig6 bracket close semicolon. This is again very similar what we did for instance 1, but the only difference is that now the port mapping is changed. For instance 2, signal A of sub1 is connected to sig3 of top level entity. Signal B of sub1 is also connected to sig3 of top level entity, and D out of sub1 is connected to the sig6 of top level entity. And in the last, we moved sig6 theta into the final output of D out. So we have written D out gets the value of sig6 semicolon and architecture. And with this, now we have completed our code for this architecture. Now let's see the whole VHDL code in one single screen. Note that we didn't copy the code for sub1 here, so it is just for the top level module. So it is entity, top level entity is port X colon in integer range 0 to 9 semicolon Y colon in integer range 0 to 9 semicolon D out colon out integer range 0 to 36 bracket close semicolon and entity semicolon. Architecture behave of top level entity is signal sig1 sig2 sig4 sig5 colon integer range 0 to 9 semicolon signal sig3 sig6 colon integer range 0 to 36 semicolon. Component sub1 is port bracket start A colon in integer range 0 to 9 semicolon B colon in integer range 0 to 9 semicolon C out integer range 0 to 36 bracket close semicolon and component semicolon. Begin instance 1 colon sub 1 port map bracket start. A is connected to sig x, B is connected to sig y, and D out is connected to sig 3 bracket closed semicolon. Instance 2 colon sub 1 port map bracket start. A is connected to sig 3 comma, B is connected to sig 3 comma, D out is connected to sig 6 bracket closed semicolon, and in the last D out gets the value of sig 6 semicolon and AND architecture semicolon. Well, there is a small mistake here in this code. Can you guess what it is? So the mistake is in the signal declaration in the architecture. If you remember, the output of instance 1, which is sig 3, that is connected to sig 5 and sig 6, which are the inputs of instance 2 of sub 1 component. Now the problem is sig 4 and sig 5 signals having the range of 0 to 9, which we have defined. But that is the output of instance 1, which should have the range of 0 to 36. So if you're going to use these signals, I mean sig 4 and sig 5 in your code, then this will give you some error in your results. And your output may not be the same as you are expecting from it. But this code will still work because we did not use sig 4 and sig 5 in our architecture. We directly connected instance 2 inputs to the sig 3, which is the output of instance 1. So let's correct this now. Correction is very simple. Just move sig 4 and sig 5 to the second declaration of signal. I mean with sig 3 and sig 6, which is having the range of 0 to 36. So the correct declaration of signals for this design would be signal sig 1, sig 2, colon, integer, range 0 to 9, semicolon, signal sig 3, sig 6, sig 4, sig 5, colon, integer, range 0 to 36, semicolon. Okay, so this is the time to quickly recall the VHDL file template once again. So we start from the library and package declaration, followed by the entity declaration and architecture declaration. This is general VHDL body, which you will use in most of your VHDL design. It is first declare VHDL libraries and packages up here, then entity name is port bracket, declare all the modules input output ports here, then bracket closed, semicolon, and entity, semicolon. Architecture name of entity name is, then declare all the internal signals and constants here, then declare the components here and begin. Now define your module behavior in this section here, and in the last, and architecture, semicolon. Okay, so that's it for today. This was quite a long session, but I hope that it made you create a strong foundation of VHDL components. And I believe that you are more confident now about the VHDL components, like how to use them, where to use them, and what are the benefits of it, etc. In the last session, we talked about VHDL components, and we understood the basic concept of VHDL components. We learned how to use them, where to use them, and what are the benefits of using VHDL components. Now we are more familiar with the VHDL body as well, and we know the general template of VHDL codes too. Now in this session, we will be talking about VHDL concurrent statements. So let's start. But before this, and to develop some basic foundation, we wanted to tell you that unlike any software programming languages, which normally executes the statements sequentially, VHDL allows you to control the execution of your statements. Means it allows you both concurrent execution and sequential execution as well. And we talked about it in our previous sessions when we talked about the process blocks in VHDL. Ideally, VHDL architecture processes the statements concurrently, means all the statements inside the VHDL architecture body executes simultaneously. But if you need sequential execution, or you are using some of the VHDL features which are only supported in the sequential execution mode, like if-else statement or case statement or loops in VHDL, then these must be written inside the process block. So the statements inside the process block will only execute sequentially. So this concludes that we have two types of executions in VHDL. First is concurrent execution or parallel execution. These statements will execute simultaneously. And second is sequential statement. These statement executes in a specified order and they must be written inside the process block in VHDL. In this session, we will be talking about VHDL concurrent statements, and we will see that what type of concurrent statements we have in VHDL and which we can use in our VHDL codes. Okay, so I have listed these 6 type of statements in VHDL, which executes concurrently. Hence, they must be written inside the architecture body. I mean outside the process block. Okay, so these are process block, component instantiation, concurrent signal assignments using assignment operator, conditional signal assignment using when else statement, selected signal assignment with select statement, and generate statement. We have already covered the first 3 types in VHDL statements in the previous session. So we will not go in much details on these topics in this video. We have also seen how the process block and the process statement works in VHDL. So in brief, all the statements inside the process block will execute sequentially, but you are allowed to write multiple process blocks within the same architecture block. And all the process blocks within the architecture always executes concurrently. This means only the statements inside the process block are sequential statement, but the process block itself is a concurrent statement. The second type of concurrent statement is component instantiation. We have seen this in the last session, that how to create the instances of components in VHDL files and how to use them and how to do the port mapping. We also know that we can create as many instances of components as needed for our requirements. But remember that all these components and their instances will execute parallelly. Hence, we said that the component is a concurrent statement. Okay, now let's talk about assignment operation. So this is called assignment operator, and we have already used this many times in the previous session. So we are not going deep today. Here I have copied some of the examples of assignment operation. I hope you are already familiar with this operator now, and you can easily guess that what these statements are doing. But still a quick brief here. So the symbol of assignment operator is less than equals to. Well, do not read this like this, less than equals to, but instead read this like gets the value of. This symbol interpreting the direction of data flow, like the data is flowing from the right to left. Either can be a signal or some hard-coded value or any other operation. Let's quickly understand this with some examples. And we will read this assignment symbol as gets the value of, okay? First statement is dout gets the value of sig a semicolon. Second statement is sig1 gets the value of a and b semicolon. Third statement is sig2 gets the value of a plus b semicolon. So this is arithmetic operation. Fourth statement is dout1 gets the value of 1 semicolon. And fifth statement is dout2 gets the value of 1010 semicolon. Note that for the concurrent execution, these all statements must be written directly inside the architecture body. Okay, so this is something on which we didn't talk about here. So this is when else statement in VHDL. This uses data flow in the output signal based on some specific conditions on the selected signal. Let's understand this with one example. So suppose our code is architecture behave of my design is dout gets the value of 1000 when din equals to 00, else 0100 when din equals to 01, else 0010 when din equals to 10, else 0001 semicolon and architecture. So this is the kind of encoder design here. And it says that D out will get the value of 1000 when the D in signal has the value of 00. Else, the D out will get the value 0100 when D in is having the value 01. Similarly, D out will have the value 0010 when D in is having 10. And if these all the conditions do not match with the D in, then the default assignment of 0001 will happen to the output D out, which is written after the else command. Now we have this next concurrent statement in VHDL, and this is with select statement. This also uses data flow based on some specific condition on the selected signal. So you can see this example here, and it says architecture behave of my design is with D in select D out gets the value of 1000 when 00, comma 0100 when 01, comma 0010 when 10, comma 0001 when others, semicolon, and architecture. Okay, so the first statement here is the common signal for which we are checking the condition, and we will assign the respective data to the output which matches the condition based on that selected input. So here we have written with D in select means we are checking the D in value in this list here. So the first statement is D out gets the value of 1000 when 00. Note that we didn't specify the selected signal name here. We are just checking it with the value. This is because we already mentioned that what signal we are checking with these values. Okay. So this means when D in will be 00, then D out will get the value of 1000. Same way, 0100 will be assigned to D out when D in will be 01. Next, 0010 will be assigned to D out when D in will be 10. And there is a default condition when no value matches with the D in, then this data 0001 will transfer to the D out. Well, notice the comma at the last of each line. Here we have used comma to separate the test condition. So you must remember that although they are written in the multiple lines, but all these lines are called as a single statement. VHDL will treat all these lines here as a one single statement. Notice the semicolon symbol that is just written on the last statement after others keyword. So this semicolon here tells that the statement is ending here, not at the previous line, when we used comma for separating different conditions. Okay, so that's it for today. Do not worry, we will be doing the practical sessions on these VHDL statements later. So you will become more familiar with those concurrent statements. In the next session, we will be talking about generate statement in VHDL. In the last session, we talked about concurrent statements in VHDL, and we also discussed process statement, component instantiation, assignment operator, when else statement, and with select statement. Now let's talk about generate statements in VHDL. So let's start. The generate statement in VHDL is one of the powerful tools which can be used for hardware instantiation. It comes with two main types. Number one is for generate statement, and number two is if generate statement. Both these type of generate statements allows you to create multiple instances of hardware components, but they both have different purposes and we use them in different scenarios. We will talk about this in some time. But in short, for generate statement allows you to instantiate many number of components with very small section of code. And with if generate statement, you can instantiate your modules when it matches with some specific conditions. The if generate statement can be used to make your design flexible because you can trigger your hardware instances on or off very easily. So if you have the requirement when you need to create hardware when some specific condition meets, then you can use if generate statement there. Both type of generate statements can be used to create component instances, signal assignments, and even for the process blocks. Now let's talk about for generated statement in little more detail. The for generated statement is especially useful for replicating the hardware. This means you can create many identical copies of the same hardware block with very minimal number of code. For example, if you need to instantiate 20 components in your VHDL file, then one simple way is to write 20 component instantiation codes manually. But this is not a good solution, and your code may look complex and it would be time consuming as well. So instead, you can use for generated statement, and that will allow you to instantiate all 20 components with just few lines of code. The syntax of this for generated statement is very similar like the for loop in the traditional programming languages like C or C++. In VHDL, you also mention label at the beginning of the generated statement. The loop parameter acts like a counter, which specifies the range of the values for each iteration, and the code within the generated statement will execute it for the each iteration. And this iteration creates the hardware instances or hardware blocks. Now let's see the syntax of for generated statement first. So we start from the label. It is any name. You should give this to identify the region for your generated statement, and this is useful for the future references. Then use colon and then write for. Then give the parameter name or range variable. Then type in. Now give the range of your loop. It will tell that how many instances it will create. Like if you give 0 to 3, then it will create 4 instances for each repetition. Next, write keyword generate. Next, you need to define the hardware which you need to generate multiple times. Then you can write your design here, or you will call the components here. And in the last, this generate statement ends with the keyword and generate and semicolon. To understand this in little more details, let's consider an example where you have a 16-bit STD logic vector signal named as input signal, and you want to create two 8-bit STD logic vector signals named as even bit signal and odd bit signals. So the even bit signal will capture the even number elements from the input signal, and odd bit signal will capture the odd numbered elements from the input signal. First, let's see that how you will write them manually. So you need to assign each element in your code, and that would require multiple lines of code. For each instance, you need to write one assignment line. Okay. However, if you are using for generated statement, then it will simplify your whole code. So let's see how to write it for the same example with for generated statement. Okay, so first of all, we will give it some label for generated statement. Then use colon and write keyword for. Then we will give some loop variable, which will define a loop parameter that runs from 0 to 7. So total 8 iteration in our example. Now within this loop, we will assign the even and odd elements of input signal to even bit signal and odd bit signal respectively. So we have written even bits count gets the value of input sig 2 multiplied by count semicolon. Next line is odd bits count gets the value of input signal 2 multiplied count plus 1 semicolon. So you can see that how this approach reduces the amount of code to perform the same task. We have completed our task in just 4 lines. Instead, 16 lines in the traditional method, right? Let's look at the another example, and it will make you clear how and where to use for generated statement. This time, I want to instantiate a component of our entity sub1 20 times. If you remember, we created this entity sub1 in our previous video to show how component instantiation works. In that video, we instantiated 2 hardware blocks of entity sub1, and we instantiated them by manually writing the component for each instance. So we have written it 2 times. So now you can sense that for 20 elements of this component, you need to write your code 20 times for component instantiation. And writing these 20 component instantiation manually is going to take a lot of time. So let's see that how the generate statement can be used here. To start, I have written the skeleton for the for generate statement first. We used generate parameter I here, which is having a range from 0 to 19, which means this loop will run 20 times. Now look at the center body of this for generate statement. We write our code similar to the previous video. It is like that we are instantiating a single component block. So just like before, I have connected signal 1 to port A, signal 2 to port B, and sum to port D out. Well, if you run this code, then you will have 20 iterations. Means it will create 20 different components of entity sub1, and all the components will be connected to signal 1, signal 2, and sum respectively. However, all 20 components having the same inputs, so they are producing the same output. So here it does not sound very useful, right? It will be useful when each component is connected to the separate input and it will give the separate output, right? So to make this more practical, we need to modify the signal. Now we will make signal 1, signal 2 and sum into integer arrays with 20 elements each. This way, each component will have its own set of input and output signals. The code now will generate 20 components, with each component having its own unique input and output signals connected to it. Now in this slide, we will see that how your code will generate 20 hardware blocks on the device. So for the first iteration, the for generate loop creates the first component instances of entity sub1. Now port sig A of this instance is connected to the element at index 0 of signal 1. Port signal B of this instance is connected to the element at index 0 of signal 2. And port D out of this instance is connected to the element at index 0 of signal sum. In the second iteration of the for generate loop, it will create the second instance of the component of entity sub1. Now the port sig A of this instance is connected to the element at index 1 of signal 1. Port sig B of this instance is connected to the element at index 1 of signal 2. And port D out of this instance is connected to the element at index 1 of signal sum. In the same way, this for generate loop will iterate 20 times and it will create the 20 components of entity sub1. Now each component has its own input and output signals, which are separated from the array index of the input and output signals. Okay, this means that each component can add 2 integers, and that allows us to use the circuit to add 20 different numbers at the same time and get 20 different sums as a result. Now before we move on, let me quickly show you that how you can create the entire integer arrays used in this example. Although we already explained that in our previous sessions for user-defined data types and custom data types. Okay, so we need to define an array of 20 integers that range from 0 to 19. I have named this new data type as int input. Similarly, we defined an array of 20 integers that range from 0 to 36, and this data type name is int output. Now we can use these two new data types to create our signals. First, we create signal 1 using int input data type. Then we create signal 2 and they both will use int input as a data type. Okay. Finally, we created this signal sum using the int output data type. Now let's talk about if generate statement. So the second type of generate statement is if generate statement. And this is used to instantiate hardware based on some specific condition. And this can make your design more flexible. Generally, this if generated statement is used to add any optional hardware structures in your design. The if generated statement allows you to trigger the hardware instances on or off easily, and this depends on the constant conditions, which is evaluated during the compilation. This means you can include or exclude certain hardware blocks based on your design parameters or configuration settings. You have to understand that this if generate statement is little different from traditional if then statement because you are only allowed to map any condition with a fixed constant. VSDL do not allows you to use any variable or anything which can change its value in the code itself. This means you can only use a fixed value of constant in this if generated statement to use any condition. This ensures that the condition is evaluated during the compilation and the appropriate hardware is instantiated accordingly. And the reason behind this is that the hardware is always fixed. Once hardware is fabricated, then you cannot add or remove any block from that chip, right? You can either use them or do not use them. But these blocks will be present always in the hardware IC chips. Because VSDL is a language for generating the hardware model. And hence this is completely makes sense here. Hope you agree with me here. Now let's see the syntax of if generated statement first. So it starts with label colon if condition 1 generate. Now here it evaluates two primary conditions, condition 1 and condition 2. If condition 1 is true, then the VHDL compiler generates the hardware, which is specified in the first section of this block. But if condition 1 is false, but condition 2 is true, then the compiler will generate the hardware which is specified in the else if condition 2 generate section. And if both condition 1 and condition 2, both are false, then the hardware described in the else section will be generated. This structure provides a powerful tool to the VHDL designers to create the hardware designs, which can dynamically adapt to different scenarios or conditions. And this enhances the flexibility and efficiency in the FPGA and ASIC design methodologies. So you can sense that each section of this if generated statement allows for specific hardware configuration to be instantiated based on the conditional checks. And this optimizes the design reuse and the complexity management in digital circuit implementations. Now let's look over the simple example. Here we have a single condition named as assign to y. Here is how it works in practice. If assign to y is declared and set to true, then signal x will be assigned to signal y. This assignment is strictly determined during the synthesis phase and remains constant once the FPGA configuration is loaded. Alternatively, if assigned to y is false, then signal x will be assigned to signal z. So the condition assigned to y must be a constant and defined in your code somewhere. Means here you cannot use any signal whose value can change when the code drawn into the FPGA. So this condition assigned to y must either be true or false, and it must be defined as a constant number in your VHDL code. Now let's talk about little complex tasks. For example, we wanted to create an optional register in your design. So if a constant condition enable register is true, then I want to implement signal y at the output of the flip-flop, which registers signal x. Means signal y will be one cycle behind the signal x. Means if the enable register is true, then one flip-flop will be added to the signal x. Otherwise, if this condition is false, the signal will move straight from input to output without any flip-flop. Means simpler output wire will be connected to an input wire without any hardware in between. Okay. So this conditional instantiation helps in creating a flexible and configurable hardware designs. So in conclusion, the generated statements in VHDL are essential for efficient hardware design. The for generated statement allows for the replication of hardware blocks with minimal code, while the if generated statement enables conditional instantiation based on constant parameter. Both type of generated statement can be used to create component blocks, signal assignments, and process blocks, and that make them a versatile tool in the VHDL design. Okay, so we are reaching to the end of this video now. This was a quite long video, but this is one of the important feature of VHDL to understand. And with this, we have covered all generally used concurrent statements in VHDL. We talked about concurrent signal assignments, we talked about process blocks, then we talked about component instantiation, then we talked about when else statement and with select statements in VHDL. And in this session, we talked about if generated statement and for generated statement. Now in the next session, we will be starting sequential statements in VHDL. We will talk about process blocks. We will also talk about if-else statements, case statements, and many more things. In the last few sessions, we talked about VHDL concurrent statements. We talked about concurrent signal assignments. We talked about process block. Then we talked about component instantiation. Then we talked about when else statement and with select statements in VHDL. We also talked about if generated statement and for generated statement in the last session. Now let's talk about VHDL sequential statements. We are going to cover if-else statements, case statements, loops, and wait statements in couple of few videos. So the very first and most important note is that the sequential statements in VHDL can only be used inside the process block. We cannot write sequential statements directly inside the architecture body of a VHDL file. In this video, first we will talk about sequential assignment operator in VHDL, which can be used to assign values into any signal inside the process block. This statement is identical to the concurrent assignment statement, which we have seen in the concurrent statement session, right? Here is an example of a sequential assignment statement where we are assigning signal X to signal Y. But this statement is now inside the process block. Hence, this will execute sequentially. This means if this statement is outside the process block, then it will execute concurrently. But if the same statement is inside the process block, then it will execute sequentially. Okay. Although you need to learn that when you should use sequential execution and when you should use concurrent execution, because their use cases are very specific. In some cases or in your simple designs, you may get the same results while executing your statements in any of them form. But in practice, if you do not use them carefully or correctly, then you may get either the compilation error or you may get the logical error in your VHDL designs. Do not worry, we will talk about them later in this series to tell you that when to use sequential execution and when to use concurrent execution. But first, we will talk about if-else statement in VHDL. The if statement provides a way of branching on the conditions. Here is the structure or syntax of a typical if statement in VHDL. Let me read it first. So it is if condition 1, then we have code section 1. Else if condition 2, then code section 2. Else if condition 3, then code section 3. Else code section 4. And if semicolon. So this sample code checks for the 3 conditions. You can check more conditions as well based on your needs, just by adding more else if statements in this. The conditions involved in this if-else statements are usually written as Boolean expressions. So they are evaluated as either true or false. We will see this with some examples in the upcoming slides. So if the first condition is true, then the code written in the code section 1 will be executed. If the first condition is false, then only the if statement checks for the second condition. And if the second condition is true, then the code written in the code section 2 is execute. And if the first and second condition both are false, then the if statement checks for the third condition. And if the third condition is true, then the code written inside the code section 3 will be executed. And finally, if none of the condition is true, then the code in the code section 4 will execute. The syntax here is very similar to C or C++. But if you notice about the keywords, then they are slightly changed in VHDL. So first of all, else if. So it is not ELSEIF, it is ELSIF. Okay. So make a note of it that else if has missing E here in this VHDL keyword. Next important point is each if statement must be ended with an if statement. And the third note is there is no bracket needed to group the statements in VHDL for the code sections. Now let me tell you the most important point with the if-else statement. And it is that if-else statement has the priority in place. This means that the first condition is having the highest priority because every other condition will be ignored if the first condition is true. Similarly, the second condition has the second priority, and it works in the same manner for the other conditions as well for the below the line. This means that if the first condition is true, then the statements will only execute the code in the code section 1. It does not matter if condition 2 is also being true at the same time. Means it will execute the statements inside the code section 1 and then exit from the if-else block. It will not even check for any other condition there. And this prioritization is having a negative impact on the hardware generation. We will see that in some time here. But before this, let's look for this simple example. This is a 4:1 multiplexer. Here is a simple example of a typical if statement used inside a combinational process. Because this is a combinational process, means the sensitivity list must include all the signals that the process will read. So the process needs to read signal A, B, C, D, and select input. So all of these signals are going to use inside my sensitivity list at the top. Okay, so let me read the code first. So it is mux process select A, B, C, and D. Begin if select equals to 0, 0, then Tout gets the value of A. Else if select equals to 0, 1, then Tout gets the value of B. Else if select equals to 1, 0, then Dout gets the value of C. Else Dout gets the value of D. And if semicolon and process semicolon. So this if statement checks for the three conditions. The first condition checks if select equals to 0, 0. Then Dout is assigned the value of signal A. If the first condition is false, then the second condition checks if select equals to 0, 1, and if this condition is true, then Dout is assigned the value of signal B. Then the third condition checks if select equals to 1, 0, and if it is true, then Dout is assigned the value of signal C. And in the last, if none of the condition is true, then the simulator executes the else section and Dout is assigned the value of signal D. Okay, so this is the hardware implementation of our if statement. For this example of multiplexer, input A, B, C, and D are on the left hand side, and our output signal Tout is on the right hand side. And the hardware consists of a few multiplexer and some logical gates. Note that I have color coded this according to the conditions being tested. So the red circuitry is used to realize the first condition. The blue circuitry is used to realize the second condition. And finally, the green circuitry is used to realize the third condition and also the default condition. Each multiplexer has two inputs labeled as 0 and 1. And the AND gate output is connected to the selection pin of multiplexer. So it acts as a select lines. So when the AND gate output is 0, then the multiplexer passes input 0 data to its output. When the AND gate output is 1, then the multiplexer passes input 1 data to the output. So let's look at the first condition, which has the highest priority. The first condition is realized by the red circuitry. I have highlighted the relevant signals with the yellow colors here to show you the clear picture of what is happening here. Let's assume that we meet the first condition and select is equals to 0, 0. Since select 0 is 0 and select 1 is also 0, so the AND gate output will be 1. This is because we have the NOT gate adjustment before the AND gate. And this causes the red multiplexer to select signal A and pass it to its output. Now let's take a look at the second condition, which has the second highest priority. The second condition is realized by the blue circuitry. Again, I have highlighted the relevant signal so you can see that what is happening clearly. For the second condition, let's assume select is 0, 1. And in this instance, the red multiplexer passes input 0 to the output, and the blue colored AND gate output will be 1. When select equals to 0, 1, this causes the blue multiplexer to select signal. This causes the blue multiplexer to select signal B and it will pass to the output. Now let's take a look at the third condition, which has the third highest priority. The third condition is shown by the green circuitry. I have highlighted the relevant signals again so you can see that what is happening. For the third condition, let's assume select is 1, 0. Therefore, both the red and blue multiplexer select input 0 to pass to the output. The green colored AND gate output will be 1 when select equals to 1, 0. So this causes the green multiplexer to select signal C and it passes to the output. Finally, let's look at what happens when all three conditions are false. Let's assume select is 1, 1, and in this case, all these conditions will be failed. Under this condition, all three multiplexer will select input 0 and it will pass through to the output. So signal D will reach to the output. So this is how the if-else statement works and how it implements in the hardware. It may be a little tricky to understand at the moment if you are completely new. But if it is the case, then I will recommend to watch this section once again because this is really important to understand for good VHDL designing, which we will be talking about in this learning series. Now I wanted to tell you another important concept in hardware designing or chip designing, and that is about timing. This is really important to understand as a VHDL designer, and this is really a great example to understand this. So the combinational circuits such as logical gates and multiplexer, they do not react instantly to their input. You can visualize this from the simple screenshot on the screen. Let's look at the simple AND gate, which is having two inputs and one output. The inputs are input A and input B, and the output is C. So the timing diagram shown below here. This shows signal A going to high at some point of time, but B remains slow. And then after some time, signal B also goes high. But you can see that output C only goes high after some time later of it. This is called timing delay, and this time delay is labeled as TPD in this diagram. This delay is also called logic delay or propagation delay or gate delay, etc. And all logic circuits are having this propagation delay, which means that the input signal takes some time to reach to the output, since it has to travel through the logical device or elements. Now before we move on, let's quickly recall few of the important points about the if statement. Firstly, the conditions must return a Boolean value. Otherwise, the compiler will give you some error. When any statement which has more than one condition to check, then it creates a cascade of multiplexer. Like in our previous example of multiplexer, we had three conditions. So we had three multiplexer cascaded together. If you look back at the circuit diagram of if statement, then you will see that signal A only needs to go through one multiplexer to get to the output. Therefore, signal A will reach to the output quickly compared to the other signals like signal B or C or D, as it only has to go through from a one single multiplexer. On the other hand, signal C and signal D have to go through three multiplexers to reach at the output. Therefore, the logical delay for reaching signal C or signal D to the output will have three times of the logical delay for signal A. And this is something the unwanted effect of using the if-else statement. However, the case statement does not suffer from this problem. So you should prefer to use case statement instead of an if-else statement whenever it is possible. And we will be talking about case statements in the upcoming session. In the last few sessions, we talked about VHDL sequential statements, and we learned about one of the commonly used sequential statement, and that is if-else statements. Now let's talk about another important sequential statement, which is case statement in VHDL. So let's start. The VHDL case statement is a sequential statement, means it can be only used inside a process block. It provides a way to branch conditions, just like if-else statements, but there are some key differences. Unlike if statements, the condition in a case statement does not need to be a Boolean expression. The VHDL case statement is similar to the switch case statement in C or C++. The syntax for a case statement in VHDL allows you to define the expression with multiple choices. The case statement evaluates the expression and checks if it is matching with any of the provided choices. If a match is found, then it executes the corresponding code. And if the value do not match with any options, then when others action will execute. The expressions used in the case statement must be a signal of an enumeration type or an integer type, and the choices must match with the data type of the expressions. Each choice must be unique and cannot be duplicated, and choices must be a fixed value, means they cannot be any signal or variable whose value can change within the code. Additionally, if all possible choices are not covered, then in such cases we have when others statement, just like the default case, which can handle any remaining cases. To understand this, consider an example of a case statement within a combinational process, where all the signals are declared as STD logic vector of 2-bit. In this case, signal select is used as the expression. When select is equals to 0, 0, then dout is assigned the value of signal A. When select equals to 0, 1, then dout is assigned the value of signal B. When select is 1, 0, then dout is assigned the value of signal C. Finally, when select equals to 1, 1, which is covered by the when others clause, then dout is assigned the value of signal D. So the code we have written here is mux colon process select A, B, C, D begin case select is when 0, 0, then dout gets the value of A. When 0, 1, then dout gets the value of B. When 1, 0, then dout gets the value of C. And when others, dout gets the value of D. And case semicolon and process semicolon. The case statement is implemented in the hardware using a multiplexer, where select acts as a select line, and it can have 4 different values: 0, 0, 0, 1, 1, 0, and 1, 1. Therefore, the multiplexer has 4 inputs. When select equals to 0, 0, the multiplexer passes signal A. When select is equals to 0, 1, then it passes signal B. And when select equals to 1, 0, then it passes signal C. And when select equals to 1, 1, then it passes signal D. Inputs A, B, C, and D only need to go through a single multiplexer to reach to the output, resulting in a relatively low logical delay and better circuit speed compared to the equivalent if-else statement like we have seen in the last session. In another example, a case statement inside a registered process block which sets the output dout to 0 in the reset condition. So the case statement is written inside the clocked area of the process block, but its syntax remains unchanged. So we have written registered process colon process reset and clock begin if reset equals to 1, then dout gets the value of 0. Else if at the rising edge of clock, then case select is when 0 0, then dout is A. When 0 1, then dout gets the value of B. When 1 0, then dout gets the value of C. And when others, dout gets the value of D. AND case, AND if, AND process. This means the data will be assigned to output only at the rising edge of the clock. And the case statement are exactly same here like the last example. The only difference is that it is now inside the if condition with the rising edge of clock. Now let's quickly see that how it will implement in the hardware. The main difference in the hardware implementation is the presence of a D-type flip-flop at the output of the multiplexer. Now it's time for some tips and tricks for you for the VHDL case statements, which you can use in your practices. First is, when writing the case statements, you can combine multiple choices into a single when statement using the vertical bar. It is a logical OR operation, resulting in a simpler code without changing the resulting hardware. For instance, if you want to assign signal A to the output when the test signal is 0 0 or 0 1, so you can combine these two choices into a single when statement. Now similarly, for the integer expression, you can also specify a range of choices using the keyword to, which simplifies your code, like you can see in this example here. So we combine these three statements here for value 0 and value 1 and value 2 in one single when statement. We are able to do this because for these three items, we are getting the same output. So we have written single when statements like when 0 to 2, then dout gets the value of A semicolon. However, there are some limitations while using the case statements in VHDL, which you need to remember while using the case statements. One of the important note is that the VHDL does not allow you to have the same choice for two or more when statements. Means one choice can only be used only one time. As you can see in this example, I have marked the duplicate values with the red color. So this is not allowed. Another important point is the test condition. The test condition which you are going to use with your when statement that cannot be any signal or variable. Means that value should be a constant or a fixed value. That cannot be any variable item. Like you see in the second example, where I have written when sig1, then dout gets a value of A semicolon. So here I cannot use sig1 in this case statement because its value can be changed in a system. Okay, so that's it for today. We will cover it in more details in the practical sessions. In the next session, we will be talking about for loops in VHDL and its application. And we will see that how it works in the real hardware. We will also talk about do and don'ts for the for loop as well. In the last session, we talked about VHDL sequential statements and we covered if-else statement and case statement. Now let's talk about for loop statement in VHDL. We will see how to use for loops in VHDL, how it works, and we will also see that how it works in real hardware. We will also cover important tips and tricks about for loops in VHDL designing. So let's start. In VHDL, for loops are used to repeat a section of code for a fixed number of times. And because it is a sequential statement, that means it must be written inside a process block. Here is a basic syntax of for loop. And you can see the keywords which are highlighted with blue color. So before we start, let's have some basics first. So for loop uses loop variable to control its loop execution. The loop variable can only exist within the loop and cannot be accessed once loop is completed. The syntax for a for loop in VHDL begins by declaring a loop variable name and the number of iteration. So it is for then loop variable name in range loop. Now you will write the code here that needs repetition and a loop semicolon. Here is a quick example of a for loop in VHDL. So it is my loop colon process a comma b begin for I in 0 to 2 loop dout I gets the value of a 2 minus I and bi semicolon and loop and process. Here I is our loop variable which have the range from 0 to 2 means total 3 cycles of repetitions. For the first iteration value of I would be 0. Then for the second iteration value of I would be 1 and for the last cycle value of I would be 2. Now here are a couple of important terms about for loop. The for loop uses a loop variable to control its execution. This loop variable exists only within the loop and cannot be accessed once loops gets finished. The loop variable name must be specified at the beginning of for loop. The code inside the for loop can use this variable name to access the loop variable. Each repetition of the for loop is called an iteration, and the range specifies that how many iterations will occur. Now here is a simple example to specify the range in for loop. Let's say we specify a range from 0 to 2. This means the for loop will run 3 times in total. In the first iteration, the loop variable will be 0. In the second iteration, the loop variable will be 1 and so on. In this example, for loop is written inside a combinational process block. The first line declares the loop variable I and the number of iterations. So the loop variable I goes from 0 to 2. So there will be total 3 iterations. In the first iteration, I will be 0. And in the second iteration, I will be 1. And in the last iteration, I will be 2. And the code inside the loop will be repeated for each iteration. So the for loop will essentially generate these 3 statements shown here in the bottom section. So dout0 gets the value of a2 and b0. Dout1 gets the value of a1 and b1. Dout2 gets the value of a0 and b2. Let's see how this works. So for the first iteration, I is 0. So we replaced I with 0. So we have our first statement as dout0 gets the value of a2 and b0. Now for the second iteration, I is 1. So let's replace I with value 1. And we have our second statement, which is dout1 gets the value of a1 and b1. In the third iteration, I is 2. So again replace I with the value 2. And we have our third statement, which is dout2 gets the value of a0 and b2. Means both of these codes in these 2 separate blocks will give you the similar output. Means both of these codes are exactly same and will generate the same hardware. So you can use both ways here. But assume that the iteration is 100 times for your requirements. Then in traditional approach, you need to write 100 statements. But with for loop, you can achieve the same thing with very few lines. So that's where you can prefer to use for loops in VHDL. But you need to remember is that the for loop replicates the statements written inside the for loop. Now let's see the hardware implementation of for loop. So as we know that the evaluated code translated into the AND gates, like we explained in the last slide. On the left, we have inputs like input A and input B. These are 3-bit STD logic vector signals and having range 2 down to 0. On the right, we have our output dout, which is also a 3-bit STD logic vector and having the range 2 down to 0. And there are 3 AND gates generated with the 3 different indexes, which are mentioned in the structure, and they are corresponding to their each output index. Now we will talk about for loops in the registered process block. Here is an example of using the for loop in a registered process. We are using the same for loop example as before, which evaluates to the three statements. So for a registered process block, we have reset and clock sections. In the reset section, we set all the signals to their default state. So Dout is 0, 0, 0. In the clock section, we write our for loop just as before. So this is our complete code. My process colon process reset and clock begin if reset equals to 1, then Dout gets the value of 0, 0, 0. Else if for the rising edge of clock, then for I in 0 to 2 loop, Dout I gets the value of E2 minus I and Bi semicolon and a loop and if and process. Now let's look at the hardware visualization of our for loop in the registered process block. You can see 3 AND gates. These are just exactly same like we have before. Here the only difference is that we have added 3 flip-flops at the output of the AND gates. Note that for simplicity, I have not included the clock and reset signals here, but they are also connected with these flip-flops. So here are some useful tips about for loops. First, you can use array attributes to define the range. Here we have some for loops as in our previous examples with signal A, B and Dout. In the second box at the bottom, I have written the for loop slightly differently. So you can see I have used the right and left attributes of Dout to define the range. So I have written for I in Dout right to Dout left loop, Dout I gets the value of A2 minus I and Bi and loop. The right attribute of Dout returns 0 and the left attribute returns 2. So ultimately for loop range will be 0 to 2 for our example. The advantage of this approach is that if the size of Dout changes, then the number of iterations will automatically adjust to match the size of Dout. In the another example, I have used the range attribute of Dout, which returns 2 down to 0. So I have written for I in Dout range loop, Dout I gets the value of A2 minus I and Bi and loop semicolon. Now let's understand this. Although the final output would be same here in terms of hardware generation for this example of AND gate, but the processing is little different because so far the loop variable in our for loops was counting in ascending order, means from 0 to 2. However, for this code, our loop variable is in the descending order. So it starts from the 2 and it will go down to 0. This means the statements will execute for I equals to 2, then I equals to 1 and finally I equals to 0. Another important keyword is exit, which you can use in for loops to take the early exit from the loop. In this example, we are running our for loop for 8 iterations. The loop variable will start from 0 and it will repeat itself for up to 7 cycles of repetitions. So the first iteration starts with I equals to 0. The second iteration with I equals to 1. The third with I equals to 2. And the fourth with I equals to 3 and so on. Now suppose in some condition we want to take the exit from this loop cycle. And this is possible with the exit statement. So here is a simple code. Note that this time we have Dout and this Dout is a STD logic vector signal and it is 8-bit long. So our code is for I in 0 to 7 loop, Dout I gets the value of 1 if I equals to 3, then exit, and if AND loop. So we specified the condition that when I equals to 3, then exit the loop. So you can see that the if condition is true when I equals to 3. So we exit the loop. There is an alternative way as well of writing the same code, which you can see in the second example. Here I have used when statement instead of an if else statement to exit the loop. So I have written for I in 0 to 7 loop, dout I gets a value of 1, exit when I equals to 3, and loop. And these two statements are equivalent to each other. Now here is an important key point to note about the for loop, that you cannot change the loop variable inside the loop. Here is an example of a violation that we try to change the value of I to 3, and this is not allowed. This was pretty basics about the for loops in VHDL. We will practice it more in the practical sessions later. In the next session, we will be talking about wait statements in VHDL. In the last session, we talked about for loops in VHDL. We learned how to use them and where to use them. We have also seen how it generates the hardware on the FPGA devices. Now let's talk about wait statements in VHDL. VHDL wait statement is sequential statement, and hence it also needs to be used within the process block. Before we start, I wanted to make this clear that the wait statement is not synthesizable. This means that we can only use wait statement in simulation of our models or test benches, but they cannot run on the FPGA devices. Also, you should know that the processes that have a wait statement inside it, they must have empty sensitivity list. This means that there should be no signals written in the sensitivity list of that process block. So quick notes, wait statements are used only in simulations. Wait statements allows us to pause the simulation in two different ways. First, we can pause the simulation for a fixed time period or duration. Second, we can pause the simulation until some event has encountered in our simulation. In the next few slides, we will look at different forms of wait statements. So first, let's look at the most basic form of a wait statement. Here is a very simple process with an empty sensitivity list. Remember that the sensitivity list of a process block must be empty if you are using a wait statement. So in the first example, I have written test colon process begin y gets the value of x, wait z gets a value of y, and process. So when this process runs, it executes the first statement, which assigns x value to y. Then simulator hits this wait statement, and the process stops here, and it will not go further from this point. So our wait statement pauses the processes, and any statement after it will never execute. So this whole process will not run again. Or you can say that the process stops here permanently, and it will not go further from this statement here. Now let's look at the second example where we have used wait for statement. This allows us to implement some fixed delay. So I have written test colon process begin y gets the value of x, wait for 100 nanosecond, z gets the value of y, and process. So here I have the same process as before. We run the first statement which assigns x value to y. Then it gets the wait for statement, and the process stops here, but only for 100 nanoseconds. After 100 nanoseconds, the process resumes and executes the last statement, which assigns the value of signal y to signal z. Now at the end of this process, the process stops here, but the whole process block will trigger immediately, just after it gets finished. This means that as soon as we execute the last statement, where z gets the value of y, the process will start again, and the first statement, which is y gets the value of x, will execute. Then it will wait for 100 nanoseconds, and then it will execute the last statement again, which is z gets the value of y. And this process goes round and round like this and infinite time until you manually stop the simulation or close the simulation. Now we will see that how we can generate a clock signal using wait for statement. So this is a simple code for our 50 megahertz clock signal. So I have written clock generator colon process begin clock is 0, wait for 10 nanosecond, then clock is 1, wait for 10 nanosecond, and process. So this is one way of generating a 50 megahertz clock signal. Let's see how it works. So at the beginning of the process, we assign the value 0 to the clock signal. Then we wait for the 10 nanoseconds, and then we assign 1 to the clock signal, and then wait again for another 10 nanoseconds. Since the process keeps repeating over and over, the result is that we get a nice 50 megahertz clock signal. Now let's look at the wait on statement. The wait on statement allows us to pause the simulation until some event happens. Here is a simple code for this. So I have written test process begin y gets the value of x, wait on a, z gets the value of y, and process. So let's see how it works. So in this example, the process will execute the first statement, which assigns x value to y. Then it encounters the wait on statement. The wait on statement will pause the process and it will wait here until signal A changes its state. So the process will only continue when signal A changes its state. This means that if A was a logical 0, for example, then it needs to change to a logical 1 for the process to continue. When A changes its state, then the process will continue to execute the subsequent statements, and the rest of the functioning will work as explained earlier. Now let's talk about the wait until statement. The wait until statement gives us more control as compared to the wait on statement. The wait until statement allows us to pause the simulation until a signal changes to a specific state, which is mentioned by the user. Let's see how it works. So look at the second code on the screen. This is for the wait until statement. So I have written test process begin y gets the value of x, wait until a equals to 0, z gets the value of y, and process. So within the first statement, x value is assigned to y. Then comes the wait until statement. The wait until statement will pause the process, and the process will only continue when signal A becomes 0. Otherwise, the process will not continue from here. Here is another application of wait until statement. Here I am going to use the wait until statement to wait until there is a rising edge of a clock signal. So before continuing, we use the rising edge function to detect if there is a rising edge on signal A. If a rising edge is detected, then the process will continue to execute next line, which is z being assigned the value of y. So we have written our code like this. Test process begin y gets a value of x, wait until rising edge of clock, z gets the value of y, and process. Okay, so that's it for today. Here is a quick recall what we have learned in last few sessions on VHDL sequential statements. So sequential statements are a fundamental aspect of VHDL programming, and it is essential to understand their proper uses and implementations. We have covered several key points. Firstly, remember that the sequential statements can only be used inside a process block. This restriction ensures that those sequential statements to execute in a specific order, which is essential for designing and simulating digital circuits accurately. The most commonly used sequential statements in VHDL is if-else statement, case statement, for loop statement, and wait statement. Each of these statements serves a unique purposes, and they are used to control the flow of execution within the process. We have learned the syntax for each of these statements. If-else statements are used for the conditional execution. This allows different parts based on the specific conditions. The case statement provides a more structured way to handle the multiple conditions, and this makes the code easier to read and maintain. The for loop statement is used for repetitive execution, and it's repeat the code over a range of values in the repetitive cycle. The wait statement is used to pause the execution of a process until a specific condition is met. So we discussed their appropriate uses and limitations. For example, if-else statement is straightforward for simple conditions, but it can become complex and how to manage with multiple nested conditions. Whereas case statement is preferred over the if statement for handling multiple choices because it is more organized and efficient in hardware implementations. We briefly covered the propagation delay in the logical circuits, which is the time that needs for a signal to travel through a circuit. We explained that why understanding of propagation delay is crucial for designing the high-speed circuits. We discussed why case statements are often preferred over the if-else statements, as case statements can help reduce the complexity and the potential delays in the logical circuits, and we have seen how it helps to do that. Additionally, we explored that how each statement translates to the FPGA hardware. This is important for gaining the deeper insights into the VHDL coding. For example, knowing how a for loop is synthesized into a hardware can help you in optimizing the design for better performance and resource utilization. And with this, we have reached to the end of this discussion on sequential statements in VHDL. So by understanding these key aspects on sequential statements, you can write more efficient and effective VHDL codes, ultimately leading to a better digital circuit designs. In the next session, we will be talking about signal assignments in deep, which is important to understand for good VHDL designing. In the last few sessions, we discussed different sequential statements. We talked about generally used statements like if-else statement, case statement, for loop statement, and wait statement. We explored that how each of these statements translates into the FPGA hardware. We also talked about good practices for efficient VHDL designs. Now let's talk about signal assignments, which is important to understand for good VHDL designing. In this session, the prime focus is signal assignments, which are written inside the process block. And this concept is most important to understand because these signal assignments in VHDL are little tricky and their behavior is different from the other programming languages like software programming languages. Because here the goal is to develop the hardware system based on the requirements. It is not just an execution of statements like in the programming languages. So my recommendation is that always consider for the underlying hardware implementation when you are working with the VHDL language. By doing this, the concept and the behavior of the signal assignments become much clearer and easier to understand. Analyzing signal assignments with considering the respective hardware implementation allows you to understand their behavior in more details. And this approach provides you a practical perspective and will help you to bridge the gap between the code and the physical hardware. As we know that VHDL process can be mainly categorized into two types, register process and combinational process. And we will discuss the rules and principles that applies to the both type of processes. And in our next section, we will focus specifically on the best practices when working with purely register process. And we will see its unique characteristics and applications. So just to give a quick recall from our previous sessions that the register process are designed to execute only on the rising edge or falling edge of a clock signal. So it ensures a synchronous behavior in the digital circuits. One key point to remember is that a register process always creates a flip-flop. These flip-flops are essential components in storing and synchronizing data with the digital systems. And in contrast, a combinational process is responsible for creating a purely combinational logic. This means it involves logical gates that performs operation based only on the current input values without any form of memory. Importantly, a combinational process does not create a flip-flop. Instead, it's a hardware that is entirely on the immediate evolution of the logic gates, and that makes it a memoryless hardware design. In this video, we will use the examples of combinational processes to understand this important concept. However, it's important to note that these ideas and rules also apply to the registered processes as well. So let's examine the hardware implementation of a typical combinational process. This will help you to visualize that how the combinational logic is constructed and how it operates in a physical circuit. Note that a purely combinational process does not include any register or flip-flops. It consists only of logical gates that performs operations based on the current input values. It is composed entirely from various logical gates, such as AND gate, OR gate, NOT gate, and other basic logical functions that collectively perform the desired operations. These gates can be configured to implement the basic logical functions, such as multiplexer, adders, multipliers, and more complex combination circuits, depending on the design requirements. The primary restriction in a combinational process is the absence of flip-flops. All operation must be performed using only logical gates without any form of memory elements. So that need to remember always. Let's consider an example of a combinational process. Let me quickly read the code first. Test colon process A, B, C begin if A equals to 1, then D out gets the value of 0. Else D out gets the value of B and C, and if AND process. So in this process, we have three inputs: input A, input B, and input C. Since this is a combinational process, so it's important to list all the inputs in the sensitivity list to ensure the process reacts to change in any of these inputs. Within this process, I have used an if statement to check if the input A is equals to 1. If A is equals to 1, then the output signal D out will be 0. Otherwise, D out will do the AND operation between the signal B and signal C. This example is a very straightforward combinational process. So this makes it relatively easy to analyze and understand. Now let's see that how this process will be implemented in the hardware that will focus on the actual physical construction. So here is the hardware implementation of our combinational process. This diagram shows that how the logical gates are interconnected to achieve this desired functionality. In this implementation, the if statement is realized using a multiplexer. When A is equals to 1, then the top input of the multiplexer is selected and D out is assigned a value of 0. But if A is 0, then the multiplexer selects the bottom input, which drives the D out. The bottom input of this multiplexer is the result of the AND operation between signal B and signal C. The input signal A, B, and C can change their states at any time, and that reflects the dynamic nature of a combination logic. So what happens to the output D out when any of these inputs changes? So the output D out will change its state after the logical delay, and this is known as propagation delay or circuit delay. This is also called gate delay or logical delay, etc. The signal must pass through the AND gate and the multiplexer before reaching to the output D out, and that contributes to the total propagation delay from input to the output. As a result, the delay from the B and C to D out will be slightly longer compared to the multiplexer first input, and that is due to the additional gate involved in the bottom pin. In contrast, changes in the signal A will experience a shorter propagation delay since A will only pass through with this multiplexer only. This example clearly demonstrates that how the propagation delay impacts the behavior and the timing properties of a purely combinational process. The key takeaway is that a combinational process is entirely defined by its logical equation, which defines the relationship between the input signals and output signals. So that is why it is important to always include all the relevant inputs to the sensitivity list to ensure the accurate and the responsive behavior of the process. If you miss to do so by mistake, then it could result in unsimulated gate delays, and that will lead to the incorrect or unpredictable behavior in the circuit simulation. Although I will say it in the behavior simulation mainly, as the synthesized results may not have that impact. Note that we cannot determine the timing difference just by examining the VHDL code. So here is the another example where we have two process blocks. The first process is at the top, named as test1, and having two statements inside it. First statement is sig x gets the value of A and B. And the second statement is D out gets the value of sig x and C. So in the first process, A and B are doing the logical AND together, and the result get assigned to signal X, which is an internal signal. Then the signal C and signal X are doing the logical AND operation, and the result will be assigned to signal D out, which is our final D output. Now consider the second process that is named as test 2. Here I have written the same statements, but now they are in the reverse order. Now the first statement is D out gets the value of sig x and C. And now the second statement is sig x gets the value of A and B. Now the question comes that will these two process blocks behave identically or they will behave differently? To answer this question, it's crucial to analyze the hardware implementation of this code. Understanding of hardware implementation will clarify you that whether the order of statements affects the functionality or not. So let's examine the hardware implementation of the first process. At the top, we have the hardware structure for the first process, test 1. The first operation assigning the result of AND operation between signal A and signal B, and the result is signal X. Then in the next step, D out is having the AND operation between signal X and signal C. Now we have a complete hardware setup for this process test 1, and that shows that how the signals interconnect in the practical circuits configurations. So this is the hardware structure for our first process block. Next, let's see the specific hardware configuration for the second process, test 2. In the test 2 process, we intentionally reverse the order of our statements to observe if there is an impact on the hardware output. Now consider the first statement is D out gets the value of sig x and C. So this determines that D out is the AND operation between signal X and signal C. Now for the second statement, we shows that the hardware implementation for sig x is A and B. So you can see that this hardware setup generates the exactly same hardware which was generated in the test 1 process. This indicates consistency in the hardware outcomes despite of different code orders. Even though when the VHDL code has different order, the resultant hardware configuration remains identical. In other words, both processes generates the identical behavior in terms of hardware output, and that ensures that the VHDL execution maintains the consistency in the functional results. So when you write your signal assignments, the order does not matter if the assignments belong to the different signals. But this is one thing, and here is a catch. Let's discuss that in the next slide. However, there is one exception, which we are going to discuss in this slide. Here we will compare two processes. The first process is test 1, so we have two signal assignments to the same signal. The second process is test 2, and this process also has the same signal assignments, but in the reversed order. This might look similar to the previous slide, but the only difference is that now the target signal where we are assigning the data is same for both the statements. So let's see how these statements will behave. First, let's focus on the first process. So I have written D out gets the value of A or B, and the second statement is D out gets the value of A and B. So in the first statement of test 1, we tell the VHDL compiler that D out is an OR operation between signal A and B. And in the second statement, we tell the compiler that the D out is the AND operation between A and B. So this is confusing because D out cannot have both the outputs, means either it can be the AND operation of inputs or it can be the OR operation of inputs, but it cannot be both at the same time. In this situation, the process has to choose the correct statement to implement. The important point is that the compiler cannot implement both the statements, right? So in such cases, the process block always selects the last assignment and ignores all the other assignments to the signal D out here. Therefore, in test 1, the first statement will be ignored and only the second statement will be implemented. As a result, An AND gate will be generated from the signal Dout. Now let's look at the second process, test 2. Similarly, we can see that the first statement will be ignored. So in test 2, an OR gate will be generated for Dout output. So this means that the order of assignments matters when there are multiple assignments to the same signal. This rules apply to the both combinational and registered process. Remember that the assignments in the sequential block, or you can say statements within the process block, only takes the last assignment. But this is not applicable for the concurrent execution, means which are directly written inside the architecture body, and it can give you the errors in your hardware generation. Now I wanted to show you an example of bad VHDL coding practice. This is very important to understand when you are writing your code for digital system design. And this is an example which you should avoid in your designs. So in this example, we have a simple combinational process where Dout gets assigned some value when A is high. The issue is that we have not specified that what will happen to the Dout when A is low. The code implies that the Dout should hold its state when A is low, right? Therefore, Dout requires some form of memory device to hold its previous state when A is low. Note that a flip-flop cannot be used here because Dout need to change its state immediately when any of the inputs changes its state. So the only memory device that can meet this requirement is a latch. So the hardware implementation can look like this. Notice that we have a latch to store and hold the value of Dout when input A is low. When A is high, the output Dout will be the result of the AND operation between signal B and signal C. And when A is low, Dout will hold its previous state. So that's the story. Well, there is nothing wrong in using the latches in the digital designs, but they are just not suitable for the FPGA designs. We told this in our initial sessions on the FPGA fundamentals that the basic building blocks of the FPGA are the logical gates and flip-flops. FPGAs do not implement the latches very efficiently. And the development tools are also not very good in performing the timing analysis of these type of circuits. As a result, latches can run slower and it may cause the glitches to the timing violation, which are very difficult to identify and debug. So avoiding the latches ensures that your designs runs faster and they are free from the glitches that can occur due to the timing violations. So the question is that how can we modify our VHDL code to avoid creating a latch? First, remember that the latches can only be created in the combinational process, not in the registered process. Register process uses flip-flops as the memory device, so there is no need of the latches here. And we only need to worry about creating the latches in the combinational processes. Latches can be created when you do not specify the state of your output for all the possible paths over the conditions. You can have multiple paths through processes because of branching statements like if statement or case statement, etc. For example, in the last VHDL code, we did not specify the state of Dout when A is low, and that leads to create a latch in the hardware. To avoid latches in the combinational processes ensures that the output are defined for all the possible branches in the code. So I have modified the example to avoid creating a latch. I ensure that Dout is assigned a value of 0 when A is not equal to 1. So here is the updated code. Test1 colon process A, B, C begin if A is equals to 1, then Dout gets the value of B and C. Else Dout gets the value of 0. And if AND process. Although the simulation output will be different here for this VHDL code. When value of signal A is 0, now the Dout will be 0 in this case. But for the previous code, Dout will not change its state when A is low. So this is the difference. And this might not be the desired behavior from your design code. And possibly you might want to take the output D out to hold its previous state when A is 0, right? So if you want D out to hold its previous state when A is 0, then you need a memory device like a latch or flip-flop. Since latches are not recommended, the only option is to use a flip-flop. And the only way to create a flip-flop is by using a register process block. Therefore, we should use a register process instead of a combinational process here. So let's see how we can convert our combinational process to a register process. Here is how we have written the same logic using a register process that employs a flip-flop instead of a latch. Test1 colon process reset comma clock begin. If reset equals to 1, then D out gets a value of 0. Else if rising edge of clock, then if A is equals to 1, then D out gets the value of B and C. And if, and process. So you can see that I still use the same if statement, which assigns the output D out only when A is high. I have not assigned a value to the D out when A is low. But this is not a problem here because our process is now a register process. So we do not need to worry about the latches in the register processes, even if all the branches are not covered. In this process, although we have not specified the state of D out when A is low, but still our hardware will not require a latch to implement this code. Instead, our hardware will use a flip-flop to store the state of the signal D out. Let's look at the hardware implementation and understand how a flip-flop can be used to implement this process. Here is the hardware that implemented our register process. Notice that we use a flip-flop instead of a latch, and if statement is implemented with a multiplexer. When A is high, the flip-flop captures the output of the AND gate. When A is low, the output of the flip-flop drives the input of the flip-flop through the multiplexer. So the signal D out remains unchanged. So there is no need for a latch. Here is the another way to implement the same circuit. This time the flip-flop has the specific enable input, which can enable or disable the flip-flop based on our requirements. The enable port of this flip-flop allows you to eliminate the multiplexer requirement from the last implementation. Most modern FPGAs includes this enable port with the flip-flops. Therefore, our process will likely to implement like this rather than with a multiplexer. Here, this enable input is driven by our signal A. When A is high, the flip-flop captures the input value on the rising edge of the clock. And when A is low, then the flip-flop is disabled. So it does not capture the input even when there is a rising edge. Therefore, the signal D out remains same as it is in the last state. With a flip-flop, FPGA development tools can better optimize the circuit timing performance and help in the timing violation, which is not possible with a latch. Okay, so that's it for today. We have covered some of the most important concepts, and I understand that if you are a complete beginners, then that may take little time to understand. So if so, then I would recommend to watch the section again, which is not clear to you. But this is really important to understand for a good design practices. So we have covered why latches should be avoided in the FPGA designs, and we also explored two ways to avoid them. The first method is to ensure that the output signals are assigned to the all possible branches of your combinational process. The second method is to use a register process instead of a combinational process block. In the next session, we will be covering signal assignments inside the register process block in the more details. In the last session, we talked about signal assignments in the combinational process block, and we also gave a brief about the concurrent assignments as well. We discussed that what are the good design practices and why latches are not good for your digital system designs, and how you can avoid latches to create your VHDL designs. And we've seen two ways to avoid them. The first method is to ensure that your output signal is assigned for all the possible branches in your combination processes. The second method is to use a register process instead of a combinational process if your requirement is not affected because of it. Now we are covering this register process block in more details in this section. So let's start. Remember that a register process executes based on a change in state of a clock signal or when a asynchronous reset signal changes. So this is our general template of a register process block. I will quickly read it first. So it is test process colon process reset comma clock begin if reset equals to 1, then D out gets the value of 0, else if rising edge of clock, then D out gets the value of function x1, x2, x3 up to xn, and if AND process. So you can see that in this template, only the clock and reset signals are included in the sensitivity list. Now, if the reset is active, then we set the output D out to 0. Otherwise, the D out gets a value based on some XYZ function on the inputs or signal, such as x1, x2, x3 here. This represents a generic register process, where D out is driven based on input signal values, or register process in this form. So, what does the hardware implementation of this process looks like? This is the hardware visualization of this process. Input x1 to x1 comes from the left, and the combination logic determines the value of the D out in the next cycle. Finally, the D out is implemented as the output of the flip-flop on the right. We saw this diagram in the previous session as well, and this is really helpful to understand our signal assignments concept. Let's replace this general function with something more specific. So here I have replaced it with a simple 2-input AND gate. So now our D out is the AND operation between input A and input B. So our VHDL code will be test process colon process reset comma clock begin if reset equals to 1, then D out gets the value of 0. Else if rising edge of clock, then D out gets the value of A and B, and if AND process. Remember, the process will only execute when signals in the sensitivity list changes. So in our case, the process executes when the clock or the reset signal changes. For now, let's assume that the reset signal is not active, means it is not applied. So now we only have the clock signal, and our processes will trigger when its state gets changed. Means when there is a rising edge on the clock signal, then our process will execute, because the clock changes its state from 0 to 1. Similarly, when there is a falling edge on the clock signal, our process also runs, because the clock changes its state from 1 to 0. Although the process runs on both the edges of the clock signal, but it only performs the useful operation on the rising edge, and it will do nothing on the falling edge of the clock signal, because the else if condition is only true during the rising edge. So on the every rising edge of the clock, the signal D out gets a value based on input A and input B. Now let's look at the timing diagram and see how this circuit operates. Here is the timing diagram, where we can analyze that how this assignment works, because understanding these timing diagrams are very important if you want to do proficient in VHDL. I have also included a screenshot of our circuit just for the reference. So I have labeled the AND gate output as signal X. So now every circuit and signal has some name, so we can easily refer them to understand. First, assume that the reset is low, means it is not asserted. So because the reset signal is at 0, so it has no impact on the circuit. Now let's look at the clock signal. So we know that our process executes whenever the clock signal changes its state, whether it goes to high or low. From our VHDL code, we know that nothing will happen to the output Dout at the falling edge of clock, right? You can clearly see this in the circuit diagram as well, because Dout is driven by the flip-flop, which is triggered on the rising edge of the clock, not on the falling edge. Therefore, Dout can only change at the rising edge of the clock signal. In this timing diagram, the rising edges of the clock are numbered from 1 to 12. So we can use these numbers to refer to the specific clock edge. Here, signal A remains high, so we can ignore it for now. Consider this just to understand it, okay? So let's focus on the input B. So you can see input B remains low until the 5th clock edge, and on the 5th clock edge, B goes high. As a result, after some logical delay, the AND gate output signal X also goes high. The logic delay is small, so sig X goes high before the 6th cycle of the clock edge. So on the 6th cycle of the clock edge, the flip-flop captures signal X, which is now high. Therefore, just after the 6th cycle of the clock edge, our output Dout also goes high. The important thing is to realize that the output signal Dout changes after one clock cycle, when the input B changes its state. Signals assigned in the register process blocks always follow this rule. So input B changes its state on the rising edge of clock 5 or after it, but the effect is seen on the output Dout only at the rising edge of the 6th clock cycle. As a beginner, you may have little difficulty to understand these timing concepts just by looking at the VHDL code. But hardware visualization can make it easier to understand these timing variations on the various signals. So do not worry if you are an absolute beginner and if you feel difficulty to understand this at the moment, because gradually you will develop a picture of these concepts in your mind. But this is really important to understand these real hardware concepts for a good digital system design. So I recommend that always think in terms of a hardware implementation when you are writing your code in the VHDL, and this will make your VHDL design easier to analyze. Here is the another example. So I will read the VHDL code first. Test process colon process reset comma clock begin if reset equals to 1, then x1 gets the value of 0, x2 gets the value of 0, x3 gets the value of 0. Else if at rising edge of clock, then x1 gets the value of 1, x2 gets the value of x1, and x3 gets the value of x2, and process. Here I have three signals, x1, x2, and x3. The reset assigns all these three signals to 0. Let's see what happens after the reset is not applied. So whenever we have a rising edge of the clock, we assign x1 a logical one. Therefore, x1 will be high just after the first rising edge. The next VHDL statement is x2 gets the value of x1. So what do you think? Will x2 will get the logical one here? So you might think that x2 should also be 1 at this point, because x1 is already 1 at this point, right? But this is not correct. Remember, x1, x2, and x3 are the outputs of the flip-flops, and therefore they need to one clock cycle to update their state. So even though x1 goes high at the first clock edge, x2 will only change at the second clock cycle. This will become more visible when we look at the hardware implementation for this process. Finally, we assign signal x2 to signal x3 in the last VHDL assignment. Now let's see the hardware implementation and the timing diagram for this circuit and understand how these three signals get assigned the values. So here is our circuit, which implements the process from the last slide. So signal x1 is the output of FF1 flip-flop. Signal x2 is the output of FF2 flip-flop, and signal x3 is the output of FF3 flip-flop. In our code, we assign a logical 1 to the signal x1 at every rising edge of the clock signal. This is implemented by hardwiring the input of FF1 to the logical 1. This way, on every rising edge of the clock, FF1 will get logical 1. Similarly, we assign the signal x1 to signal x2 at the flip-flop FF2, signal x2 to the signal x3 at flip-flop FF3. So this is very clear from the VHDL code, right? So this is achieved by connecting the output of FF1 to the input of FF2. Finally, we assign x2 to x3 in our VHDL code. This is implemented by connecting the output of FF2 to the input of FF3. Very simple. Now let's look at the timing diagram. During the first clock cycle, we see that the reset is high, meaning it is applied to the all three flip-flops. Hence, all these three signals are reset to 0. The reset signal goes to 0 after second clock adds. So afterward, flip-flops will start to capture input values from the third rising edge. Let's discuss that what will happen at the third cycle of the rising edge of clock signal. On this rising edge, flip-flop FF1 will capture the logical one present at its input. Now, after a small propagation delay in FF1, we see the state of the signal x1 changes from 0 to 1. On the rising edge of the clock cycle 3, FF2 will capture the value of x1, and the value of x1 at this point is still 0, because x1 only changed its state after some time of third clock cycle due to some logical delays, right? Therefore, on the rising edge, FF2 will still see logical 0 at its input and will capture 0 values. So signal x2 remains at the logical 0 during the third clock cycle. Same way, at the rising edge of clock cycle 3, FF3 also captures the state of signal x2. Since x2 is 0 on the third edge, x2 also remains 0 during the third clock edge. Now let's look at the clock edge number 4. So flip-flop FF1 will again capture the logical 1 at its input, and therefore x1 will remain at logical 1 as it was before. But now the input of FF2 will be at logical 1. This is because the value of x1 is high at the fourth clock edge, and therefore FF2 will capture a logical high on the fourth rising edge of this clock signal. As a result, we can see that signal x2 will go high just after the fourth clock cycle. But on the fourth edge, FF3 still sees a logical 0 at its input, because x2 has not yet changed at this clock cycle. So FF3 remains 0 during the fourth clock cycle as well. Now let's look at the clock cycle 5. So x1 and x2 will remain at logical 1 during the fifth clock cycle, but the output of FF3 is now at logical 1. This is because signal x2 is at logical 1 during this fifth cycle clock. Therefore, FF3 will capture logical 1 on the fifth rising edge. As a result, signal x3 goes high only after the fifth clock cycle. So this is what we wanted to show you. In the code, we wrote the assignments to x1, x2 and x3 one after another. However, when this process runs, we see that the values of these signals do not change to logical 1 at the same clock cycle. So this would be the result when the circuit gets implemented in the real hardware devices. As I said, as a beginner, it might be quite difficult to sense the timing variations between these signals just by looking at the VHDL code. This is why I think visualization the hardware circuit is quite useful. In practice, the timing of these signals will be straightforward, and you will not have to worry about visualizing the hardware circuits. Here is the another example. In this example, I am assigning logical 1 onto the two signals called x1 and x2. So our VHDL code looks like this. Test process process reset clock begin. If reset equals to 1, then x1 gets the value of 0 and x2 gets the value of 0. Else if rising edge of clock, then x1 gets the value of 1 and x2 gets the value of 1, and if AND process. Again, just assume that we are not applied the reset condition. So here both x1 and x2 will go to logical 1 at the same time, because this is on the same rising edge of the clock cycle. If you come from a software programming background, you might think that x1 goes high first and then x2 goes high after some time later, because the code is written sequentially, right? But this is not the case with VHDL. Remember that VHDL is not a software programming language. It is a language for describing the hardware, and in hardware, x1 and x2 will go high on the same clock cycle, even though one statement is written after one another. Again, thinking back to the hardware circuit, which will make it easy to understand it. This is because both the flip-flops for x1 and x2 have their inputs tied to the logical one. Therefore, on the very first clock edge, both flip-flops will capture a logical one on the same rising edge, and x1 and x2 will both go to the logical one at the same time. Now, this is the last example for this video, and I want you to try to understand that what will happen if you have two assignments to the same signal. Suppose we are writing a code like this: test process colon process reset comma clock begin if reset equals to 1, then x1 is 0, else if at the rising edge of clock, then x1 gets the value of x2, x1 gets the value of x3, and if AND process. In this process, I have assigned x2 to x1, and in the very next line, I have assigned x3 to x1. So what happens then? The simple answer is that the VHDL simply ignores the first statement. Only the last statement will execute. So x1 will get the value of x3. Simple. And it will be treated like that the first statement never existed in that VHDL code from the hardware perspective. Okay, so that's it for today. I hope I was able to clarify how signal assignments works inside the register process. We discussed that how the VHDL signal assignments are quite different from the software programming languages like C or C++. Software programming languages tends to assign the statements sequentially, but VHDL tends to develop a hardware piece from your VHDL design, instead just the execution of statements. In the next session, we will be talking about variables in VHDL. We will talk about how to use them and where to use them, and how they are different from the signals. In the last session, we discussed VHDL assignments mainly for register process block, and we talked a lot about hardware implications of VHDL designs, like how they works and how they implement, etc. Now let's talk about variables in VHDL. We will talk about how to use them, where to use them, and how they are different from signals. So let's start. Before we start, let's understand that what variables are in VHDL. Although they look similar to the signals in VHDL, but variables actually have some interesting differences. Using variables is not mandated in VHDL, and even some designers try to avoid using them in their designs. So it is important to understand that what variables are and how to use them effectively in your VHDL designs. Variables in VHDL are used to store intermediate values within a process, function, or procedures. We will discuss about the functions and procedures later in this series, but for now, just remember that variables can only be used within these constraints. Currently, it's important to note that this variable scope is limited to the VHDL process, function, or procedures in which it is declared. Variables cannot be accessed outside their declared action. Variables are declared just like signals in VHDL, and they can use the same data types. However, if you assign any initial value to your variables, then it will be ignored by the synthesis tool just like signals. Therefore, you should not 100% rely on the initial values, as it may lead to unexpected behavior in your physical designs. Now, let's look at an example to see how variables are used in VHDL. Let's look at the VHDL code first. So it is test process colon process reset comma clock variable x colon, integer, semicolon. So this is the declaration section. Begin, if reset equals to 1, then x is 0 and the out gets the value of 0 semicolon. Else if at the rising edge of clock, then x is 3. So x takes the value 3 here immediately and x is x plus 1. So x becomes 4 here. And if AND process. In this example, I have a test process with an integer variable called x. This is declared in the declaration section of this process as mentioned here. Note that all the variables should be declared here in this section only when you are using variables. Okay. So here is a syntax for declaring a variable. First, start with the keyword variable followed by the variable name. Then use colon and give the data type of your variable and then semicolon. You can also assign any initial value to your variable just like signals. So we use the keyword variable to declare x. No initial value is assigned to variable x in this example here. Remember this, that initial values are recognized only by the simulator, not by the synthesis tool. The synthesis tool will ignore any initialized value in your VHDL program. Now inside the reset condition, we assigned 0 to the variable x and we also set 0 to the dout. Now notice the assignment operator here. It is not same like we were using with signals. Now this assignment operator for variable is colon followed by equal sign. So it is colon equals to. So this operator is different from the signal assignment operator. Now on the rising edge of the clock, we assigned variable x. Because it is a variable, so x takes this value immediately after executing this line of code. And this immediate assignment is different from how a signal behaves. If you remember from our last session, signal does not work like this. Signals only get the last assignment. Do not worry, we will understand this in more details in some time. For example, if this variable x becomes a signal here, then it will not take the value of 3 immediately. Instead, the assignment will happen based on the last assignment, which is x is x plus 1. This means the statement x gets the value of 3 will never consider if x is a signal here. So after reset is removed, you will get the incremental value at every clock cycle. Means starting from 0, then 1, then 2, then 3 and so on at each rising edge of your clock cycle. But in case of variable, you can see that we get the output 4 at very next rising edge when the reset gets removed. So in brief, if x is signal here, then we get the increment numbers at the output like 0, 1, 2, 3 and so on. But if in the same example, if we use the variable, then our output gets 4 all the time. I hope you understand it, how it happened and why it happened. Another important point is that variables can have multiple assignments in succession. This is not possible with signals, as discussed in our last video. So with variables, I can write x is 3 and then I can add 1 to this value and this will work as explained in our last example. So with signals, you cannot perform the successive assignment like this. Although you can, but your output result would not be correct. So if you attempt to write the same code with a signal, then only the last assignment will execute. I hope you have a clear picture now of how variable works in VHDL. So let's explore another example. So this example is more practical to understand. Suppose we have an array of integer called a, which has 8 elements. And the values of these elements are 12, 4, 7, 54, 46, 5, 3 and 24. Now our goal is to write a process to calculate the sum of all these elements in this array. So I have begun the process here and it is test process colon, process, reset, comma clock, variable, temp, colon, integer, begin. If reset equals to 1, then temp is 0 and sum gets the value of 0. Else if rising edge of clock, then temp is 0, colon, for I in 0 to 7 loop, temp is temp plus AI, and loop. Now sum gets the value of temp, and if, and process. Here first I declared a variable called temp to accumulate the sum of all elements in this array A. Temp is initialized to 0 when the reset signal is applied. Additionally, I have a signal called sum, which is also set to 0 when reset is asserted. So we use the for loop to calculate the sum of all the elements in this array A. During the each iteration of this for loop, one element of signal A gets added to the variable temp, right? Since our loop repeats 8 times, hence by the end of this loop, temp will contain the total sum of all the elements in this array of A signal. Note that it is must to reset temp to 0 before starting this for loop. After the loop, we can assign the temp output to our final output, that is sum. Now let's see what the compiler reads when this VHDL code is processed. Initially, we set temp to 0. In the first iteration of this for loop, the statement is temp plus A0. In the second iteration, it becomes temp is temp plus A1. Same for the third iteration, it becomes temp is temp plus A2, and so on. And this pattern continues for all 8 iterations here. As a result, all these statements are generated. Finally, we assign the values of temp to the output signal sum, and that's it. Well, this is a long code, right? But this was just to explain you that how variable works. So let's see how you can perform the same operation with one single statement or one single assignment in one single line. That's too without any variable. So this is our one liner. Sum gets the value of A0 plus A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 semicolon. And it is simply adding up all the elements of signal A and giving the output to sum. Very simple. Lastly, let's understand that what will be your output if you have used signals here instead of a temp variable. And try to understand, will you get a different results with signals, and if that results will be correct or not. And this is the example with signals. Now you might get confused if the concept of signals is still not clear to you. But if that is clear, then it would be easy to understand for you. Note that the only difference in this code is that now we have used signals here instead of a temp variable in our last code. So this time our VHDL code is test process colon process reset comma clock begin. If reset equals to 1, then temp gets a value of 0. Sum gets the value of 0. Else if rising edge of clock, then temp gets the value of 0. For I in 0 to 7 loop, temp gets the value of temp plus AI, and loop. Now sum gets the value of temp, and if, and process. So it may appear correct because this code is exactly same. But here is a functional difference when you use signals in place of variables here. Now because you have used signals here in place of a temp variable for your intermediate assignments, and hence you will not get the correct results with this code. Why? To understand this why, let's break down this loop statement into individual assignments and then try to understand the differences. So as expected, this for loop will generate 8 separate statements, and these are: if rising edge of clock, then sum gets the value of 0. Sum gets the value of sum plus a0. Sum gets the value of sum plus a1. Sum gets the value of sum plus a2. Sum gets the value of sum plus a3. Sum gets the value of sum plus a4. Sum gets the value of sum plus a5. Sum gets the value of sum plus a6. Sum gets the value of sum plus a7. And if. Now notice that we are assigning the statement to the same signal, which is output sum. And if you remember from our past sessions, we explained that signal assignments happens at the last of process. So if there are multiple assignments to the same signal or the same output, then only the last statement will execute and all the other statements will be completely ignored. So only the final assignment, which is sum gets the value of sum plus a7, will execute here, and all the other assignments will be completely ignored. I hope this clarifies that how we can use variables in VHDL and how the results can vary if you do not use them properly. And now you should have some better picture about signal assignments and variable assignments. Please note that this concept is most important to understand, because if these fundamentals are not clear to you, then your designs will not meet the expecting results. So in case you are still have doubts, or if you are still not clear about the concept, then please rewatch these sections once again. Okay, so that's it for today. Here are some important key notes about the VHDL variables. Variables can overwrite with a new value immediately after the assignment. Variables can have multiple assignments within the same code segment. You cannot use variable directly in your architecture body. Means they are limited to use within a process, a function, or a procedure. The primary use of a variable is to accumulate results or store the intermediate values during the calculations. In the next session, we will be talking about VHDL functions, which is very useful when you are doing the repetitive things and designing the same things very frequently in your projects. In the last session, we talked about variables in VHDL, and we learned how variables are different from signals in VHDL and how these assignments actually works in VHDL. Now let's talk about VHDL functions. So let's start. Functions and procedures in VHDL are essential to reduce your code size, especially when you need to rewrite some section of your code many times for the reusable designs. So let's explore how it works. In VHDL, procedures and functions are similar to the functions and methods in the software programming languages like C or C++. They help to structure your code by encapsulating the repetitive operations. So in short, we create the functions and procedures to handle the repetitive operations so that our code looks minimal and they becomes easy to maintain. And this method is more efficient too. Once you write your procedures and functions, then you can use them anywhere in your code and as many times as you need it. And it will execute that particular operations without copying your whole code. One important keynote is that you cannot implement registers within a procedures or function. And this restriction ensures that the procedures and functions only perform the combination logic. Means only combination logic is permitted within the procedures and functions in VHDL. You can write your functions and procedures in the architecture declaration section, processes and packages. So you are flexible to organize your code efficiently and reuse your logic across the different parts of your design. So you can assume that functions are the subprograms in VHDL, and they are useful when there is a need of a repetitive section of the code. A function can accept one or more input variables, but you cannot modify these input values inside your function. Means once that function is called at any point of time, then its input remains same for that execution. and these inputs will be treated like a constant for that run instance. A function always returns an output value, and it cannot return a void or any unspecified value. The returned value must be assigned to a specific variable or signals in your calling code. Lastly, functions cannot include the wait statement. Here is the basic syntax for a function in VHDL. We begin with the function keyword followed by the function name. Now inside the bracket, we list all the input parameters along with their data types. Then we specify the return type using the return keyword. So this looks like function name, then input parameters in the bracket, return type is, then declare the constants and variables in this section. Then begin. Now write the functional code in this section here and then return something and semicolon. So you can see that before the begin keyword, you can declare your variables and constant which are needed for this function. These declarations can be used for internal calculation within your function. Variables can be used to accumulate the results to store the intermediate values. You can use them for internal calculations within your function. So you can return any data. Note that variables are reinitialized every time the function is called. So they cannot be used as a storage element. Means once the output is returned, then there is nothing stored in that function. After the begin keyword, we write the VHDL code for our VHDL function. And before reaching to the AND statement, we must return some output values. Let's understand this with one simple example. In this example, we are writing a function that adds 1 to any integer number which is given as an input. For example, if we pass the value of 100 to this function, then it will return 101. Simple. So we create a function called increment and it adds 1 to any integer number that is passed to it. So here is the VHDL code for our incremental function. Function increment input num colon integer return integer is variable temp colon integer semicolon begin temp is input num plus 1 return temp and we start by using the function keyword to declare the function. We name this function increment and specified the input parameter. So in our case, it is input num and this is an integer. Next, we specify the return type as integer since this function will return as an integer value. Then we declared a variable called temp to store this intermediate results for our calculation. Now after the begin keyword, we assign temp the value of input num plus 1. Finally, we return this temp as the output and then end our function with the AND keyword. Now at the bottom section of this code is the example that how to use this function in our VHDL code. So I have written dout gets the value of increment 4 semicolon. Means we are passing integer number 4 to this function and this function will give you output 5. In the last session, we talked about VHDL functions. We learned how to use them and where to use them in VHDL design. Now let's talk about VHDL procedures. Procedures in VHDL are quite similar to the functions, but with a small difference. A procedure does not return any value, but a function must return some value to the output. Function parameters are always input. However, procedure parameters can be input or output or even it can be in-out. And that allows procedures to have more flexibility in processing data in and out from your procedure. Input parameters passes the values into a procedure and output parameter passes the value out from the procedure. Also, there can be multiple output parameters with VHDL procedures, which is not allowed with the functions. In-out parameters allows you to pass the value as an input into a procedure, then it can modify based on the project needs, and then it can pass out to the output. So it works like that, and that makes procedures versatile for many operations. Let's understand this concept with a simple example. Here is the basic syntax for a procedure. It starts with the procedure keyword followed by the procedure name. Then inside the bracket, we list all the parameters with their data types. And they also indicate if they are in, out, or in-out. Now before the begin keyword, we declare all the necessary variables and constant. Procedures do not keep their variable values between the execution, just like the VHDL function. They are reinitialized each time when the procedure is called. So in short, procedures also do not store or keep any data after finishing its execution. Now after the begin keyword, we can write our VHDL code to implement the desired functionality. And in the last, we end the procedure with the AND keyword as normal. So overall syntax looks like this. Procedure, procedure name. Now list the parameters, is, then give the constant or variable declaration in this section. Then write keyword, begin, then write the procedure code here. Write your VHDL design or structure here in this section. Then in the last, terminate the procedure with the keyword and semicolon. Okay, now let's understand it with one simple example. So we are writing a procedure that implements a full adder circuit. In brief, a full adder is a combinational circuit that performs addition on the three single-bit binary numbers. So a full adder generates a sum of three binary inputs, and it also generates a carry output as well. And you can use this full adder circuit to create a multi-bit adder by combining these full adder elements multiple times. So let's focus on the 1-bit version first. So we have these three inputs labeled as A, B, and C in. And we have two outputs, sum S and carry. The sum S is the result of the addition of these three binary inputs, and carry is high when at least two of the inputs are high. Now let's see how we can implement this circuit using a procedure. So here is a VHDL code for this procedure. Procedure full adder in the bracket signal A, B, C in colon in std underscore logic semicolon signal sum carry colon out std underscore logic bracket closed is. Now begin. Sum gets the value of A XOR B XOR C in semicolon. Carry gets the value of A and B or A and C in or B and C in and procedure semicolon. So these two statements are our full adder elements or full adder expression. So to implement this simple full adder circuit in the VHDL procedure, we start by declaring the procedure name. Here we gave it a name as full adder. Next, we declare all the necessary inputs and outputs and parameters for this. For our circuit, we have three std logic inputs, A and B and C in. We also have two std logic outputs for sum and carry. These are declared just like a port signals, but here they are called parameters for this procedure. Now inside the procedure body, we assign the values to the sum and carry signals according to their circuit diagram, and we finish up the procedure with the AND statement. Now to call this procedure in our VHDL code, we use the procedure name and provide the inputs and output parameters inside the parentheses. So if you look at the code in the bottom section of this slide, here we are using procedure for our adding functionality. In this example, signal X, Y, and Z are the input signals, which are corresponding to the parameters A, B, and C in our procedure. The sum result is assigned to the signal sum, and carry output is assigned to the signal Cout. Okay, so that's it for today. Here is a quick recall of what we have learned. We covered that where to use procedures in VHDL and how to write your basic procedure. So you can use your procedure while implementing the frequently used algorithms in your designs. By using procedures and functions in your VHDL designs, you can significantly reduce your code size for your design requirements, especially when you have to reuse some set of your designs multiple times in your code. So you can call these subprograms as many times as they are needed in your project design, and that too with just a few lines of code. So this enhances your efficiency and also code readability. I highly recommend to use functions and procedures to create your reusable codes. These subprograms can be easily ported to other VHDL designs as well. So they can save your valuable time and efforts when writing and maintaining bigger VHDL codes. In the next session, we will be talking about packages and libraries in VHDL. In the last session, we talked about functions and procedures in VHDL. We learned how to use them and where to use them. We discussed that how these VHDL functions and procedures can save your valuable time and efforts when writing and maintaining bigger VHDL codes, which are using reusable elements in your designs. Now let's talk about packages and libraries in VHDL. So let's start. Okay, so what are these VHDL packages and libraries? If you remember from our previous sessions, we have touched upon a few packages like numeric underscore std package and std underscore logic underscore 1164 package, etc. So the primary purpose of these packages is to share the commonly used items across multiple designs. These items can be anything. It can be declaration, it can be data types, it can be mathematical or logical operations, etc. Means everything is defined there and you can use its elements anywhere in your designs without defining them across your multiple projects. You just need to include those particular libraries and packages in your VHDL design and that's it. And you will get the access of all of its elements. In most of your designs, you are going to use some very common packages like std underscore logic underscore 1164, numeric underscore std, etc. because they contain most of the commonly data type definitions, functions, and features. If you are familiar with C or C++ kind of software programming languages, there also you generally add headers in your codes. So you can think of VHDL packages just like the header files in the C or C++ language. In both cases, you declare definitions, data types, and functions and many more things that can be shared across your multiple VHDL files. And just by adding those packages, you will get the access of all of its contents in your designs and you can use them wherever they are needed. Okay, so what are these packages in VHDL? A package is a collection of signals, constant, data types, subdata types, functions, procedures, components, files, and attributes. And once you declare a package in your VHDL file, then all of these items which are defined in that package become available to you for your designs. In our previous session, we generally used std underscore logic underscore 1164 package to use the std logic data type. Similarly, we declared std underscore numeric package to use signed and unsigned data type. This is because these data types are defined within these specific packages. So this is the importance of packages in VHDL. And interesting thing is that these packages are not only predefined packages, but you can also create your own custom package. So let's explore how to do this in the next slide. Let's take an example of traffic light. We discussed this in our past sessions, so it will help you in better understanding. But a quick recap. So we created a custom data type called T-light type with the possible states red, yellow, and green. So here is the declaration of this data type. Additionally, I declared a new signal called traffic light using this custom data type. So we need to use keyword type for creating our own custom data type. We explained this in our past session, so you can refer that if needed. In that session, we defined our data type definition and signal declaration between the architecture declaration and begin keyword. These multiple dots indicates that you can add more signals and data types if needed for your designs. So you can add all of them here. So in VHDL, we simply write this as architecture, architect1 of entity1 is type, T-light type is red, yellow, green, semicolon, signal, traffic light, colon, T-light type, semicolon, then begin. Now suppose I want to use this custom data type, T-light type, to create the necessary signals for my designs. And I need to use my traffic light data type as two separate VHDL files. In this example, the first code is in the top VHDL file and the second code is in the bottom VHDL file. So we have two different VHDL files for two different projects. So in both files, I had to declare this T-light type in both the files individually if they are going to be used in these projects. So in each file, we declare this T-light type data type followed by the signal declaration using this data type. This approach of defining the elements in each individual file works completely fine, but it is a painful approach and it is time consuming as well, especially when you are using these designs in many projects because you are declaring them in each and every file. Now suppose you are looking for some modification on this data type definition based on some project demand or because of some future needs or improvements. Then you will have to modify your data type definition in each and every file individually, which is time consuming and that leads to the more human errors too. For example, you wanted to add a new color to this traffic light. Say you want a fourth color on it, like white. Then you will need to update this in each and every file, which is using this data type. Now suppose you have hundreds of files where it is being used. So you can feel that this process is actually time consuming and challenging too. So in these type of situations, packages can help you to avoid such problems. So let's see this in the next slide. Here I have created a simple package called my package using the package keyword. Inside this package body, I have declared our T-light type data type just like before. So my VHDL code for this package definition is package, my package is type, T-light type is red, yellow, green, semicolon, and my package, semicolon. And that's it. I included T-light type in my package. Note that once you finished your package definition, you need to terminate your package. So we terminated it with the AND keyword. Although I can add more declarations to this package, but for our requirement, this is enough for now. Now I saved my package as a VHDL file with a .vsd extension. Note that both packages and VHDL file has the same .vsd extension. So now let's see how we can use this package in our design. So in the bottom section, we have two separate VHDL files again. In order to use these packages, we need to declare the package first. So it is declared at the top of each file. I have marked that with the yellow arrow. So packages are declared at the top of each VHDL file. To declare a package in your VHDL designs, we need to use keyword use followed by the library name dot, then write the package name dot all semicolon. So we use the keyword use to declare this package. As you can see here, we have written use work dot my package dot all semicolon. We have written this in both of these VHDL files, as you can see. Note that here work refers to the library where my package is located. It is a special keyword indicating the current working library. Always remember that when referring to a package, use its package name, not the file name. These are two different things and they can be different as well. Once you declare this package, you can use traffic light data type to create your signals in both of these VHDL files. And you do not need to define it again in your VHDL files. In case you wanted to modify your data type, such as adding a new color like we discussed, then you simply need to change it in the package file. And that's it. Now you do not need to change it in every individual VHDL files in your projects. Okay, so that's it for today. That was a quick and concise overview of VHDL packages. We learned how to create a simple package and how to declare it in a separate design unit. We also discussed why we should use packages to share declarations across multiple design units. In the next session, we will be talking about VHDL libraries. In the last session, we talked about VHDL packages. We learned how to create your own custom VHDL packages and how to declare it in a separate design unit. We also discussed why you should use packages to share declaration across multiple design units. Now let's talk about VHDL libraries. So let's start. So libraries in VHDL act as an essential container where your compiled design units are stored. That helps to organize and manage different components of your VHDL designs. When a design unit or module is compiled, the compiler translates the VHDL code into an intermediate form and store it in the form of library. This intermediate form is essential for the simulation and synthesis processes. By default, the compiler stores all of these intermediate files in the current working library, which is automatic process. This streamlines the workflow by keeping all the necessary files in one accessible location. Most simulators and synthesis tools automatically create this library for you. This automation ensures that your design process is smooth and all the required files are properly managed without a manual setup. This library has its own name and you can use it by using the keyword work, which refers to the current working library, and it stores all the design units. You can just think of work keyword as a reference point to the current working library in simple. Now, important thing is that when you need a package or feature from any library which is other than your current working library, then you must first declare the library in your VHDL code. This step is crucial for accessing the additional resources. Each library has a unique name. Remember, when you declare a library, you must refer to its name, not its file name or its location in your file system. Here is a simple example of how to use packages from IEEE library in VHDL. These are very generic libraries and packages which are widely used in most of your VHDL designs. These are written like this: library IEEE semicolon use IEEE.std underscore logic underscore 1164.all semicolon use IEEE.numeric underscore std.all semicolon. The first statement makes the IEEE library available to your design and it allows you to access its resources. The second statement makes all the definitions from the std underscore logic underscore 1164 package in the IEEE library, which you can use in your VHDL designs now, like standard logical operators, std data types, etc. The third statement makes all the definitions from numeric underscore std package, and its elements are now available to use in your designs, which provide access to a variety of numerical operations. As you can see, using libraries in VHDL is a two-step process. First, you must declare the library. Second, you specify the individual resources or packages that you need to use from that library. Okay, so that's it for today. Here is a quick recall. We learned the concept of packages and libraries in VHDL. We discussed major libraries and learned that compiled design units are stored in the current working library in an intermediate form. We learned that the keyword work can be used to refer to the current working library, where our compiled designs are stored by default. We also learned that synthesis and simulation tools automatically create the working libraries for us. We found out that if we need to use a library other than the current working library, we must declare it in our VHDL codes. Finally, we looked at a simple example demonstrating how to declare and use a package from a library. In the next session, we will be discussing parameterized components. In the last session, we talked about VHDL packages and libraries. We discussed how to create your own custom package and how to use them in your VHDL designs. Now let's talk about parameterized components. Parameterized component is a crucial topic that enhances the flexibility of your VHDL component. By understanding this parameter addition, you can create more versatile and reusable designs, which is essential in complex systems where different configurations are needed. And that is possible without altering the core logic. So let's start. VHDL includes a feature called generics, and that helps to parameterize your modules and components. Generics are treated like a special type of constant that can be customized for each instance of your module so that your designs become more adaptable to the VHDL requirements. So the basic requirement for a generic is similar to a constant, means it must have an identifier. It must have a data type such as integer, std logic, or boolean, etc. And with all these abilities, generics in VHDL can be used in various scenarios, such as setting vector sizes or enabling a specific feature within your module, etc. Now, because we have taken a reference of constant to understand this generic concept in VHDL, so it is important to understand how generics are different from constant and how to use both of them individually in your designs. First, quickly see about constant. So constant are declared in the declarative part of architecture. So your constant can be consistently used within the architecture module in your design. And because it is a constant, so it has the same or fixed value across all the instances of your module. That's one thing. We can also declare constant within a package as well. This is helpful when you're required to access that constant across multiple modules. This approach is recommended because it provides the constant with global scope and that make it accessible through the entire design and ensure the consistency in your designs. Once you declare a constant in a package, its value remains the same across all the components and subcomponents within that design. So that maintains the consistency and reduces the chances of errors because of mismatch in values, etc. Now let's talk about generic. So generics in VHDL are identified in the entity declaration, and its scope is limited to a single instance of a VHDL component. This means that each instance have its own unique configuration, so it enhances the flexibility of your design. The main difference between a generic and a constant is that the generic scope is limited to a single instance of a component. However, a constant value remains the same across all the instances of that component. So, generics in VHDL allows you to do the unique customization for each of your instance. So, this is the advantage of generic, that their values can be unique for each instance of a component. So, the benefit is that you can use the same component with different configuration and sizes without changing the configuration on your original component. And this feature is really powerful if you know how to use it because it allows you to assign different values to the generic parameters for your multiple instances of the same component. This flexibility is particularly useful for large designs where different configurations are needed for different parts of your system. So let's understand this with an example, and it will help you to understand how generics can be used effectively. So this is our example. In this VHDL designs, we will perform a simple addition operation. So our adder module has two input ports, input A and input B, and one single output port, Dout. The adder module adds the value of input A and input B and assign the output to the Dout. So this is simply a basic arithmetic operation. So here is the VHDL code for this. Entity half adder is port A colon in std logic vector 7 down to 0. B in std logic vector 7 down to 0. Dout out std logic vector 7 down to 0 bracket closed and entity semicolon. Architecture. My design of half adder is begin Dout gets a value of A plus B semicolon and architecture semicolon. This is a simple program, but the problem with this code is, or you can say the limitation with this module is that it can only handle 8-bit numbers. Means it can be only used to sum 8-bit two inputs. But what if you want to add two 4-bit inputs or 16-bit inputs? That is not possible with this program, right? So this code has limited usability. Means it cannot be used for different vector size operations. It is just for adding two 8-bit inputs. So you cannot use this component for the addition of 12-bit, 16-bit or even 4-bit numbers. So in the next slide, we will see that how you can use generics in VHDL to make this code more versatile and usable, so that the same module can be used for adding the operation on different vector size inputs like 4-bit, 8-bit, 16-bit, etc. we are talking about. Okay, so let's see how we can achieve this through generics in VHDL. First, we will declare our generic for the VHDL code. Generics are declared in this section here, that is above the port declaration and within the entity declaration. So our VHDL code looks like this. Entity half adder is generic, then in the bracket x colon integer colon equals to 8 bracket closed semicolon. Port A colon in std logic vector 7 down to 0. B in std logic vector 7 down to 0. Dout out std logic vector 7 down to 0 bracket closed semicolon and entity semicolon. So you can see that this code is identical to the previous VHDL code, except the few additional lines between the entity and the port section. So we declared generic X before the port declaration in this entity section. So let's see how we declare generics in VHDL. We declare generics using the generic keyword. Then inside the bracket, we list all the generic values and setting up the parameters for our modules. You can also declare more generics here if needed in your design. In this example, we just need one generic value, which is X, and it is integer data type. And this value will control the vector size of our code, or you can say the vector size of inputs and outputs. We can assign a default value to generics as well, and this is optional. For example, we have assigned 8 in this example here. This means if you do not specify the value of X while using it as a component, then it will default consider it as 8. Next, we will see how to use this generic to define the width of your input and output ports so that you can control your bit sizes dynamically. It is quite simple. Just define all the ports with the range x-1 down to 0. Means we use the generic value x to set the width of our std logic vector signal. Now because x is default set to 8, so my adder has 8-bit wide ports by default. And this module is initially configured for 8-bit addition operation. Now interesting thing is if I need a 16-bit adder, then I will just change the value of x to 16. So this module is now flexible to handle the addition operation on the vector signals of different bit sizes. Let's quickly see how we will write our VHDL code for this. Entity half adder is generic x colon integer colon equals to 8 bracket closed semicolon port A in std logic vector x minus 1 down to 0 B in std logic vector x minus 1 down to 0 D out std logic vector x minus 1 down to 0 bracket closed semicolon and entity. If you notice that this is a minor change, we just updated the range from a hard-coded range, which is 7 down to 0, to a flexible range, which is x minus 1 down to 0. Now the range of std logic vector signal will depend on the value of a generic parameter x. If x is 8, then it will be 8-bit adder, and the range will be 7 down to 0. And if x is 16, then it will be 16-bit adder, and so on. So you can see that this module is now adaptable for the addition operation of the std logic vector signals of any size. And this is one of the key benefits of using generics in your VHDL design. Now let's say we have an application where we wanted to use two 4-bit numbers and two 8-bit numbers. This is a good example to understand the use of generic. In general, you have to instantiate two separate adder components in your design to achieve this requirement, right? One component will be configured as 4-bit adder and the another one for the 8-bit adder. So this is our top module, and both of the addition components are instantiated inside this module. Okay, so we instantiated two adder components within this top level module. One for the 4-bit addition operation and another is for the 8-bit addition operation. Now let's see how you code this top level module using generics without changing anything in the adder module. This process is straightforward. For the first addition operation of 4-bit signals, we map the generic value to the 4. And for the second addition operation of 8-bit signal, we map the generic value to 8. Note that we have just mapped this generic value in the top level module. Our adder module is same. We are not changing anything on that module. So this is a conceptual view to showcase how these components will be instantiated and configured. Now let's see how we will implement this in the VHDL code. So we instantiated two components. First is the adder module for the 4-bit adder. We named this instance as adder 4-bit, and we map the generic parameter n to 4 here. Means in the adder module, now the signal range will be 3 down to 0 for this instance, and it will handle a 4-bit addition operation. Note that I have not written the port mapping here to make this look clear, but in your VHDL code, just write the port mapping after mapping the generic parameter. It is just like we did earlier in the component instantiation section. Next, let's instantiate the 8-bit adder. So this is named as adder 8-bit. Notice that we always try to write the relevant naming conventions so that we can clearly identify the purpose and configuration at the time of reviewing. So remember this as a good coding practice always. Now coming back, so to configure this 8-bit adder, we simply map the generic parameter n to 8. Now this will handle a 8-bit addition operation. So it's that simple. Okay, let's have a quick brief. Generic in VHDL function as a special type of constant that provides a powerful tool for parameterized designing. By using generic in VHDL, you can configure each instance according to your specific need, and that too without altering the core designs. So your modules become more flexible and they can be used in the wide application. Like in our example, we created a flexible bit adder that can handle data of any bit sizes. So this is the power of generics in VHDL. So try it and create more adaptable and reusable components for your design. In the last session, we talked about generics in VHDL, and we learned how to create flexible and reusable VHDL code. Now let's talk about VHDL type conversions. Type conversion is a very important topic as you will be going to use them very widely in your VHDL designs because VHDL is a strongly typed language. And if you do not take care of the data types while assigning them or during the operation, then your VHDL codes will generate errors. So the question is why these type conversions are important in VHDL? Because VHDL is a strongly typed language, means it strictly follows the data type consistency. And this is important while maintaining the integrity and the reliability of your designs. Strongly typed language means that in VHDL, you cannot mix different data types within the same expression. This is not allowed. So your expression must be well defined and predictable. For example, in a single assignment, the data type on the left hand side must match with the data type on the right hand side. When these data types are same, your expression will be executed without any error. However, if there is any discrepancy in the data types or it is not matched, then it can lead to a syntax error. So in case you wanted to write an expression with mixed data types in VHDL, you will be needing type converters. These type conversions can be used to align the data types so that your assignments and the operations works correctly despite the different data types in the expression. In VHDL, these type conversions can be achieved by using built-in functions and typecasting techniques. Let's consider the most widely used data types first. Each box here in this diagram represents a signal. Black text is a signal name marked with a bold black color, and the white text are the data types. At the top block, we see signal U. This is unsigned type data. On the left, we have signal V, which is std logic vector type. At the bottom, we have signal S. This is signed data type. And at the right, we have signal I. This is integer type data. First, note that you have to use numeric underscore std package to use these type conversions, as it has already defined some of the useful type conversion functions for the conversions between these data types. Now let's see how to perform these data type conversions. First, we can use the std logic vector typecast to convert an unsigned data type to a std logic vector data type. Similarly, to convert from std logic vector to the unsigned, we use unsigned typecast. Note that U and V in these brackets here, these are the signal name where these conversions are being made. So in your VHDL code, replace these identifiers with your signal name. So to perform the typecast, we simply write unsigned followed by the signal name in the brackets. So unsigned V means convert signal V, which is a std logic vector type, to an unsigned data type. Similarly, std logic vector U means convert signal U into the std logic vector data type. So it is that simple. Similarly, we have more typecast, like for the conversions between std logic vector and the signed data type. For example, to convert a signal from std logic vector to the signed, we use signed state typecast. And for the reverse conversion, means from signed to the std logic vector, we use std logic vector typecast. Typecasting also allows conversions between the unsigned to a signed data types and signed to the unsigned data types, like with the middle transactions here in this picture. However, always remember that the length of these vector signals must match during the conversions. If the length of these signals are not matched, then you will get the errors in your VHDL designs. So ensure that the length of those signals are identical. For example, if you are converting a signal from unsigned to a std logic vector, the vector length should be matched here. Now let's see how to convert integer data types. To convert from unsigned to integer, we use to_integer function. Note that all the integer conversions are handled using the functions. These functions are highlighted in the red boxes here. So the operations without the red boxes here are being handled using the typecasting, and the conversions inside the red boxes are handled using functions. So this is just for your reference to distinguish the typecast operation and type conversion function. So all previous type conversions which we have covered was happening through the typecasting. However, these integer conversions happens through the functions. So we can go from integer to unsigned using toUnsigned function. Now, this function takes two parameters. The first parameter is the name of integer signal, like signal name is I here. And the second parameter is the size of unsigned data type. Note that you also need to take care of potential overflow. If the unsigned vector is not large enough to hold the integer value, then it can cause your overflow. We have similar function for integer to the signed conversions. Again, there is a possibility of overflow when you convert an integer to a signed data type, like if the signal does not have enough bits to hold the integer value. Similarly, you can use toInteger function from converting the signed or unsigned data type to the integer data type, and it has only one parameter as input, which is a signal name, which you want to convert into the integer. These conversion functions are available through the numeric_std package in IEEE library. So this is a valuable resource for your VHDL designs. This map summarizes the conversion paths between different data types. So try to keep this handy when you're using them. It will always helpful for your quick reference to avoid error. So just take a screenshot of this for your future references. Now let's quickly see how you can write your own type conversion functions. Here is a quick example. We will write a function which will convert a Boolean type signal to a STD logic signal. Simple. Means this function takes a Boolean signal called A and returns the corresponding STD logic value. So inside the function, we have written a simple if condition to check the value of A. If A is true, the function will return logical 1. And if A is false, then it will return logical 0. So this is our simple VHDL code for this function. Function to_std logic A colon in Boolean return std logic is begin if A then return 1 semicolon else return 0, and if AND function. So this function is taking a Boolean signal called A and convert it into a std logic output. This is a very simple example just to give you some overview of it. So you can call this function now in your VHDL designs whenever it is needed, like you have seen in the previous slide. It is as simple as that. So that's it for today. But before concluding, here is a very important note that these type conversions does not consume any FPGA resources, because these functions guide the compiler that how to interpret various signals in your VHDL code. I hope now you have the basic understanding of type conversions in VHDL, and now you are aware how to use them. If needed, you can create your own functions as well for different type conversions. In the next session, we will be covering others keyword, which can be used at different places in VHDL and having different use cases. Depends on where this keyword is being used. So it is quite important to understand its proper use cases. In the last session, we talked about type conversions in VHDL. We explained how to use them and how to create your own functions for different type conversions. Now let's talk about others keyword in VHDL. We have already seen this keyword few times before and at different places for different use cases. And now I will explain this little more detail. So let's start. Others keyword has two main use cases depending on the context that where it is being used. First, it is used in case statement. So it covers all the choices that have not been specified as choices. We discussed this in the case statement session, so we will not go in details here. Second, the others keyword is used to assign some values to all the elements of an array, regardless of its size. So this is the area where we are going to focus in this section. So first, let's see that how it works. Here we have an example of 8-bit STD logic vector signal called A. Suppose I want to assign logic 0 to the every bit of this vector. So there are a couple of ways of doing this. One simple and straightforward method is to write it out as a binary value like this. A gets the value of 00, 00, 00, 00, semicolon. This method works fine for the small vectors, but for the large arrays like 64 bits or 32 bits, it is just time consuming and just waste of efforts. The second method is using hexadecimal notations. So you can assign a value like this. A gets the value of x00, semicolon. So to write in hexadecimal, we have to use letter X followed by the hex number. Remember that hex values are written inside the double quotes. And X here notifies that the value is in hexadecimal number. This method works fine when the signal length is multiple of 4. For example, hex assignments are suitable for 4-bit, 8-bit or 12-bit signals. However, they are not suited for the signals with the length like 6 or 7 bits because these are not multiple of 4. The third method is using others keyword. So we can write this like A gets the value of others are 0, semicolon. This statement assigns the value 0 to all the elements of this array. So now you do not need to take care of the array sizes. This method is efficient and works for any array sizes. So when you are dealing with very long vector signals, this method is preferable over the other methods explained here. There is one more benefit of using others keyword in assignment when you are designing your system for flexible items. For example, you used generic in your VHDL design to adjust the width of STD logic vector signal for some of your component in your VHDL code. And you used hard-coded assignment while resetting the signal. So when you try to change the width of your signal from generic, it will come up with error because you just changed the generic value for the vector signal, but did not adjust the initialized value or reset value of those vector signals. They are still fixed to some specific length because it is hard-coded. So you will have length mismatch and VHDL will not allow that. So instead hard-coded values, what if you use others keyword for the initial assignment or for the reset assignment? Now there is no problem with your code because others keyword will assign the value to all the elements of vector signal despite of its length. This was a small but important session because good designers always try to make their code more flexible and future ready. So try to use this as much as possible in your designs. In the next session, we will be talking about tri-state drivers. In the last session, we talked about others keyword in VHDL, especially in the assignment operations, and we learned why it should be used for initial assignments or reset assignments. This is also helpful when you are assigning some values into multiple elements of a vector signal or an array type data type. Now let's talk about tri-state drivers in VHDL design. Tri-state drivers are essentials when you are working with the real FPGA hardware, and this can help you in handling input-output operations. This means that beside the logic high or logic low, these input-output pins are having a high impedance state. This is referred as tri-state, and this allows multiple drivers to connect to a single line without interference so that we can efficiently use these input-output ports as well. Note that tri-state drivers are not available inside the FPGA. This restriction means you cannot drive tri-state signals to internal nodes within the FPGA devices. Let's see how to implement your tri-state driver in VHDL. Here you can see a diagram which we are going to implement in hardware. In this diagram, you can see a triangle symbol. This is a tri-state driver. Dout signal is the output pin of our FPGA. That is driven by a tri-state driver. Din is the input signal of this tri-state driver, which is a STD logic signal. Alternatively, we could use a STD logic vector for multiple bit operations as well, like for data bus, etc. This enable signal controls the tri-state driver. It tells that when the output pin will be active. Now, to implement this tri-state driver in VHDL, we use a combinational process block. So our simple VHDL design would be like this. Tri-state colon process din comma enable begin. If enable equals to 1, then dout gets the value of din. Else dout gets the value of z. This is high impedance. And if and process. We start with the process declaration. Input signals din and enable are written inside the sensitivity list so that the process can respond on these signals. If enable signal is set to high, input din will pass through to dout. And if enable signal is set to 0, then dout will be at high impedance state. Means the output is effectively disconnected from the input at this time. In VHDL, we use this letter Z inside a single quote to represent this high impedance state. This mechanism ensures that the multiple devices can share the same output line without conflicting. If you are using vector type signal, then this Z value need to be written inside double quotes, and it should be matched with the length of your vector signal. Well, it's important to remember that dout must be an input or output pin of FPGA, and it should not be an internal signal. In the next session, we will be talking about VHDL comparators. In the last session, we talked about tri-state drivers in VHDL, and we learned how they work in FPGA design. Now let's talk about VHDL comparators and see how to use comparators in VHDL. Comparators are equally important in digital system designs because you will use them for decision making on different signals and values. So in this section, we will learn how to use them effectively to enhance the functionality and efficiency of your VHDL designs. You are going to be use them very widely at multiple places, especially in if-else statements and conditional statements. Note that comparators can be used for combinational process blocks as well as for registered process block. Combinational blocks provide immediate output based on the current inputs, while registered process blocks offers synchronized output with clock signals, which provides more stability and timing controls in your designs. We already discussed about that in past, so we are not going deep in this session here. So here is an example of simple combinational process. And combinational output means that the output is generated through the logical gates or lookup tables. They do not involve flip-flops here. So the output will change immediately when your input changes. But of course, transaction delay or gate delay will be applied. Note that I have not written the entity section here, as we practiced that many times before. So this is just an architecture section. Anyway, just a quick brief. This module has two signals, signal A and signal B, and one signal Tout for output. We will compare signal A and signal B, and if A is greater than B, we will get 1 at the output, else we will get 0 at the output. So this is our VHDL code. Architecture, behave of my design is signal A colon integer semicolon, signal B colon integer, signal Tout colon std logic semicolon. Begin P0 process A comma B begin. If A is greater than B, then Dout gets the value of 1, else Dout gets the value of 0. And if and process and architecture. So first we declare the necessary signals in the declarative section of architecture. Like we have these three signals here, A, B and Dout. Signal A and signal B are defined as integer, and we will use them to compare their values. And Dout is a kind of output signal, and it is STD logic type. and we will get the results in this signal here. Note that we assume that signal A and B are driven by some other part of the VHDL code. Means their values are coming internally from some other section of code. But for now, just focus on the comparator. The output of the comparator driving this dout signal, which is std logic type, means dout is indicating the result of comparison between signal A and B, such as greater than, less than, equals to, not equals to, etc. Like in this example, we use greater than symbol. You can use these comparators with your signals, variables, constant, and even with some specific values for your designs. Note that we have written these conditional statements inside the process block, or you can say that inside the combinational process block. So signal A and B are listed in the sensitivity list. Means process will execute when any of these signals are changed. Now, if this condition is true, means if A is greater than B, then dout will be 1. Else, if this condition A is greater than B is false, then dout will be 0. Then AND if, AND process, and AND architecture. So this is very simple. Here we have used integer data type for signal A and B, but they can be of any data type like std logic vector, signed vector, unsigned data type, etc. These data type choices are depends on the project requirements and the nature of values which are being compared. Now remember that VHDL is a strongly typed language. Means when you compare something, then both should be follow the same data type. And if it is a kind of vector or array type signal, then their length should be also matched. This is really important to take care, because if that is not correct, you will get syntax error for your code. You can also design this system for process block as well. Just define the clock and sync the results with the clock transactions. We already covered this in the register process block section, so we are not going deep today. But try to design the same with your own. If needed, you can revisit the process block section once again. Let me know if you still face any difficulty and we can cover this as well. I hope now you are familiar with different type of comparators in VHDL and how to use them for any combinational circuit or register circuit based on your specific need of your designs. In the next session, we will be talking about multiplexers in VHDL. In the last session, we talked about comparators in VHDL, and we learned why these comparators are important in VHDL designing and how these can be used. Now let's talk about multiplexers in VHDL. We will learn that what are multiplexers and how they can be used in your VHDL designs. A multiplexer is a very basic digital component in digital system designing. A multiplexer selects one signal from several input signals and forward that selected input to the output signal. The preferred way to implement a multiplexer in VHDL is by using a case statement. This is a clean and organized method on input selection, and this is very straightforward to manage the multiple input signals based on a selected line. A multiplexer can be designed either as a combinational design or a register process design, depending on your project requirement, of course. So, combinational designs provide immediate output based on the current inputs. However, register process blocks are synchronized with a clock signal for stable timing. You will be definitely using multiplexers very widely, especially for the large design units, where the selection functionality is required. So in this example, we assume that this multiplexer is part of a larger VHDL design. Means all these ports are internal signals of a module. But for now, just focus on the logical implementation of this multiplexer. So this multiplexer is a combinational design, and the output of this multiplexer is driven by a lookup table or LUTs instead of a flip-flop. Here is a block diagram of a multiplexer which we are designing. It has 4 inputs labeled as A, B, C, and G, and one output named as dout, and one select line named as SEL. This select line tells the multiplexer that which input need to be selected from all these input lines like A, or B or C or D here and pass that input to the output Dout. So let's see the VHDL code for this multiplexer in the next slide. Before we proceed, please note that this example focused on the logical implementation of a multiplexer, and thus there is no entity declaration written here. But we consider that this multiplexer is part of some bigger system design, where all these input-output ports are treated as an internal signal. So this is our VHDL code, and it is architecture behave of mux is signal A, B, C, D, colon, integer, semicolon, signal select, colon, integer, range 0 to 3, semicolon, signal Dout, integer, semicolon, begin. P0 process A, B, C, D, select, begin. Case select is when 0, then Dout gets the value of A. When 1, then Dout gets the value of B. When 2, then Dout gets the value of C. And when 3, Dout gets the value of D. When others, there is nothing. AND case, AND process, and architecture. So first we declared all the signals in the architecture declaration section. Now based on the block diagram, we defined 6 signals for this multiplexer. There are 4 inputs A, B, C, and D, 1 output Dout, and 1 select line SEL. For this example, all the signals are considered as integer data type. However, these signals can be anything like STD logic vector, signed or unsigned, etc., or even custom defined data types as well. Just remember that the input and output signals follow the same data type. Until they are same, you can use any data type. But if they are not matched, your program will not execute. Instead, it will give you the syntax error. Next, we define the process block, where we will write our code for this multiplexer. This is a combinational process block. Hence, all the signals are added in the sensitivity list of this process block. Means signal A, B, C, D, and select. So your process will execute when any of these signal is changed. Note that Dout is not included in the sensitivity list because Dout will react on the changes of other signals which are input or internal signal. So this process block does not require to read the value of Dout. Now we are implementing the multiplexer using a case statement here. So the case statement uses select signal to find out which input signal from A, B, C, or D should be routed to the output Dout. Next, we listed all possible choices for this select signal. So when select is equals to 0, then input A will be selected and it will pass out to the output Dout. The second choice is when select is equals to 1, then input B will be selected and it will pass out to the output Dout. Similarly, when select is equals to 2, then input C will be selected and it will pass out to the output Dout. Finally, when select is equals to 3, then input D will be selected and it will pass out to the output Dout. Lastly, we have used a default condition. You can write any statement which you want to refer as an invalid input. Note that this is mandated to include a default case in a case statement. In this code, the default case is doing nothing. Now, after listing all the choices, we terminate the case statement. Finally, we end the process block and architecture block. So this process block will implement a multiplexer with a combination output, and the FPGA will use a lookup table or LUTs for this implementation, and there will be no register involved here. Next, let's write the same code for a registered multiplexer, which include a clock synchronization. This is a block diagram of a registered multiplexer. It is same like our previous design, but now the output is synchronized with a clock signal. So there is a flip-flop here. Means we need to write our multiplexer logic inside a registered process block to ensure that the output is synchronized with the clock signal. Now this is the VHDL code for our registered process block and multiplexer. For registered multiplexer, we write our assignments inside a register process block, and the sensitivity list includes clock signal and reset signal. We do not need to write all the signals here in the sensitivity list in case of registered process block. Although you can write, but it will not make any changes in simulation. But if you write this, it can minor affect your simulation speed. So here is your VHDL code for this registered multiplexer design. P0 colon process reset comma clock begin if reset equals to 1, then Dout gets the value of 0. Else if rising edge of clock, then case select is when 0, Dout gets the value of A, when 1, Dout gets the value of B, when 2, Dout gets the value of C, when 3, Dout gets the value of G, when others, AND case, AND if, AND process, AND architecture. Now we begin the process body with the begin keyword. Next, we handle a asynchronous reset condition first. So when reset is asserted, then the output signal Tout is reset to 0. Then we check for the rising edge of a clock signal. Means any assignment written inside the corresponding if-else statement will be executed at the clock edge, and it ensures that the output is updated synchronously with the rising edge of a clock signal. Now inside the register process, we have written the same case statement as before. Means it will select the input line and pass it through the output based on the select signal. Then we terminate the case statement, then terminated the if condition, and finally terminate the process block with the AND statement. So this code will implement a registered version of a multiplexer where the output is synchronized with the clock signal. Okay, so that's it for today. I hope now you are familiar with multiplexer and their designs. So try to design these multiplexer using combinational and register process blocks and for different data types. In the next session, we will be talking about shift registers, and we will create our own shift registers in VHDL. In the last session, we talked about multiplexers in VHDL. We've seen how to write a VHDL design for a combinational multiplexer and registered multiplexer. Now let's talk about shift registers in VHDL, and we will explore how to implement a shift register in VHDL. A shift register made up of flip-flops, and they are connected in series. Like output of one flip-flops goes to the input of next flip-flop. So this structure is like a chain of flip-flops. Shift registers are versatile, and they can be used for converting serial data to the parallel data or parallel data into the serial data, depending how they are being used. They are also used to create variable and synchronized delay in a digital circuits as well. So flip-flops are the main component for shift registers. Hence, to design them in VHDL, we need to use registered process block. So this example is 4-stage shift register. Now, before writing the code for this design, let's understand it first. This shift register has a chain length of 4. Means you will need 4 flip-flops to design this shift register. Means chain length simply tells that the number of flip-flops in your shift register. Now let's look at the input signals. This is D in, and it goes into the input of first flip-flop. Next, all the flip-flops are connected in series, and output of one flip-flop goes to the input of next flip-flop. So output of first flip-flop connected with the input to the second flip-flop. Then output of second flip-flop connected with the input of third flip-flop. Same output of third flip-flop goes into the input of fourth flip-flop. Now this shift register has chain length of 4. So the output of fourth flip-flop is the final output. Means you are giving all your bits or data sequentially to this shift register. And if you want to see all of this input data at the output, means if you want to get parallel data from this serial data, then you can connect your 4-bit output to each flip-flop. Like you can see in this diagram here. Means this module is kind of a serial in, parallel out system. So this is one use case of your shift register. Now you will see that all these flip-flops are sharing the same clock signal and reset signal as well. We have also added one more input, that is shift enable. And when this is enabled, your flip-flops will pass out the data to the next flip-flop. And if it is disabled, then these flip-flops will do nothing. And the last signal is output Dout, which is 4-bit signal. Like we talked about that how we can get parallel data on this signal. Okay, so let's write the code for this shift register in the next slide. Now we have already covered generic session, right? So we know that how to design a flexible module. And this is the practical here, that how you can use generics in your VHDL designs. So quick brief that we are writing a code for that shift register and we can also adjust the width of it. So we will use generics and attributes in our code. In this slide, we are declaring library and entity of our module. So library and package declaration includes library IEEE use IEEE.std_logic_1164.all semicolon. Next is entity declaration. So this is the entity declaration for our module. Entity shift registers is generic bits integer bracket closed semicolon, then port clock in std logic, reset in std logic, shift enable in std logic, din in std logic, dout out, and this is std logic vector. Bits -1 down to 0, bracket closed semicolon, and entity semicolon. So our module name is shift register. Then we defined a generic named as bits, and it is an integer data type. So now you can adjust the size of your shift register. Next, we define the ports of our module. So from the block diagram, we have one clock input, one reset input, one shift enable input, and one data input din. All of these ports are std logic type. Then we have data output port dout, and this is std logic vector signal. Now the important thing is that the range of output signal is not fixed here. Instead, we have used generic parameter to define this range. So if you put 4 in generic, your range will become 3 down to 0. And if you set 8 in generic, then your range will become 7 down to 0. So this is completely flexible now. And at the last, we terminated the entity declaration. Now next is architecture part. So this is the architecture code. Don't afraid with this. We will explain it line by line. So let me read it first. Architecture, my design of shift registers is signal dsig std logic vector dout range semicolon. Begin shift register process process reset clock. Begin if reset equals to 1, then dsig gets the value of others are 0 semicolon. Else if at rising edge of clock, then if shift enable equals to 1, then dsig gets the value of din concatenation dsig dout left down to 1 semicolon. And if then dout gets the value of dsig semicolon and process and architecture. So we started from architecture declaration line. Then we define signal dsig, which is same as dout, means same data type and same length. Although this is not needed to define for this example. because we can straight assign the data to the dout. But this is just to explain you that how to use signals in your VHDL designs. Then we start our architecture from begin keyword. Now this is synchronous process, or you can say registered process. So we include clock signal and a reset signal in the sensitivity list. Next, we begin the process block with the begin keyword. Then we write the reset condition first. So when reset is applied, all the outputs or all the flip-flops output are set to 0. Now we have covered this in the last session, that how to assign values to an undetermined length vector like here. So we used others keyword here. If you are not clear about this, please watch my previous session on others keyword. So this statement will set 0 to all the output bits of vector signal. Next, we checked for the rising edge of clock signal. Now, there are many methods that how you write your code in VHDL. For example, for this design, you can instantiate flip-flops as component, or you can use loop for instantiation each component individually. But I have used this one-liner, and it will also do the same job. It might look confusing at the moment, but don't worry, I will be explaining this in next slide. But before this, let's terminate our if statement. Now, before terminating process, let's move our internal signal data to our module output. So we moved dsig data to the D output. Then terminate the process statement and then terminate the architecture body. Now, let me explain the main statement. And this statement is dsig gets the value of d in concatenation dsig dout left down to 1 semicolon. So we have dout definition as well, like dout colon out std logic vector bits -1 down to 0. Suppose bits value is 4. So the dout range will be 3 down to 0, right? Because bit value is 4 means bits -1 is 3. So it becomes 3 down to 0. Now coming to the second statement. This is dsig gets the value of d in concatenation with dsig dout left down to 1. So what is dout left? It is 3, right? So we already covered this in the attribute section. So if you have any doubt, then please revisit the attribute section for that. Now coming back, so we can write these lines as dout colon out std logic vector 3 down to 0. dsig gets the value of d in concatenation with dsig 3 down to 1 semicolon. Now let's focus on this assignment. On the left side, we have signal dsig. It is 4-bit long, right? Now we are assigning d in concatenated with dsig 3 down to 1. So length is still 4. 1 bit is coming from the input d in and remaining 3 bits coming from the trimmed dsig signal. How? Because dsig is 3 down to 1, means dsig 3, dsig 2 and dsig 1. Now look at this table. We start from the leftmost index. So index 3 is dout 3, index 2 is dout 2, index 1 is dout 1 and index 0 is dout 0. And when there is first rising edge of clock signal, we inserted d in at the third index and shifted all the indexes by 1. Means dout 3 gets d in, dout 2 gets dout 3, dout 1 gets dout 2 and dout 0 gets dout 1. So think a bit that can we map this with these 4 statements? Here is the breakdown of the elements on the right hand side. The leftmost index, which is index 3, has input d in. At index 2, we have element at dout 3. At index 1, we have the element of dout 2. Finally, at index 0, we have the element of dout1. So we understand that we can write each element like this, and this is the visual presentation of it. We start the assignment from left. So first dout3 will get d in, then dout2 will get dout3, then dout1 will get dout2, and finally dout0 will get dout1. Now just give a quick look at this block diagram and signal mapping. It is same like we have explained in the last slide, but now we are at first rising edge of clock signal. And this is the hardware representation of our assignment. And because these assignments are within a register process block, so it generated a flip-flops for each dout element. Therefore, there is a flip-flop for dout3, then for dout2, then for dout1, and finally for dout0. And at every rising edge of clock, data is shifting to the right. This is the detailed explanation that what is happening at every rising edge of clock signal. Although you can easily understand it if you are clear with the last few slides. But still, let me quickly explain it. So at first rising edge of clock signal, we start from the first assignment. We moved D in to dout3. So this is implemented by first flip-flop, labeled as FF1. That was the leftmost flip-flop in the picture, which D in was connected to the input of this flip-flop. And you can see now dout0 is moved out from this range. Means D in is inserted in place of dout3 and all the other bits are shifted to the right. Now at the second rising edge of clock signal, so D in shifted once again and now it is at dout2 position. And rest of the bits are shifted once again to the right. Means D in is moving through the second flip-flop now, which is labeled at FF2. Now at the third rising edge of clock signal, D in shifted once again and now it is at dout1 position and rest of the bits are shifted once again to the right. Means D in is moving through the third flip-flops now, which was labeled as FF3. Now finally at fourth rising edge of clock signal, D in shifted once again and now it is at dout0 position and rest of the bits are shifted once again to the right. Means D in is moving through to the fourth flip-flop now, which was labeled as FF4. So this is how our single line of code worked as shift register. And because you have used generics in your design, so you can use this with the length of any signal. Well, we missed to explain shift enable function. So here is a quick brief. So we said shift operation will only work if this shift enable signal is asserted. So we need to do something about this. So we placed our shift operation inside one additional if condition. So now our shift functioning will only execute when shift enable is equals to 1 and that's it. So this is our final VHDL code for parameterized shift register module. You can use this module to implement a shift registers of any length just by setting the bits parameter. We have also seen serial to parallel conversion using this shift register. And if you get a single bit output like dout0, then it is something like synchronized delay. Because whatever you give as an input, that will only get at the output after 4 clock cycles, or whatever the number you set in your generic value. So it added delay for the n number of clock cycles. In the next session, we will be talking about serializers and we will design it in VHDL. In the last session, we talked about shift registers and we also designed it in VHDL. We have also developed a module for serial in parallel out system using this shift registers. Now let's talk about serializers in VHDL and let's see how they works and how to design a serializer in VHDL. So let's start. So first understand that what is serializer. In simple words, serializer takes the parallel bits as an input and convert it into single bit output. Means it is a parallel in serial out system. So it takes parallel data streams and send the data to the output, of course in a sequential manner. Now question is what it do and where they are used. So these systems are widely used in digital systems and communication systems, etc. Why? Let's understand this with one simple requirement. So you have 32 bits to transfer. So if you have 32 separate lines, then you can simply transfer each bit on every line. And you can transfer all of your bits in just one clock cycle, right? But if you have just one single line where you need to send this 32-bit data, then how you will transfer it? Simple, because we assume that one line can carry one bit at a time. So you need to send one bit at every clock cycle, right? So here serializers can help you. How? Well, it will break down your 32-bit data into one single bit and pass that single bit to the output at each clock cycle. So the benefit is that you do not need to set up 32-bit channels. You manage to do it on one single channel. Of course, it takes 32 clock cycles, means more time to transfer same data compared to the parallel transmission. But still, you have a choice that how you want to do it. So at the transmission side, you use serializers, which will help you to send parallel data over a single channel. Then you will need a reverse system of it, which can take the single bit stream and convert it back to the original data stream, right? So we talked about that serial in parallel out system in the last session. So serializers are just reverse of that serial in parallel out system. If you have not seen that video, then please refer that after this one. Now coming back to the implementation part of serializer. So we need registers or flip-flops to implement a serializer. So in VHDL, we will use registered process block. So it will capture the parallel input data and shift that data one by one at every clock cycle. Means it will be synchronized with clock signal. Now in our example, we will use generic to design our serializer. Why? Because by using generic in VHDL, you can adjust its parameter for different application needs, such as width of your parallel data input. For example, you need it for a 4-bit parallel inputs, or for some other projects, you need 32 bits parallel input. So in such cases, you do not need to change your whole VHDL code. You just configure your generic parameter and boom, your whole design will work according to that. So that's the power of a configurable design, which you should practice always. So let's start with the implementation. This is the block diagram of a serializer module, and we will be designing this module. Let's quickly understand it. First, focus on input ports. So we have reset and clock signal. Reset is needed to initiate your module, and clock signal is needed for the synchronized shift of your data. Next, we have input DIN. So this input is STD logic vector signal and have parallel data streams, which we will be converting into the serial data stream. Now I have mentioned N with this port. So this port has N number of bits, and we will be using generic to define this N number in our VHDL code. Next, we have shift enable input. Means when this port is enabled, then only your data will start shifting. So it is an additional control. At the last, we have load input signal. This is important because when this pulse is given, your serializer will capture the parallel input data. Note that when there are multiple bits connected to your hardware, then they are always connected. It's not like you connect one pin at a time, then connect another, then connect another. It's not happening, right? So when all these inputs are always connected, you need to tell your module that specifically when it had to capture input data. And once it is captured, it will start moving that data to the output one by one. Note that it is just kind of a pulse, means you give it, then serializer will load that data and start transferring it. If you continuously triggered it, then only one single bit will be transferred at the output, and that have no use. So in short, this input signal indicates that when exactly it has to capture new data from D input into the serializer, so that it can ensure that the right data is loaded at the correct time. In the last, this module has one single output, that is Dout. So it is single bit output. So let's code this in the next slide. So this section is library declaration and entity declaration of our module. As I said, we will be using generic for flexible length of our input signal. So this is our library declaration first, and it is library IEEE use IEEE.stdlogic1164.all semicolon. Next, we have entity declaration section, and it is entity serializer is generic width colon integer bracket closed semicolon port clock in stdlogic reset in stdlogic shift enable in stdlogic load in stdlogic din in stdlogic vector width -1 down to 0 dout colon out stdlogic bracket closed semicolon and entity semicolon. Because this is very straightforward and we have explained it many times in previous videos, so I'm not explaining it again here. But in short, we have defined a generic parameter first, which is named as width, and then we define all the input-output ports of our module, which we have seen in the last slide. So we have input ports clock, reset, shift enable, load, and din. We have one output Dout. Just remember that din is stdlogic vector and its range is flexible now because it is width -1 down to 0. So if width is 4, it will become 3 down to 0. And if width is 16, then it will become 15 down to 0. So next is architecture section. So this is the architecture design of our serializer module. We start the architecture declaration. So let me read it first and then we will explain it line by line. So it is architecture behave of serializer is signal data register colon stdlogic vector width -1 down to 0 semicolon begin serializer process colon process reset comma clock begin. If reset equals to 1, then data register gets the value of others are 0 semicolon. Else if at rising edge of clock, then if load equals to 1, then data register gets the value of din. Else if shift enable is equals to 1, then data register gets the value of 0 concatenated with data register width -1 down to 1. And if and process, then dout gets the value of data register 0 and architecture. So architecture name is behave and module is serializer. Next, we define the internal signal, and this is data register. This is stdlogic vector and having the same range as input din. So what it will do? Well, it will hold your parallel data when you load it. Remember, I explained this in the block diagram. And then this data will start transferring to the output at each clock cycle. Next, start your architecture with begin keyword. Next, we start a registered process. So sensitivity list includes clock and reset signal. So first is reset condition. And when this reset is asserted, your internal signal, which is data register, will reset to 0. So the statement I have used is data register gets the value of others are 0 semicolon. I already explained this statement many times before, that how it moves 0 to all the elements of vector signal despite of its length. So you must know that why we have used it here, because we used generic to adjust the width of input signal. So we don't know that it is 4-bit or 16-bit or 32-bit data. So we cannot hardcode a fixed length value here. So when reset is asserted, then this data register is cleared. And after reset, you are ready to capture your input data. Next step is when load is enabled or load pulse is given, then we want to load our input DIN data into the internal signal, which is data register. And we want to do it in the synchronization with the clock signal. So we check for the rising edge of a clock signal first and then used that condition. If load is equals to 1, then data register gets the value of DIN. Means if load signal is asserted, then we will capture parallel data from DIN and we will store it in our data register. Next, we used else if condition, that else if shift enable is equals to 1, then means when this shift enable input is enabled, then only our shifting will work and your parallel data will pass to the output one by one. Now suppose shift enable pin is active, so we need to write our shifting operation. So we have written this statement here. Data register gets the value of 0 concatenation with data register width minus 1 down to 1 semicolon. Note that this statement will trigger at every rising edge of your clock signal. Means at every rising edge, 0 will be asserted at the most significant bit or MSB, and it will be concatenated with data registered width minus 1 down to 1. So 1 bit will be shifted out from data register at every clock cycle. This is what this statement will do. So this statement is the key statement of this module. And this statement is actually doing your shifting operation. So let's understand this once again. So we inserted 0 from the left side of the data register using the concatenation operator. Why? Because 1 bit is shifted out from the data register. As the new range is data register width minus 1 down to 1. And now data register length is not matched. So this is not allowed in VHDL. Means we need to add 1 additional bit to the register after shifting 1 bit from it. So your LSB or least significant bit will be transferred first. This is a common requirement in many serial communication protocols. So this completes your requirement of shifting. But till now, we have not assigned any data to the final output. But before assigning it, let's terminate all the if conditions. Now you can assign LSB or least significant bit of your data register to your final output. And you can do it inside the process block at the end of all the conditions so that your data gets transferred at the output. Remember, we have explained how this assignment works inside the process block. Inside the process, the last assignment on the signal takes place. So you can write it just before terminating your process block. Or you can assign it after terminating your process block as well. Means inside your architecture body. If you do so, both of your statements will execute concurrently. I mean your whole process block and this output assignment. Now you might confused that we hard-coded data register 0 bit to the output dout. Then how it will shift data and how I will get all the input bits one by one at the output, right? Well, that's true that we have hard-coded bit 0 to be transferred at the output. But this bit 0 of data register getting shifted by 1 bit at every clock cycle. So at each clock cycle, this bit will be overwritten by the following bit of your parallel data input. So this is how it works. Finally, terminate your architecture section using end architecture statement. So this is our VHDL code for serializers or parallel in serial out system. In the next session, we will design memory elements such as RAM or ROM, etc. in VHDL. In the last session, we designed a serializer in VHDL, which was configurable and capable of converting parallel data into a serial data stream. Now let's talk about memory modules in VHDL. For example, random access memory or RAM or read-only memory or ROM. In this session, we will be designing a single port module and a dual port module for a RAM. These memory modules are widely used in most of the FPGA designs for storing data. So they are quite important to learn. So let's start. Now, before we design them, let's understand few important things in FPGA designing about these memory modules. So in FPGA, data can be stored by two ways. Let's discuss the first approach. FPGA contains many number of registers, and synthesis tool analyze your VHDL code and detect some group of registers to form a RAM module. These registers are then grouped together to form some kind of a small memory. We generally call them register banks. These register banks are good for small memories because your synthesizer can infer these banks from your VHDL code. This means you do not need to write specific code to implement these RAM modules. So by default, FPGA can use these register banks to implement your memory in your projects. However, there are some disadvantages of register banks, especially when you are needing a larger memory elements for your designs. And if you only rely on the register banks, then they can quickly exhaust in the FPGA flip-flops. And it is not good because it will limit your ability to implement bigger systems that need lot of resources and elements from your FPGA. So we are needing some different way in such cases for more data storage. And as a second way, we can use block RAM, which is a dedicated memory in most FPGAs for larger data storage. Block RAM can handle much larger memories than register banks. They are generally hundreds of times bigger than the register banks. Now, when you want to use block RAM, you need to tell synthesizer that you are using block RAMs, not register banks. So your VHDL code will instruct that. FPGA vendors like Intel and Xilinx offer VHDL templates to help implementing of these block RAMs effectively. And you can implement many different and complex type of memories using these block RAMs. At the moment, we are focusing on two common type of modules, single port module and dual port memory module. We will start from the single port RAM first. So it has one write port and one read port. Address port is common for both, means read or write operation. You can write new data into the RAM block when this write enable signal is asserted, else it will read the data. Here, white text represents the ports of your RAM blocks. We define these port names in the entity declaration of our VHDL code. Red lines connects these ports to the signals which are in the black text. Now let's analyze the write cycle timing. So this is the timing diagram for a write cycle. So you will notice that we have given the write enable signal and data addresses input for one clock cycle. So it tells that you are writing data into the memory and you are also telling that at what address you are writing your data. Now here is an example of consecutive data writing. So we are writing value 8 and value 7 to address 0 and 1 respectively. So write enable signal is 1 for 2 clock cycles, and for the first clock cycle the address will be 0, and for the next clock cycle the address will be 1. So this ensures that both of the inputs are correctly stored at the right address in your memory. In this example, we are writing two datasets into the memory, but in a gap of one clock cycle. Generally, read and write operations are separated by one clock cycle for efficient data management. So at the first clock cycle, write enable pin is 1 and address is 0. So it will write value 8 at the 0th location in your memory. Then for the next clock cycle, we disable the write operation by setting it to 0. Then for the next cycle, we enabled it again for writing operation. This time we are writing value 7 at the first location of memory. So you can control read and write operation as per your project needs very easily. Now quickly understand the read cycle. So our write enable pin is set to 0, means now we are in the reading mode. You will notice that when reading from address line 0, we are getting data after one clock cycle. And because we have already talked about the propagation delays, you must visualize that why this happened. Note that these are from gate level simulation, not behavior simulation. So don't get confused on the results. Here is an example of successive data reading. In this example, we are trying to read data from 0th and first position. So we get 8 from the 0th position after one clock cycle. Next, we get 7 from the first position of memory. You can clearly see that in this timing waveform that the read data is behind one clock cycle. Means your RAM blocks gives the output after one clock cycle when the address is given. So in summary, we have data 8 and 7 at 0th and first position of memory element respectively. And we were reading them from memory one by one at each clock cycle. So this is our single port RAM module. Hope you are clear with the operations of a RAM module. So let's write the VHDL code for this single port RAM module. We will write our VHDL code with generics. So at the top, we declared necessary libraries and packages such as std logic 1164 and numeric_std. Both are from IEEE library. So it is like library IEEE use IEEE.std logic 1164.all semicolon and add numeric_std.all as well. Next we have entity declaration. Here entity is single port RAM. So let me read it first, then we will explain it. So it is entity single port RAM is generic dwidth colon integer semicolon e-width colon integer bracket closed semicolon, then port clock in std logic, write data in std logic vector dwidth -1 down to 0, read data out std logic vector dwidth -1 down to 0, address in std logic vector a width -1 down to 0, write enable in std logic and entity. So we have declared two generics here. These are dwidth and a width. Dwidth is to configure data size and a width will be used for address size. These generic parameters will give us the flexibility to use the same VHDL code for different project needs by adjusting the data sizes and address lines. If you do not use generic, then your data size and address size become fixed for some very specific requirement. So you may not able to use that stringent code for the wide applications because different projects have different memory requirements like different data size, different memory size, etc. So if you hardcode them, then you need to modify your VHDL code each time when you have different requirements or different configurations. So this method is inefficient and time consuming too. So always use generics as I explained in the generic session. If this is unclear about generics, then please watch that generic video once again. Because with generics, you do not need to rewrite your VHDL code just for the configuration changes. So your design will be more flexible and adaptable. Now coming back. So next we have port declaration and we will list all the input output ports of our modules here. including their name, their data types and ranges, etc. And of course, direction. Now, important thing is we used generics like dwidth and awidth to define our vector ranges for data bus and address lines. For example, if dwidth is 8, then your data line become 7 down to 0 for read and write data bus. Same awidth can configure your number of address lines and it is 2's power form. Now this is the architecture section of our memory module. So we have two sections here. At the top, we have declaration section, where we will declare or define all the internal signals which are needing for this single port RAM module. Bottom section, after this begin keyword, here we will define the functionality of our module. Let me quickly read this architecture first and then we will explain it line by line. So our VHDL code is, note that green color text are comments here. So I will ignore them. Architecture behave of single port RAM is type memory T is array 0 to 2's power a width minus 1 of std logic vector d width minus 1 down to 0. Signal my RAM colon memory underscore T semicolon begin RAM process colon process clock begin if rising edge of clock, then if write enable is equals to 1, then my RAM to underscore integer unsigned address gets the value of write data semicolon, and if read data gets the value of my RAM to underscore integer unsigned address semicolon, and if and process and architecture. So first we created a custom data type and that can hold array of words. The array's length should match the number of words to be stored and its width should also match with the number of bits in the each data words. We already know how to create a custom data type in VHDL. So we used keyword type to create our custom data type named as memory T. Now the size may confuse you a little because we have used generic parameters here, instead some hard-coded inputs. So our length has the range from 0 to 2's power a width minus 1. This tells your memory locations. Means if a width is 4, then this means you will have 16 addresses ranging from 0 to 15. And if a width is 10, then you will have 1024 addresses ranging from 0 to 1023. If a width is 8, then it will have the range from 0 to 255 and so on. So this was the addresses of our memory, but we didn't specify that what type of data it will store, like it will store character or it will store bits or bytes, what. In this code, this is also flexible. Means we are saying that it can have n number of bits and that you can configure from generics. So this is day width minus 1 down to 0 and it is std logic vector. Next, we declared a signal using this newly created custom data type. This is named as my RAM. Next is begin keyword and we will start writing our module functioning from here. Now we are using a registered process block here named as RAM process. You can choose any name because this is a register process block, so we have clock signal in the sensitivity list here. Although you should also use a reset signal, but we ignored that for the first time at the moment to make it simple. Next, let's see that what is happening at the rising edge of clock. So we have this condition. If rising edge of clock, then now we check that are we writing the data into the memory or reading the data from the memory. Means if write enable port is 1, means we are writing data into the memory. Then we have this statement. My RAM to underscore integer unsigned address gets the value of write data semicolon. So write data is our input data, and this data will be copied in my RAM, right? But my RAM has lot of addresses. So we need to tell that at which address this data should be written, right? So it will be written at 2 integer unsigned address. Now what is this? Well, our address has the range like 0 to 255 or 0 to 1023, etc. Depends on the A width parameter, means it is integer. And our input address is std logic vector signal. So we need type conversion here, like we discussed in the previous sessions. So this statement will convert that std logic vector signal into integer number, which will be our address. I hope this is clear because this will be used couple of times in our memory section. So a quick brief. Our address port is std logic vector and memory address is integer type. So in VHDL, we cannot use address port directly. We have to convert it into integer. So we perform this in two steps. First, using the unsigned typecasting operation to convert that std logic vector signal to the unsigned type. And then using toInteger function to convert that unsigned type to an integer data. This integer index will be your RAM location, where you will perform your read or write operation. So that's it. This is our write operation of our memory module. Next, we have read operation, and that is simple one-line code. We read data from some specific address, right? So we have address port to tell that which address to be used for the data read. And all the data are stored in my RAM array. So we will use address as an index to retrieve the data from the specific location. And then we will move that data into the read port. You can also write this read statement inside the else condition of this write enable condition. But the problem is that when write pin is enabled, at that time, what you will get at the read port means if read ports hold your last output, then it will create unnecessary latches. So this is written like that. Finally, we terminated all the if conditions and process block and architecture body. So this is our complete VHDL code for a single port RAM module. Now quickly discuss dual port RAM. So it has dual ports like two dedicated single port RAM. Means it has two read ports, two write ports, two write enable pin, two address ports, means everything is separated except the clock signal and the memory module itself. So look at this block diagram. You will see two sections in this module. Port A is in the left hand side and port B is on the right hand side. The advantage of this dual port RAM is that two entities can access your memory at the same time. Note that memory is same. It is not like two separate memories. They are just two separate ports only. So we have one single memory and that is shared with two different set of ports and they are completely separate. Means they have their dedicated data write, data read, address and write enable port. Note that clock signal is same for the both sets. Means all the read and write timings are identical and similar to a single port RAM. So let's write the code for this dual port memory. This is the library and package declaration. So we are using library IEEE, use IEEE.std_logic_1164.all, use IEEE.numeric_std.all, semicolon. This is entity section. Entity name is dual port RAM. So VHDL code is entity dual port RAM is generic D width integer, A width integer, then port clock in std logic, write data A colon in std logic vector D width -1 down to 0, read data A colon out std logic vector D width -1 down to 0, address A in std logic vector A width minus 1 down to 0. Write enable A colon in std logic. Write data B colon in std logic vector. D width minus 1 down to 0. Read data B out std logic vector. D width minus 1 down to 0. Address B in std logic vector. A width minus 1 down to 0. Write enable B in std logic. Bracket closed, semicolon and entity. This code is very similar to a single port RAM. The only difference is we have two set of ports now. Each set is labeled as A or B in the last. Means for port A, we have write data A, read data A, address A and write enable A. And for port B, we have write data B, read data B, address B and write enable B. Simple. So we are not explaining this much. Now this is architecture section. So this is our full architecture code for dual port RAM. Architecture behave of dual port RAM is type memory T is array 0 to 2's power A width minus 1 of std logic vector D width minus 1 down to 0. Signal my RAM colon memory underscore T semicolon begin RAM process colon process clock begin if rising edge of clock then if write enable A is equals to 1 then my RAM to integer unsigned address A gets the value of write data A and if read data A gets the value of my RAM to underscore integer unsigned address A semicolon. If write enable B is equals to 1 then my RAM to integer unsigned address B gets the value of write data B and if read data B gets the value of my RAM to underscore integer unsigned address B and if and process and behave. First we have data type definition and signal declaration. This is same like single port RAM. So I'm not repeating that again. I will straight jump to the process section. So we have this registered process block and clock is present in the sensitivity list. Next we have the condition of rising edge of clock. Then implemented the logic for port A of dual port RAM module. This code is same like a single port RAM again. The only difference is that now the port names are appended with the additional character A, like write enable A, address A, read data A, write data A. Next, we replicated these steps for the port B as well. This is also identical with the port A block. The only difference is now the ports are appended with the character B, like write enable B, address B, read data B and write data B. So both of these input output cells are independent from each other while accessing the same memory. Finally, let's terminate all the if conditions, then process block and in the last architecture body. In the next session, we will be talking about a very important concept in VHDL, which is widely used in designing. I mean finite state machines. We will understand that what is finite state machines, how it works in VHDL and how they are important. In the last session, we designed memory modules in VHDL and we learned how to code single port RAM and dual port RAM. Now let's talk about finite state machines in VHDL. We will discuss what is finite state machines, why they are important and how they works in VHDL. So let's start. This is a simple example of a finite state machine system. In this example, we have this heating system like in your geyser, etc. So let's see how you can develop this using finite state machines. We will look on different states and their transitions. So from this diagram, we see that we have three different states. These are idle, heating and ready. So it is quite simple. Idle means nothing is happening. Heating means heater is on, and ready means hot water is ready for use and heater is off. So let's say our initial state is idle, means you have just powered on your heater, and at that moment heater is off and indicator LEDs are also off. You can say this is our default state as well. Now you pressed on switch, and when it is pressed, your heater should start heating, right? Means heater will on and indicator LED will also on. So this transaction will happen. So this is our second state. Here heater is on and red LED is also on. And we got our first transactions when you pressed your on switch. So when we are at this state, we can have two options, right? Either you can switch off your heater at any point of time, or your heater reaches at the desired temperature. So when you switch off your geyser, say it returns to its default state, means this transaction is happening. And if the desired temperature is reached, then you defined one additional state for that, which is ready state. At this state, heater is off and ready LED indicator is on, means water is ready for you to take a bath now. Okay, so if temperature is reached at desired temperature, then this transaction will happen. Now, if you take a bath, then you want to switch off your geyser, right? So you made this transaction as well. Means when switch is released, it goes to the idle state again. Now you can also add one more transaction from ready state to heating state, right? For example, if temperature goes below some threshold, then you want to turn on your heater again, right? So you can add this transaction as well. Although I have not configured this transaction here, just to explain that how easy it is to make improvements further if you are using finite state machines. If there is something in your mind to improve the system, or you have feedback from your end users, you can deploy them very easily using finite state machines. So this is the benefit of finite state machines. I hope you understand it little. What is finite state machine? So it have many states, and you define those states and the transitions between them as well. And their states are finite, means you define each of your state. That is why it is called finite state machines. Okay, so let's develop this simple finite state machine model in VHDL. So this is our library declaration section and entity declaration section. Let's start by declaring the libraries and packages. So they are library IEEE use IEEE.std underscore logic underscore 1164.all semicolon. Now declare entity section. So this is our entity. Entity heater FSM is port clock in std logic, reset in std logic, switch in std logic, temperature in std logic, heater out std logic, red LED out std logic, green LED out std logic bracket close semicolon, and entity semicolon. So clock and reset are mandatory in finite state machines because FSM is a synchronized system and it is synchronized with your clock. Means every transition will occur at clock edge only. Other are all input-output ports, depends on your project requirement. So for this project, we have switch and temperature meter as an input port, and heater, red LED and green LED are our output ports. So everything is very clear from the last FSM diagram. We have switch input to turn on or off your heater, temp or temperature sensor to detect your current temperature so that if it is matched, we can change our state. And we have indicator LEDs like red LED and green LED as an output. So we explain this, that what they indicates, right? Like red LED means heater is on, green LED means you are at ready state or heater is ready. So this is our entity section. And next is architecture section. In this slide, we start our architecture and we define one new data type, which is having all of our state, means idle state, heating state and ready state. Name of this custom data type is FSM state type, and we have one signal from this data type. So our VHDL code for this section is architecture, behave of heater FSM is type, FSM state type is idle, heating ready semicolon, signal state FSM state type semicolon. Now begin. Next, we will code our main functioning. So this is our architecture, and our functioning start from this begin keyword. First, we have registered process block. So we have reset and clock in the sensitivity list. Next, we have reset condition first, or your initialized condition you can say. So all the outputs are turned off, like heater is off and LED indicators are off. Now we are also saying that we are at idle state when reset is given, and that's fair, right? And this is really important, just in case your system malfunctioning due to any reason, or while developing your system, if there is some logical error in your design and it is stuck at some infinite loop or state from where it is not going anywhere, so you can use this reset feature to jump to the default state. So this is very important to do. So we have our VHDL code like this. FSM process colon process reset comma clock begin. If reset equals to 1, then green LED gets the value of 0, red LED is 0, heater is 0, and state is idle. Else if at rising edge of clock, then. Now we will write our state machines from rising edge of clock so that everything is synchronized with timing and clock cycles. So we have this condition, else if rising edge of clock, then. Now the easiest way of designing finite state machine is case statement. Why? Because at any point of time you will be at one state only. So you will always have only one case to select. So each choice of case statement will define your current state, and you will write all the operations you want to do at that state. Also, you will specify that what will be your next state as well. Because if you do not define that, then you will stuck at the one single state. Now let me quickly read this state machine code in VHDL. Then we will explain it. So it is case state is when idle, green LED is 0, red LED is 0, heater is 0, and now next state definition. If switch equals to 1, then state is heating, and if when heating, red LED is 1, heater is 1, if switch equals to 0, then state is idle. Else if temp equals to 1, then state is ready, and if when ready, red LED is 0, green LED 1, heater is 0, and if switch equals to 0, then state is idle, and if. Now when others, state is idle, and case. So first is idle state. This is also the default state of our system. At this state, heater is off, and red LED and green LED also off. Means we'll state all of our possible outputs at this state. Now we will tell that what will be the next state and when. So from our state machine diagram, we said when input switch is pressed, then it will go to the heating state, right? So we have this condition that if switch equals to 1, then state is heating, and if. Well, you can write this state transition here like it is written, but you can also write them in a separate process block. Means one process block will drive your outputs and results, and another process block will direct your state transitions. Both methods will work fine, so you can choose any method. If you feel writing everything in one process block is complex, then you can split them in a separate process block. Now coming back, so we said if switch is pressed, then the new state will be heating. So define this heating state. Means when heating, red LED is 1, heater is 1. If switch equals to 0, then state is idle. Else if temp is equals to 1, then state is ready. And if. Now we monitor the switch input to detect if the user activates the system by pressing it or not. So at this state, heater will on, red LED indicator will turn on, and you can also mention that green LED is off. So outputs and results are defined for this state. Now specify that what will be your next state. So from the last finite state machine diagram, we can have two transitions from this state. First, when you switch off your heater, and second is when your desired temperature is met. So we write this condition. If switch is equals to 0, then state is idle. Else if temp is equals to 1, then state is ready. And if. So this is clear that if you release the switch button, then you will go to the idle state. And if the temperature is reached to the desired temperature, then the next state will be ready. You should also specify your third transition here. When switch is not released and when your desired temperature is not met. So at this point, we should stick at this state only. Means at this condition, your next state will be heating state itself. This is called self-state transition. Although I have not written that just to make it simple at the moment. Now let's define ready state. So when ready, red LED is 0, green LED is 1, and your heater is 0. If switch equals to 0, then state is idle. And if. In this ready state, the red LED is turned off and the green LED is turned on. The heater is also turned off at this ready state because the desired temperature has been reached already. So now you can guess that at this state, red LED is off, heater is off, and green LED is on. So these all are our outputs at this state. Now define your next state. So it has only one transitions in our state machine. That is, when you release the switch, then it will go back to your idle state. So simply write this with the if condition that if switch equals to 0, then state is idle. That's it. If you have more transitions, as I said, to go back to the heating state when your temperature goes below some threshold, that you can also add that transitions here as well. You may want to try that by yourself, then please try. You can take one additional input to input that what is your lower threshold, or simply take some offset from your desired temperature or percentage offset from your desired temperature, depending on your thought process. For example, you take offset of 10 degree. Then if you set your desired temperature at 60 degree, so when it will reaches at 60 minus 10 means 50 degree, it will jump to the heating state again. Same you can say that 10% of your desired temperature. So it depends that how you want to build it. Now coming back to our code. So in the last, we have this others condition. And we said that at this scenario, state will be idle. Note that other section is mandate with case statement. Does not matter that it is doing something specific or not. So it is here. And as a good practice, always include a when others statement in your state machines to return to a known state. And it will help you when your state machines or your design goes into some invalid state. Now you might question that how a simple state machine could enter into an invalid state, right? Well, in simulation, you may not encounter that if you are specifying all the states and all the possible transitions. Means I'm talking about the perfect design. But still, in real life or in actual hardware, there are many factors which can trigger these situations. Because you can have a robust logic and error-free design, but you cannot control external issues like environmental issues or hardware failures, etc. For example, hardware-related issues like power glitches, clock signal problem, timing violation, or power supply fluctuations. So these may trigger some random state which may not well defined in your system. Environment thing can be temperature of environment, humidity, etc., which can also trigger some random state. And from that state, if it is not meeting any condition to select the next state, or even just your product even not doing its operation, then issues can be anything. So in such events, this when other conditions covers everything for you. Now finally terminate the process block and architecture section of our VHDL code. And that's it. Your design is complete with a finite state machine system. Now it's time for some tips and quick recap. So finite state machines can help you in optimal design and functionality. Always design a state machine with a registered process. This will cover your transition issues and your design will always synchronize with your clock signal. Another reason of using register process is that state machine requires memory. So register process stores that state information in the flip-flops. Always give reset condition to ensure that your state machine can return to its default state. And it will also provide a well-known starting point for your designs. Next, try to define enumerated data types and list all the valid states of your state machines. Like we did for our example, we define idle state, heating state, ready state, like that. So each state is very clear that what it is and what it will do. Note that it will not add any additional hardware in your FPGA. This is just simplified code, and your synthesis tool is well developed to handle that in hardware. Just think that what if you have states like 0, 1, 2, and 3. Like 0 means idle, 1 means heating, 2 means ready, like that. How it sounds? Very bad, right? And it is not easily readable as well. So simply define them with the relevant and meaningful names. And in the background, your tool will figure out that how to decode it into a digital codes like 00 for idle, 01 for heating, etc. And trust me, it will reduce your chances of errors as well. And others can also understand your code very easily. Next, always use a case statement for any action against each state and also for defining your next state as well. So try to avoid using if-else statement as they can create priority decoders in your hardware and this can create inefficiencies in your designs. Like we explained in the previous session that how they are inefficient and how they degrade your hardware performances. As I said, you can split your code between two separate register process blocks for defining the output of each state and defining the next state. Otherwise, you can also combine both things into a one register process block, like we did in our example. If you feel that complex, then simply split it into two register process blocks, and it will not impact any hardware performance, and it will easy to read as well. So both ways are completely fine. Finally, always include a when other condition and use that for your reset transactions as well. And it will protect your design from logical glitches or hardware glitches or real life unwanted conditions. Hope you are clear with the finite state machines and now you know that what are finite state machines, how they works and how to design them in VHDL and what are the good practices. In the next session, we will be telling some important tips and tricks and good practices for FPGA designs and VHDL designs. In the last session, we designed a project using finite state machines and we learned what are finite state machines, how they work and how to code them in VHDL. Now let's talk about some good design practices in FPGA and VHDL designs. These tips and tricks are really important to learn and understand to code more robust and efficient designs. So let's start. Well, the most important thing is the code readability. Means your VHDL code should be very clear to understand. And for that, always use meaningful names for your signals, your process, your generics, your data types, constant and entities, etc. or any of the identifier you are using in your VHDL programming. And there are many benefits of it, like your code can be easily understandable. It will have lesser bugs or debug will be easy, and it will also ease any future improvements. Next thing is indentation. This is again important for code readability. We will understand it in the next slide in more details. But a quick brief that indentations are applied either by the tabs or spaces. Although spaces is much better choice when you are working on the different editors for your coding like Quartus, Notepad++, Notepad, etc. Because sometimes different editors display tabs with the different gaps and it can create some difficulty in your code mapping. But here the only point is to use indentation in your code, either tab or spaces. So let's understand this in the next slide. These are two VHDL codes here. If you closely look into it, you will see that both codes are same and they will do the same thing as well. But the only difference is that they look different because in the left, we aligned every statement based off its group, like what is inside if condition, what if inside process block, what is inside their case statement, etc. So you can clearly read this and understand this, right? But look at the right side code. Here also every statement is same. But can you read it easily? No, right? Because now you need to highly concentrate on each statement, that in which group or hierarchy it is placed, right? So tell me that in which section of code you are more comfortable to read and understand. Left one or right one? Left one, right? Because here we have used indentation, means we just align them by adding some additional tabs or spaces before the statement, and that's it. So you have choices, either use tab keys or few spaces. But I recommend spaces, especially when you are working on the different editors for your code. Reason is simple, that sometimes tabs get misaligned on different editors, but spaces are equally treated in all the editors. But when you use spaces, you enter at least 4 or 5 spaces to align your statements, unlike tabs, which is just a single press. In most of the editors, these are automatic and they are smart enough to add them. And some editors also give you choices as well. This is quite simple, I think, but important. Next tip is always try to avoid generation of latches in your designs. We have already covered this previously, but a quick brief here. Well, you do not design latches in your VHDL code specifically, but they get created in FPGA, especially when you are not careful in your branching of all the possible options in the conditional statements. Latches are generally not recommended in FPGA designs. They can be created with the combinational process block, but not for the registered process block. We already explained this, that why this happens. So any incomplete conditional statements like incomplete if statement or switch case statement in a combinational process will have high chances to generate these latches in your FPGA. So ensure that each and every possible condition is covered in the combinational process blocks. Now, clock is one of the important part in FPGA designs, and they are widely used in digital systems as well. And in maximum designs, they are external elements like coming from oscillators or clock drivers or clock generators, etc. Means some other component or external component. But the problem is that these components generally comes with a fixed oscillations and your needs might be different from a different projects. In such cases, we adjust that clock cycles based on our project needs. And this can be done through your VHDL codes. For example, you have a 50 MHz clock connected to a FPGA pin. and you need a 25 megahertz clock, or you need a 1 hertz clock cycle for a digital watch. So for this example, we can generate a 25 megahertz clock using a register and a NOT gate, like in this block diagram. So you input 50 megahertz as an input clock and 25 megahertz at the output of this flip-flop. And output of this flip-flop will be your clock signal for the rest of your designs, like you seen in the next slide. So you can see that FF1 has a 50 megahertz clock. Then its output goes to FF2, and this signal will have 25 megahertz of clock for FF2. However, this will work fine, but this type of designs is not recommended because there are some practical issues in this design. One issue is routing delay for 25 megahertz clock. That may come from your clock to output delay of FF1. Now understand what are the problems when you generate your clocks using the logical elements like we did. So your FPGA can have multiple regions from where it can get external clock signal. So your routing or placement of elements can create problem. Delay of your clock signal can also vary depending where that flip-flop is located inside the FPGA. Remember that synthesizer can place this flip-flop in any location inside the FPGA. So delay can be different for each combination. Means delay can be different from one FPGA to the another FPGA. Also, these delays also affected by the given voltage and temperature. Means it can have environmental impact as well. So this is not a practical or a real life solution. Remember that you will not see those issues in your behavior simulation because these are practical issues. Also, vendor tools such as Quartus Static Timing Analyzer, they also struggle in analyzing clocks if you generate them like this. So try to avoid using them like this. So what is the good approach then? The better solution is that use PLL or phase log loop to generate this 25 megahertz clock. Modern FPGAs typically have these built-in PLL resources, and they are very easy to use to generate various clock frequencies. PLL or phase log loops can directly drive your global clocks in your FPGA designs. Also, if you are doing this, then this is also not a good practice. Like when you add some gate or elements on your clock signals. So here goal is to capture input A only when this enable signal is applied. And this method is not recommended because these additional logical gates before the clock signal will add logical delays in your clock path. Also, as I said that applied voltage or temperature can also affect these delays. Means they can malfunction based on the external things or environmental changes. And it can also limit your maximum operating frequency for your designs. So avoid this kind of approach in your designs. So the question is how to do this. So let's see in the next slide. So this is a better way of doing that. You can see that we didn't touch our clock signal. Instead, we applied our logic on the D input or input port. So we added a multiplexer on the data path, not on a clock path. This multiplexer will ensure that you will get input A only when this enable signal is applied. So your clock signals remains unaffected by any logical gate delays, and it is directly reaching to your flip-flops without any additional component between them. So this system has better timing margins compared to the last one, and it can operate at the higher clock speed as well, means better operating frequency. Even some FPGA architectures provide some flip-flops with dedicated enable pins, like in this block diagram. In such cases, your synthesis tool will integrate that without any additional component. So this is a simple VHDL code for what we are discussing. And this code can implement any of the circuits below, depending on what type of architecture you have. If your FPGA have this element with enable pin, then it will use that. Else it will add this multiplexer design. So you can see that how easy it is to code them in VHDL. Just remember, avoid using the gate structures on the clock signal until there is no option you see to fulfill your project needs. Although this is very rare or unlikely. We discussed some of the good practices for your VHDL and FPGA designs. We learned how to improve code readability, how to use instantiation in your VHDL code, how to avoid latches in combinational circuits, and what are good structures when you are working with the clock signals. In the next session, we will continue with more tips and tricks to make your VHDL designs more agile and flexible and more reliable at the same time. This is Good Design Practices Part 2. In the last session, we learned how to improve code readability, how to use indentation in your VHDL code, how to avoid latches in the combinational circuits, and what are the good structures when you are working with the clock signals. We also learned that modern FPGA comes with many number of inbuilt registers, so feel free to use them in your designs. These can help you to enhance your timing performances of your designs. They can also simplify your debugging and verification processes as well. So try to use those registers for your input-output ports in your VHDL designs. This is a simple block diagram of what I explained in the last slide. So you can see that your input and outputs are well synchronized with your clock signal. And by doing this, you will minimize your timing issues in your real hardware. Let me explain this. So we have this simple module. It has input A and output B, and of course one clock signal. Now we are doing some operation on signal A using this logical implementation, and this can be anything depend on your project needs. And then we get the output at port B. But we didn't connect this output directly to the FPGA pin. Instead, we moved it through this flip-flop. Means your output is well synchronized with the clock signal. So it does not matter that what is your transition delay. You will get output only at the clock transition. As an additional step, we have also synchronized input ports as well. So before using this input, we passed it through this flip-flop. Means the output of this flip-flop is registered version of signal A. So your input signal is well synchronized with your system clock before further processing. This simple design practice can reduce your timing errors and help you to offer consistent and predictable behavior in different real-life conditions like we discussed. And you will get a robust design which is well equipped for different situations. Now you may question that how this method improves your timing performance and how it makes your design more robust against the real life conditions. So we will understand this with the concept of pipelining in the next slide. Pipelining is a concept to manage the data flow more efficiently at maximum possible operating frequency. So few points about pipelining is, we know that larger combinational functions also have longer delays. So it creates timing bottleneck. So pipelining helps you to mitigate these delays and boost your timing performances. Pipelining uses extra registers to break up large combinational functions into a smaller one. Let's visualize this in a real life example. So we have this big combination circuit. Just assume this like any big circuit structure with lot of elements which are connected one after another. Means output of one element goes into the input of another component and further passes through more elements like this to the output, and finally reaching at the output like we have chat signal here. Now because there are a lot of components in this structure, So your input signals has to go through from these elements to reach at the output, right? Means they will have higher gate delay or propagation delay, anything you can say. And that delay is a major bottleneck in high speed circuit designs. So they can limit maximum speed of your FPGA designs, means your hardware performance will hit in terms of circuit delays. So question is that how you will minimize that delay or how you can increase timing performance of your designs. Well, one simple way is that just reduce the propagation delay, right? How? Well, try to use better fabrication process and design smaller elements, right? But the problem is that this process is costly in terms of chip development because you need newer technology for developing them and that come with a cost. Also, you do not have much control beyond some point because that has some limit. And if you're only working on the FPGA designs, then you do not have that choice as well. You can just choose a better FPGA model and that's it. And their performances is well known, means you cannot demand better from the same chip. So the option you have is to optimize your structure design itself, means your combination circuit. How? So the simple answer is by using pipelining. So in pipelining, we simply break a large combinational chain into a multiple shorter chains. Now you will have individual delay for each segment or each set of elements, which are splitted for smaller tasks. For example, suppose if this big structure has 10 nanosecond of delay in some specific condition. Now, when you break this, you will have smaller delays for each segment. Like some group will have 4 nanosecond, some will have 8 nanosecond, and some will have 6 nanosecond like that. Now, if you are clear that what is pipelining, then let's understand how it works and how it can help you in reducing overall timing performances. Now remember that we have used register version of input and output ports here. Do you see these flip-flops at input and output ports? Means they are synchronized with the clock signal. We discussed that in the last session, that why we are doing this. So our goal is that we are trying to improve that operating clock cycle for this design, right? So let's see how it is happening by pipelining. So here we have two timing diagram. Top one has the clock frequency of 50 MHz and bottom one has the clock frequency of 100 MHz. Now in the last slide, we assume that our propagation delay is 10 nanosecond, right? And for that big combination circuit. So 50 MHz clock has 20 nanosecond of a clock cycle, right? And 100 MHz clock has 10 nanosecond of clock cycle. Means 50 MHz signal will take 20 nanosecond to complete one cycle and 100 MHz will take 10 nanosecond to complete one cycle. This is a simple math. Just divide your clock frequency from 1 second and you will get the time for a one clock cycle. Like 1 second divided by 50 MHz, then it is 20 nanosecond. And same 1 second divided by 100 MHz, then you will get 10 nanosecond, right? Now remember that what was our propagation delay for that circuit? That was 10 nanosecond, right? Means we cannot use more than 100 MHz signal for that design. If you use it, then your design will malfunction because your signal transactions will not happen before the cutoff time. So 100 MHz is your maximum operating frequency for your design. And now the task is to improve it. But before that, let's understand these two timing diagrams. Because if you do not understand this, you will not understand next slide as well. So first focus on this 50 MHz signal. Suppose we changed our input at this point. Now because your circuit has 10 nanosecond delay, so your output will change at this point, means after 10 nanosecond. So after this point, whenever you get the rising edge of your clock, you will get your final output and that will be your correct output. Remember that final output is driven by a flip-flop and synchronized with the clock rising edge. means you will get correct output at the rising edge of this frequency. Now let's do the same for the bottom timing diagram. This has 100 MHz of a clock cycle, means your clock has 10 nanosecond of cycle. Now if you change your inputs at this point, your output will still change after 10 nanosecond because that is your propagation delay, right? So after this point, your output will be captured by the flip-flop and you will get your final output. Means if anything change beyond this point, then your output will not change at this clock cycle. It will need another rising edge of your clock, means another 10 nanosecond. So this 100 megahertz frequency can also work fine because your output become valid just before the rising edge of your clock cycle. Although it is very neck to neck, hence this is not recommended because slight external changes can fail your system. Also, your flip-flop will also need some setup time. So there is a possibility that your flip-flop will not capture signal on time due to very tight timing constraint. So in short, 50 MHz is a perfect fit for this design and 100 MHz is acceptable but not recommended. Now here is the actual problem comes when you increase your operating frequency to 120 MHz. So look at this bottom timing diagram. This is for 120 MHz clock signal and top one is copied from the last slide and it is for 100 MHz clock signal. So let's focus on the bottom one this time. When clock is 120 MHz, means clock period is 8.3 nanosecond, but your design still have 10 nanosecond of propagation delay. So you can see that this is our clock cycle and we get the rising edge at 8.3 nanosecond and we change our inputs at this point. So we get our output after 10 nanosecond. But the problem is that at this point, when clock signal having the rising edge, you still do not have the valid output because it takes 10 nanosecond. So you will get the right output at this point. So as a consequence, your output is not correct at this point. Means you cannot use this frequency for your circuit because you will not get a reliable output from your designs at 120 MHz. So let's see if pipelining can help you to improve this situation. Now by implementing the pipelining, we divided the large combination logic into two or more smaller segments of combination circuit. This division will help us to manage delay more effectively. Now what we have did that we break down our big circuit structure into two separate designs and we inserted additional flip-flop between these two designs or segment you can say. This we called pipelining concept and your propagation delay is now reduced for each individual segment. So in this case, your highest propagation delay is 6 nanosecond for one segment and now this can drive your more operating frequency. Means highest delay reduced from 10 nanosecond to 6 nanosecond. Although the total delay is still 10 nanosecond, but segment delay is splitted in 6 nanosecond and 4 nanosecond. So don't get confused. But the benefit is that this flip-flop, which is in between, will capture your signal according to the 6 nanosecond delay. And then it will forward that to the next segment. So if we consider to neck operation like 100 MHz with 10 nanosecond delay, now it becomes 160 MHz with 6 nanosecond delay for the same design. Means your operating frequency is increased from 100 MHz to 160 MHz. If you break down your big structure into and insert additional flip-flops between them as bridges. So this is called pipelining concept. So we understand it, right? But there is a trade-off if you are using pipelining. You know what? Although we increased our operating frequency, but now you will need additional clock cycle to get your final output. And of course, additional flip-flop elements in your hardware. So this is the downside of this approach. but at least you get the right results and your designs is not malfunctioning. And that is more important, right? So quick brief, always try to use synchronous systems for your designs, like we did for our input output ports in the last example. Means you will have one clock signal which is driving all the flip-flops and everything else is synced with your clock signal. Ensure your input and outputs are properly synced, and by doing this, you can eliminate maximum of your timing issues in your designs. Means lesser timing glitches and errors compared to a asynchronous design. Means better FPGA designs covering more practical situations, right? Try to prefer registered process blocks over conventional process block, and it will enhance the reliability and performance of your designs. Also, synchronous designs are easier to debug and maintain, so they are more practical for complex FPGA projects. So quick summary that what we have covered till now in the best practices. First, always use meaningful names and proper indentation to enhance your code readability and maintainability. And by doing this, your code appear more professional and self-explanatory. Next is avoid using latches as they can cause timing issues and lead to the unreliable circuit behaviors. Fourth is do not generate clocks using logics. They can affect your design performances. So use PLLs or phased lock loops to modify clocks. Don't add circuit elements on the clock path. Instead, write your code for the data path, like we discussed about multiplexer example for the enable pin functionality. Use registered or flip-flops in your designs for better timing performances. Apply pipelining concept whenever you are required higher operating frequency. Try to design synchronous circuits instead combinational circuits for better reliability and performances. In the next session, we will continue with more tips and tricks to make your VHDL designs more agile and flexible and more reliable at the same time. This is Good Design Practices Part 3. In the last session, we learned that why we should use synchronized input-output for our FPGA designs and how to synchronize them. We understand pipelining concept and we learned where to use them and how it can improve your operating frequency of your designs. Now we will understand asynchronous inputs. We will know that what are asynchronous inputs and why you should avoid using them in your FPGA designs. And most importantly, how you can synchronize these asynchronous input before using them in your designs. We will learn about two-stage synchronizations. We will talk about cross-clock domains and synchronized reset deassertion. So let's start. So we know that our FPGA designs has some input ports going into the FPGA and some output ports coming from the FPGA. Out of these input outputs, we have to be very careful on asynchronous inputs. Asynchronous inputs are the inputs which can change their state at any time, just like a push button switch or RS-232 signals. These signals are not driven from a clock. So if you use them directly in your FPGA, then your designs can malfunction. So the solution is that we can synchronize all of our asynchronous input. Let's look at this simple example. We have asynchronous input named as X async, and we want to synchronize this input, right? So we pass this input through a 2 flip-flop inside the FPGA. And now output of second flip-flop is synchronized to our clock signal. And it is ready to use now by rest of your FPGA design without any timing issue. This is called two-stage synchronizing chain because it uses 2 flip-flops to synchronize your asynchronous input. It is important to note that you should not have any combination logic between these 2 flip-flops. So this is the VHDL code for this. We are needing a registered process block to implement 2 flip-flops. So we have 2 signals, temp and X-sync. Temp is the output of first flip-flop and X-sync is the output of second flip-flop. So at the first rising edge of clock, your asynchronous input will pass through the first flip-flop. It has signal temp here. Now at the second rising edge, this temp signal will pass through to the second flip-flop and you will get X-sync output. So this X-sync signal is now synchronized with our system clock. And now you can use this signal as an input for rest of your design. Means you turn your asynchronous input into a synchronized input, right? Now let's talk about cross-clock domains. This is little complex topic. So we are explaining some basics first. So the problem comes when you are working with two different clock signals in your designs. Because one clock domain is generally asynchronous to the other clock domain. Means if you sync your signals with one clock signal, then they will probably asynchronized with the another clock signal. So you need to find a way to sync that signal with both of your clock signals. If you have just one clock signal in your design, then there is no need of cross clock domain. So let's see how to do cross clock domain. Well, there are a couple of ways to do so. The simplest way is to use two flip-flop synchronizing chain, as we have seen in the last slide. Another way is to use additional signal for handshaking. For example, you can generate additional ready and acknowledge signal for handshaking between two different clock signals or between two different clock domains. When you have more data such as wide data bus cross clock domains, then you can use bell clock by force to cross the clock domain safely. Next step is use of generics. So try to use generics as much as possible in your designs. This will help you to reconfigure modules very easily, and hence you can reuse your VHDL modules in different designs with very small changes. Means you can write your designs with lesser code and also lesser mistakes, and it can save you a lot of time because now you have reduced your code redundancy. Means now you are not writing code for your whole design. You are just using your previously developed modules in your code and they are already tested. Means you do not need to test those sections of code. So your time is saved in testing and debugging as well. Next good practice is that always reset all the outputs of your synchronous process. Means always use a register process with a reset signal. Generally, this reset signal is applied when powering up your FPGA, and this is external from the FPGA. Now, when we talk about external reset signals, means outside from the FPGA, then it is recommended to synchronize reset deassertion. Why? Because these are external reset, like coming from some kind of a reset switch. Means these are asynchronous in nature or asynchronous input. So we must synchronize it to avoid any potential timing issues like we discussed earlier. And if you try to use asynchronous reset signals, then different sections of your FPGA will trigger the reset at different time because of routing delay. And this is not good because some registers inside the FPGA may already complete the reset process, but some sections may still in resetting process. So in such cases, some part of your design may lag by one cycle and some may lead by one cycle. And this is enough to malfunction your design. Means your designs may be not a reliable design. So this is a simple way to synchronize your reset signal. We used two flip-flop synchronizing chain. Output of first flip-flop is temp signal and output of second flip-flop is synchronized reset signal named as reset out. First flip-flop has input 0 at this time. Reset input mentioned by the red color and connected to the asynchronous preset pin of both the flip-flop. And output of this system is reset out. And this signal is now synchronized reset signal. And this can be used now to reset rest of your FPGA design. So when this reset input signal goes high, your reset output will also go high, and that will reset your whole FPGA design at once. And when this reset input signal goes low, then your reset output signal will also return to 0, but only after 2 clock cycles. Means your FPGA will come out from reset after 2 clock cycle when reset is asserted. So this is a simple VHDL code for this circuit. We have used registered process block, means clock and reset input is in the sensitivity list. So when reset is applied, means reset in is equals to 1, then output of both flip-flops are set to 1, means temp is 1 and reset out is 1. Now if reset is not given, then at the rising edge of clock, we moved 0 to the temp signal, and then this temp output moved to the reset out. Now it's the time for some important notes on clock and reset signal. So we should always try to use global nets in FPGA when routing clock and reset. These are high speed nets and have very low delays. Means these signals can reach to all the registers inside the FPGA in almost same time. This is very important. Modern FPGA tools are smart enough to assign these global nets for your reset and clock signals from your VHDL code. So you do not have to worry about this. Next is always use PLL to clean up input clock signal, even if you are not changing your input clock frequency. Because in real hardware, there are many types of noises. And because of these noises, sometimes single rising edge of clock appears like two rising edges. And this can give unreliable results in some scenarios. So these PLL or phase lock loop can help you to eliminate these type of problems caused by some noises, because PLL are having low pass characteristics. So quick summary. Remember that always synchronize all of your asynchronous input by using two flip-flop synchronizing chain, including reset signal as well. Always consider cross-clock domain problem when you are working with two separate clock signals. We have seen how to minimize this clock domain problem in the 12 clock crossing. These are important to design like this if you want to use your modules and designs in wide set of applications. Means by using this approach, you can reuse your modules for different projects without worrying about different kind of issues which we have discussed. Next, try to use generics in your designs so that you can use them for wider applications. Always initialize your designs and signals using a reset signal. Use global nets to route clock and reset signals. Use PLL to clean up all of your input clock signals. So these are some tips and tricks for good VHDL and FPGA designs. Try to apply them as much as possible in your practices. In the next session, we will do a simple project using LEDs and shift register. Today, we are going to create another project. So we will design it in VHDL and then we will implement it on FPGA board as well. So in today's project, we will drive a pattern on a set of 4 LEDs. These 4 LEDs will be connected with the FPGA board, and at the initial stage, only first LED is on and rest 3 LEDs are off. We will also use one switch button in this project as an input. So when I press this button on the development board, then this LED pattern will shift one by one at each press of switch like this. So at initial stage, first LED is on, right? And rest 3 LEDs are off. Now I press the button, then second LED will on and other 3 LEDs will be off. Now I press the button again. Now third LED will on and rest LEDs will be off. Now I press the button for the third time, then this fourth LED will on and rest LEDs will be off. Now if I press the button again, then again the first LED will on and rest 3 LEDs will be off. So this pattern will run in a cycle, and we are basically shifting our output when we press the switch input, right? So this is a kind of shift register, but we will see that how to implement this in FPGA. We will also have a reset switch as well. And when we press it, then we should jump to the initial stage. Means first LED is on and rest 3 LEDs are off. In this session, we will also talk about the bouncing problem in a switch. So let's move to the Quartus Prime software and start developing it. But a quick brief that what and how we will design this. So first, we will design a 4-stage shift register, which will shift the LED output when the button is pressed. So we will have something this kind of a structure. We will need 4 registers and state of each register will be connected to the each LED output. So to create that LED pattern, we need to connect these registers in a series like this. Means output of one flip-flop will go to the input of next flip-flop. Like output of first flip-flop going to the input of second flip-flop. Then output of second flip-flop going to the input of third flip-flop. Then output of third flip-flop going to the input of fourth flip-flop. And finally, output of fourth flip-flop again going to the input of first flip-flop. So it is in the loop. And then we will connect each LED to the output of each flip-flop like this. So what will happen that we will reset these register output to 1000. Means first LED is on and all the other LEDs are off. And then for each press, this data will shift to the right. Like when you press the switch, you will get 0, 1, 0, 0. Means now second LED will on and rest LEDs will be off. And for the next press, this data will be 0, 0, 1, 0. Means now the third LED will on and rest will be off. Now remember that we want our LED pattern to shift only when the button is pressed. Means we do not want to shift this data all the time at our clock cycle. So we only want to shift data when button is pressed, right? So we need a shift enable input like this, which will control this shifting of data, right? Means when this switch press is detected, then only your LED pattern should shift. So we need to think about this functionality as well. Now because this switch is asynchronous in nature, so we will convert it into synchronous signal by using 2-stage flip-flop like we discussed in the best practice sessions. And third, we will write another process to detect if the switch is pressed or not. Now this is very important because you are designing your system with a 50 megahertz of clock frequency. So if you use this to shift your LED output, then it will happen at very high speed. And you will not be able to see any shift with your eyes because that will happen at millions of times in a second. So we has to do something for it. So we will drive one extra internal signal to bypass this problem. Means your LED will shift only when switch is pressed, not at every clock cycle. So this will be interesting to see. So let's move to the practical. Okay, so we will start our Quartus software. So write Quartus and we are having this Quartus 2 10.1 web edition. So we will open this one because we have device Cyclone 2 and that is not supported by the newer version like we have installed in our machines. So we are using this Quartus 2 software that is 10.1 version. Now this is our landing page. So first we will create a new project and for that we have this new project wizard button. So click on it. Okay. Now click on next. Now give some folder name. So suppose I'm giving project 01 and give the project name. So my project name is project 01 for example. Now click on next. Click on next. Now we will select our device. So I have Cyclone 2. So I will select it. Package. I have this one 208 pins I have, and grade is 8. So there are 4 devices and I have to choose my device name. So I have this one, AP2C5Q208C8. You will select whatever device you have for your working. I have selected it and now click on next. Although I am not doing the simulation, but you can choose whatever simulation you are using. So it's the same. Now click on next and now click on finish. So the project has been created. So we have this project. Now we will open a new file, or we will create a new file. So I will create on this button, or you can go from here as well. So file, new. So both are doing the same job. And now we will select this VHDL file because we are writing our code in VHDL language, right? So select VHDL. Now click on OK. So this page has been opened. So this is our programming editor. Okay, so we will write a program here. So library IEEE, use IEEE.std underscore logic underscore 1164 dot all. Now define the entity. So write entity project 01 is port. Now you will define your ports here. So what we have clock as an input. This is std underscore logic type. We have reset in std underscore logic type. We have switch SW in std underscore logic type. And we have output. So suppose output is LED and this is out, and we have 4 LEDs, right? So instead defining 4 separate signals here or 4 separate ports here, I will choose this std underscore logic underscore vector signal. So this is 1 to 4. So each individual element is treated like a single LED as an output. Okay. Now everything has been defined as an port, input output ports. So we have these 3 inputs and 1 single output, but this is vector type. Okay. Now I have defined all the ports, then bracket close, semicolon, and entity. So and project 0. Now it's time for architecture declaration. Okay. So we are defining our program here. We are defining our functioning here. So architecture behave of project 01 is now begin, and in the last and behave. I'm just writing the structure first. Okay. So first we will design our shift register like I explained, right? So for this we will write a process block. Okay. So we will defining some process name. So this is suppose shift process. Now this is the registered process block. So we will have clock and reset in the sensitivity list, right? Now begin and end process. Now because this is register process block, so definitely we will have reset and clock. So define that body. If reset equals to 0, then now else if rising edge of clock, then end if. So this is our general body for registered process block, right? Now we will define our functioning here. Now if you wonder why reset is equals to 0, because we are using a physical switch, right? And our switch is by default set to 1. And when we press it, then it is asserted as logical low or 0 value. So by default, when it is not pressed, it is having the value of 1. And when we will press it, then we will get 0. So when it is 0, it is asserted. Okay. So that's why it reset is equals to 0. Okay. So don't confuse why reset is not equals to 1. Okay. So if reset is equals to 0, now what we want our shift register to set to the reset value, right? So for this we are needing a signal, antenna signal. So define that signal. Suppose this is shift register, and this is again std logic vector, and it is having the same range like our output. So we have LED. So I'm giving LED range. Okay. You can initiate some initial value as well. For example, I'm giving 1000. Okay. So if reset is equals to 0, then our shift register will set to default state. Okay. So shift the register will get the value of 1000. So this is our default state. Then if you wonder that why 1000, not something else, not 4 times 0, so it comes from our requirement. So what we have said that we have one LED that is on and rest of the 3 LEDs are off, right? So this is our LED 1 that is on, and we have rest 3 LEDs, these are off. Okay, so that's why it is 1000 for the reset condition, right? Now what will happen at the rising edge of clock? So if switch is pressed, so suppose give some name, suppose I'm saying button pressed. If button pressed is equals to 1, then we need to shift our registers, right? We need to shift our data into the register, right? So we will have shift register 1 will get the value of shift register 4, right? So it is moved from last to first LED. Okay, same shift register 2 get the value of shift register 1, right? Now shift register 3 will get the value of shift register 2. Again shift register 4 will get the value of shift register 3. So we have 4 stages of shift register, right? So I have written 4 statements here. This is fine at the moment because we have just 4 registers. Now suppose if you have 100 of registers from which you are shifting your data, then you need to write 100 of lines here, right? And that is impractical. Okay, so I've explained you one simple way of doing this. So what it is? So we can write that shift register gets the value of shift register 4 concatenation with shift register 1 to 3, right? So if you break down this statement, then it will be like shift register gets a value of concatenation with shift register 3 concatenation with shift register 2 and concatenation with shift register 1. So this statement and this statements are equivalent. They are exactly same, right? Now if you split this shift register again, so suppose you are splitting this shift register, so it will be shift register 1 concatenation with shift register 2 concatenation with shift register 3 concatenation with shift register 4. So for this shift registers having 4 elements, so these are the combination of shift register 1, 2, 3 and 4, right? So all of these 3 statements, like this statement and this statements are exactly same. Okay, these are just representation, different representation. Okay, so this is the statement which we will use. Okay, so I will remove these 2 statements here and we will only use this single statement. We don't need these 4 statements because this statement will do the same job. Okay, so if button is pressed, then shift register will shift 1 data at each clock cycle. Okay, so this is the mean. Now close this, and if, so we have terminated this if condition as well, we have terminated this if condition, and we have terminated this process block as well. Now we have used this signal named as button pressed, but we have not defined it, right? So first we will define this. So this is a signal button pressed. This is std underscore logic type. Now we have defined this, we have used this, but we didn't tell that how we will get this signal, right? How it will be operated. Okay, so next process we will write for this button pressed. So we will need another process. Now before doing this, we have important thing to do, and that is synchronizing this switch. Okay, we have this input switch, and that is asynchronous in nature. Means we can press that switch at any point of time. And remember, I have explained that we should synchronize all of our asynchronous signals, right? So this is asynchronous. So we need to synchronize it. How? Well, by two flip-flop chain, right? So create a new process. So suppose we are giving this some name like process underscore sync. Okay. Now this is a process. Again, this is a register process block. So we will have clock and reset in the sensitivity list. Now begin and end process. So we have just created the body for this one. Now default structure, if reset is equals to 1, then else if rising edge of clock, then and if. Okay, so this is our basic structure. Now for this sync process, I will create another signal. So suppose we am creating a signal. So what I have said, we are using two flip-flops in a chain, right? So we are needing two internal signals. So I'm creating one single name. So signal sync, that is std underscore logic underscore vector 1 down to 0. Now it is having two elements, right? Now coming here, if reset is equals to 1, then this sync signal should be 1 1. Okay. Now else if at the rising edge of clock, then sync 0 gets the value of switch. So this is the input switch, right? This one. Okay, so this is our input. And then this is one stage of flip-flop. So at the first rising edge or first clock cycle, this switch input will go to this sync 0. So this is one stage. Now for the second stage, sync 1 will get the value of sync 0. Now you can say that we are moving switch input to the sync 0. Then we are moving sync 0 to sync 1. So it is the same thing, right? But no. At the first rising edge clock, this switch input will go to the sync 0 signal. And then for the next rising edge, sync 0 will move to the sync 1. So from pressing this switch to this sync 1, you will need 2 clock cycles. So that's what it is doing. Okay. And now this switch input, which is a asynchronous signal, now this sync 1 is a synchronized signal. So this sync 1 signal, that is a synchronized version of this asynchronous input, that is switch. Okay. So whenever we are using switch, we will use instead sync 1. Okay. So that it is what it is doing. Now terminate this if condition and end process. So we have this single if condition. So we have terminated it. And this is our process section. Okay. Now we need to detect the press button when your switch is pressed, right? And for that, we will again write another process. Okay. So this is process for button triggered or button detect. Okay. Now this is process. Again, this is a registered process block. So we will use clock and reset in the sensitivity list. Then begin and end process. Now again, this is registered process block, right? So just write the basic structure of it. If reset is equals to 0, then else if rising edge of clock, then and if. Well, we have used this reset is equals to 1 by default. So we will correct it. So this is reset is equals to 0, reset is equals to 0, reset is equals to 0. Okay. So now everything is good. Now we need to create some more signals, right? So this is a delayed version of input switch, right? So we will create another signal for that. So this is signal delayed switch. Okay. And this is again std underscore logic. So when reset is equals to 0 or when reset is applied, then this delay switch, so this delay switch will get the value of 1, right? Okay. Now else if at rising edge of clock, then if sync 1 is equals to 0, means when the switch is pressed. So you can treat it just like our input switch, okay, like this one, right? But what it is doing, it is the synchronized version of your input signal. Okay, so we are using this sync 1 instead of a asynchronous input, that is switch. So this is same. Okay, just we are using the registered version, okay, or synchronized version. So sync 1 is equals to 0, and what we are needing a falling edge of our signal. Means when it was not pressed, so you will have the value of 1, and when you will press it, then your value will be 0. So you are needing a falling edge of your signal. Now if you do not do, then remember what is your clock frequency, that is 50 megahertz, and at this 50 megahertz cycle your register will shift your data. Means this is 1000, then 0100, then 0010, and that will happen at every rising edge of your clock cycle at 50 megahertz, right? And that is not our requirement, right? Because what we want, that when we press our switch, then only the shifting will be applied, and when we are not pressing our switch, then nothing will happen, right? So we are needing this condition. So sync 1 is equals to 0, and delay switch, yeah, so the spelling is correct, I'm just checking. Okay, so this delay switch is equals to 1. Then now why this one? So we are saying that our switch should be pressed, means this should be value 0, and delay switch is equals to 1. Now why delay switch is equals to 1? So we need to define it first. So let's define it. So we will define it here. So delay switch gets the value of sync 1, right? So you can say that delay switch is getting the value of sync 1, and now I am checking this sync 1 is equals to 0 and delay switch is equals to 1. That is because this sync 1 is one cycle ahead of this delay switch. Means your delay switch is one cycle backward than the sync 1. So that will detect your falling edge of your switch. Means when you press your switch, then your signal will go from 1 to 0. And that's what we are detecting, right? So this is the statement. So if sync 1 is equals to 0 and delay switch is equals to 1, then what will happen? So we have this button press signal, which is driving your shift register, right? So we need this button pressed signal to be 1. Okay, so we are using this condition, right? Button press is equals to 1, then do the shifting operation, right? So if this is happening, means when we are pressing the switch and when it is detecting it, then this button pressed will be 1. And if it is not detecting this, then what will happen? This button pressed will be 0, right? And if now it is better if you set this condition at the reset condition as well. So when reset is applied, then delay switch will be 1 and your button pressed is 0. Means that is not pressed. Okay. Now everything looks good. So this is the one if statement block, and this is the another block. Everything is closed, terminated well, and this is the process that is again terminated well. Okay, so this is our VHDL program. Okay, so everything looks good to me. Now just save this file. So save it as project01, save. Now let's compile it. Let's see if everything is good or it is having some error. So there are a lot of error, I think. Okay, so we missed to terminate well this entity. Now save Again compile. Okay, perfect. So everything is good. Okay, so everything is good and we have successfully compiled our VHDL program as well, and there is no syntax error. And logical, this is looks good. Okay, now what is the next step? The next step is pin planner. Okay, so at this step, we will define our input outputs and we will tell that these input outputs are connected to which pin of our FPGA. So this is our FPGA board. Okay, this is Cyclone 2. This device we have selected, and this has 208 number of pins. So you see these different colors. So this is A side, this is B, this is C, and this is D. Okay, so we will define our input output signals to these FPGA pins. So we have this clock signal, and in our board this is connected to pin number 23. Okay, now these are our outputs: LED1, LED2, LED3, and LED4. And now these are connected to 15 pin. Now next LED is connected to 13 pin. Next one is connected to 11th pin, and the fourth LED is connected to the pin number 8. Now reset is connected to the pin number 28, and switch is connected to the pin number 27. So I have mentioned that which signal or which input output port connected to which pin of a physical FPGA, right? Now close this window. Okay, before going further, let me tell you one important thing. Now, because what is happening, we are pressing a switch and that is being detected that when you are pressing your switch, then your signal goes from logical high to logical low, right? But a switch is a physical key, right? And that is having the mechanical system inside, okay? And that is not very smooth. So sometimes it can happen that when you press your button, then internally it will give multiple pulses, okay? That we generally called bouncing of switch. So what will happen that if you press your switch, then instead having a single pulse, it can have multiple pulses. So in that case, your shift register will shift your data multiple times. Means it is possible that at some point of time, LED 1 is glowing, and when you press a switch, then LED third is glowing. It's jump from 1 to 3. It means that it is getting two pulses in between. And that is super fast because you are working on a 50 megahertz clock frequency, right? And that is very high frequency. So bouncing is a problem in a switch. So as a solution, we need to debounce that switching. And we will do that in the next session. After understanding the concept that what are the reason for the bouncing a switch, a physical switch, and how to debounce that. Okay. So we will understand that logic first and then we will implement it. But for now, just implement this program. Okay. So what we have did, we have written our VHDL code. Then we did the pin planner, means we assigned our input output ports to a physical pin. We mapped these things. Okay. And now it's time to program our device. So we will open the programmer from here. Now select our file and we have this start option flashing here. Now just click on it and boom, your FPGA is programmed now. Okay, so now let's see that how this program is actually working on the real life hardware system or real life FPGA device. So you can see that we are pressing our switch single time, but our LEDs are shifting more than once. And that is because switch bouncing problem, which we were discussing about. And we will solve this in the next session. Okay, so that was our project. This may seem little complex at the moment, but try it with yourself and you will become comfortable by time. We have also observed bouncing problem of switch in this practical. So what was happening that we were pressing our switch at a single time, but we observed multiple shifts. Because of that shift bouncing problem. So we need to solve this problem by debouncing our switch. So we will understand the logic of debouncing in the next session, and then we will apply that in this project. In the last session, we implemented a LED pattern on a FPGA board, and we used a switch input to control that pattern. But we faced a real life problem due to nature of a push switch, that when we were pressing our switch or releasing our switch, it got few switches between active and inactive state. And because of that switch bouncing problem, our LED pattern shifted more than one time. So in this session, we are going to show you that how you can debounce your switch input. So look at this waveform first. That is coming from your push button. This is the moment when you are activating your switch. And this is the moment when you are deactivating your switch. So y-axis is our logical values, which comes out from your push button with respect to the time, which is our x-axis. So initially, we can see that our push button is in inactive state. And at this point, we have pressed our switch. So it goes to active state. But if you notice, then you will see that between this smooth active transition, we have multiple active inactive pulses. This is because of bouncing problem of a switch, and this creates problem in our design. Now, if you wonder that why we have this problem, then it is because button itself is a mechanical device. Therefore, when you activate it, it does not go from inactive state to the active state seamlessly. And it goes through the over of number of pulses because of mechanical contacts, which oscillates few of the times before its terminals are properly connected. And as a result, you get multiple pulses from switch like this. Means kind of a multiple active deactive state during one single press. But eventually it settles down to the active state in some time. And similar thing also happens when you deactivate the switch. So you get same kind of pulses instead of a clear deactivation signal. So it actually goes through a number of pulses again. And then after some time, it settles down to the inactive state. So this was the problem. And because of this problem, our shifting LED program counts each pulses as an individual input. So it was shifting the LED pattern more than once, and we observed jumps in our pattern. For example, in this waveform, when we activated our switch, it bounced the signal 3 times. Like in our last program, we were using falling edges of the signal, right? So your program will capture 3 falling edges here. So your LED pattern will shift 3 times here instead of one single shift. That same thing is happening when we are releasing the switch. So I hope you understand the problem. And now we will solve this problem by debouncing of switch. So the basic idea of debouncing a switch input is to clean these extra pulses so that we can get a clean transition of our input signal without these pulses, right? So we do this by a simple counter. So let's see how to do this. First, we will use 2 thresholds to control this counter. So the lower threshold of our counter is 0. And when it is 0, we will deactivate our debouncing signal. Means it will return value 1, just like our switch input, which was a pulled up switch. So we are following the same states as our input switch. You can change this also if you need. Like in case of inactive, you set it to 0. And in case of active, you set it to 1. But in our case, we are using same like pulled up switch input. Means inactive is 1 and active is 0. So that we do not need to change much code on our last VHDL code. So we are saying that when this counter value is 0, we are at inactive state, or our debounce signal is 1, right? So you can see it here also. We start the counter from the value 0 and our debouncing signal is inactive. Next, we have this upper threshold. Suppose this upper threshold is this green dotted line. And we will say that when our counter reaches to this point or at this threshold, then our debound signal becomes active. So it will be 0. And our counter is increasing at each and every clock cycle from this point when you press your input switch. So our counter will count each clock cycle all the way up to here. And once it reaches here, we will change our debound signal to active state or value 0. So let's see how this works. When our input switch is not pressed, then our counter remains 0. Now when you press your switch, your counter will increase at each clock cycle. Notice our debound signal, we still not activated it because we are waiting this counter to reach to this upper threshold. So our counter will take some time to count each clock cycle and reach to this upper threshold. Let's understand this with these waveforms. So we started from this starting point. Our push button is inactive and our counter is 0. Now at this point, push button is active and our counter starts counting. Now at this point, push button is bounced and it becomes inactive. So from this point, our counter starts decounting. Now we limit our counter to 0, means it will not go into the negative number. So it remains at 0 now. Now if your inactive pulse is not that long, then you may have this counter at some mid number and that is fine. But lowest floor is 0 and we will define it in our VHDL code. Now look at this second pulse when push switch gets activated again and our counter will start again. But after some time our push switch bounced again. So our counter starts decounting. And you will notice that till this point, although we have multiple pulses from our input switch, but we have not triggered our debound signal to active state because our counter is still not reached at the upper threshold, which we have set. Now suppose you are at this point of time and from now your input switch become stable. So you can see that it is pressed and active now. So our counter starts counting again and now it is not decounting. So after some time it will touch our upper threshold. Generally this upper threshold is in millisecond, like 50 milliseconds. So it is not like that you have to press your switch for a very long time. And that time period is enough to eliminate these switch bouncing problem. Okay. So at this point, our counter reaches to our upper threshold. And now we have activated our debouncing signal. Means now it has changed its state from 1 to 0. And it will remain active till the time our switch is pressed. Now there is an important thing. If you notice that our input is active, but once we reach at this upper threshold, we are not increasing our counter. Means we are not increasing counter from this upper threshold, even if your input switch is active. So it will continue at this state only. And our debound signal is also active at this point of time. Now let's say we deactivated our switch. Then what will happen? So like previously, when you release your switch, this counter will start decounting. So from this point, you can see that our counter start decounting. Now again, we have this bouncing pulse. So our counter starts counting again. Then at this point, switch is deactivated. So counter starts decounting. And that is happening few of the times until our switch is bouncing between active and inactive state. So you will notice that our debound signal is still active even after these few pulses. Why? Because our counter is still not reached at 0, which is our lower threshold. So debound signal is is still active. And after some time, our input switch will settle down to inactive state, right? And then our counter starts decounting uninterruptedly. And after some time, it will touch our lower threshold, which is 0. And at this point of time, we will deactivate our debounce signal. And now if you notice that we need to stop our counter at this lower threshold so that it won't go to a negative number. It's very important to set that upper and lower floor for this logic to work. And your counter should not go beyond that range. So you can see that at the input switch, it bounced couple of times when you press the switch or releasing the switch. And once we treated this with our debouncing logic, we get a clean and reliable debounce signal as a result. And now we will use this debounce signal to shift our LED pattern from the last session. And that we will do in the next session. In this session, we will fix the bouncing problem of a physical switch in a FPGA board. So if you remember from our previous session, we designed our LED pattern system. It was shifting the LED when you press your button on the FPGA board. But we faced some problem that when we single press our switch, it was shifting more than one LED, right? But we were expecting that when we press the switch, then our LED should shift to the right by one precision. But unfortunately, it was shifting by more than one precision when we were pressing our switch, right? And we found that it was happening due to the bouncing problem of a physical switch. Then in the last session, we explained that what is that bouncing problem in a physical switch, why it happens, and how we can solve this problem. So a quick brief that in bouncing problem, you press your switch once, but it gets captured as a multiple activation. So your LEDs were shifting multiple times. So in the last session, we discussed that. And we discussed the strategy to solve this bouncing problem with the help of VHDL code and logic, right? So if you are still not clear about the bouncing problem of a switch, and if you do not know the logic that how we are going to solve this problem, then please watch my last video to understand the logic which we are going to implement in this session. Okay, so enough introduction. Now let's move to the Quartus Prime software and implement that debouncing logic into our LED pattern project. Okay, so now it's the time to design the same system like LED shift registers with debouncing feature of that switch. Okay, so we have explained this problem, right? That what will happen if your switch bounce, because that is a mechanical system or that is a physical hardware, right? So you might try to press it once, but that is having the mechanical in nature. It can give multiple pulses. And because of that, your shift registers jumping to the multiple LEDs means instead jumping of one flip-flop, it jumps multiple flip-flops. Okay, so that was the problem. Now we will solve that problem with the debouncing of switch. Okay, so this is the same code from our last session, and we are just updating that. Okay, so a quick brief. This is our library declaration. This is our entity section. So we have this project 01. We have clock as an input, reset as an input signal, and switch as an input signal. We have one single output, but that is having the 4 elements. So we have 4 LEDs as an output. Now this is the architecture section. So we have defined few signals. We explained what are these signals and what they do in this program. So I'm not repeating that again. But we have this shift process. This is doing the shifting operation. So when reset is asserted, we have this shift register as a default value 1000. We explained why it is having this value. And if button is pressed, then your shifting operation will be taken only at the rising edge of clock, because this is a registered process block. Okay, so this is sorted. So this is doing the shift operation when this button pressed is equals to 1. Okay, now we have defined this process sync. So what it is doing, we are having this switch that is asynchronous in nature. So we have synchronized this input. Okay, so for that we have this sync process. Okay, and in the last we have this switch detection process. Okay, so it is detecting that if button is pressed or not. Okay, so if this condition is met, means when your signal is going from logical high to logical low, then we are saying that button is pressed, and when it is not happening, then we are saying button pressed is 0. And we have reset condition as well. So we are saying delay switch is 1 and button pressed is 0, means it is not pressed. Okay, now what we need to do, that we need to improve our synchronized version of our switch. Okay, so we are not touching this switch input because that is asynchronous in nature, and we have already synchronized it with sync 1, right? And we are using this here, right? So as I explained in my last session, we are needing few additional signals for that, and these are one for the counter. So define that signal, give some name. So suppose this is counter and this is integer, and give some range. So I'm giving range 0 to. Now we are needing one threshold as well, right? So define a constant, and that is our debounce period, suppose, and that is integer type, and it is having the value of say 25 million. Okay, so we have defined this, and now we are needing one additional signal. Okay, because till now we are using that sync 1 as in switch detection, right? So we are needing one additional input. So we are saying that is signal, give some name. Suppose this is debounce switch, because we have down debounced. You can give any name, right? So this is again std underscore logic type. Okay, now we need to write an additional process to debounce that input switch. Okay, so give it some name. So I'm giving process for debounce. This is again a registered process block. So reset clock is in the sensitivity list. Now begin. So create the structure first. If reset is equals to 0, then do something. Else if at rising edge of clock, then do something, and in the last and if, right? So first write the reset condition first. So what will happen at reset, when reset is applied, so our counter should be 0. So that is the first thing that we need to do. And what else? We will debounce our switch as well, right? So we will reset it to some value. So give it debounce switch, that's a value of 1. So what this means? That means the switch is not pressed. Okay, because when you press it, it will go to the 0 logic, right? So that's is the reset condition. Now what we want? Now we want that when the switch is pressed, then we will increase our counter, right? So write that condition. If sync one signal is 0, means when it is pressed, then increase the counter. So counter is counter plus 1. Okay, so this is happening when switch is pressed. Okay, else now we have one more problem. Like if we leave this statement as it is, then it will start counting and counting and counting and counting again and again at each and every rising edge of clock. But we need to trim our counter to stop counting at some specific threshold. And what is that threshold? We have defined this as a constant. So this is constant debounce period, right? So let's copy it. So we are needing additional condition. What? That only count this or only increase the counter when this condition is met. When your counter is having the less value than your threshold, and your threshold is debounce period. Okay, and then this condition will be met, then we will increase our counter, and if Now what it is doing, that it will only count at the rising edge when the button is pressed, switch is pressed, and when counter is less than our threshold value, right? Now we have the second stage of this, that when you release the switch, then your counter start decounting, right? So we will use the same condition. If counter is greater than 0, then counter is counter minus 1, and if. Okay, so what it is doing now, suppose if we don't use this condition, then what will happen? We have this counter value at some specific range, like the maximum range is 2.5 million, right? So when it is at this point, then and when you release the switch, then at every rising edge, your counter start decounting, and there will be state when it will become 0. And if you don't limit this condition, then it will go in the minus values, negative values, right? And we don't want this. So we have stopped it when counter is 0. Okay, so when counter is greater than 0, then reduce the number, and when it is reached to 0, then stop the counter. Okay, and this logic is having one advantage as well. Now we have defined the counter and everything is well till the time. But till now we have not specified this debounce switch. We have just give the reset condition for this one, right? So we need to specify this debounce switch. Okay, so what it is very simple. So from the last session, when we explained the concept of debouncing, we explained that our debounce switch is treated as a pressed when our counter is reached to the threshold level, right? And what is the threshold level? So let's write the condition first. If our counter reaches to the threshold period, so our threshold is debounce period. So we have defined this constant, remember? Then when it is happened, then that means the switch is pressed. Means our debounce switch signal is pressed, means 0. Else, if counter is equals to 0, then we will say that our debounce signal is not pressed, or 1. And just terminate this condition, and if, and everything is good. Now there is one more step, that we have specified this debounce period switch, but we have not used this for button detection, right? So we need to use this instead of sync 1 signal, right? So what I remember, that we have used this sync 1 signal at this place only. Okay, so instead this sync 1, we will use this debounce signal now. Sorry, it's not debounce period, it's debounce switch. So let's copy it here, let's copy it here, debounce switch, everything is good. Okay, so let's do that and just replace it as well. Now we have replaced our sync 1 switch with the debounce switch. Now everything is good. Okay, now let's save it. So I have saved this one, Control S, and now compile our design. So let's compile. Okay, something is not good. Okay, so we have not terminated the process block. Now it is good. Okay, now again. Okay, so this time everything is good. Our design is compiled successfully. Now it's time to program this updated VHDL code with the debouncing system into the FPGA board. Okay, so let's open the programmer once again. Select the hardware. Now select the project and click on Start button. And it's done. Okay, so now let's move to the FPGA board and see if that bouncing problem is solved or not. Okay, so we have gone through the demo and we have pressed the switch few of the times after making the changes, and it looks much better now. Means the logic we have written to solve the bouncing problem of a switch was working well. And I am pretty satisfied with the results now because our LED pattern is now shifting by one precision when I press my switch on the FPGA board. So that's what we are expecting from our project, right? In the future sessions, we will be doing more projects and we will be solving many such problems. In this session, I will show you how to generate a PWM waveform in VHDL. And in the next session, we will implement it on FPGA board. So we will generate a PWM signal of 1 Hz with 50% duty cycle. And we will see the results on the real LED. I will tell you that how you can adjust your duty cycle of your PWM signal and of course frequency as well. I will show you that what are the important parameters that you need to consider for getting a very specific PWM signal. Means very specific duty cycle and frequency of your PWM signal. So let's start. So question is that how do we generate a PWM signal in an FPGA? And the easiest way to generate a PWM signal is using a counter. So it's kind of a register which is increasing its value at every clock cycle. And once it reaches to a certain value which we will define, then it is set to 0 and then keeps incrementing once again at each clock cycle. So look at this graph here. Here x-axis is your counter value with respect to time, which is your y-axis. And you can see that your counter value keeps increasing with time until it reaches to this maximum value. And then at this maximum point, it comes back to 0. And on the very next cycle, it starts increasing again. And this is happening continuously. Now, question is that what will be this maximum value for your counter? So this is basically a deciding factor of your PWM signal. And it will decide your PWM period or frequency you can say, or PWM cycle you can say. So this is one parameter to decide your PWM period, and it is very important. There are more parameters also to decide this periodicity. For example, your input clock frequency or your FPGA board frequency. Like in our FPGA board, we have a 50 megahertz clock, which we will use. So for this 50 megahertz clock, we will have a 20 nanosecond of clock period. Means one cycle will complete in 20 nanosecond. It is just a simple math. You divide 1 second over 50 megahertz and you will get a 20 nanosecond. This means that our counter will increase by 1 at every 20 nanoseconds because we are increasing our counter at each clock cycle. And for 50 megahertz clock, each cycle takes 20 nanoseconds. Now, if we want a 1 second period for our PWM signal, which we are generating, then the question is that how many counts we need if we are increasing our counter at every 20 nanosecond. So it is simple math again. We calculate 20 nanosecond for one clock cycle of 50 megahertz and we want 1 second PWM signal. So divide 1 second by 20 nanosecond. So your answer will be 50 million times. Means our counter need 50 million increments to get exact 1 second. Note that our clock frequency is 50 megahertz and we are calculating it for this clock signal only. If your clock frequency is different, then this number will be different too. Just use a simple formula to get the total number of increments, right? So for this 50 million increments, we start our counter from 0 and we will count it up to 49, 999, and this will be our 1 second. And once we reach at this number, that is 49, 999, then our counter will reset to 0 again for calculating next 1 second. So it is in the loop. This odd number is because we are starting counting from 0, not 1. And this number is actually 1 less from 50 million. Okay, so don't get confused. Now look at this waveform again. So we start our counter from 0, then we are increasing it continuously at each clock cycle, and we reach to this maximum number, that is 49,999,999, and it is our exact 1 second time. Now we reset our counter to 0. So you see that after 49,999,999, our counter starts counting again from 0 to get another 1 second. And at this point, it will again complete counting of 49,999,999, means we get another 1 second. So this counter runs continuously in this cycle, like from 0 to 49,999,999. So each time it completes counting from 0 to 49,999,999, we get exact 1 second. And because this process is repeating over and over again, so we have this periodic waveform. So you see, we marked each second on the time domain here. So this was cycle duration, means we get 1 second repetitive cycle. And PWM pulse will have rising edge and falling edge between this 1 second cycle. So the question is that how we can set the duty cycle of our PWM signal. If you do not know that what is PWM duty cycle, then in simple word, it is the ratio between how long your signal remains at logic 1 and how long your signal remains at logic 0 state on one single cycle. So how we will achieve this? Simply, we need to pick a value from this counter range, that is from 0 to 49,999,999 in our example, and that will decide your duty cycle. For example, suppose we want to generate a PWM signal with 50% duty cycle. This means that for 50% of the time, our signal will be at high state, and for rest 50% of the time, it will be at low state. So let's say we picked this point, marked with this blue line, and it is halfway between 0 and 50 million, means 25 millions around. So this value will be used to set PWM duty cycle. So let's see how it works. We will monitor our counter value and we will compare it with this blue line point or this intersection point value. And if our counter, which is red color inclined line, because our counter is increasing at every clock cycle, reaches to this point and intersect with this blue point, we will change our output. For example, if the value of our counter is below this line, then we will set our PWM output to 0. And when our counter is above this line, then our PWM output will set to 1. So let's see this in the graph. So look at this region first. Our counter starts from 0 and it reaches up to this blue line, which is 25 million. So up to this point, our PWM output is 0. Now for this reason, when our counter, this red inclined line, counts from 25 million to this upper threshold, which is 50 million, then our PWM output is 1. Now once we reach at this upper threshold, which is 50 million here, we has interesting thing. So you can see that at this point, our red line come back to 0. Because at this maximum point, we reset our counter to 0, right? So at this point, our counter value is below this blue line. So our PWM output goes 0. Now the counter starts counting and slowly it will reach to this blue point. So till this point, our PWM output remains 0. And once we reach at this blue point, our PWM output will be 1. Again, it reaches to this maximum point. And until then, our PWM output is 1. And at this point, our counter reset to 0 again. So our PWM output become 0. And you can see that this is happening again and again. So we will get this continuous PWM output. So the question is that how it will control your PWM duty cycle. So let me tell you that this PWM output actually has 50% duty cycle. Why? Because it is low for 50% of the time and it is high for rest 50% of the time during one cycle. Like you see 0, 1, 0, 1, 0, 1. Now to change the duty cycle, what you need to do? You just need to pick another point for this blue line. For example, if you increase this blue line pointer to some higher value, then you will see the reduced duty cycle. Because till this blue point, your PWM output is low. And above this blue point, your PWM output is high. And you see now our output signal is at 0 for longer duration. And it is at 1 for shorter duration. For example, here we have reached this intersection point. So now our counter will take longer time to reach to this point. And for that period, our output is 0. And above this point, the output is 1. So you can see that our output is 1 for shorter time compared to the logic 0. So we get reduced duty cycle, something like 20% in this case. So if you want exact 20% duty cycle, then get 80% of 50 million. And that will be your intersection point. Simple. Now, on the other hand, if you lower down this blue line pointer, for example, something like here, so you may guess that our counter will be below this line for shorter duration and above this line for longer duration. So our PWM output will be high for longer duration and at 0 for shorter duration. Means you will get higher duty cycle of your PWM signal. So this is the hardware block representation of our design, or you can say flow chart as well. So we are needing this counter, and in our case, it is driven by 50 megahertz clock cycle. And this is our blue line intersection point, or you can say duty value. And we will compare this value with our counter value. So in our project, we are developing 50% duty cycle signal. So this value will be 25 million in our case, because our counter is counting from 0 to 50 million roughly. So 50% is our midway, that is 25 million. Don't worry, because we will be developing this system in the real FPGA in the next session. So we will compare this counter value with this duty value, which is 25 million. And if the counter value is less than this duty value, then our PWM output will be 0. And if the counter value is greater than this duty value, then our PWM output will be 1. So that's how we can control the PWM cycle and PWM duty cycle. Means if you need higher duty cycle, reduce your duty value. And if you need shorter duty cycle, then increase this duty value. And if you want to change your PWM cycle, then you can control it by changing your maximum counter threshold based on your clock frequency. So that's whole story short. I hope this is clear to you, because in the next session, we are developing it into VHDL, and then we will implement it on FPGA board as well. In the last session, we learned how to design a PWM signal and how to control its PWM duty cycle and how to control its PWM cycle. And now in this session, we will design it in VHDL, and then we will implement it on real FPGA board. So quick brief that what we are using and what we are designing. We will use our own board 50 megahertz clock frequency for our counter. We will design a PWM signal with 1 hertz cycle and with 50% duty cycle. So what we need for that? We need a counter which will count 50 million times. Means from 0 to 49, 999, 999, right? And then we will need duty value. So for 50% duty cycle, we will have this value like 25 million. So we already explained this in our last session that from where these numbers are coming. So if you are not clear about these numbers, then please watch my last session first. That is really important. So now we will move to our Quartus software and let's design this in VHDL. Okay, so let's open Quartus Prime software. So click on Start button, write Quartus. We will open this Quartus 2 10.1 web edition because we are working on the Cyclone 2 device and the recent Quartus release is not supported that old FPGA. So we are having this old version and this supports Cyclone 2 device. So this is the startup window. Now we are creating a new project. So we have this button here for creating a new project. So we will click on it. Okay. Now this is the new project wizard. So click on next. Now here I will give my project directory and my project name. So first I will select the directory. So I am making a new folder here for this new project and give it some name. Suppose my project name is PWM underscore LED. Okay. Now select it. I will copy this. Now select it and okay. Now give the project name. So I will copy the same name PWM underscore LED here and then I will click on next. Now this is the add files page. So if you are working on some big project and if you are going to use any existing VHDL file, so you can add your files here. You just need to click on these three dots and then you can add your files in this project. Okay. But we are working on a fresh new project. So we don't have any file to add at this moment. So I will just leave it blank and click on next. Now this is an important step because we are working on the FPGA device. So we need to select our device in this page. So like I said, I am working on Cyclone 2 device. So I will select it from here. So Cyclone 2. Now you can see there are many devices here, right? And we have few filters here that we can use to shorten this list. Like we can select package from here. So my package is FQFP. Then there is a pin count. So I can select my device based on my pin count. So my device has 208 number of pins. So I will select it. And then speed grade. So I know that my device has 8 speed grade. So you can see this has filtered out only 4 devices. So I can choose my device from this list now. So I have this FPGA device EP2C5Q208C8. So this means that we have PQFP package, 208 number of pins and 8 is the speed grade, right? 2C is Cyclone 2. Now once you select your device, then click on next. You can select your tools here. For example, if you're doing the simulation, then you can select it from here. For example, quiz test simulator you wanted to use, right? And then select the format. So you are working on VHDL, so select VHDL if you are doing the simulation. But we are not doing the simulation, so it doesn't matter. Now click on next. So this is the summary page. So this is showing that what we have selected in the previous steps, right? For example, we have Cyclone 2 device. This is device name. Project name is this. This is the location where my project is saved. Quiz test simulator we have selected. So these have some summary information. Now just review it and click on finish. Now Quartus have created a project for you. So you can see this PWM LED is here. So Quartus has created this project for you. This is our project navigator window. And this is the hierarchy view. We have more views like files view. Now, because we are working on the fresh project, so that is why there is no file here because we have not created it yet. And even we have not added any files during the initial steps, right? So this is file section. Every file will be displayed here once it is created or imported. And this is hierarchy view. So this view is important when you're working on some big project, which is having many number of modules and components in a bigger system. So everything will be displayed here in a hierarchy view. So this view is very important. Next, this is the task section. So you are having many of things here. For example, this compile design. Here everything is grouped together based on their jobs or functions. For example, this analysis and synthesis. So this is the first step after you write your code. because this will compile your program and will check for the any syntax error if it is having, and it will tell you that where it is syntax is happening. Next, we have this place and route option. Now, before this, if you expand this analysis and synthesis port, then you will see many tools inside it. For example, this RTL viewer. You can use this to view the RTL schematic of your VHDL design. Next thing which we will use, that is pin planner. And what it will do, that you will define your input output ports in your VHDL module, and your FPGA will have many number of input output pins. So using this pin planner, you will tell to this Quartus software that this pin or this port is connected to this FPGA pin. So this is very important when you are working on the FPGA devices. Now collapse this analysis and synthesis, and next we have this assembler. So once you compiled your design and if you see everything is good, you gave the pin planner and everything is okay, then you need to generate programming file, that is binary file, and that will be generated using this tool, assembler generate programming files. Now let's go down. Then you will see this program device or open programmer, and we will be using this tool to program our design into the FPGA. So these are a couple of tools which we will be using in this session. Although these options also available at this top section. So you can directly use these buttons for these operations. For example, this is our programmer button. So you can just click it and open the programmer. You can also open from here and you can also open from here. Now this play button is actually your compile design. So start compilation. So you can use this button to start compilation of your VHDL design. You can also do this from here and you can also do this from here, right? Now let's create a new project. So here is a button that is for new file. Okay. You can also open by going to file menu and click on new. You can also press Ctrl N from the keyboard. So everything will open the same thing. So I will click on this new button. Then this window will open, that is having lot of things, but we are working on the VHDL programming language, right? So we will select this VHDL file and then click on OK. Now this is our editor where we will write our VHDL program. Okay. But before this, if you notice, this file name is vhdl1.vsd. So Quartus automatically gives this kind of name like vhdl1.vsd, vhdl2.vsd. And I personally do not like this. So before writing the VHDL code, we will save this as per the relevant name, right? So first I will save this file. So I will click on File and click on Save As. So I will save it. Now I will select my project. So my project name is PWM LED, right? So I will select it. So this is the default directory of your project and you can save your file here itself. But personally, I do not like it. So what I want to save my VHDL file in the separate folder. So I will click on this, click on new folder, and I will give it some name like SRC. That is acronym of source. So I know that all of my VHDL file or source file are present in this folder. Okay. So my project name is PWM_LED. This is .vsd file and then everything is good. Click on save. So you can see that this name is source_PWM_LED.vsd. And this is much better, right? So now it's time to write our code. So start our code. First, we will give the library and package declaration. So give it library IEEE use IEEE.std_logic_164.all. Now we will give the entity declaration, right? So write the entity, then entity PWM_LED1 is port, bracket start, and bracket close, semicolon, and entity. So this is our entity structure. Now give the input output ports. So what I have clock as an input. So give it std_logic, and we are having one LED output. So write it, that is LED, and this is output type, then std underscore logic, right? So everything is good. This is our entity declaration. Now it's time for architecture declaration. So start it. So architecture behave of PWM underscore LED1 is now begin in the last and architecture or and behave, right? So this is our structure of architecture. Okay, so remember from the last session that what we are needing for this PWM signal, we are needing a counter that will count from 0 to 50 million because we are working on the 50 megahertz clock frequency. So for getting the 1 hertz cycle, we need a counter from 0 to 50 million, right? So write the code for a simple counter. So we will do it in the register process block. So I will start counting process. Then this is a process. Now this is a register process. So clock is in the sensitivity list. Now because I just wanted to make it simple, so I am not giving any reset signal here. But if you want, you can add reset signal as well. So you will add this reset signal as the entity section as well, and here in the sensitivity list. Okay, so let's start this. So we will start it from begin and then in the last and process, right? So this is the minimal structure for this process. Now simply write our basic structure for a registered process block. So this is if rising edge of clock, then and if, right? So what we are doing that we are counting our counter at each rising edge of clock. So we will write this statement that our counter is counter plus 1. Okay, so this will count at every rising edge. But we are needing few more conditions to count it, right? For example, we want this counter to count 50 million cycles, right? So from 0 to 49,999,999, right? So give that condition that if counter is less than 50 million, so 50, 1, 2, 3, 4, 5, 6, 50 million, then our counter should be 0. Else, so what is happening that when the counter is less than this 50 million value, then so it should be greater than 50 million, right? So what is happening then till the time this counter reaches to 50 million, it will count 1 on each rising edge of clock, right? So that is what it is doing. Now terminate this if condition. So and if. Now let's properly format it correctly. It's looking so messy. So if rising edge of clock, then okay, now else. So this will happen and this is and if. Okay, so this looks better. Now because we are using counter here, but we have not defined it. So quickly define it first. So this is a signal, name is counter. This is integer type and it is having the range of 0 to 50 million. So 50, 1, 2, 3, 4, 5, 6, right? So till now what we have did, we have created this process block, and in this process block we have this rising edge condition. So it is checking rising edge of clock. Now we are saying that when counter reaches this 50 million value, then it will reset to value 0. Okay, so this is our first condition. And if it is less than 50 million value, then it will count at each rising edge of clock. So that's what we are doing. Now suppose we are making this project for a 50% duty cycle for a PWM signal. So for that, we will use this counter to select the duty cycle of our PWM signal. So what I am doing that I am writing another if condition, and I am giving the condition that if counter is greater than 25 million, so 25,000,000, then what will happen? This LED output will get 1, logical 1 as an output. else when counter is less than 25 million, then what will happen? This LED will get logical 0 value. Okay. Now terminate this if condition. So and if. So we have defined our LED output and we have defined our counter as well. So here is a quick correction that we have used this 50 million, right? And we are starting our counter from 0. So we are having one extra cycle here. So if we want exact 1 second cycle, we will reduce it by 1. So it will be 49,999,999, right? So this is just one less from 50 million value. Okay. So because we are starting our counter from 0 and we are needing exact 50 million cycles. And we have explained that in the last session, remember? So if you didn't watch that video and if you are not aware that how to calculate the duty cycle of your PWM signal or how to tune the duty cycle of your PWM signal, then please watch my last video because I have explained everything there, that why we are using this 50 million counter, why this value is 25 million, right? Because we are working on a 50 megahertz clock frequency and we are converting this 50 megahertz clock frequency into the 1 hertz frequency at 50% duty cycle of PWM signal. Okay. So this is our VHDL code for our entity and for our design. So it's time to compile it. Okay. So we can compile it from here, from this button, or you can just double click on this here. So simply click on this compile button. So it is saying to save your file. So I will say yes, save it. Okay. So it is giving some error, right? And we know that what is this error, because we have intentionally did this to show you that what is this problem, because many of you will face this. So let me tell you that what is this error. So for that, we will go to our source file, means this pwm.led. Now, if you notice that we have the project pwm_led. So Quartus is actually looking for this module, which is named by this name, this pwm_led. And it is actually not finding any file with this module name, because this module which we have designed, that is having the name pwm_led1. So one way is to just change its name like pwm_led so that it can match with your project name, this, okay, pwm_led and pwm_led. So that is one thing which you can do. But another option is you can change this project name itself, right? So right click on it and click on setting. Now, because we have only one single module in this project, so this is our top level entity. So top level entity is the entity which is your final project. So if you click on these 3 dots, you will see all of your designs here. Now, because this is a simple project and it is only having one single file, so that is listed here. But if you are working on some complex project that is having lot of modules and lot of components in your project, then that all of these modules and components will be listed here. And then you need to select your top level module from this list. But for this project, I have this pwm_led1 that we have written in our VHDL program, right? So I will select it and I will click on OK. Now, once you select it, now you need to apply it and click on OK. So you will see that your project name is now changed to pwm_led1. And now it is matching with your entity name as well. So I hope this is clear to you. That means you must have at least one VHDL code matching with your project name. Okay. So that's very important when you're working on Quartus software. So I have changed this. So we will just click on start compilation button. Okay. So it will start compilation. So you can see a lot of bars here. These are in progress. So it is saying that my compilation is completed. And this is the compilation report. So switch back to our VHDL project. So what we have did, we have written our VHDL code and we have compiled it successfully without any syntax error. And we have these two ports in our project. So one is the clock frequency that is input to our module, and we have this LED as an output. So we told our Quartus software that we have these two ports, but what we didn't tell that at what FPGA pin these input output ports are connected. So we can do this with the help of pin planner. Okay, so I gave you a brief about this pin planner, right? So it is an analysis and synthesis tool, and you will see pin planner here. Okay, that you will also see at the top here. So this is our pin planner. Sorry, this is our pin planner. So I will open it. Now this is our FPGA device. Okay, so this is Cyclone 2 and EP2C5Q208C8 is our device name. And we have selected this device in the starting, remember? That is why it is very important to select right device based on your FPGA board. Now this FPGA device having many number of pins. You can see this is side A, this is side B, this is side C, and this is side D. And each side having lot of input output pins or general pins. So if we zoom it little and take the pan tool here and let's drag it little. So this is our starting point. And this is our first pin of our FPGA. So if you go down, then 51, 52. So this is side A, and that is having total 52 pins here. And then this is side B, starting from 53 pin to 104 pin. Next, this is side 3, starting from 105 pin up to 156 pin. And finally, this is going up to 208 pin. So remember, we have selected our device that is having 208 number of pins. So you can see that. Now zoom out this. So what we are doing here in this pin planner, that we are telling that our module inputs and output ports are connected to which pin of this FPGA, right? So you can see these input output ports are listed here, right? So we have this clock as an input and we have this LED as an output. So this is mentioned here, clock input, LED is output. And we have few blank areas as well, which we are going to fill. So location is our pin number of FPGA, like 27, 28, 30, 31, 32, like that, right? So coming here to the location. Now, if you are working on some specific FPGA board, then look at the board specification, that at which pin your clock is connected for your FPGA board, because you must need to tell that where this clock input is connected in your FPGA device, right? So for my device or for my FPGA board, this clock input is connected to pin number 23. So I will type pin underscore 23. So this is the way of giving the location, right? Pin underscore and then give the pin number. Okay. So pin 23. Now our LED output is going to pin number 15. Enter. So remember, you need to mention these input output pins based on your FPGA board, right? So next thing is input output bank. Now this is because our FPGA devices has many number of banks, and each bank has its own individual power source. And these banks can be isolated by each other and can serve by different voltage levels. And that will be specified by your FPGA board manufacturer. That will tell which bank has what power supply. So you can see that these both pins are belongs to this IO bank number 1. Now this is input output standard. Now for this device, this is fixed. You cannot change it, but recent devices are flexible enough where you can set these voltage levels as well. So in our case, this is very strict. Now, one important thing, when you click on this, after giving the location, that will be mentioned in the FPGA device here as well. So you can see that we have connected this clock signal here. So it has marked with a different color. You can see this blue boundary here. So this is selected. Now, if you click on this LED switch, so this will move to here. we have connected this LED output to this pin. So you can easily see that which input is connected to which pin right from here. Now if you notice, then there is no save button here. And that is because this pin planner automatically save data when you change it. For example, if you change this, then it will save automatically. So there is no save button. So once you change everything based on your board specification, then you can leave it here and just close this window. And now it is saved for this project. And now we have changed this pin planner. So we need to recompile this program, right? So we will click on this start compilation button once again. So click on it and you can see the bars are started and the processing is happening. And the full compilation is completed. Okay, so click on OK. Okay, so this is the compilation report and this is our VHDL code. So now it's time to program this code into the FPGA device. Okay, so for this, we will open this programmer. You will open it from here. Like you have this option, program device, open programmer, and you can open it from here as well. So we will open it. Okay. Now I will expand this little so that you can see everything here, what is available. So this is our file name, that is pwm_led. And this is our device name, that is EP2C5Q208. So note that if you didn't select the right device during the startup steps, then your FPGA will not be programmed properly. Okay, so make sure that you select your FPGA device correctly. Now we have this checksum. This is just for the file validation. Then we have user code. This is FF, means none. Now make sure that this program or configure button is ticked. That is very important. Now we will leave everything blank here and we will check our hardware setup. So we will click on it. Now you must see your USB blaster here in this list. If it is not available here, that means your USB blaster is not connected with the PC, or it can be driver problem. So install the driver, reconnect your USB device, and then check if your device is visible here or not. And once you see your device here, then just select it and close it. And you will see it from here. USB blaster, USB 0 something, okay? And we have this progress bar here. So you can see it is progressing during the programming time, okay? So we will select this PWM file. Now remember about this .sof file. So this file is volatile in nature. Means if you power off your FPGA board, then all the configuration will be wiped out from your device. Means you need to reprogram your FPGA device every time it is powered up. Okay, so click on this device and you will see this start button flashing here. So just click on it and you will see the progress bar. So it is quick, 100% successful. Now we will move to the FPGA board to see if that is working correctly or not. What we are expecting that our LED should glow at a cycle of 1 Hz. Means for half of the second it should be on and for half of the second it should be off. And it should be happen in the repetitive manner. Okay, so half second off, half second on, then half second off, then half second on, like that. Okay, so let's move to the FPGA board and see if it is working fine or not. So you can see that this is our FPGA board and we have connected this LED to the output port, which we have specified for our FPGA device. And now you can see that it is turning on for half a second and then it will go off for half a second. Then switch on for half a second and then switch off half a second. So it's on, off, 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 on. Okay, so this was our 1 second PWM signal with 50% of duty cycle. And that is working perfectly fine for this project. So that was our project. We have created a PWM signal of 1 Hz cycle and with 50% duty cycle. And we have used 50 MHz clock frequency to drive this PWM signal. And at the output, our LED was blinking at 1 second cycle with 50% duty cycle. Means for half a second it was turning on and for another half second it was turning off. So that's how it works. In the future sessions, we will be designing more systems in VHDL and FPGA. In this session, we will be talking about 7-segment displays. And in the next session, we will use this 7-segment display into our project. So this is pretty basics, that what is 7-segment displays, how they work, and how to drive them in VHDL, etc. So this is a very simple package of 7-segment display. This is well-defined package of LEDs, and they are placed in such a way that they can show numbers or some characters. And if you count these LEDs, they are 8 in total. Out of this, 7 LEDs are used for displaying numbers or digits, and 1 is reserved for DP or decimal point. Now each LED here is derived by a separate pin. So you can see 8 pins here. So they are labeled as pin A, pin B, pin C, pin D, pin E, pin F, pin G, and pin DP. These are your 7-segment display pins. You will also have one extra pin in your display, and that is common pin, and it is connected to the second terminal of all the LEDs. So this can be either common anode of all the LEDs or common cathode of all the LEDs. And that's define your type of 7-segment display. Means if it is common anode display, then this common pin will be anode of all the LEDs. And if this common pin is cathode of all the LEDs, then it will be common cathode type of display. Now you can see in this 7-segment display package that each LED label is placed here with their name. So this is LED A, this is LED B, this is LED C, this is LED D, this is LED E, this is LED F, and this is LED G. And last, this is decimal LED. So these are total 8 LEDs including decimal point. And you can control each LED individually by using your 7-segment pins. And all the LEDs having one common terminal. This can be either anode terminal if you have common anode type 7-segment display, or it can be common cathode terminal if you have common cathode type 7-segment display. So suppose you have common anode type of display, which is generally used. So we will design our 7-segment decoder for this common anode type of display. Although the concept is same for common cathode type of display as well. The only difference is that the pins are just inverted. So you can simply use a NOT gate to invert your decoder output, so that you can switch between common anode or common cathode type of display. Now by default our all the LEDs should off because we are not displaying anything. So in this case you will apply logical 1 to all the pins of your 7-segment display. Why? Because you are using common anode type display and its common pin is already connected to this plus VCC. And if you apply the same voltage to the another terminal, means these 7-segment pins, then current will not flow through these LEDs. So they are off, right? So when they will glow? They will glow when you will apply logical 0 to 7-segment pins. So these second terminal will 0 or grounded, and then current will flow through these LEDs and your LED will turn on, right? For example, consider this first LED or segment A. So when you apply logical 0 to this terminal, then the current will flow through this LED and it will glow, right? So this is basic concept. Now by using this concept, if we wanted to see number 3 on this 7-segment display, then we need to make sure that these specific LEDs should on and rest LEDs should off. So you can see that each segment is marked with their name here. So for number 3, we should turn on these LEDs like LED A, LED B, LED C, LED D, and LED G. and LED E and F are turned off at this time. So you can see on the left side that corresponding segments are logical 0 so that they can glow, and segment E and F are logical 1. Okay, so this is basic concept, how 7 segment display works and how we decide which LED should on and which LED should off to display any specific number. Now we will create this table for each digit, and this will tell that which segment should glow and which segment should not glow to display any specific number. So let's create this table, and this is very important because we will be using this table to design our 7 segment decoder in VHDL. So we will start from number 0. So for 0, all the LEDs are on except this segment G. Means for common anode type display, we will set logical 0 to all the segments of this package except segment G, right? So our output will be 0, 0, 0, 0, 0, 0, 1, 1. Last LED is our decimal point. Okay, so don't get confused. So let me brief this. We have this LED as an output port, and this is STD logic vector signal, and this will have 8 elements inside it. So it has the range from 7 down to 0. So segment A is our LED 7, segment B is our LED 6, segment C is our LED 5, segment D is our LED 4, segment E is our LED 3, segment F is our LED 2, segment G is our LED 1, and segment DP is our LED 0. So that's how we will design this. Now for number 1, segment B and segment C are on and rest all the segments are off. So our output will be 1, 0, 0, 1, 1, 1, 1, 1. Next for number 2, segment C and segment F are off and rest of the LEDs are on. So our output will be 0, 0, 1, 0, 0, 1, 0, 1. Next for number 3, segment E and segment F are off and rest of the LEDs are on. So our output will be 0, 0, 0, 0, 1, 1, 0, 1. Next for number 4, our output will be 1, 0, 0, 1, 1, 0, 0, 1. So I hope you understand this and you can complete it for rest of the numbers. So I am not repeating it again for all the numbers. So quickly see for this number 8. For this, all the segments are turned on. So our output will be 0, 0, 0, 0, 0, 0, 0, 1. And for number 9, only segment E is off. Rest all the LEDs are on. So our output will be 0, 0, 0, 0, 1, 0, 0, 1. Now remember that this is the table for common anode type of 7 segment display, which glows the LED when you set logical 0 at the output, right? If you are using common cathode type display, so you need to give logical 1 to glow the specific LED. Means that will be invert of this table. Means replace logical 0 with logical 1 and replace logical 1 with logical 0, or simply use NOT gate for this inversion. We will be using common cathode type of 7 segment display in our next project. So I will show you that table as well. Okay, so that was a brief about 7 segment display. And now we know that what are these 7 segment displays. We learned common anode type of 7 segment display and common cathode type of display. We learned how they works, and we created a matrix table for 7 segment decoder output for common anode type of display. So in the next session, we will be using this 7 segment decoder knowledge to design a project, and we will implement it on a FPGA board as well. We will also discuss 7 segment multiplexing technique, which is very important when you are working with more than one display. In the last session, we talked about 7-segment displays and we learned how they work and how to code them in VHDL. Now in this session, we will do a practical on 7-segment display and clock signal. So what we will do that we will develop a simple counter using 7-segment displays, and this will count from 0 to 9. We will write VHDL code for this and then we will implement it on FPGA as well. So let's see how we will do. First, we will write a process block for generating a 1-second signal. Basically, we are converting 50 MHz clock signal into 1-second signal. And then we will count it from 0 to 9 for each second. And when this signal reaches to greater than 9, then we will reset the signal to 0. And this cycle will run in an infinite loop. So our counter will start from 0 and it will count up to 9 for each second and then back to 0 again. And finally, we created a 7-segment decoder for common cathode type display so that we can see our counter on 7-segment display output. So this is the plan for this project. So let's jump to the Quartus software and start developing it on FPGA board. Okay, so we will start Quartus Prime software. So go to Start and write Quartus. So we will open this Quartus 2 10.1 web edition. We are using this version because we are working on Cyclone 2 device and that is not supported by the recent Quartus release. Okay, so that's why we are using this. But if you are working on the recent Quartus release and the recent FPGA devices, then you can use the recent releases from Quartus software. Okay, so don't worry about it. The steps are same. So first you will see this project wizard and you will see this create a new project button here. So click on this button to create a new project. So I will click on it. Okay. Now this is the new project wizard. So once you see this screen, just click on next button. Okay. Now at this page, you need to give the project directory and your project name. Okay. So for this, we will click on these 3 dots to give the project directory and locate your location. So for example, I want to create this project on this folder and I want to create it on a separate folder. So I will click on this make new folder and I will give some name to it. For example, this project is counter. Okay, so give it some name, counter, and then select it and okay. Now give the project name as well. So make it simple and I'm giving the same name, that is counter. Okay, so this is the project directory and this is the project name. And once you finish this, just click on next button again. Now, if you have any existing file which you want to use in this project, then you can add that file into this project just by clicking the 3 dots and give the file location, and Quartus will add that file in your project. But we are designing this project from the scratch. So we are not having any files to add in this case. Okay, so we will just click on next. Now this is an important page because here you will select the FPGA device on which you are working. For example, I am working on Cyclone 2 device. So I will select that Cyclone 2 from here. If you are working on some other device, then select your FPGA device. That's very important, right? And once you select your FPGA device, then all the FPGA listed with Cyclone 2 will be listed here. So you can see there is a long list here. So we need to select our FPGA from this device list. Okay, and that's huge actually. So what we will do that we will use some filters to shorten this list. How? So you can see there is a package selection. So I will select that my FPGA, it is PQFP type. So I will select it. Now pin count. So I know that my FPGA has 208 number of pins. So I will select it. Now speed grade. So my FPGA is having the 8 grade. Okay, so I will select it again. Now you can see that this FPGA list is filtered out, right? So you can see only 4 FPGA devices are listed here. So I can select my FPGA device much easier, right? So my FPGA device is this one, EP2C5Q208C8. This means I am having Cyclone 2 device, so 2C, then 5Q, that is QFP package, then 208 number of pins and speed grade is 8. So this is C8. So these are the properties of your FPGA device and that's reflected by the name as well. So once you selected your device, then just click on next button. Now, if you're doing some simulation or time analysis, then you can select the tool for the simulation purpose. For example, for simulation, there are few tools here. These are listed for the simulation purpose. So you can select any one of them which is set up in your machine. Okay. So for example, I am using this Quartus simulator. Then I can select the formats or the language. If you're working on Verilog, then select Verilog. We are working on VHDL, so I will select VHDL. But for this project, I am not doing any simulation. So it's fine if you leave these fields blank at the moment. So just simply click on next button. Now this is the summary page and it is showing whatever you have chosen from the previous steps. For example, this is your project directory. This is your project name. This is your FPGA device and this is your FPGA name, right? You have selected simulation like Quartus simulator, VHDL as a language, right? You have selected none as a timing analysis. So these all the settings are summarized here, which you have chosen in the previous step. So just review these informations and just simply click on finish. So once you click on finish, then Quartus will create the project for you. Well, this is quick. So you can see that Quartus has created the project that is named as counter. But if you notice, there is no file listed here. If you go to the file tab, then still there is no file because we have not added any file to this project yet. And even we have not created any file as well. So first what we will do that we will create a new file. So we will go to the file tab and we will click on this new button. Okay. So this is Control N from the keyboard as well. So you can simply press Control N or you can go to this file tab and click on new button. So, okay. So click on new button. Now this is a long list, but we are working on the VHDL programming language, right? So select the VHDL file. And once you select it, then click on OK. Now this is the project editor where you will write your VHDL code, right? But before that, let's save this VHDL file first. So you can see that Quartus has given some name that is VHDL1.vhd. But we want to save this file as our own way. So first what we'll do, we will save this file. So go to file tab once again and click on save as. So here this is save as button, click on it. Now locate the folder locations. So my project is inside this projects folder and then inside this counter folder, right? So I have created this counter, right? Now you can save this file inside this folder as well. But what I prefer to save all my VHDL files in a separate folder. And I name this as source. So SRC. So that is the acronym of source. That is why, because by doing this, I know that all of my VHDL files or the source file are located at the separate folder that is named as this source. So always try to use a separate folder for your VHDL files, right? So click on source and select this folder. So this is selected. Now click on save button. So this is counter and then click on save. So you can see that the title of our VHDL file is now changed. Now it is counter inside the source file. Okay. So let's write our VHDL code for this project. So first we will give library declaration. So write it library IEEE use IEEE.std_logic_1164.all. So this is our library declaration and package declaration. Now the next is entity declaration. So write it entity counter is and entity, so and counter. Now port declaration. So give it port and bracket closed semicolon. Now what we have in this project, we have one clock signal as an input. So write it clock, that is input type, and this is std_logic type semicolon. And we have 8 output LEDs for our 7 segment display, right? So suppose our output name is LED. This is output type. And we are saying this is std_logic_vector and having the range of 7 down to 0. Okay. So this is our entity declaration. We have clock as an input and we have LED as an output, but it is having 8 elements inside it. Okay. For 7 segment display. Now the next thing is the architecture declaration. So write it. So first I will write the architecture body. So write it architecture behave of counter is now begin and in the last and architecture. So and behave semicolon. So we have just written the architecture body. Now first what we will do that we will convert 50 megahertz signal into 1 second pulse, right? Because we are counting our counter from 0 to 9 at each and every second, right? And we are using 50 megahertz as in clock frequency. So that is very high. So we need to convert this 50 megahertz signal into a 1 second signal. So for that, we will use a registered process. So write a process for this. So first we will give some name to this process. Suppose I am giving process clock. Okay. So this is process and clock is in the sensitivity list because this is a registered process block. Now begin, and in the last and process semicolon. So we have just created the body for this process. Now write the structure for the register process block. So this is if rising edge of clock, then and terminate this if condition. So and if. Now we will write the functioning of this. Okay. So what we are doing that we will count each and every rising edge of clock signal, which is 50 megahertz. So we will count it up to 50 million times to get 1 second. We already explained this many times in the previous project sessions, right? So I'm not repeating much in this session, but in brief, we are using 50 megahertz of clock frequency and we are converting it into a 1 second pulse or 1 second signal, right? So what we will do that we will count from 0 to up to 50 million times. So for each rising edge of this clock frequency of 50 megahertz, our counter will increase by 1 and slowly it will reach to the 50 million count, right? And once it reaches to 50 million count for this 50 megahertz clock frequency, we will get exact 1 second from it because it will take 1 second to count 50 millions for this 50 megahertz clock frequency, right? So write this counter. So what I am writing that if this counter is greater than 49,999,999, then now if you wonder that why this number that is 49,999,999, that is because we are starting our counter from digit 0, not 1. So this number is actually 1 less from 50 million. So we are starting from 0 and we'll count up to this number and that will give us exact 50 millions increments, right? And that's what we want. So if counter is greater than this number, then what will happen? We will reset our counter to 0. So write it, our counter should be 0, right? Else what will happen? Counter should be counter plus 1, means it will increase 1 on the last counter value. Okay, so that what this statement is doing. So our counter part is done. So we will terminate this if condition. So write and if. Now we have divided this 50 megahertz clock frequency into a 1 second cycle because we are counting it 50 million times, right? But to use this frequency divider, we need an additional signal. Like for this example, we are counting from 0 to 9 at each second, right? So we will create a signal that will count from 0 to 9. So write it. The steps are almost same like we did for this counter. So we will write that if second is greater than 9, then what will happen? That our second should be reset to 0, right? Now else if. Now what we want that we want to increase this second signal at each and every second, right? And for that we are using this clock signal, right? To convert that 50 megahertz to 1 second. And we know that whenever it will complete 50 million cycles, we will get exact 1 second. Okay. So what we will write that else if counter is equals to 0, then what will happen? The second will get the value of second plus 1. So we are increasing 1 into the last second value. Okay. Now this is completed. So terminate this if condition as well. So this is and if. Now we have used this counter and second in this process block, but we have not declared it. So first what we will do that we will declare these signals in this program. So we will declare it in the architecture and begin section. Okay. So this is in between architecture and begin section. So declare it. So we have this signal that is named as counter and this is integer type and it is having the range from 0 to 50 million, right? And we have the another signal that is named as sec and that is again integer type and having the range from 0 to 9, right? Even let's do it 0 to 10. Why? Because we are using the condition that is greater than 9, right? So greater than 9 means when the second value having the value of 10, then it will reset to 0, not at 9, right? So we have given the range from 0 to 10. So our frequency divider is ready. Our 0 to 9 digit counter is ready. And now the only thing left is to drive our 7 segment display output. And how we will do this? We will use a 7 segment decoder for this. Okay, so we will write the 7 segment decoder with VHDL with select function. So write it with second select LED, which is our output, gets the value of 11111100 when 0. Next will be 0110000. This will be when 1. Next will be 11011010 when 2. Next will be 11110010 when 3. Next will be 01100110 when 4. Next will be 10110110 when 5. Let's correct it. When 5. Next will be 10111110 when 6. Next will be 111 and 00000 when 7. Next will be 11111110 when 8. Next will be 11110110 when 9. And let's all 0 when others. That will not meet actually. Okay, so because our counter will start from counting 0 and it will go up to 9. Okay, and we have defined what will be our 7 segment output for these respected values. We have already explained that from where these numbers are coming out, right? So I'm not explaining this in this session. If you want to understand this, just watch my last video. Okay, I have explained everything there, like what are 7 segment displays, what type of 7 segment displays are available in the market, what 7 segment display we are using, and how these 7 segment display works, and how to write a 7 segment decoder in a VHDL programming language. So that's what we have did in this section of code here. Okay, so we have completed our VHDL code for this project. We have divided our 50 megahertz clock frequency to a 1 second cycle. Then we used another counter to count from 0 to 9. And then this counter will drive our 7 segment decoder. Okay, so that's what we are doing in this project or in this section of VHDL code. So once you do this, just save your project. So click on save or Control S. And then the next step is compiling your project. So you can see this play button here. You can just click on it to start compilation. So just click on it and it will start compilation. So it may take little time to process it. So you can see all the information are logged here, that what is happening with your program. If your syntax is correct, if it is having any syntax error, if it is having any warnings. So you can see everything in these logs here. Okay, so you can see that I am getting this message that is full compilation is completed and I am not having any error, but there are 11 warnings. Okay, but we will ignore these warnings at the moment because we know we have not completed few of the steps. For example, we have not completed timing analysis. We have not completed pin planner. So these all warnings are related to same. Okay, so I will click on this OK button. And if you want to see what are these warnings or errors, so you can see here. For example, this is the warning: found 8 output pins without output pin load capacitance agreement, right? Next is critical warning: timing requirements are not met, because we have not set the timing constraint for our project at the moment. So you can see timing requirements not met. Okay, so there are many warnings listed here, but just ignore it for the moment. Okay, so you can see this is your compilation report and you can switch to your VHDL project or your VHDL program from here as well. So these are two separate tabs here. You can just switch it between your compilation report and your VHDL source code. Okay, so we have compiled it and we don't see any syntax error in this program. So we are good to go to pin planning our design. So for this, you can see here is a button for this pin planner. So you can just click on it and open the pin planner. Alternatively, you can see it in the task section as well. So you can see, just go down little and you will see this pin planner here as well. So you can open it from here as well, or you can simply open it from this button. So just click on this pin planner button and this will be open. So this is our FPGA view. So we have selected Cyclone 2 as an FPGA device, and this is our device name, which we have selected during the initial project startup steps, right? If you remember. Now this FPGA has 4 sides. So this is side A, side B, side C, and side D. and all the side having lot of number of pins. So you can see these symbols here, these all symbols are denoted as a FPGA pin. Now, if I zoom it little, so you can see these number of pins are listed here. Okay, 11, 12. So let me take a pen tool and I little move it up. So this red point is our starting point, and our counting of pin is started from here. That is 1, and it will go up to 52 for this side, then 53 for B side, go up to 104, then 105. This is side C, goes up to 156, and this is side D, 156 to 208. So if you remember, we have selected FPGA devices that is having 208 number of pins, and that is listed here as well. That is 208. Okay, so this is your FPGA view. But what we are looking for this window. So you can see that Quartus has listed all the input output ports for this project. So what we have two ports here. One is clock and second is LED. But that LED is having 8 elements inside it, because this was std_logic_vector 7 down to 0. So Quartus already differentiated it here. For example, this is LED 7, this is LED 6, and goes up to LED 0. Okay. So what we will do in this pin planner, that we will tell that what pin of this project will connect to the what pin of this FPGA. Okay, for this FPGA, this is the port name and this is your FPGA pin. So we will link this port with this FPGA pin. So that what we will do in this pin planner. Okay, and for this you need to look into your FPGA board specification, because that will tell you that at what FPGA pin your clock frequency is given, and for what FPGA pin your 7-segment display is connected. So all the information should be listed in your FPGA board specification. Now coming back to this table, so you can see that this is our signal name or port name. So this is clock, and you can see that is input in the direction. Okay, because we have defined it. And you can see that all the LEDs are our output pin. So you can see all the LEDs are listed as an output direction. Okay, and there are few fields. These are blanks at the moment, and we are going to fill all this information here. So what we will fill, that we will tell the location of clock. So for our FPGA port, our clock is given to this pin number 23. So I will write pin_23. So that's the way how you define the FPGA pin to a specific port. That is pin underscore and your pin number. Okay. Now I will give the pin numbers to the LED output. That is our 7-segment display output. So for my FPGA board, it is connected to pin number 34. LED 6 is connected to pin number 35. So give it 35. Next is connected to 39. So give it 39. Then LED 4 is connected to 44. So give it 44. LED 3 is connected to 43. So give it 43. Next is connected to 37. So give it 37. Next is connected to 40. So pin number 40. And the last LED is connected to 41. Okay. So I will give it 41. So I have listed all the input output pins for my project. Now, if you click on any of the signals or any of the port here, for example, I have selected this clock signal. And if you go to this FPGA view, so you can see that this FPGA pin will be highlighted as in blue border. So that means this particular pin is selected from the FPGA, and that is connected to this clock port. Same way, if you select this LED 7, so you can see that this is connected to pin number 34 of this FPGA. Okay, LED 6, that is connected to pin number 35. LED 5, that is connected to pin number 39. LED 4, that is connected to pin number 44. LED 3, that is connected to 43. LED 2, that is connected to 37. LED 1, that is connected to 40. LED 0, that is connected to 41. So we have specified all of these input output ports with this FPGA pin or this FPGA board. Okay. Now, important thing is that you do not need to save anything after making all these changes, because pin planner automatically save all this information for you by default. So whenever you make any changes in this list, this pin planner will automatically save. So you will notice that there is no save button in this window here. Okay. Because this is automatically gets saved when you are making any changes in this view. Okay. Now there is one important thing to tell you about FPGA. So all these FPGAs are having some number of banks inside it. For example, this FPGA has total 8 number of banks, and each FPGA pin belongs to some specific input output bank. So you can see that all of these input output ports which we have defined in this project, these are connected to these FPGA pins, and these all FPGA pins are belong to this input output bank. Now important thing is that these all input output banks having their own power supply, means these all IO banks have their separate power pin. Okay, so if you specify the location of your input output ports, it will automatically fill your input output bank. Like here we have just filled the location and input output bank has automatically filled. Same as with the V reference group as well, because this FPGA has a predefined set of standards for input output. For example, you can see that input output standard is by default set to 3.3 volt LVTTL, and you cannot change this for this FPGA. But the modern FPGAs are more flexible, where you can select these input output standards as well based on your FPGA board manufacturer. So you will get more control. But for this FPGA, this is very straight because we do not need to change anything in this specification. Okay, so we have specified all the FPGA pins for all our input output ports. Now once you completed it, just click on this close button because it is already saved. Now one more thing, that you do not need to go again and again to this pin planner until you are adding any new port into your entity or into your project. Okay, so for this project, you just define it once and then forget it, and it will remain same for all the changes which you are making in this program. Okay, so we have defined the input output ports and we tell the Quartus that what ports are connected to what FPGA pins, right? Now after doing this, you need to recompile your design. So again, go to this play button here and click on this start compilation button. So click on it. Now again, it will compile your program and will give you the results. So you can see that the full compilation was successful and there is 10 warnings still because we have still not completed the timing constraint part, but we will ignore it. Okay, so just click on OK. Now this is the time when you program your VHDL designs into your FPGA board. So what we will do, that we will open the programmer. So you can see this button here. So this is for programmer. You can open this programmer from this button, or still you can go to this task section and you will see this programmer device or open programmer here as well. So you can open it from here or you can open it from here as well. So just click on this programmer. Now click on OK. So this is your programmer. Okay, let me wide this little so that you can see all the information listed here. Okay, so this is our counter.sof. So this is our binary file which will be implemented into our FPGA. Okay, and this is our device name, that is EP2C5Q208. This is checksum for some validation of this binary file, user code FF, that is none, and make sure that your program and configure button is ticked. This is your progress bar. So once you start flashing your FPGA device, you will see the progress here. Okay, and now this is your hardware setup. Then you can see that USB blaster USB 0. This is listed here for my device. Okay, if you do not see anything here, then just click on this hardware setup button and you should see this programmer device listed here. If you're not seeing this here, that means your programmer is not connected with your PC, or maybe there can be a driver issue. So in that case, just update your driver and reinsert your USB device or programmer device. Okay, and once you see this device listed here, just select it and click on close, and then you will see that your device should be listed here. Okay, so once you see it here, so select your binary file and then you will see this start button flashing here. Okay, so just click on this start button and you can see the progress here. So that is quick, 100% successful. And now we will move to our FPGA board to see that what we are getting at the output of our 7-segment display. We are expecting that our 7-segment display should count starting from 0 and it will go up to 9, and it will count at each and every second. Okay, so it will start from 0, then count 1, then 2, then 3, and it will go up to 9 at each second. So let's move to the FPGA board and see if we are getting the right results or not. So this is our FPGA board and this is our 7-segment display. So you can see our counter starts 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay, and you can see that is happening continuously in a loop. So that means our FPGA design is working well and our VHDL code is perfectly fine and it is doing the right job for what we have designed it, right? Okay, so that was our demo for this project. Hope you liked it and learned from it. So you seen that first we converted 50 megahertz clock into 1 second signal. And then we counted it for each second from 0 to 9. And once its value greater than 9, we reset it to 0 and counting starts again. Just a note, because I'm using Cyclone to device, so I have used this Quartus old version. But steps are almost same for designing and implementation on Quartus. In the future session, we will be covering more such projects and we will be implementing them on FPGA board as well. In the last session, we worked upon 7-segment displays. We designed a single bit counter that counts from 0 to 9, and then we will implement it on FPGA board as well. Now we will discuss one of the most important technique in 7-segment display, and that is widely used when you are working on more than one 7-segment displays. So let's consider that you have these 4 7-segment displays. Means you can display upon 4 digits on it, right? And for that you will need 8 multiplied by 4, means total 32 output pins for 4 7-segment displays, right? This actually can do, but this is not a practical solution. So here we will use 7-segment multiplexing technique, and you will surprise that you can operate these 4 displays with just 12 number of output pins. But this is not easy to do because there are a lot of synchronization required to perform this task. So let's understand the technique first. So you can see in this diagram that we have 8 LED output pins, which will drive each segment of LEDs like we discussed in the last session. But the difference is that these 8 LED pins are common for all of these 7-segment displays. Means these data pins are actually shared by all these 4 displays. So the problem is, if you want to display number 0, then all these 4 displays will display 0 because they all have same common data lines. So if you are sending 0 through these pins, then you will see 0, 0, 0, 0 in all the displays. And if you send 1, then all these 4 displays will show number 1. But we don't want this, right? Because we might want to see different numbers in all these 4 displays, right? For example, I want to see 2, 4, 6, 8. Means each display showing different numbers. So how it is possible? Confused? So let's see how to do this. Okay, so if you notice, then you will see few additional pins here. These are anode 1, anode 2, anode 3 and anode 4. Now this anode 1 is actually connected to the anode pin of first display. Means the anode pin of all the LEDs of this first display is connected to this anode 1. Same way, this anode 2 is actually connected to the anode pin of second display. Means the anode pin of all the LEDs of this second display is connected to this anode 2. Okay. Same way, this anode 3 is connected to all the anode pins of this display 3. And anode 4 is connected to the anode pin of display 4, right? So let's see how it works. Now suppose we want to display digit 1 on this rightmost display. So what we will do, that we will send the data of digit 1 from these data lines. And now it is captured by all these 4 displays, right? But what we will do, that we will only select this rightmost display to show the digit. And we can control this by using this anode 1 pin. Means we will send logical 1 to this anode 1 pin. And all other anode pins are logical 0. This means that whatever the data we are sending over these data lines, it will only be displayed on this rightmost display because we have selected it by using this anode 1 pin. So this is our step 1. When we select display 1 and we get the number 1 on that display. Now we have total 4 steps in it. 1 step for each display. So step 1 is done and we displayed digit 1 on this rightmost display, right? Now step 2 means it's the time for this second display and we wanted to see digit 2 in this display. So first we will select this anode 2 pin, means this anode 2 pin will set to high and rest of the anode pins are set to low. Means our display 2 is powered up and rest of the displays are powered off. So we will send digit 2 data now over these data lines. Means now our second display will show digit 2. Now step 3. Suppose we wanted to see digit 3 in this third display. So the steps are same. We will select this display number 3, means we will power up this anode 3 pin and we will power off all other anode pins here. Means anode 3 is logical high and other anode pins are logical low. And now we will send the data of digit 3 from these data lines. So this third display will show digit 3. Same process for step 4. Now we are displaying digit 4 on this fourth display. So select this anode 4 pin and power it up by giving logical high to this pin and logical low to all other pins. Now send the data of digit 4 through these data lines and it will display digit 4 on this fourth display. Okay, so till now it looks good, right? Because we can see each individual digit on this 4 displays. But there is a problem. You know what? The problem is that you can only see one digit at a time. Means either you can see this first display which is displaying 1, or you can see second display which is showing 2, or you can see this third display which is showing 3, or you can see this fourth display which is showing 4. But you can only see one digit at a time or one display at a time, right? Because we are controlling this, that which display should on at any specific point of time. And we want to see all the digits at the same time from all these 4 displays, right? For example, from the data we have given, what we will see? We should see the number 4, 3, 2, 1 like this, right? And to achieve this, we need a trick because theoretically it is not possible. So what we will do, that we will display these digits repetitively and at a very high speed. So if we are displaying them repetitively and at some good speed, so they will be looked like that all the displays are on and showing the digits. So let me explain that what is happening. So focus on this first display. This is showing digit 1, right? So what will happen, that this digit 1 will be flashing many times within a second on this display 1. Same, this digit 2 will be flashing many times within a second on this display 2. Same, this digit 3 will be flashing many times within a second on this display 3. And same for digit 4, which will be flashing many times within a second on this display 4. Means all these 4 steps which we have discussed are repeating at very high speed. For example, you are switching them at millisecond or at every millisecond. So this is really fast. So all these 4 displays are showing the digits many times in a second, and our eyes cannot segregate them at such high speed. So it will display like all the displays are on and showing the digits. Well, this is the concept that is being widely used in almost all type of displays, not only on 7-segment display. Okay, so let's wind up this session. I hope this is an informative session, and if you understand this concept, then please try to implement a 4-digit counter into a FPGA board, which will count from 0 to 9999. And let me know if you're facing any difficulty in logic, and I will record a session if I get multiple requirements for it. Okay. Okay, so by now we have designed many projects in VHDL. and we implemented them in FPGA board as well. And now we will be talking about one of the most important part of designing process, and that is testing or verification of your designs. So we have many different type of simulation tools to simulate our VHDL designs. And you can test your VHDL designs by changing the values of your input ports. And you can see if you're getting the right result or not. So this is a manual approach of testing. However, VHDL allows you to automate this testing process, and we use test benches for this purpose. There are many different options available for writing these test benches in VHDL. For example, you can specify that what values you want to test at what time. You can also test your designs by reading the inputs from a text file. So it will read the data from the text file and will use it for the test values. You can also write your output to some text file as well, and later you can verify the results as well. So there are many different ways to test your designs, and we will be talking about them one by one. So first understand what is Testbench. So Testbench is a VHDL module itself, and we need to write a separate VHDL code for these test benches. Test benches has two major tasks. First is test benches provides the input values to your VHDL designs. And second is that it ensures that your output of your VHDL design matches with the correct and expected results. Test benches are very flexible, and you can control that what test you want to perform and for how much time. So this is a basic structure of your VHDL test bench. We have this DUT, or you can say device under test. Sometimes we will also say it UUT, or unit under test. Basically, this is your VHDL design which you have written and you wanted to test. Okay, so this device or this design will have some input ports and some output ports, right? Now, do you see this block of gray color? This you can assume like your test bench. So what we will do that we will instantiate our VHDL design to this DUT inside this VHDL test bench module, just like how a component instantiate. So this DUT model is like a component of this test bench. Okay. If you notice, you will see that we have not defined any input output port for this test bench. So we have input output ports for this DUT model only, but we do not have any input output port for this test bench module. Okay. Because we are driving these input ports of this DUT inside our test bench. And then based on these input values, we get our output from this DUT model. And finally, we will compare these results. Means we drive all the input ports of this DUT inside this test bench. And for this, we write our VHDL test bench code. And you can use VHDL process, VHDL procedure, VHDL functions, or any other VHDL module, or even some combination logics to drive these input ports. Even you can read this set of inputs from some text file, which you can import into your test bench. VHDL can also create a text file to store your output data, and it captures all the logs of your output so that you can verify the results later from that text file. Even test benches can print messages on your simulator console window, and you can print any message in your simulator console. For example, some error message or some warning message or even some kind of note. And this is very important because you can print a message if some error has encountered. So you know that what is the problem. This is a simple VHDL syntax for printing a message on your simulator console. So we start from report keyword followed by your message, inside the double quotes. And optionally, you can also tell the severity label as well. So these severity labels are note, warning, errors, and failures. And you have to write them exactly like this. And if you're not defining any severity label in your message, then it will be by default considered as note severity. Okay. So VHDL syntax is report, message string, then severity, severity label, semicolon. Now, these are the few examples of reporting messages. So first is report, this is a message. Now, because we have not specified the severity label, so this is by default considered as a note message. Now, second example, report, this is a warning, severity, warning, semicolon. So this will print, this is a warning message with the warning severity. Okay. Now, important thing is that if in any case error or failure is reported by the simulator, then your simulator will print that message and then it will stop simulating. But if you get a warning message or a note message, then simulator will print that message but continue the simulation. Okay, so remember these differences between warning note messages and error and failure messages. Now, once we provided the input to our VHDL design or DUT and we get the outputs, then we need to validate these outputs, right? Like if they are correct or not. So we have these assert statement to validate our output. So this is a kind of Boolean condition and it will print a message in your simulator window if the condition is not met or if the condition is false. For example, you can compare your expected output with your design output. And if both are the same, means everything is good. But if they are not same, means there is some problem in your design, right? So assert can print a message in your simulator window that your output is not correct. Something this kind of message. So this is the syntax of assert statement. Assert, condition report, string in double quotes, severity, severity label, semicolon. For example, assert overflow is equals to 0, report message overflow, severity warning, semicolon. So what it will do that until your overflow is logical 0, everything will fine. Means until this condition is true, it won't display anything. But as soon as overflow is detected and this condition get false, means your overflow triggered logical 1, you will get this message, message overflow. And that's have the severity of warning. Now, as I said, test benches can also read a text file or even write into a text file. So for that, first we will need a library std and we need to declare text IO package from this std library. And then you can use text file to read data from it or to write data into it. So we can store set of inputs into the text file. Then Testbench will read this file line by line and perform the task on these set of inputs. And after getting the results, it can write the results into the output text file as well. So this is really a powerful tool because now you can change your input set just by updating the text file. Instead, writing different set of inputs into the test bench itself. So you can test your design by using many multiple set of input combinations. And you can leave your simulator running for a long time. Like you can leave it for a whole day and you can perform as many tests as possible. Now understand how we do this. So this happens in 4 steps. First, we open a file. Second, we read from a file. Third, we write into a file. And finally, we close the file. So for that, we need to declare a text file as variable before we open it. This is an initial step or a prerequisite, you can say. And we need to declare it either inside the declarative part of architecture, means between the architecture statement and begin statement, or you can declare it inside the declaration part of a process block, means between the process statement and begin statement. So this is a syntax for declaring a text file in VHDL. We start from file keyword followed by the file handle and then specify the format like text. This file handle name is actually a variable in VHDL, which will be used for input-output operations later. So the syntax is file handle, text, semicolon. Like for example, file1, text, semicolon. So we have created a text file named as file1. Simple. Now, once you declared your file in VHDL, you can open it now. So this is your VHDL syntax to open a file. File open, bracket, file handle, comma, file name.txt, comma, open mode, semicolon. Now these open modes are read mode, write mode, and append mode. So we use a VHDL function file open to open a file. Then inside the bracket, we give the file handle name and then file name inside the double quotes. And finally, you specify the open mode. Note that each element is comma separated here. Like for example, first example is file open, bracket, file1, comma, input vector.txt, comma, read mode, semicolon. So you may guess it will open a file with file1. Name of text file is input vectors.txt and it will open in read mode. Second example is file open, bracket, file2, comma, output vector.txt, comma, write mode, semicolon. So this will open a file with file2. Text file name is output vectors.txt and it will open in write mode. Don't worry if you are not clear about it at the moment, because I will show you that how to write a VHDL code for reading data from a text file and for writing data into a text file in the separate session. But this is just pretty basics. Now this is our final step, that is closing the file. So this is pretty simple. This is the VHDL syntax for closing a file. Simply write file close, file handle, semicolon. So we use VHDL function file close followed by the file handle and then semicolon. For example, file close, file1, semicolon, file close, file2, semicolon. In the next session, we will look into the VHDL code, that how you can write data into a text file in VHDL. In this session, we are continuing with VHDL test benches, and we will create a VHDL test bench to write the data into an output text file. So for writing the data into a text file, we need to follow 4 steps. First, we open a text file in write mode. Then we write data into a line buffer. Then we print the line buffer data into a text file. And finally, once all the lines are printed, then we close the file. Now step 1 and step 4 is actually one-time activity. Means we open the file at the starting in write mode and we close the file in the last once all the lines are printed. But step 2 and step 3 is repetitive until we write all the lines in the output text file. So in the step 2, we have this line buffer. This is actually a variable that is declared in the declaration section of your process block. And this acts as a buffer. and it holds the text of one single line. And later, this line can be written into the output text file. Means we load data into a line buffer by using this statement. Write line buffer, comma, data to write, semicolon. We use write function for this, followed by line buffer and data to write inside the brackets. And once we have data of one line in this line buffer, we print this data into our output text file. So this is step 3. And for that, we use this statement. Write line, bracket, file handle, comma, line buffer, semicolon. So we use a write line function followed by the file handle and line buffer inside the brackets. And now we repeat this step 2 and step 3 until we write all the lines in our output text file. And finally, at the end of simulation, we simply close our output text file, which is step 4. Okay, so let's write a VHDL Testbench to write some data into an output text file. So first, we will declare necessary libraries and packages. So as I explained in the last session, we need additional library, and that is std. And we need to declare text IO package from this std library. So declare them first. Library IEEE use IEEE dot std underscore logic underscore 1164 dot all use IEEE dot numeric underscore std dot all library std use std dot text io dot all semicolon. So we have used library IEEE and its packages because we are needing them for different data types like std logic, etc., which we have used in our DUT device or device under test. So they will also be used in this test bench as well. So first we declared library IEEE and its packages, and then we declared std library and its packages so that we can read or write data from a text file. Next step is entity declaration. So this is very straight because we do not write any input-output ports in test benches like we discussed in the last session. So our entity declaration will be entity testbench is and entity testbench semicolon. Now it's time for architecture part. So this is our architecture part for this test bench. First, we declare some signals or constant inside the architecture declaration section. So first is constant string. Second is signal x, which is std logic vector 3 down to 0, which has initialized value as 1010. And third is signal y, which is integer type and having an initial value of 100. So declare them constant c colon string colon equals to this is a string semicolon. Signal x colon std logic vector 3 down to 0 colon equals to 1010 semicolon. Signal y colon integer colon equals to 100 semicolon. Now we start our architecture with begin keyword. And now we will write our process block in VHDL. So write file write process colon process file output file colon text semicolon variable line buffer colon line semicolon begin. Now if you notice, then we have not written any signal in the sensitivity list of this process. So this is a special type of process block with no signals in the sensitivity list. And you must remember that this type of process blocks are not synthesizable, means we cannot implement them in FPGA. But we are fine with that because we do not implement test benches on FPGA. We are only using them in our PC just to simulate and test our designs. Now, important thing is, because we are not writing sensitivity list here, so we will use wait statement inside this process to control the execution of this process block. Wait statements are used to precise the execution of VHDL code inside the process block, and they are great for test benches. Now we have declared a file handle named as output file, and that is in the text format. Next, we declared a line buffer. This is a variable and having data type as line. So this will hold data of current line. Next, we start our process block from begin keyword. So first step is opening a file in write mode, right? So we have this statement here. File open, output file, comma, output file.txt, comma, write mode, semicolon. So file open is a VHDL function to open a file. Then output file is a file handle, which we have declared in the declaration part of this process declaration. Then we specified the output file name, which is output file.txt. And in the last, we specified the opening mode. So this file will open in write mode. Note that if this file, output file.txt, is not present in your drive, then VHDL simulator will automatically create it for you. And if it is already existing, then your file will be overwritten with the new data. Now we will write 3 lines one by one. So you can see there are 3 groups here. Each group is actually write 1 line into an output file. Means these 3 set of VHDL line will write first line in your output file. Another 3 set of VHDL line will write second line in your output file. Finally, these 3 VHDL lines will write third line in your output file. Okay, so let's understand these lines. So first we have written write line buffer, comma, string, signal x is, colon, bracket closed, semicolon. Write line buffer, comma, x, semicolon, write line output file, comma, line buffer, semicolon. So what we are doing, first we are copying all the contents for our line 1, and then we will write this complete line into the output text file at once. So what is happening? First we are writing data into a line buffer, and in this code we are combining 2 data into 1 line. So first 2 VHDL statements here are copying data into a line buffer. So first we have this string, which will print signal x is, colon, and now in the second line we append this line with value of x. So after executing these 2 lines, our line text will be signal x is, colon, 1010, and then we will print this line into the output text file. So we have this third statement, write line output file, comma, line buffer, semicolon. So write line is a VHDL function, output file is our file handle, and line buffer is the current line. So it is your data from previous 2 statements here. So always remember that first we print all the data into a line buffer, and once all the data is copied in the line buffer, then only we print the line into the output text file. Okay, if you understand this, then we followed the same steps for line 2 and line 3 in these sections here. Like for line 2, we have these 3 VHDL statements. Write line buffer, comma, string, signal y is, colon, double quotes closed, bracket closed, semicolon. Write line buffer, comma, y, semicolon, write line output file, comma line buffer, semicolon. So first statement will print the string signal y is, and then second statement will print the value of y in the same line. So your line data will be signal y is colon 100. And finally, it will write this line into the output file from this third statement. Same for writing the third line, we have these three statements here. Write line buffer, comma string C is colon bracket closed semicolon, write line buffer, comma C semicolon, write line output file, comma line buffer semicolon. So our line data will be string C is, this is a string, because first we copied string C is and then we printed value of constant C, which is again a string data type, and the value is this is a string. So our line data will be string C is colon this is a string. And finally, we write this line data into output text file. So I hope this is clear to you. Now, once you write all the lines in the output text file, you have to close your text file as a final step. Remember, we discussed this in the last session. So we have this close statement here in VHDL. File underscore close output file semicolon. Here, file close is our VHDL function and output file is our file handle, which we have declared, right? Now, this is an important step because we want this process to execute only once. Otherwise, every time this process executes, it will open the file, then overwrite the file, and then close the file. So this will happen in the infinite loop, and we do not want this because once file is closed, it is closed. And if this process is re-triggered, then our file will be overwritten every time. Means we need to pause this process now. So we use this wait statement. So this statement is very simple. That is wait semicolon. And now your simulator will pause here or stop here. So this is very important step here. And now finally terminate this process block with end process semicolon, and last terminate this architecture block with end architecture semicolon. So this is the output file which will generate from this code. So you can see that it will print 3 lines in this output file.txt. Signal X is colon 1010, signal Y is colon 100, string C is colon this is a string. In this code, we have only written 3 lines in this output text file. But I think now you can extend this list very easily. Well, generally we write important data into the text file. For example, values of our output or matrix of input and output, etc. so that we can analyze them in the future. You can also print important messages like warning, notes, etc. and even error messages or failure messages, etc. In the next session, we will read data from a text file in VHDL Testbenches. In the last session, we learned how to write data into a text file in VHDL Testbench. And now we will learn how to read data from a text file in VHDL Testbenches. This can be used to read input values for your test modules as well. So we read the data from the text file in 4 steps. First, we open the text file in read mode. Then in second stage, we read data line by line from the text file, and this happens in 2 steps. So you can see step 2 and step 3 in this slide. First, we use readLine function in VHDL, and the syntax is readLine bracket file handle comma line buffer semicolon. So this statement reads one line at a time from the file handle and copy that data into the line buffer. And at step 3, we read this line buffer into a testbench signal. And the syntax is read bracket line buffer comma signal name semicolon. And now we repeat this step 2 and step 3 until we read all the lines from our text file. And finally, we close our text file. So this is step 4. This is a simple VHDL code for this reading process. So first look at this text file. Name of this text file is inputfile.txt, and we will read data from this text file. So you can see we have two columns here. First column has integer data type and second column has 4-bit std logic vector data. Now let's move to the VHDL code. So we start from the architecture part here. We are not explaining library and declaration for this test bench because it is same like in the last session. But you have to write it in your VHDL editor when you are using this code for reading data. And remember, you need to include additional std library and text IO package in your test bench to read data from a text file, because we are using its predefined functions in our code. So architecture behave of test bench is begin. Now we start a process block here. So file read process colon process. Now again our sensitivity list is blank here. We are not writing any signal in the sensitivity list like we did in our last session, because we are going to use wait statement in this process block. Now first we will declare file handle. So it is file input file colon text semicolon. Means file handle name is input file. Now we will declare line buffer as a variable. So it is variable line buffer colon line semicolon. So we have a variable named as line buffer and it will store data of one line. Now we have to declare a variable to store individual data from our line buffer. So we have two types of data. In first column, we have integer type of data, and in second column, we have 4-bit std logic vector data. Although we have one extra thing here, and that is a space in between these two columns. So this space is read as a character. So we need to declare three variables here. First, we declare a character variable for a space. Then second, we declare this integer variable. And then we declare our 4-bit std logic vector variable. So we have written these lines. Variable character colon character semicolon. Variable int colon integer semicolon. Variable vector colon std logic vector 3 down to 0 colon equals to 0 0 0 0 semicolon. Remember that all these variables and file handle has to be declared in the declarative part of this process block. Now begin keyword. So we will write our process block from here. Now what was our first step? Our first step is to open the text file in read mode, right? So we have this statement. File open input file, comma input file.txt, comma read mode semicolon. Now we already explained this line in the last session as well, so we are not repeating it. But in short, input file is our file handle for this test bench. Input file.txt is our text file which we are going to read. And this last thing is open mode. So this time we are opening our file in read mode. Okay. Now you have to read these three lines from our text file and you read data line by line. Means we need to read this file in a loop of 3 cycles. So you can use for loop here because you know that you need to run it for 3 times. But in general, you can have n number of lines in your text file. So instead of a for loop, we prefer to use while loop with some additional functions. Consider we do not know that how many lines we have in our text file. We just want to read all of these lines from the text file. So we use this special type of function, and that is AND file. So we have this while loop with AND file function. So it is while not of AND file bracket input file loop. So we read our data until we reach at the end of file. So this while loop keep looping until you reach at the end of your text file. Now we read data from each line. So as I said, first we copy the whole line in a line buffer and then we read specific data. So we have these 4 statements here. Statement 1 is read line input file, comma line buffer, semicolon. So this statement copy one complete line into the line buffer variable. And in this line, we have 3 different type of data. So we copy all of them in separate variable. So first is read line buffer, comma int, semicolon. So this will read integer data from the line buffer and copy it into the int variable. Here, read is a VHDL function. Second line is read line buffer, comma char, semicolon. So this will read space character from the line buffer and copy it into the character variable. Third line is read line buffer, comma vector. So this will read 4-bit std logic vector data from the line buffer and copy it into the vector variable. And now AND loop, semicolon. So this cycle will run 3 times because after 3 times we reach at the end of file. And now the 4th step, which is closing our text file. So we have this statement file underscore close input file, semicolon. And now we will use wait statement. So as I explained in the last session that this statement is very important here because this statement will pause this process here and your process will only run for one single time at the start of simulation. If you do not write this wait statement here, then this process will rerun in an infinite loop. Means it will open a file, then it will read the data from these statements and then it will close the text file. Now, because you have not paused it here, it will again re-trigger this process block. So it will open the file again, read the data again, and again close the file. Then again repeating the same process. And we do not want this. So we need to permanently pause our process block here. So we have this wait statement. If you do not understand this, then please watch my last session. And now finally we terminate our process block and then terminate our architecture block. So you see that how easily you can read or write data into a VHDL test bench from a text file. And suppose you have different set of inputs to test your VHDL design. Then just read these inputs, test your VHDL module, and write the results into a separate text file. And finally, compare the results if they are correct or not. Or even you can create another text file with an expected output from the set of input sets. And then you can compare them inside the test bench itself. And if they are not matched or if you're not getting the expected results from your design, then you can print a message in your simulator tool itself. Like the expected output is not matched kind of something. So that's a huge possibility of its use cases. In this session, we will design a finite state machine project and we will use a PLL to understand the concept of Quartus IP wizard. These are two different things, and today our primary focus is on Quartus IP catalog. Quartus catalog includes many widely used modules, which you can use in your projects for free. Means you do not need to write a VHDL code for these predefined modules. So you can simply select the IP from Quartus based on your project needs, import it, and boom. Now you can use that in your project. This is as simple as that. No VHDL code, nothing. Interesting, right? So let's understand it by one simple example, and we will use it in our today's project as well. So suppose your FPGA board frequency is 50 megahertz and your project requirement is to use 25 megahertz of clock frequency. Then what you will do? Simply you will design a frequency divider, right? But instead that, you can simply import a predefined IP in Quartus Prime, and that IP will do this job for you. And so you do not need to write any VHDL code for this frequency divider. So this is one example. But Quartus Prime supports a wide range of IPs from different categories. For example, Quartus has memory elements like RAM, ROM, etc. Processors, communication protocols like Ethernet interface, audio and video interfaces, etc. Serial communication protocols, error detectors and correctors, filters, signal generator, and this list is really big. So today's task, we will use a PLL IP for frequency division. We will learn how to import it, how to configure it, and how to use it to get our desired requirements. Then we will use that output clock signal to drive a finite state machine, which will be our prototype of a manual traffic light system. Okay, so let's understand the finite state machine requirements first, and then we will move to the coding part. All right. Okay, so let's assume that you are at this stage 1, and at this time you can see that red LED is on and this yellow LED and this green LED are off. So this is our state 1 configuration. And now when you press this switch 1, so this is our switch 1, then we will move to stage 2. So we will jump to this stage 2. Now at this state, you can see that yellow LED is on and other two LEDs are off. So this is red and this is green. Now if you press this second button, so suppose this is switch 2, and when you press this, then you will jump to this state 3. And at this state 3, you can see that this green LED is on and rest two LEDs are off. Alright. So now when you are at this state 3 and again you press this switch 3, so suppose this is our switch 3, then our finite state machine will jump back to this state 1. Okay. And this will go in a loop. You press this switch, then you will jump from state 1 to state 2. Now you press this switch 2, then you will jump from state 2 to state 3. And when you press this switch 3, then you will move from state 3 to back to state 1. Okay. And these are the outputs for each individual state. So this is our design idea. Now let's go back to the Quartus Prime software. Okay, so let's open the Quartus Prime software first. So click on this Windows Start button. Now write Quartus Prime. So this is the Quartus Prime version we are using. So click on it. Now for this task, we will create a new project. So click on this new project wizard. So this is the new project wizard window. Now click on next. We have already gone through to this process multiple times in this session. So this time we will be a little fast. So first we will create a new folder for this new project. Suppose I want to save my project in this folder, and here we have this My Designs folder. I will select this. Now this time I will create a new folder and I will give the name that is IP test. Okay. Now enter and select this folder. Now we will give the name of this project, and suppose the project name is same, that is IP_test or IP test. Now click on next button. Now select this empty project button and then click on next. At this page, you can add any existing VHDL file into your project. But for this project, let's leave this as it is, as we are not going to add any existing file into this project, right? So click on next. Now at this page, we will select the FPGA device that we are going to use in this project, right? So for example, I am going to use a Cyclone 4 device. So I will select this Cyclone 4E from the device family. Now you can use these filters to shorten the list of the FPGA devices. So you can see that all the FPGA devices belongs to Cyclone 4 family, and this is quite a big list. So you need to select the exact FPGA device you are going to use, right? So we can use these filters here to shorten down this FPGA device list. Okay, for example, the package which we are going to use is QFP. So I can select this TQFP package. Now I have another filter that is pin count. So I will select this 144 pins, and the next filter is speed grid. So our FPGA is having the speed grid of 8. So I will select this. Now you can see that only 4 FPGA devices are listed here. So I can choose my FPGA device much easier, right? So for example, I have this FPGA and you can read it by name as well. So this is EP4C. So this is Cyclone 4. 4C means Cyclone 4. And in the last, that is C8, so that is 8 speed grid. Okay, so that we have selected here, right? And also you can see that this FPGA device comes with what elements or what features. For example, this FPGA device has total 92 input-output ports. So total pin count is 144. That includes VCC, ground, and the power pins for each bank. So out of this 144, 92 input-output pins are available. Okay. Next, you can see the memory bits. So this number is the total number of memory bits you are having in this FPGA device. You also have embedded multipliers, that is 9-bit. So you have 30 in total. Next, you have 2 PLL in this device. And we are going to use 1 PLL for this project. And we will have 10 global clocks in this FPGA device. All right. So after selecting the FPGA device, I will click on next. Now because I'm not doing the simulation in this project, so I will leave this page as it is and I will simply click on next button. And finally, I will click on this finish button. So you can see that our IP test is created here and we have selected Cyclone 4 device and this is your FPGA device, right? Now first I will create a VHDL file. So for this, I will click on this new button. Now I will select the VHDL file from this window and simply click on OK. Now the first thing that I will do that to save this file by giving some reasonable name. So for example, this is vhdl1.vsd because that is automatically created by the Quartus Prime software. So I will go to this file tab and then I will select this save as. Now as usual, I will create a new folder here and I will give it name, that is source. So that is our source file. Now enter. Now I will open this folder and I will save this file as IP test, and that will be our top level module as well for this project. So simply click on this save button. So you can see that the name of this file is updated, that is iptest.vsd. Okay. And now we are using the same code that we have previously designed in this learning series, and that was our FSM project. Okay. So I do already have that VHDL code. So simply I will open this file and I will copy the whole text. And now I will paste it into this VHDL file. Okay. And now let me quickly brief this program so that you can just recall. Although we have already explained this program previously, but still let me give a quick brief to you. So this is our library section. So library IEEE and use IEEE.std_logic_1164.all. Next, we have this entity section. So our entity name is test01. So that is our project name as well. So we need to change this test01 to IP test for this project. So I will copy this, paste this, and paste this here as well. Now remember that your top level module or your project name must match with the entity name here. Okay. So previously that was test01, but our project name is IP test. So that is why I have changed this name to the IP test. Okay. Now this module has 4 ports. So you can see we have these 4 ports here. We have clock. So that is input type and std_logic. we have reset, that is again input and STD logic. We have one extra input, that is switch, and this is STD logic vector, and the range is 1 to 3. Means this port having the 3 indexes inside it. Alright. Next we have the LED as an output type, and this is again STD logic vector, and the range will be 1 to 3. Means 3 indexes inside this output. Okay. Now we have this architecture section from here till here. So what we have did here, that these 2 lines are for the custom data type, because we are going to use a finite state machine in this program. So we have this custom data type that is named as state, and this will have the element of red, yellow and green. Okay, and that is our traffic light. Now once we define the data type, we will create a signal from that data type. Okay, so signal present state, and that is of state data type. Means this present state signal can have these 3 possible values. So that is red, yellow and green. Alright. Next we have started the architecture section, and we have simply created our state process. Now this is the register process block. So we have clock and reset in the sensitivity list. And now first we have given the reset condition. So if reset is high, then our LED output will be 0. Means all the LED outputs are off. Okay. And also we will reset our state or the present state, that will be red for the red signal of our traffic light. Now what will happen at the else if condition, means at the rising edge of the clock, we will use the case statement here. So case present state is, so when this present state is red, LED output will be 1 0 0. Means the red LED will on and yellow and green LED will be off. Okay. So for example, the first LED is red, second LED is yellow, and the third LED is green. Alright. Let's mark this comment. And now we have the condition that if the switch 1 is pressed, then our present state will be yellow. So when you press this switch, you will jump to this next state. So that is yellow. Alright. Now at this state, the LED output will be 0 1 0. Means the yellow output or the yellow LED will glow and the rest 2 LEDs will off. Alright. And now we have the same condition that if switch 2 is pressed, then we will move to the next state, and the next state will be green. Okay. So when you are at this green state, then the output will be 0 0 1. Means this green LED output will be 1 and the rest will be 0. Alright. And when you press this switch 3, then your state will change to red. So this is the very simple finite state machine program. And in the last, we also have this when others condition. So this is same like the reset condition we are having. So we have this LED output that is 0 and the present state will be red. Okay. And in the last, finally, we AND the case with this statement. Then we AND if to terminate this if condition. Then we will AND the process, and finally we will AND the architecture. So this is our very simple finite state machine program. So first we will quickly compile our program to check if this program is having any syntax error or not. Alright. So I will go to this play button and I will click on this to start our compilation process. So this is asking to save our program. So yes, we wanted to save this. Now the compilation of our program is started. So it will take a couple of seconds. So we will wait for the results. And it is done. And the good thing is we do not have any syntax error in this program. Alright. So now this is the time to use the IP catalog in this design. So what we will do, that we have this clock that is 50 megahertz in our board frequency. So this is 50 megahertz. And now suppose we are having the requirement to use a 25 megahertz of a clock frequency to drive this state process. This means that we have to divide this input clock or this board clock frequency by 2, right? So one way is you can simply write a VHDL code to divide your input clock frequency, and for doing this you have to write a complete code for that clock division. But here instead we are writing a VHDL code, we will use a PLL for doing this clock division for us, right? So you can see that we have this IP catalog window here, and if you don't see this window like this, then you can simply open this from the tool tab. So you can see this tool tab here, And here down the section, you will see this IP catalog. So simply click on this IP catalog button and you will get the same window here. Okay. So this we call IP catalog. And inside this IP catalog, you are having multiple categories for these IPs. For example, we are having this basic functions. So you can expand this as well. So inside this, you can see we have arithmetic IPs. We have clocks, PLL and resets. We also have on-chip memory. So you can see that if you wanted to use RAM or ROM, so you can simply directly use them from this catalog window. We do also have shift registers. Apart from this, we have this DSP for digital signal processing. So here we are having this error detection and correction techniques. So you can use them. You are having filters. You are having signal generations. So you can use any of them into your project very easily, right? We do also have the interface protocols, like for audios and videos, we are having these. We also have Ethernet interface. So you can simply open this 1 gig multiple rate Ethernet. We do also have the serial communication like SPI, LPC, etc. Other than this, we also have memory interfaces. We do also have processors. So you can use these NIOS too in your project. You do also have embedded processors. You can also use them. Next, we have peripherals and then university programs for audio and video, clocks, communications, memory, etc. Right? So you can see that this Quartus Prime software already have multiple and different type of IPs for your use, right? But in this program, we are really interested in the clock IPs, right? So we have this clock IPs inside this basic functions category. So simply select this basic functions. Now you will see this clocks, PLL and reset. So simply expand this. Now we are having the PLL category here and we are going to select this Alt PLL for this program, right? So simply double click on this. Now this type of window that will open. So here it is asking for the folder name or the folder location. So what I suggest to create all the PLLs in the separate folder, and I do generally create a new folder named as IPs. And now I will create another folder for PLL, or you can give some other name like for clock, because in this program we are only going to use one PLL. But if you're designing some bigger project, then you might be interested to use more than one PLL in your project. So it's better to differentiate them by folder. Okay, so simply I will create another folder that is PLL and I will give the name PLL or even clock PLL to this IP. All right, now click on save. Now you can see we have two options, that is VHDL and Verilog. So I will select this VHDL tab and after this simply click on OK button. And now this is your IP wizard. Now let me quickly adjust the window size here so that you can see everything in one view. Okay, so this is our first page of this IP wizard for this clock PLL. All right. Now at the top left, this is our block diagram for this PLL. Okay, so you can see that the name of this PLL is clock PLL and we have selected this name for this, right? And now here you can see the FPGA device. So that is Cyclone 4E device. Now this module having the two inputs and two outputs. So the inputs are in clock 0 and asynchronous reset, and the output are C0 for the output clock and one is locked output to lock this clock PLL. All right. Now if you look here, then it is by default selected 100 megahertz for this module, and we know that is not correct for our board, right? Because our FPGA board is using 50 megahertz of clock frequency. So first we will correct this, and you can see that it is asking here to choose the input clock frequency. So what is the frequency of the input clock, or in clock 0 input? And it is by default selected 100 megahertz. So we'll correct it to 50 megahertz. Okay. Now once you do this, you can also see, so that is updated in the block diagram as well, right? Next thing that is important in this page, that is the speed grade of our device. So now we know that the speed grade is 8 for our FPGA because the device that we have selected is this. And you can see that in the last that is written C8. means this is having the speed grade of 8. So simply select our speed grade, so that is 8. Now leave everything here and just simply click on next button. And now in this page, you can control your input and output ports. So for example, these are the optional inputs here. And in this block diagram, you can see we have two inputs. That is clock, so that is mandatory. But this asynchronous reset is the optional signal or the optional port for this PLL, right? But it is always better to use the reset in your projects, right? So I will leave this input port as it is. But if you do not want to use this reset signal, you can just simply untick this and you can see that input port will be gone from the port diagram as well. So now I will take it back because I wanted to use this reset port in our project. Similarly, we have optional output ports and you can see we have this logged output, and for this project, we do not need to use this output logged port. So I will simply untick this from here and you can see that is gone from this block diagram as well. Alright. So now simply click on next button and I will leave these settings as it is. So simply click on next. Now this is the page for clock switchover. So in your project, in case you are using more than one clock frequencies as an input, so in that case, you can use this clock switchover. So once you tick on this, then you will have the extra clock frequency in the input port and you can select whatever the frequency you are having on that second clock input. And also you will also have one extra input port for clock switching, and you can use this to either select the clock 0 or clock 1 dynamically in your program or dynamically in your project. Alright. But in our FPGA board, we only have one clock frequency. So I do not need to use this clock switchover. Alright. So I simply untick this option from here and then click on next. Now this is asking for the dynamic configuration. Now we know that we are having the board frequency of 50 MHz and we wanted to get our output as 25 MHz. So this is very strict that we knows the input and we knows the output. Alright. So we do not need to use any dynamic configuration in our program or in our project. Alright. So I will leave all the settings as it is and simply click on next button. Now this is an important page because in this page we will configure our output clock frequency. Alright. So we will have a couple of options to choose our requested output. So for example, I can use this multiplication factor or the division factor. Now because our input frequency is 50 MHz and the output frequency is 25 MHz. So we know that the output frequency is the division of 2 of the input frequency, right? So you can use this clock division factor and that will be 2 for our requirements, right? So you can see that the actual setting will be 25 MHz. So that is one way of selecting your output frequency, but I will prefer this second way, and that is enter output clock frequency. So I will select this option and here I just need to give that what frequency we wanted to get at the output. Alright. So for example, in our case, we wanted to get 25 MHz at the output port, right? So I will simply write that 25 MHz that we want to get at the output. And once you do this, your Quartus Prime software will automatically adjust the multiplication factor or the division factor according to your configurations from the input or from the output. Alright. Another thing that you can select in this IP catalog or this PLL module, that you can control this clock phase shift for your output clock frequency. So you will have multiple options to select this. So you can select this from the degree perspective or from the nanosecond perspective or picosecond perspective. So Quartus Prime is quite flexible on the requirements, and that is why this PLL can be used in many different ways and can cater multiple of your requirements. For example, you can also control the duty cycle of your output clock frequency. So by default, that is 50%, means 50% time it will be at logical high and 50% time of one clock cycle at state 0. Alright. And based on your requirement, you can adjust this duty cycle as well. But for our project, 50% duty cycle is completely fine. So I will not touch this setting at the moment. Now, once you are happy with the configuration of your output port, you can simply click on next. Now, if you notice, that is the same page as we have in the last page, right? Because this PLL allows you to select multiple output ports based on your project needs, and you can select up to 5 clock outputs. So you can see these tabs here. So that start from C0 and goes up to C4. So if you want to have one another clock output of, for example, 10 megahertz, so you can simply tick this box, and now you can select the output frequency. For example, this second clock output is 10 megahertz. So you can see that in the block diagram, two clock outputs, that is C0 and C1. So C0 is configured for 25 megahertz output and C1 is configured for 10 megahertz output. And you can see the division factor is 5 because the input frequency is 50 megahertz and we wanted to get a 10 megahertz from that. So once you are happy with the second clock, you can click on next and it will ask for the third clock frequency. So again, if you want, you can use this to generate the third clock output. And for example, this time you wanted to get 100 megahertz as an output clock frequency. So once you select this, you can see that now the configuration is set that a clock multiplication factor by 2 because our input frequency is 50 megahertz and we expected to get 100 megahertz of clock frequency. All right. So you can see this C0 is for 25 megahertz, C1 is for 10 megahertz, C2 is for 100 megahertz. So like this, you can select for C3 and C4. But for this project, we only wanted to have one clock output of 25 megahertz. So I will simply unclick this and I will simply unclick this C1 as well. So in this case, I will only have this C0 output of 25 megahertz, right? So now simply click on next, then next. So this is C3. Now this is C4. You can select these clock outputs from here as well. And once you have all these clock outputs configured, you can simply click on next button. Now I will leave this page as it is and then simply click on next. Now these are the couple of files that will be generated from this PLL. So you can see that these two options are grayed out, means these two files will be mandatory generated by this PLL, but you can select the file from these 4 files if you wanted to generate them or not. So for example, this CMP file, that is VHDL component declaration file, suppose I wanted to generate this, and suppose I also wanted to generate this template file for component instantiation, right? So that it can save some of my time while instantiating our component into top level module project. All right. So you can simply tick this option as well, or you can leave also. Now, once you select all of these things, now simply click on this finish button. Now this is asking that if you wanted to add this PLL catalog or this IP catalog, or even we should say this module into our existing project or not. Now for this project, I wanted to add this IP into a project, right? So I will simply click on yes. Now if you notice at this file, so you can see that this is QIP file and that is generated in your IP folder that you have selected. So by mistake, if you forget to add this file into a project, you can also do that later as well. So just simply click on yes here in this window. Now, if you look at this hierarchy view, then you can only see the IP test here. We are not seeing the IP module here because we have just added that into a project, but we have not instantiated that in our top level project or top level module. So if you change the view from hierarchy to files here, now you will be able to see this QIP file, and here you will see this clockpll.vsd project. So this is our IP, right? Now if you open this file, because this is a VHDL file, so you can see that how this PLL is created. So we have this library declaration, next we have this entity declaration, and finally we have this architecture declaration or architecture section. So you can see that this architecture section is quite long, all right? So these are all comments, but the main part is up to here. Okay. So this is our architecture section. Now, if you try to read this file, then you won't be able to see any logic about the division of clock frequency. Instead, this is a kind of a netlist that is generated by the Quartus Prime software. All right. You won't be able to see any logic about the clock division here, right? So that's our VHDL file, and what we are really interested in this entity section, because we have to use this part to declare the component and to instantiate the component into our top level module. So what I will do that I will copy this part that entity part from here. And now I will go to this IP test.vsg, which is our top level module. And now I will instantiate this component here in this top level module, right? So first we will declare this component. So this is a component here. And now this is AND component. Now I will copy this part to instantiate this in our program. Now first I will give the name of this component. Suppose this is clock PLL. All right. Now we do not need this is keyword from here. So I will remove this. Now the next section will be port map. So write port map. And now we will connect the ports of our components with our top level module ports or signals. So let's write the structure first. And we do not need this statement here for this component instantiation. So we have these 3 ports to interconnect with our top level module. So this asynchronous reset will be connected to a reset. So let's write it reset. Now this input clock 0 that will be connected to our main clock frequency or our system clock frequency. So that is clock here in our case. So this is clock, and this C0, so that is our output of our component. So that will be a 25 megahertz of clock frequency. And for this we will use one internal signal, and let's say the internal signal is clock underscore 25 megahertz, right? So this is the internal signal that is of clock of 25 megahertz. And this is our system clock frequency, and that is 50 megahertz. All right. So first we will define this clock signal, that is our internal signal. So I will define this. So that is signal clock 25 megahertz. Then that is std underscore logic type. All right. Okay, seems that I have mapped the component in the wrong section. So this will be coming here, and that part, that is component declaration, that will be going to this section. All right. Now this is good. No, that is not good. So what I will do that I will copy this part once again, and I will paste it here. And now replace this entity word with the component word. Same, I will copy this and paste it here. Now give the name of this component instantiation. So suppose this is clock PLL. Now we do not need this is keyword in the last. Now this will be port map, and now this looks good. All right. Now coming to the finite state machine, and now here we also need to change our clock signal. At the moment, this input clock, that is our 50 megahertz signal or 50 megahertz input, that is driving our finite state machine. But what we want, that we want to drive this with this 25 megahertz of clock frequency. So I will use this 25 megahertz of clock signal to drive this finite state machine, right? So I will replace this clock with the clock 25 megahertz. Now everything looks good. Now one more thing that I want to tell you, that this is one component instantiation of this PLL. Now if you wanted to use more clock signals, then you can also do this by the component instantiation. How? You can just simply copy this part from here. Now paste this. Now suppose this is clock PLL2, and now this time you wanted to have 12.5 megahertz of clock frequency to use in your project, and that is actually a half of 25 megahertz, right? And now what I will do, that I will connect this 25 megahertz of clock frequency to the another PLL as an input clock, and at the output I would be getting a 12.5 megahertz, 12.5 megahertz for example. So this is our another internal signal for 12.5 megahertz clock signal, right? This means that you can generate or you can instantiate as many clock signals as needed as per your requirements. All right. But here is a catch, because if you select the FPGA device that you are going to use in your project. So for example, if I select this hierarchy view from here, our device is this one, and this device only have 2 PLLs inside it. Means this is our first PLL and this is our second PLL, and both of these PLLs are now occupied by this project. This means that you are not able to use any third PLL in this project because the limitation of this device, because this device only have 2 PLLs inside it. So if you wanted to use more than one clock output, then better to select it from the IP wizard itself. Like I demonstrated that you can select up to 5 clock outputs from that IP, right? But now for this program, we do not need this second PLL or second output clock frequency. So I will remove this section of code from here. Now the next step is compilation. So we will do the full compilation of this program. So I will click on this Start Compilation button. So you can see that it has been started and it can take up to 10-15 seconds. So you can see the process here or the progress here. So that is completed in 15 seconds and everything is good. All you can see in the green color, right? Means our VHDL code is free from any syntax error. And now we will give the pin planning to this module. So I will select this button. So I will click on this pin planner button. So you can see this is the top view of our FPGA device. So this is our side A, this is side B, this is side C, and this is side D. And this FPGA is having total 144 pins. And Quartus Prime software already identified all the input-output ports from our top level module. So you can see we have this clock as an input, reset as an input. We have 3 switches as an input, and these are LED 3 outputs. So what I will do here that I will select each port from our module and we will tell the Quartus Prime that this port is connected to which pin of this FPGA. Alright. So for example, this clock pin or this clock port is connected to the pin number 23. So you can see this pin is highlighted now and you can see that this clock input that is connected to the pin number 23. So that is mentioned, right? Now the next input is reset. Suppose this reset is connected to pin number 25. So I will give this pin number 25. Next we have 3 inputs for the switch input. So let's say these are connected to pin number 88. Now pin number 89. And this switch 3 is connected to pin number 90, right? Same, we have these 3 LED as an output. And let's say this is connected to pin number 85. Next is connected to 86 and next is connected to 87. So you can see that all the selected pins are highlighted in the FPGA top view here. Alright. Now note that these pin descriptions can be different for different boards and it depends on the FPGA board manufacturer. So you will be getting the specification sheet with your FPGA board and that will specify that which input or which peripheral is connected to the which port of your FPGA device. So you have to select your pins according to your FPGA manufacturer or the FPGA board manufacturer. Alright. Now you can see that all the input-output standards are selected by default to 2.5 volt. And for my FPGA board manufacturer, that is connected to the 3.3 volt. This means that I have to modify this 2.5 volt as per my FPGA board specification. Alright. So I will select this 3.3 volt LVTTL. Same for all the ports of this module. Okay, so that's done. Now because there is no save button in this window here, because pin planner automatically saves your configurations when you are making any changes to it. So you do not need to save anything here. You just simply click on this close button. And now because you have changed the configuration, so you need to recompile your program first. So simply click on this play button to start the compilation. Now while this is compiling our program, let's see that what files Quartus has generated for our IP component, right? So I will go to this IP test folder. So that is our project name. And here we are having the separate folder for our IP. Okay. So this is our folder. Simply open it. And here we have this PLL folder. Remember, we have created this folder for the clock PLL, right? So this is the benefit of creating a new folder for each IP component. So now here you can see that we have this clock PLL. So that is VHDL file. And that is the same file that I've shown you in the Quartus Prime software. I will show you this once again in a couple of seconds. Now this is the second file for the component instantiation. And we have generated this from the optional section, right? Now this is the main file, that is script file QIP. And if you wanted to use this PLL on some another project, then you can just simply import this QIP file and then this IP will be added to that project as well. Okay, so that is a quick brief. Now go back to the Quartus Prime software. So this is our clock PLL.vsd that I have shown you in the folder. Now, as I said, if you forget to add the IP into your project or you wanted to add any different IP into this project, then you can simply do this by selecting this FPGA device and now right click. Now go to settings and here you will see this files option and from here you can browse the file and then you can simply add that into this project. Alright. Now once you do this, we can open the programmer. So you can see the button here we will simply click on this programmer button, and this is the window will open to program your module into the FPGA device, right? So you can see that this is your FPGA device. This is the file name that will be written into your FPGA device. This is the name of your FPGA device. Now because this time our hardware is not connected, so I don't see any hardware is listed here. But in case you have connected it, then that hardware will be listed here. And even if after connecting your hardware is not displaying here, then simply click on this hardware setup and your device should be visible here in this box here. And if it is displayed, just select it and click on close. Okay. And after that, you will be able to see the hardware here in the section. And once your hardware is listed here and you select this programmer file, then you will see this start button will be popped up. So just simply click on start button and the progress of programming your module onto the FPGA will start from here. Okay, so that was a quick brief. Now because we have used the PLL and we have checked everything for this top level module, so now this is the time to review the netlist viewer and the fitter reports. And these are really important to understand this netlist viewer and the fitter reports when you are working on the Quartus Prime software and developing any project for your requirements. Okay, so let's close this programmer window. Okay, so that was our today's project. We learned a new concept of Quartus IP and we practiced a finite state machine too. We learned how to import a PLL IP in Quartus Prime, how to configure it, and how to use it in your designs. Now remember that the configuration of all the IPs listed in different categories can have different steps based on what it do. Like memory IPs will have different settings. Processors will have different settings like that. Now the next session is going to be interesting because in the next session, we will see the physical structure of this design. Means we will see that how different elements inside the FPGA are interconnected to meet today's requirement in real hardware. And we will use RTL Viewer and Technology Map Viewer for our designs. We will also see that how to navigate between these different elements in the netlist viewer. In the last session, we have designed a finite state machine project and we have used a PLL IP to drive that finite state machine. And we have also compiled our design. Now we will see the netlist viewer of this design. So we will use RTL Viewer tool and Technology Mode Viewer tool to analyze our design. Okay, so let's move to the Quartus Prime software. Okay, so now I'm going to show you that how you can review your designs in more details in Quartus Prime software. And for this, we are going to use some very important tools of Quartus Prime. So first thing that I wanted to show you that is Netlist Viewer. So for this, you need to go to this Tools bar or Tools tab. Now here you will see this Netlist Viewer option. And here you will see a few options. Like the first one is RTL Viewer. So we will look into this RTL Viewer. And also we will also look into this Technology Map Viewer post fitting. So RTL Viewer will give you some high-level overview of your module and Technology Map Viewer post-fitting will give you some detailed overview or the detailed mapping of your project. Alright. So first I will select this RTL Viewer. So now this is our RTL Viewer window and this is the high-level block diagram of our top-level module. So in the left you will see the input part. So here you can see all the input ports are listed. And generally at the right, you will see the output ports. So for this module, you will see that we have reset as an input, clock as an input, and we have 3 switches as an input, right? And at the output, we have 3 LEDs. So now if you notice that all these 3 outputs are derived from the registers. Although you can see one register here in this block diagram, and you may think that this is one register that is driving these 3 LEDs, but that is not correct because this register view is actually a combination of 3 different registers for 3 different LEDs. So if you notice at the name of this register, so that is LED 1, register 2 down to 0. So this is the name that is given by the Quartus Prime software. And if you look at our VHDL code, so that is our VHDL code. So here we have not listed any such register in our VHDL code, right? But still they appears in the RTL viewer. Like here, they are just appeared just before the outputs, right? And they are placed here because our LED outputs are derived from a registered process block. So if you look into the code, so that is our VHDL code. And if you go to the finite state machines where we are driving all of our LED outputs, so here you will notice that these all the LED outputs are derived at the rising edge of clock signal. And these are written inside the registered process block. And if you remember from our previous session, then I explained that if any output that is derived from a registered process block, then they are mostly derived from the registers. So that is why we are having these registers placed here just before the outputs. Alright. And these are actually three registers. So one is register 2, next is register 1, and third one is register 0. So these are actually three registers. Now if I come to this first block diagram or this first block of this RTL viewer, then I can see this PLL is placed here at the very start from the inputs, right? And we have instantiated this clock PLL as a component in our top level module, right? So if you remember that our PLL was having the two inputs and one output. So the one input is asynchronous reset and the another input is in clock 0. And we had one output that was the clock output of 25 megahertz, right? And that was named as C0. So you can see that this reset input is connected to the asynchronous reset of this clock PLL. And our input clock signal or our input clock port is connected to the input clock of this PLL module. And the output of this clock PLL is actually driving our internal logic of finite state machine, right? So this is actually a finite state machine. We will come to this little later. But before this, let's look at this switch input. So we have three switches as an input. So you can see that switch 1 we are having, then switch 2 and switch 3. Alright. Now if you notice that there are some lines, these are narrower, but there are some lines that are wider. So these wider lines are actually telling that these are containing multiple lines inside it. So for example, this line having 3 switches input. Alright. Now one more thing, that if you select any line from here, then it will highlight all the traces of that wire, like from where it is coming and from where it is going and from which components this wire is connected to. Like for example, this wire or this reset wire or this reset port is connected to this clock PLL. Then this is connected to the state machine and it is also connected to this registers or LED registers, right? So it will give you an easy view of all the traces of any internal connections. For example, you can select this line and you can see that this C0 or the 25 megahertz of clock frequency that is connected to this present state, that is our state machine, and also that is connected to the LED registers, right? Now let me give a quick look about the netlist navigator. And this is our netlist navigator, and that is really important to use because this netlist navigator have listed all the components or all the elements including input ports, output ports, internal signals, wires, elements, registers, everything is listed here. So you can use this navigator to easily navigate all these things inside this RTL viewer. For example, if I select this ports view, then you will see these input ports and output ports. And if you remember that our module has clock input, reset input and switches input. Now because switches was STD logic vector and it has 3 elements inside it, so you can expand this view, and if you want you can select individual switches as well from here. Now if you click on any element of this navigator, then that element will be highlighted into this RTL viewer. For example, if I selected this clock signal, then you can see that is highlighted in the RTL viewer. Same way, if I select this reset, then that will be highlighted too. Now, if you go to this primitives, and if you wanted to see that how many registers you have used inside this module, then you can also see this. So simply you select this register section and you will see that you are getting 3 registers inside this module. And if you select this, then that section will be highlighted. And also you can extend this to see the individual elements of these registers. Now here we are also seeing this instances tab This will be generally coming when you have used any component instantiations in your top level module. Like in this project, we have created an IP for clock PLL and then we have instantiated that into our top level module. So you can see that that instance has been coming here as a component, and if you expand this, then you will see this clock PLL that we have created or that we have instantiated into a top level module. Now you can also expand this. Now go to primitives, blocks, PLL1. So that's how you can navigate it. Okay. The same thing you can do by clicking of any of the module. And once you select any of the element or any of the port or signals, then it will be also highlighted into the netlist navigator as well. For example, if you select this reset port, then this navigator will also select the reset port here. All right. Same for if you select the clock, then it is selected clock. Now coming to the finite state machines. So as I said, we have used finite state machines into this project, right? And Quartus Prime has already identified that what we have used inside our program. So once I select this, you can see that state machine, which is named as present state, that is selected. And now you can also expand this view. So for this, if you double click on this present state, so this state machine window will open. And now this is telling you that your module are having three different states. So that is red state, next is yellow state, and next is green state. So if you are looking at your VHDL code, the same thing we have defined in our code as well, right? So we have three different states, that is red, yellow, and green, right? So that is visible in the graphical view here in the state machine. Now, if you look at the bottom section of this state machine, then it is telling you about the transitions. So what are transitions? So if you look at the two different states, so for example, this red and yellow, then you will see this connecting line. So this connecting line is treated as a transition. So that is telling that you can go from red state to the yellow state. And when you select any transition, then that transitions will be highlighted here. Okay. So this column is telling your current state. The second column is telling your destination state or target state. And the third column is telling you the condition that when your current state will jump to the next state. Means at what condition your current state will change to target state. So for example, if I select this transition that is from red state to yellow state, so that transition was happening when the switch 1 is pressed, right? So this red to yellow transition will happen when the switch 1 is pressed, right? Same way, if you look at this transition from yellow to green, then we have this transition selected. So transition from the yellow state to green state will happen when the switch 2 is pressed, right? Same, this third transition, so that will happen when the switch 3 is pressed. So if it is pressed, then we will move from green state to red state. Also, we have another transition, and that is called self transition. Means we are going from the red state to the red state in a cycle. So that is called self transition, right? Now, because we have specified that what will happen when the switch 1 is pressed, means when switch 1 is pressed, we will move from red state to yellow state. But we have not specified that what will happen when switch 1 is not pressed. So if switch 1 is not pressed, then we will be in self transition state, right? So you can see that current state is red, target state is again red, and that is dependent on the switch 1. So when switch 1 is 0, then this transition will happen. And that is repeated for all three different states. So that is repeated for yellow and that is repeated for green as well. All right. So this view is give you a better picture about your states and about your transitions, right? So you can use this view to review your finite state machines results. So now I will close this window and I will go to the netlist viewer once again. So this RTL viewer is giving the high level overview of your top level module. And now we will review our module in little deep. So for that, I will close this RTL viewer window. Now I will go to this Tools tab. Now select this Netlist Viewer. And this time I will select this Technology Map Viewer Post Fitting. Alright, so simply click on it. Now this time you can see little complex view of your module. And this is the actual presentation which will be implemented in your FPGA board. Like these are the elements will be used or these are the resources will be used inside your FPGA, and these are the interconnections that will be happening inside it. Okay. Now this left side view is your input ports and the right side view are your output ports. Okay. And now because this view is a little complex, so this time it is more sensible to use this netlist navigator to navigate our elements inside this graphical view. Alright. So let's look at the outputs first. So first we will zoom this area. So simply click your mouse button and select the area where you want it to zoom in like this. So you can see that this area is zoomed in now and you can see all the elements listed here. So we have these 3 LEDs as an output. Now again, once I click here, this also map these LED outputs in the netlist navigator as well. Okay. So you can see that we have 3 different registers here that is driving our 3 LED outputs. Now if you notice, then these outputs are coming from the registers outputs, but also passing through the input-output buffers. Quartus Prime is also capable of adding the tri-state buffers here as well. But for this project, we do not need any tri-state buffer. So basically, this is our input-output buffer, and here these are acting as an output buffer. So that is OBUF. So this is for LED 3. Next one is for LED 1, and this last one is for LED 2. And all of these are driving from these 3 different registers. Okay. And we have seen these registers in the RTL viewer as well. Now you can see that the input of these registers are coming from some combination logic, right? So these combination logics are either the combination of the basic gates or even they can be simple netlist or the fitters. We will come to this in some time. But before this, let's zoom out this view. So just simply right click from your mouse and select this, go to top level. So once you select this, then you will see this top level view. And now we wanted to see the input ports of this module. So same, I will zoom in this area. So I will click from my mouse and I will select the area where I wanted to zoom in. And now you can see that this is our input area. And here we have this clock input. And again, that is passing from the input-output buffer before reaching to this clock PLL, right? Next, we have this reset input that is passing through the input-output buffer, then passing through this clock control, and then to the PLL. Next, we have these 3 switch inputs. Now, till here, this is vector type, and the one element of this switch input is going to this input-output buffer. So this input-output buffer is for switch number 1. And similarly, we will have 2 more input-output buffer for these 2 extra inputs. So I can see that this is the input-output buffer for switch 3. But I cannot see this input-output buffer for switch 2 in this view, right? So what I will do that I will go to this netlist navigator. And now here you will see these buffers are listed for switch 1, switch 2 and switch 3. So when I select this buffer for switch 1, so it has selected. So for switch 3, it has selected. And I wanted to see this for switch 2. So simply I will click on this and now it will navigate to that input output buffer. So that's how easy it is when you use this netlist navigator. Now again, I will right click and go to this top level view and let's zoom this area. So we have this clock PLL. We have already explained this in the RTL viewer. So this is same, but this time what I wanted to show you is this combinational block. So you can see the expression for this combinational block here. But even if you wanted to analyze this combinational block, then you can also do this. So simply right click on this combinational block and go to this properties. Now once you click here, then this properties window will open. And here you can see, let me widen it little. So now you can see that this combinational block that is named as selector 2, that is a combination of different AND gates, OR gates, XOR gates, etc. So you can see that there are 4 inputs that is coming in to this combination logic and there is 1 output coming out from this combination block, right? And how these combination blocks are generated, you can see the graphical view of it, alright? Now the inputs of this combination block is named as data A, B, C, D. And if you wanted to know that what are these names and how these ports are connected into your top level module, so you can see them in the bottom section of this properties window. So for this, you will select this fan in and you will see that data A is connected to selector 00, data B is connected to selector 01, and same data C and data D is connected to the switch 3 input, right? So if you select this, then you will see that is connected to the buffer or the input output buffer of switch 3, all right? Same thing you can see for the outputs. So your combinational output is connected to this present state dot green. Now if you move this little, so you can see this present state dot green. So that is a register that is generated for the green state, right? Similarly, if you wanted to see the relation between the input data and the output data of this combinational block, then for this you will get the option of truth table here. So you just simply select this truth table and now you can see all the combinations between the inputs. So these are 4 are your inputs and your output. Okay. Similarly, you also get the equation view. So here you can see that this is the equation for this combinational block. All right. And these are your input datas. Now, if you remember from our previous sessions from the FPGA basics, then I have explained that how CLB works in the FPGA. So inside the FPGA, they are created based on the lookup tables. So these are basically the CLBs used inside the FPGA. All right. Now again, select the Netlist Navigator. So here is the tab for Netlist Navigator. So I will select this. Now this time, if I select this present state dot green, so you can see that all the registers are listed here. So we have 3 registers generated for the states and we have 3 registers generated for the LED outputs. So these 3 registers are for the LED outputs. So you can see, and these 3 states for the present states. All right. So from this view, you can see that how many registers are used in your project, how many input output ports are used in your project, and how many elements or different elements are interconnected to meet your requirements for your project. So this is really an important view to understand if you are working in VHDL designing or Verilog HDL designing. Okay, so that was our RTL viewer and technology map viewer for this finite state machine project. And next we will be looking at some important reports that is generated by the Quartus Prime software. And this is really important to understand these reports for better designing. So for this, first we will look onto the fitter reports. Okay, so let's close this window from here now and jump back to the Quartus Prime software. Okay, so that was our RTL view and technology map view of our design. RTL view gives a high-level structure design, and if you want to drill down, then you can use technology map post-fitting tool to analyze your design. We have learned that how the Netlist Navigator is useful to navigate between different elements used in your design, right? Now, next we will look into some very important reports that are generated by Quartus Prime after the full compilation of your design. In the last session, we have analyzed our design graphically. We have used RTL Viewer for high-level structural design and Technology Map Viewer for detailed structural design. We have navigated through different elements in our design too. Now, this is the time to review some of the important reports to analyze your design in little more details. And by doing this, you will know that how Quartus Prime take the decisions to configure your designs. And you will also need to learn that how you can override Quartus Prime configuration based on your specific design requirements. So we are going to start with fitter reports. And these reports will tell you about the resources utilization of different elements of your FPGA that was occupied by your design. For example, how many CLBs are used? How many registers has been used? Are these logical registers or input-output registers? How many memory elements has been used? How many PLLs are used? How many input and output ports are used? So these reports contains a lot of information about your design and your FPGA device. These reports also tell you about that how much resources in FPGA are remaining too, so that you can know that how complex design you can still make on your FPGA device. We will also discuss global netlist, and you will learn that what signals or ports should be promoted to the global netlist in your design, or should be treated as a fast signal or not. Okay, so that is enough introduction. Let's jump to the Quartus Prime software. But before this, one important note that all of these filter reports you will be able to see only after a full compilation run. Now, let's move to the Quartus Prime software now. Okay, so after the netlist viewer and the RTL viewer, we will look into the filter report, and for this we will go to this compilation report section, and now here you will see this filter report section. So once you expand this, you will see a lot of reports here in this category. Now remember that this filter report will only be published after your full compilation. So once your compilation report is fully completed, then you can come here to review these filter reports. Alright. So first important report is this summary. So it will give you a quick brief about the resource utilization, your input-output port utilization, your FPGA device, your top level module, etc. So for example, this is your top level module that is named as IP test. You have selected this Cyclone 4 family device and the device name is this one. Now you can see that the total logical elements that has been used by this program or this IP test module, these are 9 in total, and your FPGA device means this device has total 6272 total logical elements. So that's come up with the less than 1% resources, and that can give you confidence that how complex you can design your project for this specific FPGA device. So this project is really very small and that is only consuming 9 elements from this 6272 total elements. Alright. Now next is total registers. So your module is using 6 registers for this project. Next is total pins. So your FPGA device has total number of 92 input-output pins, and out of this 92, your project is using total 8 input-output ports, and that counts 9% of total. You can also see about the memory elements or the memory utilization. So this 276,480 is your total available memory bits, and we have not used any single bits for this memory elements. And remember that this is different from this total registers. So in this module, we are using 6 registers, but we are not using any memory bits. These memory bits mainly comes when you are using memory IPs in your module or the RAM elements or the ROM elements inside your module. Alright, so we have not used any such elements in this program. So that is why this is 0 here. We do also have the multipliers inside this FPGA device. So this FPGA supports 39-bit multiplier, and again we are not using any element from it. Alright. Now the next is total PLLs. So this FPGA device supports 2 PLLs, and out of this we have already used 1 PLL in this project. Means you can use 1 extra PLL in this program. So this is the quick overview of the resource utilization of your FPGA device. Now coming to the next report, so this is settings, and here you can see all the settings that has been used by the Quartus Prime software for this project design. Alright. And the important thing is that these 2 columns that display the default values and also your configured values, so you can easily navigate if any of the values are different from the default value. So you can go through them if you really wanted to read them. But for this project, we have not changed much of the configurations, so maximum settings are same as their default values. Alright. Now next important report is this resource selection. So if you expand this, then you will see multiple reports listed here. So the first one is resource usage summary. So this report is a little drilled down version from the summary report that we have reviewed. So you can see that the total number of logical elements are 9 out of 6272 total elements, and these 9 elements are bifurcated into these 3 type of elements, right? So you can see that the combinational block with no registers, so these are used as 3 number of total counts. Next, 2 elements are only registers. These are not derived by the any lookup tables, and rest of the 4 elements are the combinational elements with registers. Now this is important to understand that CLBs are the basic elements inside your FPGA device. So for example, this device has total 6272 CLBs inside it, And these CLBs are derived from a kind of lookup tables. Means these three elements are derived from the lookup tables without any registers. These two elements are only registers and they are not derived from any lookup table. And these four elements are the combination of the lookup tables with registers. Alright. Now, if you are not aware about the CLBs and the lookup tables and how these works inside the FPGA device, then please watch my FPGA Basics section. That is really important to understand that how the CLBs and lookup tables works for an FPGA and how Quartus Prime software configures them for any desired requirements. Now coming to this next section. So now this is telling that there are three elements that has been used as in 4 input functions, and rest of the 4 elements are used as in less than 2 input functions, and 2 are registers only. So you can see these are 2 are registers only. Alright. Now if you go a little down, then you will see this register section, and if you remember from the netlist viewer, then we have seen total 6 registers there, right? So 3 registers was for driving the LED outputs and 3 more registers for driving the current state of our finite state machine, right? So in total, we have used total 6 registers for this project, alright? So you can see that there are total 6 dedicated logical registers that has been used out of total 6272 registers, and that contributes less than 1% of resources. Now this is really important to understand the input-output registers. So these input-output registers are important because if your registers are placed far from the input-output ports of your FPGA device, then the signal will take more time to reach to the input-output registers, and that will add up the timing delays while reaching to these registers. Although this time will be very small, and this is acceptable if you are working on some slow speed devices, like here in this case we are designing. But if you are really working on some fast device that is operating on some really a very high speed frequency, then we will prefer to use these input-output registers to drive our output more quickly. So if we wanted to get our output little faster, then we can use these input-output registers which are placed near to the input-output ports of your FPGA device. Alright. But for this project, we are not using any input-output registers. So all are dedicated logical registers here. Alright. Next is input-output pins. So you can see that we have used 8 input-output pins out of total 92 pins. Alright. Next is the memory elements or the memory blocks. So you can see that we have total 30 number of memory blocks here, and that can store this number of bits. So you can see this is total block memory bits, and these are grouped inside this 30 elements or 30 memory elements. Next we have these 9-bit multipliers, and we have not used any one in this project, so the utilization is 0%. We have used 1 PLL out of 2, so that contributes the 50% utilization of PLLs. Next we have these global signals. So we have 2 global signals in this project. We will come to this little later. Next we have this global clock. So we have 10 in total, and we have occupied 2 number of them. So that contributes 20% of resources. You can also look at this maximum fan out. So that is 7 here. This means that one signal is driving how many elements far in the FPGA. So for this project, we would be having one signal that is derived 7 different elements. And you can look the netlist viewer to map that signal. Okay. And next is total fan out. So that is 60. That is okay, but maximum fan out is really important to understand. Now coming to the next report, and this is next is input pins. So you can see that all the input pins are listed here. So we have clock, reset, and 3 switch inputs, and these input ports are connected to these pins of FPGA. Next column is input output bank. We have already explained these banks in the previous session, so you can go and look for them if needed. Next is combinational fan out. So you know that clock has the one combinational fan out because that is only connected to the input of our PLL, and all the other elements are derived from the output of that PLL. So this clock has the fan out of 1. And same you can see for the reset. So that is connected to the 7 elements, or you can say that reset is driving 7 different elements inside our project. You can also map it into the netlist viewer. Alright. Registered fan out, we have 0. Now if I go to little right hand side, then you will see this global nets. We will talk about this global nets little later. Next, we have these input-output standards. So we have selected these values for our input-output ports. So for our FPGA board, this is 3.3 volt LT, LB, TTL. All right. So same way you can check for the output reports or the output pins. So these three are our LED outputs, and these are connected to these FPGA pins 85, 86, and 87. Next column is the input-output bank. Input-output standards 3.3 volt TTL. So you can go and look into them one by one, but I'm not going in detail much here. Now the next report is PLL summary. So that will be generated if you are going to use any PLL inside your project. So we have used one PLL in this. So that is a summary of it, that what is the input frequency, what is the output frequency, what will be the VCO frequency. So there are many informations listed here. You can just go through them if needed. Next is PLL uses. So we have used this clock PLL inside this project. So that is having the output frequency of 25 megahertz, and that will use the division factor of 2. The output clock will be clock 0. Duty cycle will be 50-50. So you can quickly review them if these are matching with your requirements or not. Now the next important report is resource utilization by entity. So this report is really important when you are using many modules inside your top level module and you really have a big hierarchy of your designs. So for example, if you select the hierarchy view from here, and this is our top level module, and if you expand this, then you can see that we have used this PLL as a component here, right? So you can see the same thing here as well. So this is our top level module, and inside this we have used this component as PLL. Okay. Now if you look at this PLL, then all the resources are 0 here because they are not consuming any of the resource from the FPGA CLBs, because we are using a dedicated PLL for this clock PLL component. All right. But for this IP test module, which is actually having a finite state machines, we are consuming FPGA resources, or we can say that we are consuming the CLB resources from our FPGA device. So for example, we are using 9 logical elements. We have 6 dedicated logical registers. We are not using any input-output registers. We have already seen them in the previous reports as well. So this report is a bifurcation if you are using many modules inside your project. So you can see that how much resources are consumed by the each module. So this is really important view if you are working on really complex design. Now the next report will be control signals, and this is really important to understand. So generally all the clock signals and reset signals are treated as in control signals. And this report tells you that what are the signals which are driving multiple elements inside your FPGA. So in this case here, we can see that we have 3 signals or 3 ports. These are treated as a control signals by the Quartus Prime software. And Quartus Prime automatically identified them for your projects. So Quartus Prime has identified 3 different signals which should act as in control signals for this project. And these are clock and reset, and 1 clock output from our clock PLL. Alright. So these are the location of input-output ports or any other signals that has been used. So clock is connected to pin number 23, reset is connected to pin number 25, and the 25 MHz clock output is connected at the PLL1. Alright. Now if you look at this global column, so that is telling that if the port or signal is a global net or not. So you can see that Quartus Prime has selected this PLL output, that is a 25 MHz clock, as in global net. Also, the reset port is acted as a global net. But our main clock frequency, that is our port frequency, that is not treated as a global net. Now this is decided based on this fan out numbers. So you can see that this clock input has the fan out value is 1, because this clock input is directly connected to the input port of our PLL, and then we will be getting a 25 MHz of clock signal, and that 25 MHz of clock frequency was driving all the other elements inside the FPGA, right? So that is why this clock input is treated as not a global net, okay? But this PLL output, which is again a clock frequency, and that is driving 6 different elements inside our FPGA. So that is why that is treated as a global net. Alright. So that is really important to understand that what should be your global nets and what should not be a global net. In case you are thinking that some of your signals are driving multiple elements of your FPGA, but Quartus Prime did not consider that as a global net, then in that case, you have to configure that signal and promote that to the global net. Okay. And don't worry, I will tell you that how you can promote any normal signal to a global net signal. Okay. Now, if we go little right, let's see what extra details we have. Now we will jump to the next report, and that is global and other fast signals. And this report is actually a subversion of this control signals. So you can see that we have these two signals. These are identified as the global net. So these two global nets are listed here. So we have this 25 megahertz of clock, that is a PLL output, and we have reset. All right. So you can see that this FITR report has a lot of informations which you should review for almost all of your projects. And they will give you a good overview about the resource utilizations, your signal specifications, input-output port specifications, and many more things. And now we will tell you that how you can change the configurations if you wanted to override the Quartus decisions on your projects. Like how you can promote the normal netlist to a global netlist, or how you can promote the normal registers or the dedicated registers to the input-output registers. Okay, so that was some of the important FITR report that I think you should review for all of your projects. These gives a lot of insights about your designs and your FPGA device. Next, you will learn that how you can modify Quartus configuration and promote any normal signal into a global netlist signal, and also how you can change any dedicated logical registers into the input-output register. In the last session, we have learned different FITR reports in Quartus Prime, and we also learned about different type of elements in your FPGA device. We learned about normal signals and fast signals and global signals as well. And we have seen that Quartus already configured few of the signals to the global signals. Now we will learn that how you can override Quartus configurations and promote any signal into a global netlist or a fast signal based on your project needs. Also, we will learn that how you can override register configuration and upgrade any dedicated logical registers into an input-output register. Okay, so let's jump into the Quartus Prime software. Okay, so in the last session, we have seen this summary report under the FITR category, and we have reviewed multiple reports inside this. Like we have reviewed this resources usage summary, which was telling that what are the FPGA resources has been used for this project, right? So you can see that we have used total 6 registers, and all the registers are dedicated logical registers. I already explained that what was dedicated logical registers and what was input-output registers, right? And what are the situations when we need to promote any dedicated registers into the input-output registers, right? So we will see that how we can promote any dedicated logical registers into the input-output registers now. Also, if we go a little down on this list, then we will see this control signals. And I already told you what are global signals or global nets in an FPGA device and how they need to be configured for your project. So in our project, we have seen these two signals, that is a PLL clock output, and the reset was already configured by the Quartus Prime as global net. So you can see that is yes here, but our clock input, so this one, that was not configured as a global net, right? So that is no here, and that is completely fine because this clock has the fan out of 1. This means that this clock signal or this clock input is only driving one element in our project or one element in our FPGA. So there is no need to mark it as a global net, right? But we will see that in any case, if you wanted to promote any signal or any port to the global net, then how you will do this, alright? So we will promote this clock, which is our input port, to a global net, right? So for this, we will use assignments editor. And to open this assignment editor, we will need to go this assignments tab, and here you will see this assignment editor. So we will open it. Now this is the window for assignment editor. And here you will see all the signals are listed here. Now, if you look at this top right, then you will see this category field, and you can use this category field to use these filters. So for example, if you only wanted to list the locations of your input output ports for your project, so you can select this locations here. So once you click on it, so you can see that the list is shortened down and now it is only displaying the locations of your input output ports, right? And you can see that this column is displaying all the input output ports of your project. So we have clock as an input, reset, we have 3 switches input, and we have 3 LED outputs, right? And you can see the values of these input output ports as well. If you remember, then we have configured these values from the pin planner tool, right? So here you can see this pin planner. Let me quickly open this. So we have used this tool or this window to configure all the input output pins with our FPGA device, right? So either you can use this way or you can also do this from this assignment editor as well. Both the procedures works fine, alright? Means you can assign the pins from the assignment editor as well. Now if I change the category to input output standards, so you can see the configuration on all the input output ports of our project, right? And we have configured them to the 3.3 volt LVTTL from the pin planner, right? So if you want, you can do this from here as well. Now we will try some more categories. So the next is logic options. And here you will see multiple filters or multiple categories inside this. For example, this time we will select this global signals. Now, if you quickly look into this compilation report, then we have these control signals here. And here we have 3 signals that are listed in this control signal. And out of these 3 signals, we have 2 as in global nets. But this clock signal is not configured as in global net, right? So now we will use this assignment editor to promote that clock signal into a global net. So let's see that how we will do this. So for this, we will go to this 2 column and we will double click on it. Now we will use this find tool. This we called node finder. So we will click on it. Now we will list all the nodes for this project. So you can see that all the nodes are listed here. So you can find your node and you can select it. But this is a small project. So this list is actually a very small list. But if you're working on some bigger project, then this list can go very long, right? So we can use the filters or we can use some searching criteria to find the correct node, right? So what we will do that because we know that we are promoting the clock signal to the global net. So we will search for the clock, now asterisk mark, and now I will list all the nodes which contains this clock. So you can see now this list is shortened down to 2 values. And we know that we are promoting this clock as in global net. So we will select this and then we will click on this. So this means that this clock signal is now selected. So now we will click on this OK button. Now we will go to this next column, that is assignment name. So when you double click here, now you can see all the parameters or all the options which you can select for this clock. Okay. Now because we are going to promote this signal as a global signal, so we will select this global signal. All right. Now, if you wanted to know that what are these names and what they do, then Quartus is very good on this. So you can see that when you move your cursor to any of these groups, then Quartus is giving you a good descriptions about it, right? So for example, I'm selecting this global signal. So in the bottom box, you can see the description about this assignment name. Okay. So you can go through all of the assignments and you can learn that what they are and what they do. Okay. But for now, we are promoting this as a global signal. Okay. So the next column is value. And now once you double click here, so you have 2 options. So first one is global clock and second one is off. Now because we are promoting our clock signal to a global clock, so we'll select this. Otherwise, you can select this off. Okay. So click on this global clock. And now that's complete our step to promote the clock signal as a global net. Okay. Now at the same time, we will do one more thing, that we will promote our dedicated registers for the LED to the input output register. So if you look at this resource user summary and you go to this registers field, then you can see that we are using 6 registers in this project and all these 6 registers are dedicated logic registers. So out of 6, 3 registers are for LED outputs and 3 registers for your present state. And that is why we do not have any input output registers in this project. So what we will do that we will promote one of the LED registers to the input output register. Although this is needed for a really fast system, but the purpose of this is to tell you that how you can promote any dedicated logic registers into the input output registers. And by doing this, you will learn that how to optimize your project based on your requirements and the FPGA limitations, or we can say FPGA resource limitations. Alright, so let's go to the assignment editor once more time. And now this time we will select this input output timing category. Alright, so now this time we will add one LED output registers to the input output register. So for this we will select this two column, we will double click. Now we will use this search tool. So this is node finder. Now let's look for all the nodes this time. So we will list all the nodes, and now we can see that we have this register that is for LED1. So we will select this by click on this button. So now this is selected here. Now click on OK. Now select the assignment name. Now because this is an output signal, so we will select this fast output registers. Okay, so select this. If you want, then you can read the description for this fast output registers. Okay, now we have this value field. So double click on it and select this on option. Okay, so that's it. We just wanted to change two configurations for this project. So now we will save this, and now we will run the full compilation for this project. Okay, so you can see the compilation is started. It may take 10-15 seconds, so we will wait for the outputs. Okay, so this is almost done. Okay, so now let's go to this filter report one more time, and now select this resource section. And if you look at this summary, and now if you go to this total registers, so now you can see the total register count is still 6, but the dedicated logic registers are 5 now, because we have promoted one registers for the LED1 output to the input output register, right? So this input output register is selected for the LED1 output. Next, we will check for the global net. So for this, we will select this control signals report. And now if you look at this, then you can see that we have 3 signals here: clock, reset, and PLL clock. And all of these signals are now promoted to the global net. So this column, you can see these are all yes. So if you remember that this clock signal was not a global net in the last compilation, right? So now this is promoted as a global net. So that's how you can optimize your projects by manipulating the Quartus Prime configuration settings, right? Same way, you can look for the assignment editor for more categories, like you can select synthesis configurations, input output timings, features, global signals, input output standards, locations, etc. And you can also explore the different type of assignments just by double clicking here and just select what assignment type you wanted to review. Okay, so you can just select anyone and you can see the description in the bottom box. All right, so you can select any assignment type and you can use that to know what they do and how they do. Okay, now we will look for some other Quartus settings which are important to understand if you are working on the Quartus Prime software. Okay, so you have seen that how we have promoted our clock input port to a global net. Also, we upgraded one of our LED register to a output register. Next, we are looking into some of the important settings in the Quartus Prime software that you can use to optimize your designs. Now, this time we will look into some of the important settings in Quartus Prime software that you can use to optimize your design. We will talk about VHDL compiler version. We will talk about compiler optimization modes. We will see some of the synthesis advanced settings and filter advanced settings as well. Okay, so let's move to the Quartus Prime software. Okay, so now let me quickly tell you about some of the important settings in the Quartus Prime software. And you can configure these settings for each individual project based on your needs. Alright, so for these basic settings, we will go to this device selection where we have designed our project. So we'll select this device and right click. And here you will see this settings option. So click on it. So let's adjust the size of this window so you can see everything in one view. So now in the left panel, you can see different category to select it. And in the right hand side, you will see the configurations for that category. Okay. So for example, the first category is general. And from here, you can select your top level entity. So for example, in this project, we have used 2 entities or 2 modules. One is for PLL and second is for your finite state machine or IP test, right? So at present, we have selected this IP test. So that is our top level module. And if we wanted to change this, then we can click on these 3 dots and you can select whatever the top level module you wanted to choose. Okay. And this is really helpful when you are working on some bigger project and that have a lot of modules and component instantiations. All right. So let's select the IP test for now and click on OK. Now the next category is files. So if you wanted to add any existing file into this project, then you can browse that file and you can simply add that into this project. So for this, you can click on these three dots. Now you can locate your file or you can locate your module. Simply select it and then click on open. Okay. And after that, that module will be added into this project. So that is one way to add any existing file into your project. But you can also do this by going to this project navigator window and select this files tab. Now you can go to this files, right click, and you can select this add and remove files in project. And this will open the same window as well. The next one you can select from this EDA tool settings. So from here, you can tell your Quartus Prime that what tool you wanted to use for simulation. So you can see that it is having a couple of options. So you can use ActiveSDL, you can use Quista Simulator or any other tools, right? So that's give you a good options for your simulations. Now the next important setting or next important category is compiler settings. So here you can see this optimization mode and that is currently selected to balanced. So from these settings, you can choose the aggression level of your compiler. Like if you wanted to focus on the performance or you wanted to focus on the power consumptions or you wanted to focus on the compactness of your FPGA or the compactness of your design, right? So please remember that there are a trade-off of selecting these options. And these trade-offs can be of three different types on FPGA. So one trade-off can be in your power consumption levels, second trade-off in your compactness of your design into the FPGA, and the third trade-off can be into the timing analysis or the timing performances. So you need to wisely select the right options for your project needs. And by default, that is selected to balanced. So this will balance out your designs on these three different factors. All right. So you can go through them one by one. And if you wanted to try, then you can change these optimization modes as well. Okay. Although the differences can be seen in some really big projects. So you can design them and test them. Now, if you go a little down, then you will see these two different settings. These are advanced settings for synthesis and this is advanced settings for filters. So if you open this advanced settings for synthesis, you will see a lot of configurations inside this. So you can see this is really a big list of Quartus configurations for the synthesis operations. All right. And as I said, that Quartus is really good in the documentation and the explanation. So you can select each configuration and you can see the description inside this bottom box. Okay, you can select any configuration and you can read the details about that settings. Okay, and accordingly, you can change your settings for your projects. Okay, for example, if you go down, then we have this setting for the state machine. Because we have used the state machine in our project, so we can review this. So you can select this state machine. So you can select this save state machine off or on. Also, you have state machine processing settings as well. So by default, that is selected to auto. And if you wanted to change the state machine processing type, then you can see a couple of options to choose from, right? So if you wanted to Gray or Johnson or minimal bits, then you can select the processing time based on your needs. Now remember that these settings are global for this project. So if you're using multiple finite state machines in this project, and if you select this Gray or Johnson or minimal bits, then that configuration will be applied for all the finite state machines you are using in this project, right? So please make sure that these are global settings. Now quickly look at the filter settings. So you can see that the list of this filter advanced settings is also quite long. So you can go through them and you can read the descriptions about all of these settings. So I recommend you to spend some time to understand these advanced filter settings and advanced synthesis settings. Okay. So for example, we have this weak pull-up registers here. So you can configure them if you really wanted to use them externally in your hardware. So same way, there are a lot of settings you can tweak to optimizing your projects or to optimizing your designs. Okay, so let's cancel this for now. Now, if you select this VHDL input, then you will see these three options. So 1987 is the oldest one and 1993 is by default selected. But what I recommend you to select this VHDL 2008. and this will allow you to offer some advanced feature that was introduced in 2008 version. So these are a couple of important settings that you can use to configure or to optimize your VHDL designs in the Quartus Prime software. Also, you can go through these different categories as well. So these are for timing analyzer, assembler, design assistant, power analyzer settings, logic analyzer interface, etc. So please spend some time to understand these settings for designing a better project. And if you have any query, then you can post it in our community. Okay, so that was a short video. Although we have seen some of the basic settings as well, but they are quite useful in day-to-day projects. And with that, we are closing this chapter and ending this course here. You can share your feedback with us. We will be very happy to read them. If anything you want us to cover, then do let us know from the comment section. We will try to include that in our next course. So till then, learn new things and upgrade yourself. Happy learning.